I started this channel many years ago, but in 2016, I started a new format where I answered your questions about space and astronomy. And we've been continuing to do those questions now for 10 years. We've answered a lot of questions. I recently built a search engine that allows us to kind of go through and search through all of the questions that have been asked before. And we found out that the most commonly asked questions is black holes. It's not that surprising, really. In fact, so many questions about black holes that we wondered what would happen if we turned that into a supercut. One big video that contains all of the questions that I've ever gotten about black holes. Turns out the thing is 10 hours long, contains 300 questions. So here you go. You now have a supercut of me droning on for 10 hours straight. You can use this to fall asleep to without feeling any worry that you're going to make me sad. Turn it on in the background to keep you company while you're doing some kind of boring manual labor. I'm here for you. Now we've got two versions of this, one with music and one without music. And so there's two audio tracks. There's the English US, which is the one without music, and then the English Canada, which is the one with music. So you can decide which one you prefer. I've also planted a few Easter eggs at various breakpoints through this video, and so you're going to have to just watch the whole thing to find them. All right, let's get started. 10 years, 300 questions, 10 hours. Black holes. Dr. Wong, have we figured out how small a natural black hole can be?
So there's two sizes of black holes that we know of, right? There are the stellar mass black holes. These are the ones that are formed when a star with many times the mass of the sun explodes as a supernova and collapses down and forms this black hole. And you get somewhere between, I forget the number, 6, 10, 12 times the mass of the sun for a stellar mass black hole. And then there's the supermassive black holes that have been around pretty much since shortly after the Big Bang. There's some connection between the galaxies inside of them and the black holes themselves. There's no natural formation that can form a black hole that has lower mass than one of these stellar mass black holes. There's no process in the universe that can make this happen. So the one possibility is that there were these primordial black holes that were formed back shortly after the Big Bang. And it's kind of amazing to think about. The density of the universe back shortly after the Big Bang was so high and so hot and so dense that you could have these places of higher density where you would have these black holes of maybe an asteroid's worth of mass or an Earth's worth of mass just spontaneously be formed, just because the universe was just compressed so tightly. And so then maybe these primordial black holes have just been floating around the universe ever since, evaporating, exploding when they've completely evaporated. So far there's no evidence that these primordial black holes exist right now. And there's no natural method that you could do to get a black hole that's formed anyway but the death of a star.
Mavis, a black hole cannot swallow everything. Even gamma rays can escape its pull.
So gamma radiation is just another form of electromagnetic radiation. There's radio waves, infrared, visible light, go through the rainbow, ultraviolet, X-rays, gamma rays, but it's just a different wavelength of light. And black holes can absolutely suck up gamma radiation. Gamma radiation needs to follow the paths of space-time, and if there is a black hole there that's distorting space-time, the gamma radiation is going to follow that path right in. And if the black hole itself is generating gamma radiation, it's still all getting absorbed because you have to be going faster than light speed to be able to escape the black hole. So, black holes can absolutely eat up all the gamma radiation out there.
Abhinav and Araman Rao. If the speed of light doesn't limit us, what speed would help us escape a black hole?
So the whole point of a black hole is that it is an object where the escape velocity is faster than the speed of light. So for the least possible mass black hole, you're going to be right at the speed of light is your escape velocity, which is impossible. So you just can't go faster. So I guess the question is that if you could go faster than the speed of light, which you can't, then every black hole is going to have a different escape velocity. One that is, just formed as a black hole might have an escape velocity of the speed of light. But then a supermassive black hole with millions of times the mass of the sun is going to have an escape velocity that is hundreds of thousands, millions, billions of times the speed of light, which is impossible on top of impossible.
Dima R. Can a galaxy have more than one supermassive black hole? Could there be a galaxy that, instead of stars, planets, or moons, would only have black holes?
Yeah, so every galaxy so far seems to have its own supermassive black hole. And there's a couple of exceptions, but in general, there is a supermassive black hole at the heart of every galaxy. And these supermassive black holes can interact when the galaxies themselves collide. As you can have these situations where one galaxy and its black hole will steal the galaxy's black hole from whatever it collided with, and then maybe you're going to end up with these two supermassive black holes orbiting some central gravitational point, like a binary planet or something, or a binary star system. But they're two supermassive black holes, and so this other galaxy's had its supermassive black hole stripped out of it, and this galaxy has two of them in it. And then we can theoretically be able to detect the gravitational waves that are emanating from these interactions between these supermassive black holes. So to have multiple supermassive black holes, you kind of have to steal one from somewhere else. One of the ideas for supermassive black holes was that maybe there's this in-between size, these intermediate black holes. And maybe if an intermediate black hole gets massive enough, it becomes a supermassive black hole. But these intermediate black holes have actually been really hard to find. Astronomers have looked inside globular star clusters and still haven't even been able to find them. So it's a big mystery right now.
CGUX Curry. What would happen if a quasar and a black hole interacted with each other?
So a quasar is really just a supermassive black hole, but one that's actively feeding, where the material is falling in, it's coming in too quickly, the black hole can't clean its plate fast enough, and the material, goes up onto this accretion disk that surrounds the black hole, and then these magnetic fields form, these jets come out of the black hole, and it becomes very, very bright. But a supermassive black hole and a quasar are literally just the same thing. They're just two different forms. One is actively feeding, one isn't. So what happens? Can they interact? They can absolutely interact. They can orbit one another. They could collide and form an even larger black hole. And maybe that, more massive black hole would have more capacity to absorb material. So, they're really just the same thing, but just at different phases.
Victor Manuel Leite de Matos. Can we revert a black hole to a star?
Once material has become a black hole, it can never go back. There's no return back to a star. There's no way to decrease the density of the black hole back to the point that you could then turn it back into a star. The black hole, as we've talked about in other episodes, is going to evaporate over long periods of time. And then as it evaporates, it becomes lower and lower mass, gets hotter and hotter and hotter, and eventually it's just going to explode, or at least is that final little bit of energy, and then it's gone. And there's no way to get back to a star.
Stewie Sheenan. Where is the Roche limit of the supermassive black hole? Is it in the accretion disk?
When a supermassive black hole tears apart these stars, what you're seeing is the Roche limit of the black hole and the star that it's interacting with. So a star is coming in on a comet-like trajectory. It gets within the Roche limit, the place where the gravity of the black hole overcomes the gravity of the star itself holding it together, and it gets sort of torn apart into this disk of material, and then it gets added to the accretion disk. So where that exact point is, it depends on the mass of the black hole, and it depends on the mass of the star itself and the density and so on. But that's essentially what you're seeing, is these stars get torn apart as they're getting within that Roche limit of the black hole.
Aiden Reynolds. Well, guess what, idiot? Have you been in a black hole? Honestly, I don't think you know what you're talking about.
You go first, and then you report back on how it worked out, and if you're still okay, then maybe we'll follow.
Sting Duke. Why not somehow speed up the Hawking radiation process?
So the idea of Hawking radiation, this is that the black holes evaporate because these virtual particles are appearing right at the event horizon of the black hole, and one's zipping off into space and one's falling into the black hole, and this energy can't come from anywhere. It has to come from the mass of the black hole, and the black hole gets smaller. So the question is, could you make it happen faster somehow. Well, the only way you can make it happen faster is to take the black hole and put it in a freezer so that it is surrounded by a place that is colder than the black hole itself is. Because right now, the supermassive black holes and stellar mass black holes, they are currently colder than the universe itself. So they're just going to keep getting warmed up by the universe. So the only way you could speed it up is to take them to some place, put them in a freezer, and really make that freezer cold so that then the evaporation can start to really get rolling on the black hole. But it's not going to speed you up much. It's not going to make them go away any faster. And you need a really big freezer.
Hercules Rockefeller. Are there super duper black holes at the center of galaxy clusters?
Yeah, there are the stellar mass black holes, there are the supermassive black holes, and there are the super duper mass black holes, where these galaxy clusters have come together and the supermassive black holes have interacted with each other and merged, and they have billions and maybe even trillions of times the mass of the sun. They're incomprehensible how massive these things are.
Jasim Chowdhury. What came first, supermassive black holes or the galaxy?
This is still a point of argument between astronomers. What seems to be the case is that there is some connection between the mass of the black hole that's in the galaxy and the formation and age of the galaxy itself. Which one formed first? We don't actually know. And it might be that they both formed together. As the galaxy gets bigger, the black hole gets more massive. There's some natural process there, but it's actually still a mystery.
Stick to Pac-Man. Is a supermassive black hole created from a supermassive star?
Maybe. So astronomers still don't really know how the big supermassive black holes formed, but they do know that a regular star, there's a limit, so around 65 times the mass of the sun, where they can't get any more massive. And when they do explode, they explode without a black hole, without any remnant at all. They just disappear they sort of completely explode. So we know that you can't get a black hole with a much more massive star. There had to be some other formation, whether they were formed right from after the Big Bang or whether clouds of the sort of primordial gas left after the Big Bang just came together and formed those first supermassive black holes. Astronomers don't know, but they do know that you can't get a star any bigger and have it actually form a black hole. Now, it's possible that early on, the stars were pure hydrogen. So there's other models for how these really, really big stars. I've seen simulations where people have done 65,000 times the mass of the sun to try and simulate what that could turn into. So it's still a big mystery and a big point of contention. But these days, no, you can't get them. Justin Morgan, how big can a supermassive black hole get? Could they go up to 1 trillion solar masses? There is no limit to how massive a supermassive black hole can get. Supermassive black hole, or any black hole, can consume an infinite amount, can consume all the matter in the entire universe and still be a black hole. It can just keep going. So you could take all of the mass and energy and everything in the entire universe and jam that into a black hole, and it still would be fine. It's not going to explode. It's not going to fall apart because it's too much matter. No problem. Shashank Vaidya. Is our solar system orbiting the black hole? Our solar system is orbiting the center of the Milky Way, right? Like the way the planets orbit the sun. And so it takes about 225 million years for the sun and the solar system go all the way around the center of the Milky Way. And at the very center of the Milky Way is a supermassive black hole. So yes, although, I mean, we're really not orbiting. It's not like that is the gravitational center that we are orbiting, but it is at the location that we are orbiting. The real thing that we are orbiting around is the center of mass of the entire galaxy and its dark matter halo, which is the vast majority of the mass of the Milky Way. And that whole thing is turning, and the black hole happens to be where the center of that is. Horia Ion. So the universe's speed is faster than the speed of light, and the black hole sucks the light in. Is it possible that the universe is expanding slower near black holes? So the expansion of the universe that's going on is sort of a stretching of space-time. And that's completely separate from this sort of the warping of space-time that happens from black holes. So a black hole is embedded in the larger space-time, and the black hole can be expanding away with the galaxy that's around it. And it's not going to slow down the expansion of the universe. So it doesn't matter where these black holes are and how big they get and how massive they are, the expansion is still going to happen regardless of what they're doing. So the sort of the expansion of the universe and the warping of space-time by black holes is not connected. Rugged Alan, I've read something about a month ago that a bunch of astronomers from around the world were starting a project that would take the first picture of a black hole that's at the center of our galaxy. Yeah, so you're talking about the Event Horizon Telescope, and this is actually going to be a worldwide collection of radio telescopes that are going to be directed at the supermassive black holes, Event Horizon, and maybe some other close galaxy supermassive black holes. And if everything goes well, they will be able to resolve right to the edge of the event horizon, and we will get some new information about what happens right at the event horizon of a black hole. It's actually still a mystery what goes on in that edge right next to the black hole. Now, it's not going to be like we're going to see this cool picture like out of Interstellar, but we are going to get scientific data about what's going on in that nearby environment. It's really exciting. And as soon as this whole worldwide telescope comes online, I'll totally talk about it. Fish sticks. Is it possible that all the antimatter just fell into black holes? Maybe. Like antimatter can absolutely go into black holes, and that just makes the black hole more massive. But the problem is that sort of the way it appears right now is that the black holes, especially the supermassive black holes, formed in relation to the mass of the galaxy as the galaxy was growing, as the stars were forming, and so on. And so it would be weird that all of that would be antimatter would be disappearing just into black holes. Like, that's not something that astronomers would expect. So I'm not an astronomer, but from what I understand, no. We would see the interactions of all that antimatter early on. We would see it exploding. Probably didn't go into black holes. Sketchy Games wants to know, what about creating a black hole and stand near it to dilate the time around so you can travel to the future without moving? Is that possible? Yeah, totally possible. Did you see the movie Interstellar? That's what happened, right? They went down to this world that was orbiting a black hole, and the time dilation made it so that because they were close to the gravity of the black hole, their time was different from the time for the rest of the universe. And when they finally came out of this gravity well, they had lost whatever was 40 years or 80 years or something like that. So if you spend a lot of time near a black hole, time will happen differently for you. You will experience less time than the rest of the universe. The problem is that it's a one-way journey. So you can skip hundreds, thousands, millions of years if you want, but you can never go back. Is there a habitable zone of a quasar? Yeah, so around a quasar is all this material that is about to fall into the supermassive black hole, and it kind of piles up and heats up and really turns into like the core of a star. Nuclear fusion is happening in this ring, in this accretion disk that's around a black hole. And so that material is going to be blasting out radiation that's going to then heat the area around it. Now, would you have a habitable zone? I don't know, because you're going to have this horrible radiation environment with gamma radiation. It's going to be a really awful place. But there would be a distance from this accretion disk where liquid water could form, but it's kind of so extreme and stuff doesn't last for that long. It just, swirls into the black hole and disappears. So, there probably would be a place where there would be liquid water, but it wouldn't be a habitable zone in that you would want to live anywhere near there, or the planets could form, or life would have a chance to evolve over vast periods of time. Google's 989. Would a black hole fall apart if its rotation completely stopped to a halt? Nope. No. In fact, all black holes are rotating, and the only limit on their rotation is relativity. If there was no such thing as relativity, black holes could just rotate faster and faster and faster and faster, and they would just tear themselves apart. But the reason that they don't tear themselves apart is because literally the laws of physics stop them from being able to rotate any faster. But if you just had a black hole just stop rotating and just sat there, nothing would happen. It would just still act like a black hole. So, nope, can't kill them that way. Keep trying. Stephanie, can life exist in a galaxy with an active nucleus, a quasar? Life can absolutely exist in a galaxy that has a quasar. We actually did a video about this, and that if the quasar, or the supermassive black hole at the center of the Milky Way started actively feeding and turned into a quasar, which might happen when Andromeda collides with the Milky Way, we wouldn't even be able to see it from here on Earth. Another theory that's even more interesting is that, in fact, one source of sort of star formation, one of the causes of star formation, is the supermassive black holes actively feeding. They put out these kind of jets of material, and that material may rain back down into the galaxy and contribute and help trigger star formation. So it might very well be that we actually need quasars to help kick off some of the star formation in a galaxy. So yeah, for sure, no problem. The last billionaire. Why are black holes black? Well, black holes aren't actually black. It's just that black holes are absorbing all of the electromagnetic radiation that is coming off of them, all of the blue light, all of the red light, all of the radio waves, all of the gamma radiation, all of the colors, all the light that would be coming is being absorbed by the black hole out to the event horizon. And then outside of that, you've got whatever is coming in is getting either perturbed by the event horizon, getting distorted. So it's not that a black hole is black, it's just that a black hole is absorbing all the radiation. And so since there's no radiation coming from it, it looks like this black spot in the sky. Northern Chev. Can a black hole exist without an accretion disk? In theory, I wouldn't think you could detect one without witnessing its effects on something nearby, like a star. When a black hole is actively feeding, when it's got material falling into it, that's when you get this accretion disk, because it's like a bathtub that is overflowing the drain. And so the material is waiting to go into the black hole, and it sort of piles up in this accretion disk around it. But if the black hole's run out of food and it's consumed everything around it, there'll be no accretion disk, and you can't spot it visually. The only way that you can know the black hole is there is by its effect gravitationally, how it is interacting with some binary object. If it's got a star that's going around it, then you can see the star getting whipped around by something. So if there is no binary object, if there is no material falling into it, the black hole is effectively invisible. And there could be very close black holes that we can never see because they don't have any object around them and they're not feeding right now. Alphonse Bourguicha. What type of radiation does a black hole release? Can we use it to detect them? A black hole doesn't release energy. If it's consuming material, then it's going to release energy in the form of radiation particles as it's sort of waiting, it's building up in the accretion disk. But once the black hole's finished consuming everything that it's going to eat, then it's all gone. And so this is one of the problems with black holes, is we can really only detect them while they're actively feeding. And then there's times when they're not actively feeding, and then they're just completely dark. And so a black hole could be moving close to the solar system, and we wouldn't even know where it was. We would just be affected by its gravity. Now, you're probably thinking of Hawking radiation, which is this other idea, but it just gives off like regular particles, photons, maybe heavier, neutrons, electrons, various particles, but it happens so rarely that you wouldn't really be able to detect it on an ongoing basis. Kurt Reber regarding accretion disks. Among all the known black holes, do these disks always flow in the same direction? Why or why not? No, there's no preferred direction of rotation or orientation of anything in the universe. When we look out into the universe, we can see these accretion disks going one way, we can see accretion disks going the other way, we can see them edge on, we can see them face on, we can see them in every single possible permutation, and it's random. And that's good, because if there was some preferred direction, if everything was always going counterclockwise from our perception, that would be really weird. So nope, the universe is random. The largest surveys done show that in all directions, everywhere we look, there is no preferred direction for anything. Hein Duplessis, if a virtual particle pair appears on an event horizon, one falling in and the other having to find another partner in order to disintegrate, surely this will add mass to the black hole. Now, I did a great show with Dr. Paul Metzetter where we talked about what really virtual particles are, that it's actually not this idea of a particle appearing and one going in and one going out, that it's all about fields. And I don't know, my eyes kind of glazed over and he was wibbly wobbly field. Anyway, the point is that but we'll sort of go back to these layman terms, right? So when you've got this virtual particle appearing on the edge of the event horizon and one particle is flying off into space and one is dropping into the black hole, you would think that because these particles are dropping into the black hole, it's making it more massive. But you've got to remember that, the vast majority of these particles are photons. And so we're seeing photons coming off of the black hole, theoretically. It's never been observed, but we're seeing photons coming off of the black hole. Now that violates the laws of physics. Energy and matter cannot be created or destroyed. So where is this energy coming from? Well, it turns out the black hole has to pay the price to allow this photon to escape into the universe. It has to give up mass according to E equals mc squared to allow this photon to get away from it. And so as an outside observer, you are seeing light and particles and atoms of hydrogen and grizzly bears being released from the black hole, and the mass of the black hole has to decrease to compensate. I don't know about the grizzly bears part. The Guardian wants to know, what happens to a black hole when there's no more matter around it? Most of the time, most black holes have no matter around them. They've consumed all the matter nearby. So they're just there. Now, there's still going to be energy from the background of the universe falling into them. There's going to be particles, high energy particles falling into them, but they're just going to go straight in. The rest of the time, there's going to be nothing around them. It's only when they've got too much material to consume all in one bite that you get the accretion disk building up, and that's when the things actually are hot. That's sort of the scary thing about black holes. There could be a black hole moving towards our solar system, and we wouldn't even see it because it's not consuming any material. So most of the time, they're just there. You1. Hello, Fraser, and happy 2017. I have a question on you. If energy and mass are two different manifestations of the same thing, does energy curve space? Energy and mass are interchangeable in the words of Einstein, right? E equals mc squared. So if you could collect together, let's say an Earth's worth or a sun's worth of, instead of mass, the sun is made of mass, it's made of hydrogen. If you could collect it together, but it was energy, like photons of energy compressed down into this area, it would act the same way. It would twist, it would bend space-time, and material would orbit around it. Now, the problem is, I don't know how you can get energy that compact together without it wanting to escape, but this is absolutely energy, mass. And so if you have a black hole, and that's something that's going to keep all that material together, the black hole could be made of mass, it could be made of matter, it could be made of energy, all in the same thing. And it doesn't matter. It just distorts space-time, things will orbit it. And this is why you can't even really say that a black hole is made of mass, of matter, or antimatter, or energy. It's just black hole. Only black hole. Yora. What does it mean for a black hole to rotate? We can't see the matter inside because the event horizon hides it, and the event horizon itself is not an object. So how do we know that the black hole is rotating? There are very few things that you can actually know about a black hole. One is its mass, and the other thing that you can know is its rotation. If you imagine, obviously with a black hole, it's surrounded by this event horizon, so you can't know what the black hole itself is doing. But what happens is that the black hole, as it's rotating, the faster it's rotating, its event horizon actually flattens out, kind of like the way the Earth is flattened out, or the way Jupiter is flattened out. The faster something rotates, the more that flattens out. And so astrophysicists can actually calculate and measure sort of what that flattening is doing. So there's this idea of the naked singularity, which you can imagine a time where the black hole is rotating so quickly that the event horizon flattens out to the point that the black hole is revealed. And actually, the laws of physics prevent this. You can't rotate as fast as the speed of light, and so you can never get to this place where the black hole, the actual singularity, can be revealed by the rotation of the event horizon. One of the other things that astronomers can see is the material that is accreting into the black hole. They can actually measure its movement around the black hole. And in some cases, with some like supermassive black holes and such, they clock this stuff at a significant portion of the speed of light. Literally as fast as these things can rotate, they do rotate. It's a pretty mind-bending accomplishment for black holes. Patrick Bergenhold. What happens when a black hole loses enough mass through Hawking radiation to no longer have enough to be a black hole? Will something pop out? Black holes, we've done an episode on this, that the black hole, the size of the black hole is inversely proportional to its temperature. A black hole that is incredibly massive, a supermassive black hole, is very cold. A black hole that is very small is relatively warmer. You get to a black hole that's maybe a little less massive than the moon, and it's closing in on room temperature. Or maybe it's like the size of an asteroid, like Vesta. It's about room temperature. And as you get smaller and smaller and smaller, the black hole gets hotter and hotter and hotter because it's evaporating this temperature faster and faster and faster. And when the black hole gets low enough mass, it just fires out the remaining energy in this very bright blast. And there's never a point when it's not a black hole. It's a black hole until the final particles are released as radiation and the thing is gone. And this is maybe how we will be able to detect black holes in the future, is seeing them evaporate out there in space as they release that last little bit of energy. I'm at Al Racy. What if the black hole at the center of the galaxy expired? How important is it? The supermassive black hole at the heart of the Milky Way, it's 4.1 million times the mass of the sun, which sounds like it's a lot, but it's actually a very tiny fraction of the entire mass of the entire Milky Way galaxy. And so it's not like acting like an anchor for the whole galaxy. The reality is that the huge cloud of dark matter that surrounds the Milky Way is the thing that is actually anchoring the stars and keeping everything in place as they rotate. The black hole is not that important. Now, supermassive black holes and smaller black holes, they won't expire. They can't run out of energy, die the way stars do. The only way we know is that maybe over long, long periods of time, they will evaporate. But by the time the supermassive black hole at the heart of the Milky Way has evaporated, all of the stars in the Milky Way will be gone. Planets will have probably been eaten by various black holes. There would just be nothing left. And so at that point, it won't really matter. Abdul Ahad. Is it possible in any galaxy to have more than one black hole? Sure, but it sort of depends on the kind of black hole that we're talking about. There's two classifications of black holes. There's the stellar mass black holes. These are the ones that show up after a much more massive star than our sun explodes as a supernova, and then you get this black hole as a remnant. And these can form all over the Milky Way, and there are probably thousands, hundreds of thousands, maybe more in the Milky Way. I'm not sure the exact number. But then there are the supermassive black holes. And so the Milky Way has the one at the heart of the Milky Way. Andromeda has one at the heart of Andromeda. And the only time that you get multiple supermassive black holes is when galaxies collide. And the two, if you get the right kind of collision, then the supermassive black holes at the heart of the two galaxies will come together, they'll orbit around each other, and eventually they'll merge. So if you find two supermassive black holes in any one galaxy, that means that two galaxies recently merged and the supermassive black holes are in the process of coming together. API endless. Can you even have a matter or antimatter black hole? Does the distinction between matter and antimatter even exist at the level of compaction? You can't. Black holes are made of black hole. Anything that goes into the black hole, be it matter, be it antimatter, be it energy, it all just gets compacted down into black hole. There's no memory necessarily of what that stuff was. And so it doesn't still maintain the property of matter when it goes in, and that's why you can't have matter and antimatter really explode in a black hole. They are just black hole, and same with light. And so you could take a black hole's worth of matter and have a black hole. You could take a black hole's worth of antimatter and have a black hole, and you could take a black hole's worth of energy using E equals mc squared to make the same amount. They're all just the same. They're all just black hole. And so really this idea of a matter black hole and antimatter black hole actually don't make any sense, because it's just a black hole. Rohan Shah. Fraser, can one black hole suck in another black hole? Absolutely. Well, you wouldn't call it sucking in another black hole. What'll happen is that the black holes will merge. So you take the mass of the one black hole, you take the mass of the other black hole, and the two come together, their event horizons cross, and then inside the singularities, now we got ravens. There you go. Last week, there's ravens right above us. Okay. And whatever happens at the singularities inside this event horizon, they'll merge together, and you'll now have a black hole that is the addition of the two masses of the other two black holes. And this can happen again and again. And now, with the recent discovery of gravitational waves, we saw these black holes merge together for the first time by detecting the gravitational waves that were pushed out into the universe as two black holes came together. And over the next couple of years, the instruments are going to get more sensitive, and there's going to be more technology and maybe even space-based missions, and we're going to get better and better at detecting these sort of mergers of black holes. So it's a pretty exciting time for this. Curry the vegan. How do we know that gravitational waves we detected were caused by two black holes merging? The LIGO instrument, which detected the black hole merger, was really calibrated to find the most energetic and powerful gravitational wave events that are possible. And the only thing that we know about are merging black holes. I mean, maybe you could have a supernova that ejects a companion star away, but really nothing gets the gravitational waves going more than two, 20 mass black holes crashing into each other. So it had to be for the scale of the gravitational waves. And it's crazy, right? That they were so faint, we could just barely detect the most gravitationally energetic events in the universe that we can find. Hopefully, in the future, they'll get more sensitive and find other classes of events. But right now, it's just the biggest ones that are possible. Re-zero. Question: how does gravity escape a black hole? That's a great question, right? You can imagine, the black hole is so powerful that nothing, not even light, can escape its grasp. And so how can gravity escape its grasp? But gravity is not this thing that's reaching out and sucking things in. It's not like a vacuum cleaner, right? Gravity is the distortion of space-time caused by mass. So the gravity from a black hole wouldn't even exist if the black hole didn't have mass and it was distorting the space-time around it. And so you can kind of, you've seen that kind of classic picture of like something that looks like it's, I don't know how to describe, like a funnel, right? Where you've got this point of mass at the bottom and everything is kind of pushing in. And so when objects are moving through space, going around a black hole, for example, to them, the space is straight and they're moving forward, but actually they're following a curved path around a black hole or down into a black hole's gravity well. So gravity is not a thing that a black hole can suck in. It's just what you get when you have a lot of mass. Lord Black, can a galaxy exist without a black hole in the center? Right now, astronomers think that there are supermassive black holes at the heart of pretty much every single galaxy in the universe. But there are some without black holes, but it looks like some kind of event happened to kick the black hole out. And so what you can get is these collisions between galaxies, especially when there's a big difference in the mass of the black holes at the heart of them. So you say you've got one that's got maybe a black hole that has 5 million times the mass of the sun, a tiny supermassive black hole, and then one with, say, 1 billion times the mass of the sun, and they collide together. The low mass one can actually get kicked right out of the galaxy. And so you could end up with and as these two galaxies kind of go past each other, and now you've got a galaxy where one has had its black hole stripped away. But it wouldn't, the galaxy would be kind of torn up and messed up, but it wouldn't necessarily not be able to be a galaxy anymore. These supermassive black holes, they don't act like an anchor for the center of the galaxy. They're really only a tiny percentage of the mass of the whole galaxy. What really holds a galaxy together is the halo of dark matter that surrounds it. All right, let's get started. Video universe. Hey, I have a question. What happens to a black hole that, let's say, has the mass of Mars or Jupiter and is next to a star that has 12 masses of the sun? What happens to the black hole? Well, if the black hole is orbiting around the star, then it'll just go around and around and around forever until the star dies. But if the two are sort of side by side and there's not that orbital velocity, then the black hole is going to fall into the star and make its way down. It's going to fall through the star and then come back and fall through and eventually find its way to the very heart of the star. And then it's going to gobble up the star from the inside. And eventually you will have a black hole with 12 times the mass of the sun and no more star. Red, yellow, lead, better too. How dense was matter at the Big Bang? How did extremely massive black holes not get created, or did they? Could be the ones at the center of galaxies. The density of matter right at the Big Bang or shortly after the Big Bang was the entire universe was in a region smaller than an atom. So really dense. And so you're asking, well, like, how did black holes not get created? One of the ideas for this idea of primordial black holes. So right now, most black holes are formed when massive stars die and they collapse inward and you get a black hole. There are also these supermassive black holes, which could be, they started as a stellar mass black hole and they just accreted more material and more black holes came together and you got stuff with millions or billion times the mass of the sun. But, there's no other natural process that could get you a black hole with less mass. But maybe shortly after the Big Bang, you had space being incredibly compact, very tight together. You could have had these overdensities, these folds of space where matter was compressed so tightly that it formed into black holes. You could have got black holes of different sizes. You could have black holes that are, say, have the mass of an asteroid or the mass of a house or the mass of a couple of atoms or the mass of a planet, in addition to the mass, and maybe the supermassive ones as well. So this is one line of thinking, and some astronomers think a very far-out possibility is that dark matter is actually clouds of these microscopic black holes. But not very many astronomers actually believe this. Shrub. If a very large star was to go supernova just a few kilometers from a supermassive black hole, would that be enough to launch the black hole out of its galaxy? I know that those black holes can be millions of solar masses, but supernovae are more powerful than I can comprehend. Supernovae are powerful, but supermassive black holes are an incomprehensible amount of mass. A supernova might contain, say, 12, the star that goes off, maybe say 12 times the mass of the sun, 20 times the mass of the sun, 50 times the mass of the sun. That's a lot. But a supermassive black hole is 4 million times the mass of the sun, 1 billion times the mass of the sun, 10 billion times the mass of the sun. Like, these things are just so much more massive than any kind of supernova. The only thing that can kick a supermassive black hole out of a galaxy is another supermassive black hole. These galaxies come together, the supermassive black holes interact with each other, and one can kick another one out of its host galaxy. And that's really the only process that will do that. Now, if you have a large star with a companion and that star explodes as a supernova, that companion star can be kicked out of the galaxy. But to do that to a supermassive black hole, no. Rohan N. Does light that enters a black hole increase its mass? Because light has some energy, that energy has to go somewhere, right? That's exactly right. The amount of energy, as energy goes into a black hole, it just adds to the mass of the black hole. It's, according to Einstein, E equals mc squared. So if you have energy in photons going in, according to Einstein's calculation, mass, speed of light squared, you're going to get a certain amount of mass. You're not going to get very much as these photons go in, but given enough time. And one of the reasons why black holes aren't evaporating yet is because they're still receiving energy from the cosmic microwave background radiation, which is all around us in all directions and is dropping photons into the black holes and making them increase in mass over time. And it's until into the distant, distant future, that the background temperature of the universe is so low that they're not generating any more photons, or very, very few photons, that the black hole will finally be able to evaporate faster than it's accumulating radiation from the background of the universe. Vahuk Lam, quick question. Not sure why anyone wants to, but what might be the most effective way to destroy a galaxy? Building von Neumann machines to slowly push everything into the center black hole? Are you some kind of supervillain? If I tell you how to do this, do you promise not to actually do it? Because the Milky Way is where I keep all my stuff. All right, here's what you do. You build a Shkadov thruster, which is a gigantic mirror on one side of the sun. And then what happens is the sun's gravity pulls itself towards the mirror, but the mirror reflects the sunlight off of it and gets pushed away from the sun. And what this does is this makes the mirror drag the sun around wherever you want it to go in the Milky Way. It takes a long time, take you a couple of billion years, but if you had enough time, you could steer every single star in the Milky Way into the supermassive black hole at the heart of the Milky Way. Now, you would create a quasar while the stars are being fed into the black hole, but if you're patient, and if you're a supervillain like that, you probably are, you could just gather them all up, feed them all into the black hole, and just kill the entire galaxy. And you would end up with a black hole with 200 billion times the mass of the sun. Congratulations, you monster. Ethan and Roberts. Would it be theoretically possible to accelerate a spacecraft to say 1/10 the speed of light by slingshots around the planets in our solar system, or is it only possible for a black hole to do? How would doing this affect the solar system, as so much energy would have been used? We did a whole episode about gravitational slingshots, and here's the short version of this, right? Is that you take a spaceship and you get close to a large planet, like say Jupiter. As you fall towards Jupiter, you are falling in and out of Jupiter's gravity well, and that cancels out. You fall in, you fall out, you gain speed, you lose speed, it's the same thing. But the whole point is that Jupiter is going around the sun, and it has an orbital momentum, and as your spaceship falls into Jupiter's gravity, Jupiter pulls your spaceship up to its orbital speed going around the sun. Now, you steal a little bit of Jupiter's momentum. So you actually lower its orbit around the sun, and you get a speed boost. In theory, you could keep doing this, gain more and more speed boosts, go faster and faster and faster. You couldn't go the speed of light, although theoretically you could gather an almost unlimited amount of energy from the planets. But the problem is that as you got closer and closer to Jupiter, you would have to skim through the cloud tops. And so there's kind of a maximum speed. The other problem is just the physics involved of going close to those planets and really getting cranked around by their gravity as you do this gravitational slingshot. And to take it to that extreme concept, you got that black hole, you come in for a gravitational slingshot of a black hole that's maybe orbiting the center of the Milky Way, and you're going to get cranked in this really tight radius. And what kind of spaceship could go from 0 to a significant portion of the speed of light in that one slingshot? So the gravitational slingshots are really going to be used by us to increase our speed within the solar system, but not necessarily to go to the kinds of speeds that would get you from star to star.
Here's a black hole fact. The first black hole ever discovered was Cygnus X1 in 1972. Kip Thorne thought it was a black hole. Stephen Hawking thought it wasn't a black hole, and so they had a bet. And in 1990, Hawking paid up. He admitted that it was a black hole.
I'm not even going to say this name. Could there be Lagrange points of two closely orbiting massive black holes that exist within the event horizon of one of them or inside the overlapping horizons of both, where a spaceship or station could exist unharmed? Black holes are just masses with gravity, and so they would create Lagrange points as well. You could have, say, a supermassive black hole, and then orbiting around that is, say, a stellar mass black hole, and that would create those 5 Lagrange points. You'd have one a little closer to the stellar mass black hole, one on the other side of the supermassive black hole, and then the two stable L4 and L5 points further along on the orbit. Could you have it be inside an event horizon and not do damage? You have to define what damage means. So if you have like a supermassive black hole that with millions, maybe billions of times the mass of the sun, the event horizon reaches out a long way, even like the size of the solar system. And what that causes is that you could actually go into the event horizon of a supermassive black hole and not even feel it. The tidal forces would be so low. But I don't think that you could have a black hole be at a point where you would end up with that sort of stable Lagrange point. You would still get some level of tidal forces. The other problem is that once you get inside the event horizon, the whole point is that you're never going to escape. There's no way back out. So you could have a space station inside of there, maybe orbiting the black hole, but it, in the end, is going to lead to the singularity in the middle. James Haney. Would it be possible for a Type 4 civilization to find a way to plug a singularity? And if so, what would be the effects of blocking up this intra-pan universal recycling system? I'm not sure how you could plug up a black hole. Like, the only thing you could do is you could feed a black hole so much material that it chokes and the material piles up and it gets really hot and then it releases energy as a quasar. And that's what a quasar is, right? A quasar is a black hole, a supermassive black hole that is feeding so much that it can't choke it all down. And so it's actually releasing all of this additional, the material piles up around it, gets super hot and dense, and turns into a star that releases a tremendous amount of energy. And so really, if you tried to overfeed a black hole, all you would do is create a quasar, but the black hole would still keep gobbling up all that material, and eventually it would all be gone, and then the quasar would shut off. And if you tried to feed it more, then you just make another quasar while the black hole made its way through it. And eventually, you would make a supermassive black hole that's so big and so capable that you couldn't choke it up anymore because you just ran out of matter in the universe. So I like your thinking, but it just wouldn't work. Black holes they can't be killed. Frank Lisk. Does a photon have mass? I've read that it doesn't, but why do black holes pull a weightless radiation? Again, it's important to remember that black holes and all mass, when they exert gravity, they are not pulling, right? They're not grabbing gravity. They are distorting space-time so that straight lines are curved. And just imagine, right, if you're on a fabric and you pull the fabric down, and you get this sort of curved line. If you drop a ball, the ball's going to go around and around. The ball thinks it's going in a straight direction, but actually it's following the curves of the fabric. And that's the same thing that's happening in space. And so it works for planets moving around black holes, and it works for photons of light. Photons are just following a straight line, but they are following the curvature of space-time around that's been warped by the black hole. Exo-elite. Instead of the universe expanding, could everything be moving towards some bigger black holes which are scattered in the universe? This is the kind of thing that you could test. You look out into the universe and you look at how galaxies are moving. And so under the current theory, which is that everything is expanding apart from each other, what you get is when you look in every single direction, the further a galaxy is, the faster it's moving away from you. But if there were these big black hole blobs out there, then what you would see is a bunch of galaxies moving away from you because they're being sucked towards this black hole. But then you'd see other galaxies on the other side of the black hole, and they would be coming towards you because they are all getting sucked into this gravitational well. And that's not what we see. We see everything moving away, not something's moving towards us and something's moving away from us towards these centers of mass that you would predict if that's what was out there. So in this case, you can just make the observation. You can see that it matches that the universe is expanding and not clumping together. Slain Macroth. Can a black hole swallow dark matter? Before I answer this, we always got to say we don't know what dark matter is, whether it is what kind of particle it is. But right now, most astronomers and particle physicists are sort of settling on this idea that dark matter is some kind of, particle, but it doesn't interact with regular matter and it doesn't give off any kind of electromagnetic radiation. That said, all of the astronomers that I've talked to believe that if dark matter is out there and it is some kind of particle, then it absolutely can fall into a black hole, because dark matter, even though it doesn't interact with regular matter in terms of radiation, things like that, it definitely interacts with gravity, and that's what black holes are all about. So if a black hole has distorted space-time and a particle of dark matter is passing along and it follows that path into the black hole, it would be consumed by the black hole. What would happen inside? We don't know what's going on inside black holes. What kind of particle is it? We still don't know, but I feel pretty confident that it would follow that path into the black hole. Black hole asks, shouldn't you know this? Anyway, can a star become so large and hot that it turns black as it no longer emits visible light? Right, so as a star gets larger and contains more mass, it gets hotter and hotter and more massive and hotter. And there's this limit, which is somewhere around like 150 times the mass of the sun, where as the material is falling in, the star gets so hot and so bright, and it's producing these ferocious solar winds that no more material can fall down onto them. So that's kind of the limit of how much a star can accumulate at this time in the universe. Back in the early universe, they could have gotten a lot bigger, maybe thousands of times the mass of the sun. But so you've got this star, and so the largest possible stars that we know of, we can see them. They are blue, they're so hot, but still have way less gravity than, for example, a neutron star or definitely a black hole. You would have to take that size of that sun and then compress it down into an object that's tiny before you would get it to a point that it would no longer emit its radiation, that it would absorb all of the radiation that it's emitting, because it would have turned into a black hole. So there's no stars that can do that. Now, when a star dies, then that's when you do get a black hole, but only under that process. Cole Piss Drunk Hero. How much faster than C would one have to go in order to escape the gravity of a supermassive black hole at the center of the Milky Way? Right, so the idea of a black hole, right, is that you get this object where the gravity on it is so strong that nothing, the escape velocity to get off this object has exceeded the speed of light, so that nothing, no rocket can escape it, and any light that gets emitted comes back down. Now you would think that you would then, you could calculate some point where you could be going faster than light and be able to escape from a black hole. But the problem is that a black hole twists up space-time and tangles it up so much that there is no speed. Once you're within the event horizon, there's no getting out of it. There is no path, no direction that you can take that gets you out of the black hole. Even if you're going faster than the speed of light, all the paths lead you back into the singularity to your doom. So unfortunately, there is just no speed limit that would get you out of any black hole, be it a stellar one or a supermassive black hole. Orza. If dark matter interacts with normal mass just by gravity, then shouldn't dark matter have an effect on black holes too, like any kind of pull on them? Absolutely. Dark matter, we still don't know what it is, but we do know that it interacts. It doesn't interact with regular matter in any kind of normal way, but we do know that it interacts with all matter with its gravity. In fact, it is the vast majority of the gravity-producing material in the universe. And so absolutely, it's interacting with black holes. You can imagine, a cluster of dark matter having black holes fall, be attracted towards them and fall through them. So absolutely. In fact, one of the sort of kind of fringy ideas, this still hasn't been completely disproven, but most astronomers don't believe in this, is this idea that one answer for what dark matter is that it's actually microscopic black holes, primordial black holes left over from the formation of the universe at a time when you could get matter compressed so tightly that smaller kinds of black holes could form. At this point, most astronomers don't think that's the case, but it still could be possible that in fact, dark matter is just black holes, tons and tons of tiny little black holes that account for that enormous amount of mass in the universe. Liam.edu. Can dark matter black holes exist? That's actually kind of like two questions, right? Like one is like, can dark matter fall into black holes? And I think the answer is absolutely. The dark matter isn't affected by any other kind of way with regular matter except through gravity. So dark matter is absolutely attracted to black holes. If dark matter passes through the event horizon, then all paths lead to the singularity, so it's not coming back out. So it will add to the black hole. So, but the other sort of part of the question is, would you have a black hole that's made of dark matter? And I think the answer to that is no, right? That once you get within the event horizon of a black hole, you can't really distinguish what it is anymore, whether it's matter or antimatter or photons of light or dark matter. All of that material just becomes more dark matter within the event horizon. And this is one of the problems that Stephen Hawking has come up with the information paradox, which is that if black holes do evaporate over time, then all that difference of what the material was when it went in is lost. The information about it is gone as it evaporates back out into the universe and the black hole disappears. So, but dark matter can absolutely go into black holes, and what happens inside, we still don't know. Rob Nijkamp. Hello, can you please explain what is the difference between a quasar and a gamma ray burst? No problem. A quasar is a supermassive black hole that's actively feeding on material. So a black hole with millions of times the mass of the sun, and it is actively feeding, and so the material is falling into it and piling up, and you're getting these jets that are coming out, and that's what we see halfway across the universe. And a gamma ray burst is the death of a massive star. And in many cases, the massive star dies in such a way that it creates these jets as it dies that are blasted out halfway across the universe. And so in both cases, right, with a quasar, when we're looking right down the jet of the quasar, we are seeing this super bright object. And with a gamma ray burst, we're looking right down the jet of the explosion. The difference is the gamma ray burst only lasts for a few seconds, a couple of minutes at the most, while a quasar can last for years, hundreds of years, thousands of years. But both kind of give off as much energy as the rest of the galaxy combined. So actually there's a lot of stuff that's pretty similar to them. And then of course, when the star that creates a gamma ray burst dies, it becomes a black hole, but a regular mass black hole, not a supermassive black hole. Hope that helps. Robert Jones. Can we not theoretically create a black hole? And what are the pros and cons of doing so? There is actually an experiment in the works with the Large Hadron Collider to create an artificial black hole. And the way they will do that is they will smash particles together with such force that they will crush into this incredibly dense object. And if everything's done right, it'll collapse into a black hole. Now, momentarily after, like before it even hits the ground, it will have evaporated with Hawking radiation into a little blast of energy. And the only way that you'll know that it even happened is because you get that little blast of energy. And so what are the pros and cons? There aren't really any pros and cons. The pro is that you find out that black holes exist, that black holes evaporate, and Stephen Hawking gets his Nobel Prize. The con, well, some people's cons think that, one of the problems is that you would then have this black hole that would fall into the earth and would gobble up the earth from the inside out. But sort of the theory that predicts that a black hole should be created is also the theory that explains that it will evaporate again. So there's not a lot of people that think there's any real risk of producing these black holes inside the Large Hadron Collider. Damien Reloaded. Regarding attempting to create black holes in the LHC, given the cosmic radiation is orders of magnitude stronger than anything we can produce inside the LHC, wouldn't it be a better idea to try and detect them in the upper atmosphere or in space? This is a great thing. When people talk about the risks of the Large Hadron Collider, and they're worried that if the LHC is going to smash atoms together with so much energy that it's going to tear open the fabric of reality and destroy the universe, collisions of that strength are happening across the universe naturally. I mean, not to mention supernovae, but as you said, you've got cosmic rays that are coming in from space at energies way higher than anything that could ever be made in the LHC. They're smashing into the atmosphere and they're falling apart. Now, this is really cool. One of the really cool things is this thing called Cherenkov radiation, and there's a special kind of telescope that can detect these cosmic rays as they hit the atmosphere, and then they split up into a bunch of particles that reach the ground. And they're going so fast that, in fact, the time dilation is part of the equation as astronomers are calculating and detecting these cosmic rays. So it's an amazing science. I highly recommend that you look into this. It's called Cherenkov radiation. We actually did an episode of Astronomy Cast all about it, and maybe I'll do an episode here about it as well. Sammy Sam. We know when a big star explodes, some are universally small and others are big enough to collapse into a black hole. So is it possible for such a star to be big enough to collapse into a black hole, but for some reason failed to do so? If a star is big enough to collapse as a black hole, once it's past, say, 8 times the mass, I think, of the sun, it's going to turn into a neutron star. Bigger than that, some of them turn into neutron stars, some of them turn into black holes, and beyond a certain point, they turn into black holes. There's some of these giant stars that when they collapse, they form directly a black hole and they don't actually produce a supernova. And then the other thing that's really interesting is for some of the largest ones, they explode and they don't leave a black hole behind at all. They just explode in a big cloud and there's nothing left. And that's just kind of mind-bending that some of the most powerful supernova actually leave no remnant at all. Murder Vader. Seriously, want to enter a supermassive black hole just to see what happens. Yarg. The really cool thing, obviously that's suicide, don't do it. But the really cool thing about supermassive black holes is they're so massive that the event horizons are so big that you wouldn't even necessarily feel going through the event horizon. So you can imagine, say, a supermassive black hole with millions of times the mass of the sun, it's going to have an event horizon that is as big as our solar system. And so you can imagine the spacecraft flying in and you're going to just pass through the event horizon and just keep going. And who knows what happens after that? You're never coming back out. You just have to be, you're trapped in the event horizon, but you wouldn't necessarily feel that transition as you moved into it. As opposed to, say, a stellar mass black hole, which is very smaller, that event horizon is much smaller and the tidal forces that are going to spaghettify you are a lot stronger. And so that's one of the things that's fascinating. So the crazy thing is that you could, although, who knows, once you cross the event horizon, there's possibly this firewall. There could be tremendous amounts of energy that are going to irradiate you once you move across this border. But from a gravity tidal forces sense, it's actually a very smooth trip. But don't do it. Martin Schumann. What happens if the black hole at the center of our galaxy disappeared? Will everything be the same as it is right now? Or will we fly away in a straight line till another galaxy catches us? The black hole, the supermassive black hole at the heart of the Milky Way, is about 4.1 million times the mass of the sun. Sounds like a lot, but actually it's less than 1%. It's a fraction of the total mass of the Milky Way. And the thing that's actually holding the Milky Way together is the mutual mass of all of the stars and dust and planets, but also this huge halo of dark matter that surrounds the Milky Way and acts like an anchor. So if someone came and just disappeared the supermassive black hole at the middle, you would have a bunch of these stars that are orbiting around the black hole, kind of like comets actually. They would lose their gravitational center. There might be some other stars that are kind of jostling around a little, but for us, wouldn't even feel it. And so would have almost no real impact on the stability and structure of the Milky Way. It's not like that black hole is the anchor of everything, and if you lose it, everything flies away. Aniket Yadav. If we could physically feel gravitational waves, what would it be like? Because of the discovery of gravitational waves, I've had this question quite a bit. Gravitational waves, as they pass through the Earth, the way they're detected by LIGO is that they measure, essentially as the wave ripples through the Earth, it pulls the two detectors apart and then pulls them back together again. And there's a laser beam that's bouncing back and forth in between them. And it's so sensitive that it can tell when that beam has been stretched, essentially. And so matter is physically being stretched. And so if you're really close to a neutron stars colliding or a black hole that was coming together, you would feel these gravitational waves passing over your body, and they would be pulling you and pushing you. in the direction that the waves are traveling. And if you were close enough, it would be catastrophic. You would get torn apart. But the thing is with black holes and things like that, there are tidal forces from the gravity as well, which are doing this idea of spaghettification. So you know exactly how much you would experience from the tidal forces compared to the ones you would feel from the gravitational waves. That's, you know, I need to get some physicists to do the math for me to actually come up with the numbers. So I'll probably do this as a video later on. Daniel Buckner. What's the maximum speed you could achieve using a gravitational slingshot around a black hole? Right, so you're trying to think of a way that you could use black holes to speed up your spacecraft. And before we talk about like black holes, let's talk about for a second how gravitational slingshots work, which is that, you know, when the Voyager spacecrafts or New Horizons used the giant planets in the solar system for a gravity speed boost. You kind of imagine the spacecraft falling into the planet and it picks up velocity, but then as it moves away from the planet, it's being pulled back by the planet, and so that velocity decreases. What the gravitational slingshot does is it lets you take advantage of the orbital momentum of the spacecraft. So for example, Earth is going 30 kilometers per second around the sun. So if you try to do a gravitational slingshot around the Earth, you would fall into the Earth's gravity well, you gain speed, and then you would fly back out, and then you would lose the speed, but you would steal some of that 30 kilometers per second of orbital velocity, and in fact, you would slow the Earth down. So that's kind of how a gravitational slingshot works. It's not about the falling in and falling out. It's about you essentially raising to the orbit of the object that you are chasing. So could you do that with a black hole? Absolutely, right? A black hole is merely a massive object that orbits the center of the Milky Way, just like all the other stars. You could do that with a star, you could do it with a black hole, you could do that with anything. The thing with a black hole is that you could get very close. And so by getting a lot closer than you could with, say, a star, then you could gain more of the black hole's orbital velocity. But the problem is that you could try to get close to a black hole and you're going to get torn apart by the tidal forces. You've got this radiation that's coming from the area around the black hole. And if you cross the event horizon, you go in. In theory, it should be possible to go up to relativistic speeds by using multiple black holes, each time stealing more and more orbital velocity. But once you go faster than, say, the black hole is orbiting the center of the Milky Way, they're going to be stealing velocity from you. You're going to be speeding them up. So really, you're not going to be able to use black holes better than you could use any object that you'd be getting in the Milky Way. A problem as well is just the massive amounts of time that are going to happen for you to get from one location around one star to another star. But when you look at how fast the objects are going around the Milky Way, you could, in theory, gain a lot of that velocity by stealing orbital velocity from those objects as you went faster and faster. Meisel DD, what does it mean for a black hole to spin? How can it have a speed when the singularity has zero radius? All of its mass is concentrated into zero volume, right? You can't know much about a black hole, but you can know a couple of things. You can know its mass, and the way you can calculate the mass of a black hole is by measuring how things are orbiting around it. And there's a mathematical formula for gravity that includes two objects, and if you know those two objects and how long they take to go around each other, you can get at the mass of those objects, which is really amazing. And so that's how astronomers find out the mass, is they calculate orbits, and that tells them the mass. To find out the rotation, what astronomers do is you've got this accretion disk that's around the black hole, and the faster the black hole is spinning, it changes the gap between the event horizon of the black hole and the accretion disk that is around it. The bigger the gap, the faster the black hole is rotating. And in theory, if you could come and actually look at the black hole and see the event horizon, you would see the event horizon flattening down as the black hole spins faster and faster. And black holes are limited by relativity. They cannot spin faster than the speed of light. They can spin to a significant portion of the speed of light, but as they get closer and closer, they're prevented. And this prevents the black hole from revealing itself. And this is one of these things that's known as a naked singularity, which you can't have because the relativity stops the black hole from being able to, the singularity from being revealed. And unfortunately, they will always be mysterious and hidden and we can't tell. But that's how astronomers figure out the rotation rate of black holes. Every black hole. Does it mean that there are galaxies detected without supermassive black holes in the center? What holds those galaxies together then? Pretty much, right? Most of the galaxies out there in the universe have a supermassive black hole at the middle. The ones that don't are the ones that had some kind of gravitational interaction or a merger with another galaxy, and the black holes interacted with each other and someone got kicked out into deep space. So it probably used to have a black hole and now that black hole is gone. What holds the galaxy together? Well, the black hole is not an anchor to the entire galaxy. The black hole is a tiny fraction of a percentage of the mass in that entire galaxy. The thing that really is holding the galaxy together is this sphere, this halo of dark matter that surrounds the galaxy and holds it together. And that's what's really holding the galaxy together. It's not the black holes. Derek Burge. Is there a theoretical upper limit to how massive a black hole can be? Not that I'm aware of. You could put all the matter and energy in the universe into one single black hole, and it would just be a black hole with the mass of the entire observable universe. Of course, depending on how big the universe is, maybe we know the universe is going to be much larger than the observable universe. So you could just keep gathering up more matter and just put it into a black hole. There's not some limit where a black hole just gets too full and then does something, tears open a hole in space-time and that we know of, maybe, but there really is no limit to what a black hole can do. And in fact, the more massive the black hole, the longer the black hole is going to take to evaporate and give up its mass using Hawking radiation. So if you want to kind of make the universe live the longest you possibly can, you want to gather up as much of the universe as you can into one black hole. Of course, it would be in a black hole, but it would last the longest compared to in this situation where particles are going to be, zipping away from each other. But, there doesn't seem to be any limit to how much a black hole can handle. Dazanar. We haven't detected a supermassive black hole in Triangulum. I mentioned in previous episodes that every galaxy has a supermassive black hole in the middle of it. And yeah, Triangulum, which is a nearby galaxy, doesn't seem to have a supermassive black hole in the middle of it. And I said in that episode, and a question showed that the reason they don't is because they've had some kind of interaction with some other galaxy that has kicked out their black hole. And it turns out it really looks like Triangulum in the ancient past had some interaction with Andromeda. And so one of the possibilities is that Andromeda kicked out the supermassive black hole from Triangulum just in one of their interactions in the past. And it tells us that maybe in the future, when the Milky Way and Andromeda come together, that Andromeda is going to kick out our supermassive black hole, which kind of makes us feel sad, right? It's like, oh, that's our black hole, our 4.1 million times the mass of the sun monstrosity of death and destruction. Sure, it's going to destroy everything, but at least it's ours. But anyway, So it really appears that you get, through these galactic interactions, you get this rebound where the much lesser mass black hole is just booted out on an escape velocity out into deep space and never to be seen again. And so it's entirely possible that that's what happened to Triangulum and some of the other galaxies out there that don't seem to have supermassive black holes. Bernard Jordan. As space is expanding faster and faster, there will be this time, the big rip, when not even a black hole can resist the space expansion. For how long could there be black holes accounting for that factor? So the big rip is this idea, one of the implications of dark energy, right? This mysterious force that's accelerating the expansion of the universe. And what it means, or so the possibility of the big rip, it sort of depends on whether the force of dark energy is increasing. Essentially, if the acceleration is increasing. So we know that the universe is being accelerated apart, and that's fine, right? But if the force of that acceleration is increasing, then what you're going to get is it's going to be stronger. You can imagine sort of if there's this outward force that's in every cubic meter of space, and it's some set amount. And so if you have 2 cubic meters of space, then you're going to have, the same amount of force. But if that actual force within that cubic meter of space is increasing, then you're going to get a time when, for example, galaxies start to get torn apart, and eventually solar systems start to get torn apart, and eventually planets, and then black holes will eventually not be able to withstand the force of dark energy. Now, if this accelerating dark energy scenario is real, then when this happens depends on how this acceleration is increasing. And there's a couple of estimates that are out there. One says maybe 22 billion years as a time based on some calculations. But really, until we really can nail down just how fast the universe is expanding, we won't know. Right now, we don't even know if this big rip scenario is even possible. But if it is, then we'll be able to calculate when the universe will tear itself apart. And eventually, black holes, atoms themselves, it'll all just come apart. And it's, again, I always sort of think this is so strange when we think about the future of the universe, 22 billion years, long after we're all gone. And yet it just is unnerving to think that it will just tear itself into nothing. So anyway, sweet dreams. Ashlyn Murphy. If the black hole is at the heart of the Milky Way, wouldn't it be hidden in the zone of avoidance? How do we know the orbits of the stars around it? The zone of avoidance is actually a fairly old term, and this was back in the day. There was this big cloud of gas and dust that obscured the center of the Milky Way, and it was this place where astronomers really couldn't see behind it and see behind the Milky Way. But over the last few decades, they've gotten better and better with different wavelengths of light. And the one that's really good at penetrating through this gas and dust is infrared astronomy. And so in the olden days, the zone of avoidance was this huge area that they just couldn't see behind and made the great attractor this big mystery. But now, using infrared astronomy, you can actually see right to the center of the Milky Way and even to what's going on the other side of it. And the thing that they can actually see in infrared is they can see these stars moving like comets around this missing invisible thing at the middle of the galaxy. And that's how they're able to calculate the orbits of these comets and use that to determine the mass of the object that's in the middle of the Milky Way. And now, using radio astronomy, this year, the Event Horizon telescope is going to be producing a photograph of the event horizon around this supermassive black hole. So the technology has just gotten a lot better. Omega views. Can stellar black holes be quasars too? First, quasars are, of course, the actively feeding supermassive black holes in the universe. You get a black hole with millions, sometimes billions of times the mass of the sun at the heart of a galaxy. Material falls into it. The black hole can't eat it all quickly, and so the material piles up and forms this accretion disk. And because of all the energies and matter that's swirling around it, you get these jets of material that go out of the top and the bottom from the black hole and blast off into space. So that's what a quasar is. And because of the masses of the black holes involved, billions, trillions of times the mass of the sun, you know that there is, they're just generating so much, they can generate more energy than the rest of the galaxy, all the stars in the galaxy combined. And this is why they're visible from so far away. We can see them billions of light years away. Now, a stellar mass black hole, they're the ones that are at the, when a star, several times bigger than our sun dies and it produces a black hole. And just like a supermassive black hole, they can feed on material. And the sort of most common version of this is where you've got a black hole and some other star beside it, and they're orbiting each other, and the black hole is feeding material, pulling material off of its companion star, and that material is forming an accretion disk around this black hole, and you can get that same situation. The problem is just that the stellar mass black holes, they're smaller, they're less energetic, and so you can't see them as far away as you can with the quasars, which are just millions of times more massive than these stellar mass black holes. Momin Alharo. Have we seen a black hole ever? We've not directly observed a black hole yet. However, astronomers from across the world gathered together all of these radio telescopes to essentially, they combined the observations from these radio observatories to make a gigantic telescope the size of the Earth. And the purpose of this is called the Event Horizon Telescope. And its job was to image the event horizon of the supermassive black hole at the heart of the Milky Way. And the observations have been done. We're waiting, and I love this story. We're waiting on the data to come from Antarctica, because there's one of the telescopes that's down in Antarctica, and they had to wait for summer in Antarctica to have an airplane fly out all of the data tapes, because so much data was gathered together. And now they're doing all the data analysis and collating and crunching it all together. And hopefully within the next couple of months, we're going to see a photograph of the event horizon around a black hole. Now, we still can't see a black hole because black holes are invisible because they absorb all of the matter and energy that falls into them. But we can infer that they're there. We can tell that they're there by watching the movements of stars at the center of the Milky Way. If you look in certain kinds of wavelengths, you can see stars moving in the center of the Milky Way, and they're going around some invisible, like an anchor, right? They're moving like comets. Over the course of just a couple of years, you can see these stars whipping around this blank spot in the middle of the Milky Way. So we know that something with about 4 million times the mass of the sun is right there, and yet we can't see it. And so the only explanation for that is a black hole. But hopefully within a few months, we're going to get these first pictures of a black hole itself. Although I'm sure it's going to be underwhelming, right? It's going to be a blob, like a super interesting blob that scientists are going to be really excited about. And most people are going to be like, I'll look at the one in Interstellar instead. But still, it's going to be exciting. Nastro PC. My plan, if you slingshot a massive spinning mass close to a black hole, say magnetar, could you spin up the black hole, giving it angular momentum and make its event horizon more and more oblate? And with the poles of the event horizon closer to the singularity in a more strongly warped space-time, would the Hawking radiation flux from the increase? So I don't know exactly what's going to happen with Hawking radiation as you flatten out the event horizon, but let's talk about some of these concepts, because some of them are very interesting. When you spin up a black hole very quickly, the event horizon does flatten out. Now, it can't flatten out to the point that the singularity is revealed. As the black hole gets faster and faster and spins closer to the speed of light, relativity demands that it can't keep spinning up faster and faster. But you do get this flattening of the event horizon, which is really interesting. But the part that's really cool is that black holes are one of the most efficient ways to turn mass into energy. And so, when you think about things like nuclear explosions, we think about chemical rockets, these are all just, potentially a fraction of a percent or maybe a couple of percent converting from taking the energy out of the matter itself. But with black holes, you can take that up to 42%. That is sort of the theoretical amount. And the way that you do this is you drop matter into the black hole, and that matter gets torn up, and you get this enormous amount of energy that gets thrown back out in terms of material that gets hasn't quite gone in and gets spun out as kicked off into space, and then also the gamma radiation that pours out of it. Now, still more than half goes into the black hole. And so you can imagine having a black hole, sort of the most future civilizations, the most advanced civilizations are going to have pet black holes that they drop matter into, and they're going to extract the energy that comes out of it, and they're going to be spinning it up, and they're going to be spinning it down and extracting rotational energy out of that black hole and the accretion disk. It's a mind-bending idea to think about, that black holes are sort of the most useful ways to generate energy in the universe. Christian Borio, does a black hole have a size, or is it just a point of mass? Great question, right? Take a black hole, or let's take something larger, right? So you've got like a star. Star has outward pressure, which is the fusion at the core of the star is generating radiation. The radiation is pushing the star and and that is counteracting the gravity that's trying to pull it inward, and the star has a size. And the more energy that's going on in the middle of the star, then the bigger the star will be, depending on the amount of gravity, but the star has this kind of minimum size. And a white dwarf star, for example, no longer has that fusion in the core. It's no longer generating that energy, and so it collapses down to this degenerate matter, which is sort of held in by this thing called the Pauli exclusion principle, essentially kind of the minimum size that you can mash atoms together before they start to like try to be in each other's space. And a neutron star is even smaller. You've been able to push it even beyond that, and now you're mashing protons and electrons together, and everything is just neutrons. You can get something that's even smaller. And then if you have more gravitational pressure than that, then the whole thing will collapse into a black hole. And the question is there some kind of size, right? Is there another level, but it's inside the event horizon of a black hole and we just don't know what it is? And the answer is we don't know. Maybe there is some other fundamental force, quark pressure or something that we don't understand, that then black holes reach this size and then they don't get any smaller. Or maybe there's a bunch of levels where you can have a black hole that of a certain mass has a singularity or a nucleus that's of a certain size, and then if it's a more mass, then it can overcome that and get smaller. But then the other idea, and this is the one that is kind of bizarre to think about, is that all black holes are just getting smaller and smaller within, the singularity is just getting, and it's getting smaller at an increasing rate forever, infinitely small, at an accelerating rate. We just don't know which one it's going to be, and we may never know. There's no real easy way to be able to perceive inside the event horizon of a black hole. So it may very well be that we're never going to know. But it's a great idea to think about. Balaz Suhajda. Hey Fraser, we use massive cosmic bodies to bend light and magnify distant objects, soon using them to observe exoplanets and their atmospheres as they were long ago. I wonder if it could be possible to find rays of light that have left Earth long ago and through the curvature of space end up returning to Earth with high enough resolution to allow us to look back into the past. Is that completely out of the question? It's mostly out of the question. So you're exactly right that the Earth is giving off photons, reflected photons from the sun. They're going off into space. They are going to continue off in that direction forever unless they run into something. But if there happens to be, say, a supermassive black hole at the heart of the Milky Way, then some of those photons are going to go into the black hole. Some of them are going to get distorted by the black hole, and the occasional one is going to do a 180. It's going to go all the way around the black hole, and it's going to come right back at us and pump back into the Earth. But the chances, like the number of photons that are actually going to happen, is incredibly low. As well, the distance, right? The distance from the Earth to the supermassive black hole is 22,000 light years away. And then again, that same distance to come all the way back here. So 44,000, it's going to be all distorted. So the amount of usable light that you could get is going to essentially be zero. So there will be photons that are going to be making this journey, but not that we would practically be able to detect any of them. Danny Filth. Hey Fraser, if Hawking could have lived a couple of months again, he would have seen what he spent most of his life studying, an actual photograph of a black hole. I didn't mention this in the QA, and I was going to mention it, but then I kind of forgot, but Stephen Hawking died, and that's super sad. I mean, he lived an amazing and long life considering the horrible ALS disease that he had, but he gave so much in terms of science communication. I read some of his books or tried to read them. It was an amazing impact on so many people. So what a treasure to have as a science communicator, as a physicist, and his passing is a real loss to all of us. And you're exactly right. The Event Horizon Telescope has taken its picture. The scientists are collating the data. And within the next couple of months, we're going to see the first ever pictures of the center, the black hole at the center of the Milky Way. Now it's going to be like a blob, right? Prepare yourselves. It's not going to look like anything like Interstellar, but it's still the fact that we're going to get those first images, something that he spent a good chunk of his life trying to understand, feels kind of bittersweet that he won't have been able to have seen it. So farewell, Stephen Hawking. Thank you for everything. Gavin Minton. can dark matter, whatever it is, fall into black holes? If so, would black holes be composed primarily of dark matter since there's more of it than regular matter in the universe? All right, well, I got to preface this, of course, by saying we have no idea what dark matter is. But all evidence seems to be pointing towards this idea that dark matter is a particle. And so if dark matter is a particle, then it would absolutely fall into a black hole. But the thing is that the amount of dark matter that's going to fall into black holes is probably going to be a little lower than regular matter. And I'll sort of explain. So when you've got a black hole and say a star gets too close to the black hole and the tidal forces tear it apart, then the star, all this material will start to fall into the black hole, and it's too much for the black hole to feed on. And so the material piles up into this accretion disk around the black hole and sort of waits its turn and gets ground up and then finally makes its way into the black hole. And sort of this gas and dust is sort of bashing into each other and getting piled up. The problem is that it seems like dark matter, whatever particle dark matter is, it has essentially no cross-section, which means that it doesn't sort of bonk into itself or to regular matter. And, there's been these great observations made, like the bullet cluster, where these huge clouds of dark matter pass right through each other and they don't collide and form any larger concentration of dark matter. While gas and dust does. They collide, they sort of bunch up, and they create this area of larger density. And so the dark matter particles, they're not going to bounce into each other and get ricocheted in and sort of build up into this accretion disk around the black hole. If it's a straight shot, then the dark matter is going to go into the black hole. But if it's a real near miss, then it's just not going to bunch up in the way that regular matter does. So if dark matter it's on a direct line with the black hole, then it'll go in. If it crosses the event horizon, it's going in. But apart from that, it's probably not going to make it into the black hole.
Here's a black hole fact. A black hole with the mass of a mountain would have the event horizon the size of a proton, but it would be thousands of degrees, extremely hot and bright, and would explode very soon.
Ben Appleby, thanks for another great video. Could a galaxy collapse in on itself? If so, what would happen? Would you get an insane-sized black hole or a star? Well, that's sort of the same kind of question as saying, could the solar system collapse in on itself, right? The solar system is essentially perfectly stable because the sun is at the middle, the planets formed out of this rotating disk of material that was around the sun, and then they cleared out their orbits and they keep going. And they are essentially moving on this trajectory that is the leftover momentum from their formation. If they were going any faster, they would raise their orbit. If they were going any slower, they would lower their orbit. Right? They are going the perfect speed to maintain their orbit forever. And that's what's happening with all of the stars in the Milky Way. They're orbiting around this collective center of the galaxy, and they're going to do that for as long as the galaxy exists. There's going to be no force. Now, if you could somehow crash the Milky Way into another galaxy and messed up their gravity so that you would sort of reduce all of that momentum that all of those stars are having, then they would go inward to the middle of the galaxy. But there's no reason to say it. There's no reason why a galaxy would collapse in on itself, just like there's no reason why the solar system would collapse in on itself. Boycott Google? When there's an active galactic nucleus quasar with lots of stuff falling in and piling up, will the layers closest to the black hole be made up of neutronium or even quark star core matter, if that exists? Will the layers a bit further out do nuclear fusion? Imagine it like a two-dimensional huge star with a black hole at the center. For those who don't know, a quasar is essentially an actively feeding supermassive black hole. So imagine a black hole is one at the heart of the Milky Way with 4 million times the mass of the sun. Let's imagine lots of material was falling into that black hole and it was too much for it to be able to feed on. That material would rotate around it and form this big accretion disk. And then these big magnetic fields sort of sweep around within this material, and it causes these jets to blast out of the top and the bottom of the black hole. And so when we see quasars, we see these really bright objects that seem like stars, but what they really are is this jet of material coming off of a supermassive black hole. So in that environment that's around a supermassive black hole that is actively feeding, the quasar, you actually get this stellar material piling up in a way that it's so hot and it's so dense that it does become like the core of a star. And that's why they're so bright. is because you've actually got nuclear fusion. You've got, all of this. These stars have been just like torn apart and mashed up and turned into a star disk around the black hole. And then it all gets gobbled up by the supermassive black hole. But yeah, for a while there, you've got conditions that are like a star, and that's why they're so bright. A supermassive black hole, when it's actively feeding, can let out more radiation than the rest of the entire galaxy combined. Irritable John syndrome. They say there's a supermassive black hole at the center of almost every galaxy. I'm curious, what would be at the center of a galaxy if there was no supermassive black hole? I can't think of anything else with enough gravity to attract all the stars and materials that make up a galaxy. It's important to understand that the supermassive black hole at the heart of, say, the Milky Way is not the anchor of the galaxy. It didn't form and then suck all of the stars and planets and stuff into orbit around it. The supermassive black hole formed kind of in conjunction with the galaxy. And so think of it instead, what really a galaxy is this gigantic halo of dark matter. Right? 90% of it is dark matter. And then there is the regular matter that we can actually see, the stars and stuff. And it is sort of embedded within this halo of dark matter. And this whole thing is rotating around. And these supermassive black holes, they happen to be at the middle because they're very dense and they sort of make their way down to the middle of the galaxy. If there was no supermassive black hole, it wouldn't really make a difference to the galaxy. And actually, astronomers see other galaxies out there that don't have supermassive black holes. So Triangulum is a good example. It's a galaxy, it's very big and bright, and astronomers seem to think that it doesn't have a supermassive black hole. They can kind of tell by the way that the central core of the galaxy functions that it doesn't seem to have a black hole there. And so there must be others, because this is a fairly big one that's fairly close. So it's important to really see, right, that these black holes are not vacuum cleaners that are sucking in material. They are just places with a lot of mass. If you replaced the sun with a black hole with the same amount of mass, all of the planets would just continue to orbit around it perfectly happy. So it's not the black hole that's the anchor to the galaxy. It's the dark matter. Almir Selkovic. Is the event horizon from a spinning black hole round, or does it bulk out like planets or stars? Right, so you're talking about how planet stars, as they spin more rapidly, they flatten out and they become an oblate spheroid. And the answer is yes. Black hole event horizons will flatten out the faster that the black hole is spinning. And one of the really cool things about this is that as the black hole spins faster and faster and faster, this event horizon will flatten out, but it can never spin so fast that the actual singularity will be revealed. This is called a naked singularity. And the reason is because the Einstein's general theory of relativity defines that you can't go faster than the speed of light. And one of the things you can't do is a black hole can't spin as fast as the speed of light. So there is this limit that a black hole can spin predicted by relativity, and that defines how much this event horizon will flatten out. But it's an amazing thought. And of course, when the Event Horizon Telescope comes online, or when that first picture is released, people promise me spring 2019, hopefully, as we see that image, we may be able to detect that flattening out as the black hole is rotating, or maybe not. But it's a really interesting idea to imagine. Ranu Loik. I'd like to know, how do black holes influence space travel? Obviously, if you flew right into a black hole, you would be influenced by your space travel. but beyond that, right, you need to stay outside of the Roche limit of the black hole, and that depends on what your spaceship is made of. But within several astronomical units of the black hole, depending on the mass of the black hole, a supermassive black hole can have an event horizon that's the size of the solar system, while a stellar mass black hole can have an event horizon that's actually quite small, just a few kilometers across. So as long as you stay outside of of the Roche limit of your black hole, then your spacecraft is going to be able to survive. It'll be very uncomfortable. Now, the cool thing about black holes, though, is you could use them for planetary slingshots, right? I guess black hole slingshots. So you could harness the orbital energy of a black hole to kick you faster into some other destination that you want to do around the Milky Way. And if you watched, oh man, what was that movie? Passengers? Is that the one where the guy is on this spacecraft? I'm like, no, you remember? Anyway, there's this movie that came out, I think it was Passengers, where they had this big spaceship and they were traveling and everyone was asleep, and guy woke up this other woman to keep him company, dooming her to a lifetime on a spaceship. But in that, they were using stars for gravitational assist, which I think is a really cool idea. So you could use black holes as well. So as long as you stay, far enough away from them, you can use them to speed up your travel, depending on where you're looking to go in the Milky Way. Hebrucks Hartman. Suppose two black holes are orbiting one another in such a way that their event horizons overlap. Which way would I fall if I entered that zone of overlapping? All right, I'm trying to imagine your scenario here. You've got two black holes. They're orbiting around a common center of gravity. They're orbiting around each other, and their event horizons are overlapping. And in this situation, once you get to this, they are spiraling in on each other, and they're going to merge. And this is how we saw the gravitational waves from black holes colliding into each other. So this situation probably isn't going to last for very long. But the reality is that what a black hole can do to you, it will do long before you get within the event horizon. There are the tidal forces that will tear you apart. There's the radiation streaming out, the gamma radiation coming from the region around the black hole. It's a very bad place to be. But so what's going to happen, right, is that as you get closer to these black holes that are going around each other, is their tidal forces are going to tear you apart, and they're going to separately, whichever one was able to get you a little bit closer, that's the event horizon that you're going to fall into, and then those two black holes are going to spiral into each other and turn into one black hole, and now you'll have one nice big event horizon. So for that brief moment, as the black holes are just slightly overlapping, they're going to be tearing you apart and eating you separately, and then bring those separate parts of you together forever. Well, until they evaporate. Scott Rick, are black holes cold? So black holes are a bunch of things, right? There's the singularity, the part of like infinite density where all of this mass is mashed down into this tiny singularity. Surrounding that is the event horizon, which is the region from which you'd have to be going faster than the speed of light to be able to escape. Of course, you can't escape even if you can go faster than the speed of light. It's just that the escape velocity is faster than the speed of light. But the thing is that this is what Hawking figured out, is that black holes will evaporate. And this is because these virtual particles are appearing right on the surface of black holes and going off into space. And the vast majority of these virtual particles are going to be photons. In other words, they're going to be light, and light gives you temperature. And so if you could look at a black hole's event horizon, you could measure its temperature. And for the most massive black holes, the supermassive ones, they are incredibly cold, just a fraction of a degree above absolute zero. The less massive, the smaller the event horizon gets, the warmer that the event horizon of that black hole is, the more photons that are streaming off of it. And when the black hole gets really small, just as it's about to die, it gets red hot, eventually blasts off as gamma radiation, and then the black hole is gone. So in general, black holes are incredibly cold. They are a tiny fraction over absolute zero. They are way colder than the background temperature of the universe, and it's going to be an incomprehensible amount of time until the universe cools down to the point that you could actually measure the temperature of black holes as being higher than the background temperature of the universe. Colin Forrest. Quick question, Fraser. Hypothetically, can a black hole travel faster than light? I understand it's just a super dense star at its heart, but because of its natural warping of space-time, can this theoretically work as a natural warp drive? No. Nothing can move through space faster than the speed of light, including a black hole, no matter how much it warps space-time. Black holes, at the end of the day, are still a mass attempting to move through space-time, and they can't move faster than the speed of light. What's kind of amazing is that black holes can collide with each other, and one gets kicked out and can be moving, say, relativistic speeds, 10% the speed of light, things like that. Also, black holes rotate. and you can actually see that the rotation speed is limited by the speed of light. So a black hole will spin up faster and faster and faster, but then because of relativity, they top out as how fast they're able to spin. And you can actually detect and see how fast black holes are spinning inside their accretion disks. So no, you can't move a black hole faster than the speed of light, no matter how weird they are.
Kalankit Hasina. Can we detect black holes using Hawking radiation? All right, so for people who don't know, Hawking radiation is this theorized radiation particles that should be seen coming off of black holes. And it's because there's these virtual particles that are popping in and out of existence across the universe. And normally they pop in, they bounce into each other, annihilate, and disappear. But if you can get the situation where it appears on one side of the event horizon of the black hole and another one is on the other side, and one goes into the black hole and one goes out into the universe, then you should see these particles. And the answer is, like, theoretically, I mean, the vast majority of these are going to be photons. They're going to be seen as heat, as light coming off of the black hole. But the problem is the amount of time, how often these happen is incredibly long. We have to wait for quadrillions of years until the universe is cold enough that these supermassive black holes are going to start to evaporate. Right now, it's still just too warm. And so there's just too much particles floating around in the universe and going into the black holes for them to even start to evaporate. But you should occasionally see this situation where a photon of light would come out of a black hole. But it'd be really hard to know that specifically was Hawking radiation and not just regular light that was coming from a region that was really, really close to the black hole, or just the cosmic microwave background radiation. So we're going to need other ways to see black holes.
Andrew Stewart. Is it possible that there is a stellar mass black hole hiding just outside our solar system? I remember before the Planet 9 stuff became big, there was a story about a planet or a brown dwarf between us and Alpha Centauri, still connected to the solar system, but very far out. The smallest possible black hole is going to have many times the mass of our own sun, maybe 5 times the mass of the sun, 10 times the mass of the sun. It's going to have a lot of mass. So if there is a black hole that is near to our sun, it is the dominant gravitational object in our region. We are orbiting that black hole. It's not like it is just hanging out around in the outskirts of the solar system like a large planet might be, or even like a brown dwarf. But a lot of these theories, these ideas that there could be some other object out in the outer solar system, is to correspond with, there's this idea that some of the mass extinctions that have happened a long time ago could have been caused by, say, some brown dwarf, that it's in a really long orbit and it takes 10 million years to come in relatively close to the sun, and it messes with the Oort cloud and sends more comets down inward, and we experience, more comets likely to smash into the Earth. But the evidence really seems to be that there aren't any large objects out there. Astronomers are just teasing out the influence of perhaps some object that is maybe even Earth-sized, that is causing some interaction with the other Kuiper Belt objects out there. And that is sort of where the thinking is going right now. But you never know. Now, one of the really interesting outputs from the Gaia mission was that it mapped out the movements and positions of all of the stars that are around us. And it showed us that, in fact, in the near future, within the next few tens of thousands of years, other stars are going to come actually quite close to the sun, within a couple of light years, which is enough to cause a disturbance to the Oort cloud. So it could very well be that in fact, as the stars are just moving around the Milky Way, they interact with each other and they cause these disruptions on a fairly regular basis. So that's the more likelihood than a black hole.
Michael Murphy. Could the random collisions of molecules cause a black hole to form on Earth, and would it eat the planet? Planet Earth has been here for 4.5 billion years, and we haven't gotten a random black hole to form inside the Earth and consume the Earth. So we can assume that it doesn't happen. And one mechanism that could maybe make that happen is cosmic rays from space. They're these sort of heavy particles that are accelerated to enormous velocities by supernova explosions or supermassive black holes, or in fact, astronomers don't even know, but they crash into the atmosphere with just tremendous velocity. And it appears that the most energetic of these could theoretically compress particles and form microscopic black holes. The issue is that if they did that, they're going to have the velocity. They're going to have this velocity imparted to them by this particle, and it's going to kick the black hole through the Earth and out into space. And so if that process is happening, the black holes are being ejected. And so scientists have thought, well, maybe there are places in the universe where these cosmic rays can crash into something that wouldn't be able to kick out the black hole. And one idea is, say, white dwarfs and neutron stars, which are already incredibly dense, and if the cosmic ray hits them and it kicks out a particle, the black hole won't be able to escape. And so it will gobble up the neutron star from within and make it disappear. And so that's like, there are some natural ideas for how you could get these microscopic black holes to form. But then, of course, the other thought is that these black holes will evaporate almost as quickly as they do form. So far we have no evidence that any microscopic black holes do form in any natural way. The only sort of agreed upon way of you can really call that is that they would be left over from the Big Bang, that there was this moment in the early universe when space was compressed so tightly that there would be overdensities and underdensities, and in some of those overdensities you could have regions that black holes could form at all kinds of masses, Earth-sized asteroid mass, solar mass. And then as the universe continued to expand and grow less dense, then those black holes would be released into the universe. But so far there's no evidence that they exist.
Raymond Ross. If neutron stars are the absolute limit of matter being packed before going black hole, how can we not have more black holes in the past? We go farther and farther back, matter is more packed, so boom, neutron stars, black holes, ramming into each other, more black holes. Did inflation solve this? All the matter we see, which is a tiny percent I know, packed into a singularity or something, then inflation happens and we get neutron stars today, black holes if the mass of the star is large enough. But roll back and I just wonder, are there more black holes that we know? I mean, isn't neutron star state the absolute limit of packed matter before going black hole style? Make some sense for me, please. All right, so the question that you're really asking, I think, is why wasn't the early universe, when it was packed together in this incredibly dense state, why wasn't it just a black hole, right? How could it have been less if it was packed as tight as a black hole? How come it's not a black hole? And the reason is that a black hole is caused when you've got a difference of density. And that early universe was equally dense for maybe ever, right? It could have been infinite in all directions of this incredible density. And then inflation happened and things expanded and it went on from there. And so without those differences in density, you couldn't get that black hole forming. That's the first part. Now it's possible that there were, in the very early universe, there were places where as that initial expansion was happening, and you were sort of after the Big Bang and things were becoming less dense over time, that there were like Holdy folds where you had like a little bit more density. And it's possible that that density could have caused like primordial black holes to be formed, because even though the entire universe was expanding and you didn't have those large density differences to just turn everything into a black hole, you could still have like little localized areas. And this is one of the ideas that astronomers have, is that maybe out there are these primordial black holes, or maybe primordial neutron stars that are left over from the Big Bang. And we could theoretically see them as they evaporate over time. So maybe there's one out there with the mass of a house and it evaporates. And maybe there's one out there with the mass of the moon or the mass of the Earth. And then beyond a certain point, and maybe they served as the seeds of the larger black holes that we see today. But there's no evidence for that right now. It's an idea that some people entertain, but no one is, not many people think that they exist. So that's why everything isn't in one big black hole. Jeremy Weinrich. How can stars capable of collapsing into black holes possibly fight back against overwhelming gravity? Is their matter spread out over a large enough area that the force isn't strong enough to overcome fusion? So stars are the size that they are because they are in perfect balance. there is, of course, the gravity that is pulling everything inward. And that wants to turn the star into a white dwarf, right? Compact all of that matter down into just this tiny little ball where the limit is the bonds that, that atoms won't allow themselves to be packed any closer together. And so then the question is, what's the force that is pushing outward to counteract that inward force? And the answer is light. It's called light pressure. And so you've got the fusion in the core where, because of all the pressure from the gravity pulling inward, you've got atoms of hydrogen being compressed together into atoms of helium. And then that process releases photons of gamma radiation. And then those photons bounce around inside the star and they eventually make their way out to the outside of the star and then out into space. And we see that as the light from the star. But that process of those photons inside the star push against the gravity that's pulling it inward. And so for massive stars, they generate a lot more fusion in their core. They generate a lot more radiation inside of them, and they can be bigger. And then you get these interesting situations like a red giant, where the future of our sun again, where you've got this situation where it's producing a lot more radiation, and so it makes the star get a lot bigger. It actually makes it cool down from its visual temperature because it's gotten so much bigger and more spread out. And other situations where stars could be smaller, like a red dwarf star. So really, every star that you ever see is in this perfect balance. Gravity pulling inward, light pushing outward, and it is as big as it needs to be.
Here's a black hole fact. Black holes can never split. They can only merge.
Leukemania. Are they going to try to image the supermassive black hole at the center of M31? Or all of the galaxies in our local group for that matter? When James Webb gets launched and activated, will that be of any help in gathering these types of images? So that was the other main question that I got a bunch of, which is why aren't they going after all of these other galaxies as well? M31, the Andromeda Galaxy, the one that is rushing towards us right now, that supermassive black hole is 100 million times the mass of the sun, while the one that's in the Milky Way is only 4.1 million times the mass of the sun. So it's definitely a much bigger one. But the problem is that it is also a lot farther. It is 2.5 million light years away, while the one that's inside the galaxy is only 25,000 light years away. So what is that, 100 times as far away? Much farther, right? And what was the sort of the fluke of luck is with M87, the one they took the picture, it is vastly farther away, 55 million light years away, but it is gigantic, 6+ billion times the mass of the sun. And so on the sky, when you sort of like, if you just look in the sky and look for the big black holes, the one at the heart of the Milky Way is the biggest visually from our perspective, and then the one at M87 is the second biggest. But based on their success with M87, I really wouldn't be surprised if they then turn their telescope on other targets and start taking lots more pictures of whatever they can reach, and then just see if they can learn any insights about these various supermassive black holes. And it might be that the one at M31 is right within the limits of what is possible. So I wouldn't be surprised in the next couple of years to see more images, more attempts, as well as, of course, the one that's in the Milky Way. I can't wait. Bob. If the life of the universe from its birth to the death of the last black hole was a calendar year, what date and time is it now for us 13.8 billion years in? Right, so if you look at the age of the universe right now, 13.8 billion years, that's what, a 13 followed by 9 zeros, right? Yeah, so 13 times 10 to the power of 9. The last black hole is expected to evaporate after a 1 times 10 to the power of 100. And now that's not just 10 times as long. That is much, much, much farther. We're dealing with exponents here. So if you were to think of like the age of the universe so far in a calendar year, we're not even in the first nanosecond of the calendar year compared to the amount of time that we're looking at into the far, far future. We're not even into the first day when you think about the age of things like some of the red dwarfs and white dwarf stars are going to cool down to the background temperature of the universe. So we are absolutely in the earliest stages. Now, you posted your question on YouTube and a couple of other people posted some ideas. And one thing that and I apologize who gave the answer, but it was a great one, which is that if it's the Big Rip, this idea that the accelerating expansion of the universe is going to tear apart the universe at an atomic level, it's estimated that that is going to happen in the next 80 billion years or so. So actually, we could be a quarter of the way through the calendar year if the universe will die as a Big Rip, as opposed to the heat death. And if it's the heat death, then the universe will last a long, long, long time. We can't even comprehend. We barely can do the math to figure it out. Big Rip, we're kind of a quarter of the way through. I'll let you know which way it turns out once we get more data. Carl Ivory. If a black hole is so massive that not even light can exit it, how fast does something have to travel to exit? What is the escape velocity of a black hole, if any? Right, the way I always describe a black hole is it's a region, right? There's like, the event horizon is the area where the escape velocity is the speed of light. And so because the escape velocity is the speed of light, it's black because it is literally absorbing all radiation that's falling into it. It's absorbing its own radiation. And so you would think, well, you could just go faster than the speed of light. And in fact, you could calculate the speed to go. But the problem is that actually a black hole tangles up space-time so much that all pathways lead to the singularity. They all lead back down into whatever lurks in the middle of a black hole. And so there is no speed you could go. If you could go faster than the speed of light, you would still end up in the singularity. Once you cross the escape, once you cross the event horizon, there's no coming back out, even if you can go faster than the speed of light. So don't do it. Stay outside of all black holes. Gene Stealer UK. Fraser, are gravitational waves being created all the time or just with very large collisions? How is it possible for LIGO and the other laser interferometer telescopes to differentiate between background noise caused by stellar collisions, or is that just not a thing that we have the sensitivity to detect now or maybe never at any point in the future? Right, so every single moving mass in the universe is generating gravitational waves all the time. As you walk, you are generating gravitational waves. But the gravitational waves are really subtle and there's no way really for us to detect them. It's only with the most extreme events that we can actually detect the gravitational waves. And in fact, we can't even detect supermassive black holes merging into each other because that process is too slow. It has to be these medium-sized mass black holes that are spinning around each other, and in the final moments, just before they collide, you get these gravitational waves. And now we're starting to be able to detect neutron stars. So as the sensitivity, as this new science gets developed, the sensitivity of the detectors are going to get better. The kinds of extreme events they're going to be able to detect will start to come down. They'll be able to detect more massive black holes coming together more slowly. They're going to be able to detect smaller mass black holes coming together in the way that they do. They're going to be able to detect black holes eating neutron stars colliding with each other in different ways, and maybe even neutron stars which are off axis and just sort of wobbling as they turn. So that's sort of what the future holds. As we discover more, I can't wait. Jonathan Hobbs. If two neutron stars collided, would they always make a black hole? If they didn't make a black hole, is it 100% of the mass from the two bodies that collided be captured in the remaining body, or does some escape from the sheer energy during the collision and gets blasted out into space? I'm a huge fan of the show, and I'd really like to know what you think. So we talked earlier about this idea of the kilonova, that at one point, two neutron stars can whirl around each other and collide and they detonate. And what remains? We know that tons of gold and other material was seeded out into the universe, so definitely something gets out. And astronomers are still trying to figure this out. Again, this is all relatively new. We've only seen one, maybe a second kilonova. And what appears to happen is they either collide and form a new neutron star. Enough material gets blown out, they come together, Your remnant is another neutron star, or maybe the two collide, you add up their mass, and now you get a black hole. And this is something that astronomers are still trying to work out. And the only way they're going to be able to do that is to see more examples. Right now, we've only got the big one. We want more examples of kilonovas so that we can study them more carefully and start to piece together what happens. What is the object that remains when these two neutron stars smash into each other? Neutron star or black hole? Stay tuned. Devo. Can a star and a black hole orbit each other and create a really weird binary system thing? They absolutely can. In fact, this is the way that astronomers have found black holes in the past. Because a black hole, right, is so powerful, so dense that nothing, not even light, can escape its pull. And so how do you see something that is invisible? And you don't. Right? You can maybe detect if it's got some kind of disk of material that's swirling around it, and that's when it's got some other star that it's feeding off of. And so you get this situation where maybe back in the day there was like a really massive star and then maybe a smaller star like the sun. And the two stars were in a binary system around each other, and then the really massive star exploded as a supernova and then collapsed down as a black hole. And now you've got a black hole and a star like the sun orbiting around each other. And so material swirls off the star and goes into an accretion disk around the black hole. So it's like this disk of material that builds up around the black hole because it's like too much material for the black hole to be able to eat. And so it piles up like water swirling around your drain. And that gives off illumination, that gives off light. And so astronomers are able to detect this. As well, if you've got, say, the black hole and the star in a sort of a plane where they're passing in front of each other from our field of view, then the light from the star is going to change as the black hole is passing in front. So you get some really interesting situations. So yeah, it can absolutely happen. And there are plenty of these examples out there. X-ray binaries, I think they're called. And I would love to be able to see one of these up close. Can you imagine what it would look like with a black hole and a star swirling around and this? I'm sure Chad's going to put up a really cool picture to show you, or an animation to show you what it'll look like. But it's a scenario. Francois Morin. Hi, Fraser. I heard that SO2 orbits the black hole at the center of our galaxy every 16 years. Could we predict when this star or others will collide or be swallowed by a black hole? Any chance that I could witness this event? Astronomers use very sensitive, very large telescopes to be able to perceive the supermassive black hole, the region around the supermassive black hole at the heart of the Milky Way. They need some of the biggest telescopes that have ever been built that use infrared radiation to be able to peer through the gas and dust to be able to see that region. And they can see stars and gas clouds and things like that are interacting in the environment around the supermassive black hole. But the reality is that you could smash all kinds of stars into the black hole. Our black hole could turn into a quasar, which is some of the brightest objects across the universe, and we wouldn't even see it, right? It wouldn't even be visible in our night sky as a bright source, even if it was as bright as a quasar that we see in other places. And it's just because it is so far away. And it is shrouded by gas and dust. So unfortunately, no matter what happens to the supermassive black hole, you would never be able to see it. Even if it doubled in brightness, tripled in brightness, went 75 times as bright, you need very special instruments to be able to see it. Vivek Sharma. Now, we all know that black holes bend light, so there may be some black hole out there perfectly placed in such a way that light from Earth reaches it and gets bent due to gravity, and instead of falling inside the black hole, just does a half rotation of black hole and shoots out behind the Earth like a tangent. And then it's possible to see how the Earth was millions of years back, considering we have a great telescope. Yeah, that's like guaranteed. That when you look at a black hole from any angle, you are seeing the light that is emitted from you that is going around the event horizon of the black hole and being emitted in the opposite direction. In fact, that gives black holes part of their shape. And there's a great video by Veritasium where he sort of shows you what the different layers that you see of the black hole and sort of leading up to those first images of the supermassive black hole at the heart of M87. And I'll put a link to that in the show notes because it's such a great, it sort of shows you what each piece. And there's one layer where light is going around the black hole and coming back. Now, of course, the problem is the number of photons is so small. So when you said you need a great telescope, you need a ridiculously great telescope. You need the perfect telescope that can see every single photon and turn that into an image. And the reality is that we will never have a telescope that powerful to be able to do that. But it's a great idea, great thought process. And maybe if you're closer, then maybe you could start to see something, but then you wouldn't want to be that close because then you'd be getting torn apart. So, but it's a great thing to think about. Vasilij Milicevic. Are there any theories of what material black holes are made of? If it's so dense in there, it must be very high on the periodic table. The short answer is that we have no idea what's inside a black hole, what's inside the event horizon of a black hole, right? We kind of understand what a neutron star is, where the pressure and gravity is so strong that it's able to overcome the fact that protons and electrons really don't want to be near each other, and it smashes them together and turns them into neutrons, mostly in a neutron star. And that is like the limits of our understanding of what matter can do when it's incredibly compressed. Now we see black holes, so we know that there's another stage, there's something else. But the problem, of course, is that the escape velocity of the gravity is so strong that nothing gets out. No light gets out, no matter gets out. There's no way to see what's going on in there. And so astronomers have tried to calculate using their theories. And the best theories that we have for particle physics, for quantum mechanics, falls apart when you're in the environment of a black hole. And so maybe there's like a thing inside the event horizon. It's some object that is more dense than a neutron star, some future phase that material can go into that is more dense. And it's like some rapidly rotating something. But maybe it just continues to compress forever. So it's whatever forces have stopped, there's nothing to stop it from continuing to just compress and compress and compress and compress. And it just does that forever, faster and faster and faster. But all that mass is still there, compressed into this infinitely small amount of space. Astronomers refer to this as the singularity. And the reality is they just, right now, we have no idea. Anyone who figures this out gets to have a Nobel Prize. Desiese. Our galaxy is warped because it collided with another galaxy. Could its supermassive black hole be out there waiting to be discovered? Fairly recent news that's coming out now, people have done fairly accurate estimates of the shape of the galaxy. And of course, that's really difficult because we are inside the galaxy. So how do you measure the shape? And it's very difficult, but they've been able to work out that in fact the galaxy isn't this flat disk, it actually has a slight warp to it, which means that the Milky Way interacted with some other galaxy in the ancient past. Probably not like a full-on Milky Way Andromeda collision, but more like we have absorbed various dwarf galaxies. And some of those dwarf galaxies probably had supermassive black holes in them. And what happened to those supermassive black holes? Well, either they merged with a supermassive black hole at the heart of the Milky Way, or they were kicked out into deep space, or maybe they're still orbiting around within the Milky Way somewhere. Where are they? We don't know. Now, you don't have to be worried about this, of course, right? The sun has been orbiting in the Milky Way for 4.5, almost 5 billion years, and no big black hole has come close enough to disrupt the orbits of the planet. So we can kind of assume that the chances of this happening are very low. But maybe over time, as we do more and more surveys, maybe as the Gaia spacecraft explores more and more of the Milky Way, we will start to notice the ripples of other supermassive black holes moving through the Milky Way and shifting stars out as they move through their wake, which is a really fascinating idea. So all hail Gaia. Steve Peary. Hey, Fraser, you mentioned gravity waves and lasers looking for them. Could future humans send messages very long ranges using gravity waves? What speed would be possible for those waves? Good news. Whenever you move, you are generating gravity waves. And anybody who wanted to would be able to use a very sensitive gravity wave experiment, maybe some super laser system, and detect your movements just by how you are rippling space-time as you move around. Of course, the amount that you are rippling space-time is infinitesimal. It's essentially impossible to detect. It's only when you smash black holes together, right? When black holes are about to collide and they're winding around each other and they're just, tangling space-time up into a knot. Only then can we detect the effect, the ripples of space-time. Now, there was the impact of 2 neutron stars back in 2017. And what this did was this told astronomers, because they were able to see the explosion and they were also able to detect the gravitational waves, it told astronomers that gravity moves at exactly the speed of light. So, in other words, if you wanted to use gravity waves to somehow communicate with somebody, those gravity waves would move at the speed of light. And so it's not really a faster way of communicating.
Here's a black hole fact. You can describe a black hole with only 3 numbers: the mass, the charge, and the spin. All of the other information that went into the black hole is destroyed. And so if you had a black hole made of a dead star, or if you had a black hole made of rubber duckies, it would be exactly the same thing.
San Lin Hatet. Fraser, could you explain why the Big Bang didn't recollapse into a black hole at the singularity? We've done videos about this, and I think I've answered this in a previous question show, but sometimes a question just keeps coming up again and again. So, this is for the next generation of Fraser Cain question show watchers, which is, in order to have a black hole, you need to have a difference in density, an overdensity in one place and an underdensity in another place. And in the early universe, the whole universe was roughly the same density. So there was no place that one region could compact down into a black hole and then suck the rest of the universe in. The whole universe was sort of pulling on itself equally as it was expanding away from itself, and so it never got the chance to actually pull into a black hole. The other thing, and this is sort of important to think about as well, is that the universe was not a ball, right? At the very point of the Big Bang, the universe was not this sphere that went kaboom and exploded, and then at any point it could have gotten a certain point and then just imploded on itself again and turned into a black hole, right? The universe could have gone on forever. Even before the Big Bang, or right at the Big Bang, the universe still could have been infinite. So, imagine matter compressed down to the point that atoms lose their atomic bonds and everything is just this soup of quarks, gluon, this plasma everywhere, and yet it could have gone on forever. Infinity in all directions. That's what the universe could have been back in the beginning. And so it's very hard to imagine turning infinity into one black hole, a finite black hole in one place. So you need to have this overdensity and to be able to have a black hole form. And the universe was just too even for this to happen. Scott Whedon, I have a question for you next show. How can astronomers rule out the mass of the black hole at the center of the galaxies as being the missing matter that keeps all of the stars from flying off, rotating at the speed that they go around? One of the great discoveries about 50 years ago was this idea that galaxies are actually rotating too quickly for them to be able to hold. And in fact, if you spun up a galaxy at the speed that they're rotating with the mass that they have to work with, they should be tearing themselves apart. And so the extra mass that is acting as an anchor to hold the whole galaxy together is this idea of dark matter. And dark matter has since been seen in, or, not seen in other places to sort of, in terms of the way that it causes light to bend in space as it's moving over vast distances, and other sort of signals seen in the cosmic microwave background radiation. So astronomers have known for a long time that there's more to galaxies than we can see. And so one possibility is that, in fact, maybe it's this supermassive black hole that's at the heart of the galaxy. Well, so one of the weird things about galaxies is that when you look at the stars, so let's imagine the solar system, right? When you look at the planets, they're going around the sun. The planets that are closest to the sun, right, Mercury, go the fastest. And then you've got, Venus goes a little slower and Earth goes a little slower. And as you get all the way out to Pluto, it's moving very slow. And it goes a very long way around as well. But when you look at a galaxy, the motions of the stars are not the same. All of the stars are moving at the same speed, regardless of where they are in the galactic disk. So you've got the stars, say, at the close to the center of the galaxy, moving at, if you just could measure their velocity in kilometers per second. And then as you move out to say wherever the sun is, it's moving at roughly the same speed. And so from this, astronomers knew that what we can see is not what truly is, that there must be this big halo of mass. And then in fact, this whole thing is spinning and the stars are moving within it. And the reality is that these supermassive black holes, even though they're really massive, they're only 1% of the mass of the galaxy, right? The supermassive black hole at the heart of the Milky Way is 4.1 million times the mass of the sun, but that's only 1% of the mass of the entire galaxy. So it doesn't act like an anchor to the galaxy. And so the point I think that's great, right, is that astronomers thought of that. They thought maybe there's some concentration of mass at the core of a galaxy, and that acts like the mass of a star to cause all of the stars to orbit around it like planets. And yet the speed, the motions of the stars didn't match up with what they expected to see. And so they had to essentially search for other ideas. Tamid Hussein. Everyone says that black holes evaporate. What are the leftovers of black hole evaporation? This idea of black hole evaporation, right? This is one of the amazing ideas provided by Professor Stephen Hawking, and that there are these virtual particles and they appear near the event horizon of black holes and they remove its mass. We've done a bunch of episodes about this, but over long periods of time, that's not exactly what it really is. It's really that you've got sort of particles, vibrations, there's more to it. But the gist is that black holes can evaporate. And so you get this situation where the black hole over vast periods of time disappears particle by particle, and its temperature rises. And as its temperature rises, it actually gives off more and more particles. So a black hole can eventually be, say, I forget what it is, about the size of the moon and be about room temperature. And then it just gets hotter and hotter and hotter. And so a black hole might have the mass of my house and be as hot as the sun. And eventually, as it gets hotter and hotter, it's giving off photons, and the photons are in the form of really high energy, high temperature particles. So you're seeing gamma radiation blast off this small object. And then in the very end, when it's almost out of particles, it sort of blasts off all the gamma radiation and then it's gone. So there is nothing left over when a black hole evaporates. Master 144th. Does Sagittarius A star spin the same direction and along the same plane as the Milky Way? Is it what causes the Milky Way to spin as it does? That is such a great question. And you sort of assume it, right? But then you got to say, well, how do you know? So yes, the supermassive black hole that's at the heart of the Milky Way does spin with the same axial tilt as the rest of the galaxy. So the question is, how do you know? And so what astronomers did was they used really powerful X-ray telescopes to scan the area around the supermassive black hole. And the problem, of course, is the supermassive black hole isn't actively feeding. And so you can't really see what's going on there. Now you can have stars going around it, but that doesn't define the spin of the Milky Way's black hole. But astronomers were able to see twin jets, really faint, but twin jets of material coming out of the black hole. And these align with the north and south poles of a black hole. And so what astronomers found was that the direction of these jets were parallel to the axial tilt of the entire galaxy. In other words, the rotation of the black hole is the same as the rotation of the galaxy. But the question is, the other half of your question, well, I guess the second part of your question was, does it go in the same direction? And I don't know. I really tried to figure this out, and I couldn't find anybody who had a real clear answer. And part of it might be is because nobody does know, but if somebody does know, please let me know. But the question is how do you know the direction that a black hole is spinning? Right? And the way you tell is that you look at the accretion disk that is around a black hole. The gap in between the black hole's event horizon and the accretion disk tells you which way the black hole is spinning compared to the way the accretion disk is spinning. So you can tell which direction an accretion disk is spinning by measuring the velocities on one side and measuring the other, measuring the Doppler shift, and that tells you which way the accretion disk is spinning. And then you measure the gap between the black hole and the accretion disk. And by measuring that gap, if the accretion disk is very tight, it means the black hole is spinning in one direction. If the accretion disk is very wide, it tells you that the black hole is spinning in the opposite direction. And I don't know if there's enough material that is going around the black hole for them to figure that out. So again, please, if somebody, I couldn't find a science journal, I couldn't get an answer on Twitter. So if somebody has an answer, I would love to hear it. Does the black hole cause the galaxy to spin? No. The supermassive black hole is like 1% of the mass of the galaxy. It's the gigantic halo of dark matter that is around the galaxy that is causing the whole galaxy to spin. The black hole just happens to be the most dense, most massive object in the entire galaxy. And so it happened to sink down to the very middle of the galaxy. And that's what you see wherever you look out into the universe. But the black hole is not like the anchor and the thing that is dragging the galaxy around. It's just one other object in the galaxy. Rocco V. 1% of the mass of the galaxy? That's huge. No way that's right. Yeah, last week I said that the mass of the supermassive black hole at the heart of the Milky Way is just 1% of the mass of the galaxy. The bulk is actually the dark matter halo that surrounds the entire galaxy. And a bunch of people pointed out that, in fact, the mass comparison of the supermassive black hole to the rest of the galaxy is way less than that. So the exact number, I ran the math, I took the mass of Sagittarius A star, divided it by the mass of the Milky Way, and multiplied it by 100 to get the percentage. And the number is 0.00084%. So it's a fraction of a fraction of a fraction of 1% of the mass of the Milky Way. So I won't make that mistake again. And it's amazing how little. So the supermassive black hole is not the anchor of the Milky Way. It is not what everything orbits around it. It is just one, very important, very massive chunk of the galaxy, but it is not what everything is orbiting around. Sicknicks. Why is a black hole still a black hole if it loses enough mass to go below what a black hole could form in the first place? Like, why do stellar black holes not evaporate and turn into an object without an event horizon when they get below the mass of an object that a black hole will be formed? Black holes are defined by their density. So as long as you've got a bunch of material compressed into a size where the escape velocity from this object exceeds the speed of light, you've got a black hole. And once it becomes a black hole, it will never not be a black hole. Now, this idea of Hawking radiation, that black holes can evaporate over vast periods of time, just means that the black hole is going to have less and less mass over time. But it will still remain a black hole until the last moment. Until it's just a small collection of particles, it's incredibly hot, it gives off a blast of gamma radiation, and then it's gone. So there's no point where it's like it's holding itself in and then it reaches some minimum mass and then it pops up into like a neutron star or something like that. Once it goes black, once it turns into a black hole, it is never going to return to the laws of physics as we understand them. Vegeta AFH. Hey Fraser, will James Webb be used to view the black holes that were recently viewed? The image of the black hole, M87, which was done by the Event Horizon Telescope, was this worldwide network of radio telescopes that all aligned at the same time and gathered their data at the same time. And then computers processed that and made a telescope essentially with a baseline, with a size of planet Earth. And the important word that I said there was that they were radio telescopes. James Webb is an infrared telescope. Although they're still photons, they're still on the electromagnetic spectrum, they're different kinds of, different wavelengths of photons. And so James Webb can't work with the rest of those telescopes as part of this worldwide network. It would have to be a radio telescope in space to be a part of it. Or the Event Horizon Telescope would have to be a network of infrared telescopes. And then being able to align the wavelengths in infrared is so much more difficult than doing it in radio waves. But I'm sure that James Webb will be used to probe the cores of galaxies that are known to contain supermassive black holes. It was the Hubble Space Telescope that helped astronomers understand that there are these supermassive black holes at the heart of almost every galaxy. And so James Webb will take those observations to the next level. And again, because the light is getting red shifted as these galaxies are moving faster and faster away from us, it will be able to perceive and observe these galaxies that are really far away and a lot less evolved than the current state, right? It's going to be looking back in time. And so what will we say be looking at the supermassive black holes and galaxies as they looked a billion years after the Big Bang, as opposed to closer. So it will be looking at black holes, but it won't be doing the same work it can't be part of the Event Horizon Telescope. That's a whole other project. John Gallant. Hello, Fraser. With the advances in technology around gravity waves, will there become a time when the detectors can predict a merger well enough in advance to alert all the other observatories, like in 30 minutes, look at this region? One of the most incredible things about the discovery of the kilonova, that was these two neutron stars that spun around each other and then they collided. Well, one was that we saw the burp of gravitational waves as they were just about to collide. And then the moment that they did, we also saw the flash of radiation at the same time. And that proved once and for all that gravitational waves and electromagnetic radiation, light, move at precisely the same speed. The speed of light. But incredibly, right, we saw this buildup of gravitational waves, this chirp as these two neutron stars were spinning around each other, and just seconds before they actually collided, they were causing so many gravitational waves. That's what astronomers were able to detect. So you can imagine some time where the gravitational wave detectors get a lot more sensitive. Instead of being able to only detect the waves in the last couple of seconds, maybe they can detect them in minutes or hours or days. And you could get to this point where you can inform the visible astronomers that an event should be observable in this region of the sky. Turn your telescopes, wait, there it is. And maybe even say with colliding black holes, maybe it's invisible, but maybe there's radiation swirling around them, and maybe that radiation collides, the accretion disks of material around the black holes as they come together, and that releases a flash of radiation. And maybe that's a way that astronomers could confirm gravitational waves or colliding black holes, things like that. So there's a ton to be learned, and there's tons of advancements in this high-speed astronomy that gets done. One of the most fascinating instruments out there is this thing called SWIFT, and it's a gamma ray observatory that scans the sky all the time on a regular basis, and the second that it detects a gamma ray burst anywhere, it turns and then observes the gamma ray burst, because you got to act quickly. And so I'm really looking forward to sort of the new gravitational wave observatories extending the period that they're able to detect these impacts, and then the collaboration between gravitational waves and other forms of astronomy, this multimodal form of astronomy. It's a really exciting time to be watching this stuff evolve. Podkova. Is there a known or theorized phenomenon that could reflect Earth's light back? So, for example, if you had a large enough telescope, you could see dinosaurs in the flesh. Obviously, you need a telescope far beyond reality, just a thought exercise. So, you're using this idea that as we look out into space, we're looking backwards in time. And if we look far enough away, we could look at some object or aliens looking at us from 65 million light years away would see dinosaurs roaming the Earth. And there is something out there that would provide this function for us, and that is a black hole. So black holes, the gravity well on a black hole is so strong that it warps space-time. And when you look at a black hole, you're actually seeing when you see what looks like the event horizon, you're actually seeing light that's being completely curved around the black hole. And some portion of the light that you're seeing is reflected directly back from the direction that it came. So in theory, right, we could look at a black hole that is 32.5 million light years away, that we could see light that is being reflected from Earth. So Earth's light the Earth is reflecting light from the sun. The light is going out into space. It is making its way around a black hole, and it's coming back to us, and we would be able to look at it and see how the Earth looked 65 billion years ago. But as you said, it's a purely theoretical exercise. We just have no way to resolve objects that small, that far away. Earth-sized worlds orbiting in galaxies 30 plus million light years away, that would be pretty tough. So theoretically, but practically no. Sassy Plu. Do black holes come in a multitude of shapes with a variety of dimensions like that of galaxies, or is there just the one commonly drawn black hole that's more or less hole-like? Well, there's this famous quote that black holes are neither black nor holes, right? They're not black because they're actually essentially absorbing all of the radiation that's falling into them, and they don't emit any light whatsoever, so they're kind of invisible. And they're not holes. That graphic that you see of a black hole that sort of looks like this funnel that's going down is sort of it's trying to give a representation of how space-time is warped, but it's really only doing it in 2 dimensions. The best idea of what a black hole is, when you sort of think about it, just take the Earth, right? And think about the gravity on the Earth. Everything on the Earth is sort of pulling towards the center of the Earth. Now, imagine if the Earth had way more gravity, and you still, everything would be pulling towards the center of the Earth. And imagine if Earth had so much gravity that light couldn't escape. It was that strong. And now you couldn't see it because the light wasn't there, but still you'd have all this, right? All of this incredible, intense gravity pulling into this one central spot, the singularity. So the thing that does change how a black hole might appear depends on its spin. So a black hole that isn't spinning is going to be essentially a sphere, a perfect sphere. But as the black hole spins faster and faster and faster, the event horizon, sort of that point where light can and can't escape from the black hole, that flattens out. And so as a black hole reaches literally the limits that are predicted by Einstein, as it starts to approach, I forget what the number is, like some significant portion of the speed of light, the event horizon has flattened out, but it can never flatten out at the point where the singularity will actually be revealed. And that is sort of the limits of it. And so black holes, if you could get really close and see how they might look, they would look different levels of flattened, rotating spheres, oblate spheroids, depending on the speed that they're rotating. But apart from that, there's no real way to distinguish them apart from the mass of the black hole, and that defines the size of the event horizon. Mr. Villalobo, can dark matter get so dense as to create a dark matter version of a black hole? So the first caveat, of course, is that we don't know what dark matter is. So can dark matter be a black hole? Well, we don't know what it is. So maybe if it's the kind of thing that can be turned into a black hole, but we don't know what it is, but maybe it can't if it turns out to be a thing that can't be turned into a black hole. So we don't know. However, here's what we do know, right? Which is that, dark matter was originally discovered a long time ago, in that its presence was detected. Astronomers were calculating essentially the rotation speed of galaxies, and they were looking at how fast the stars were rotating inside the galaxy. And what they found was that, you would expect, like say here in the solar system, that the planets all go around the sun at different speeds. Mercury goes the fastest, Earth goes slower, and Pluto, maybe a planet, maybe not a planet, goes the slowest, right? But in a galaxy like the Milky Way, the stars are all going the same speed. If they're going close to the core of the Milky Way, if they're going far away from the core of the Milky Way, they're going roughly the same speed. And the only way that astronomers could explain that is if you surround the entire galaxy in this halo of dark matter, right? That in fact, the matter that we can see is only about 1/5 of the actual matter that is inside the galaxy. And that's serving as this gigantic gravitational anchor that's holding the whole galaxy together. So, and so astronomers said, okay, so maybe it's a particle, or maybe it's just gravity working at a scale that we don't understand. But then over the decades, science did more and more analysis. They did other kinds of surveys. And one of the most useful ones that they've done is this idea of gravitational lensing. So they look out into space and they look at how the light from distant galaxy clusters is getting distorted by the mass of stuff that's closer to us, right? And so the light actually takes this sort of curved path, this distorted path, like when you're looking down a hot road and you can see how the road is sort of wiggling and wobbling. The road isn't actually doing that, but the light is distorting the path that the light is making, right? The heat on top of the road. So astronomers were able to map out the quantity and the distribution of this dark matter, which started to move away from this idea that it's just we don't understand gravity at the largest sizes, but that there actually is some kind of particle. But then astronomers said, okay, so what kind of a particle is it? Is it something like that we already understand, or is it something else? We obviously can't see it, but does it interact in any other way? And so astronomers looked for examples where dark matter was interacting with itself. And so when you look at, say, two clusters of galaxies and they smash into each other, right? The stars, because they're essentially just little point objects, they pass right by each other like two gigantic swarms of bees. But the gas in the galaxies, that actually piles up in the middle. And so you'll get this example where these two galaxies pass right through each other, the stars pass right through each other, but the gas piles up in the middle, and you get all of this sort of heated up gas that's in the middle. And so astronomers said, will the dark matter do the same thing? Will it pile up in the middle, and would we be able to detect it? Because they can see, again, that distribution. Watch how the light is being distorted. And what they found is, no, the dark matter does not bump into each other. It passes right through. And so that tells astronomers that probably the cross-section of whatever this particle is very small. Essentially, dark matter can pass by dark matter and not bounce into each other. So this is a long way of coming back around to this idea of, can you get dark matter into a black hole? And so while dark matter doesn't seem to interact with regular matter through any of the other forces, through electromagnetic radiation, through any of that, the one thing that it does do is gravity. It absolutely interacts with gravity. And so in theory, right, if you had a large amount of dark matter and you compress it into a small amount, it would have more and more gravity and more and more gravity, and eventually it would get so much gravity that it would turn into a black hole. And there's no reason to think that dark matter couldn't fall into a black hole and add to the mass of the black hole, based on, the amount of gravity that it's able to produce. So that's kind of like the current thinking. But again, we still don't know what it is. And so more evidence will be necessary to finally know once and for all what kind of particle it is, how does it work, how does it interact, and could it indeed turn into a black hole?
Here's a black hole fact. When a star gets too close to a black hole, it is torn up into this long stream. Now, half of the material can fall into the black hole and the other half is thrown out into space. This is a tidal disruption event, and it can give off as much energy as the rest of the galaxy combined.
Michael DeMaria. Great episode, but Dr. Hinkle didn't answer the actual question about having a solar system of planets orbiting a non-star object. So the rather cool question remains about a solar system orbiting a massive object that isn't an actual star. We'll love to see that one get answered. Sure. So in last week's question show, the question was, could you get essentially a planet forming without a star? And this is this idea of a rogue planet. And the answer is absolutely, right? Wherever you have gas and dust collecting together, it's going to get to a certain point. It's going to have hydrostatic equilibrium. It's going to form some kind of spherical object. And if it's not near a star, then it's just going to be a planet. It might be a brown dwarf, or it might be like a Jupiter-sized planet, or maybe even something a little more rocky, and it'll just float in the Milky Way on its own. But the question is, could you get planets around something that isn't a star? Well, the only other objects you could have would be some kind of degenerate star, like a white dwarf or a neutron star or a black hole. And each one of those were a star in the past. So what you would probably have is you would have like a star, like a very large, very massive star, lives its short life, explodes as a supernova, and then collapses into a neutron star or a black hole. And any planetary system that was around it would suffer damage. In some cases, they would just be obliterated. The planets might get consumed as the star is expanding out to form like a red supergiant, and then it collapses down into the black hole. But in theory, if the planets were far enough out when the whole thing formed, and if they could survive the shock wave from the supernova, then you would still have objects orbiting around the black hole or the neutron star. And so there's no reason why it couldn't happen. You just wouldn't want to live there. The other thing that's kind of neat is you can imagine things like, say, a star like our sun turning into a red giant and then dying as a white dwarf and cooling down. And in many cases, as the shape and the density of the star changes, the planets will shift on their orbits. And so you could end up with a white dwarf star ending up with planets orbiting around it inside the habitable zone where they could still remain warm enough for liquid water to be present over fairly long periods of time as the star slowly cools down until it becomes the background temperature of the universe. But you would need very special conditions for that to happen. But it's certainly possible. I think planets have been potentially detected around white dwarfs, or the rubble of planets crashing into each other around white dwarfs. So there's hope, even after the sun dies. Master Pack. Neil deGrasse Tyson mentioned that dark matter interacts with nothing, even itself. Therefore, it can't be concentrated and ergo be a black hole. Yeah, so last week I talked a bit about black holes and dark matter going into them, and I was sort of going along in the right direction, but I sort of didn't continue that line of thought, and so I really should finish this. We talked about dark matter and sort of the search for dark matter particles and the fact that astronomers are very certain that they are some kind of particle that has no cross-section. And what that just means is that particles of dark matter don't bounce into each other in the way that gas bounces off each other and the way stars would smash into each other, right? And so when large clouds of dark matter pass each other, they pass through perfectly without bumping into each other and slowing down and creating some kind of concentration of dark matter. And so what that means practically is if you put a black hole into the middle of a cloud of dark matter and the dark matter would be affected by the gravity, it would be orbiting around the black hole. But you wouldn't get these bounce offs, these interactions that happen with regular gas. And so when you see like an accretion disk around a black hole, that's because all of this mass, all of this matter, this hot gas, is bumping into each other and slowing down and going into this disk, and eventually it all goes into the black hole. But if you had the dark matter, it would be flying around the black hole, but none of it would be bouncing into each other to slow itself down to go into this accretion disk in the same way. That said, if a piece of dark matter made a direct hit, tried to pass through the event horizon of the black hole, then in it goes, and it gets added to the mass of the black hole, whatever it is. So in theory, it wouldn't scoop up dark matter in the same way that it might scoop up a lot of regular material, but if all of this dark matter was directed right into the black hole, then it would add to the mass of the black hole, and the black hole would become more massive, and there would be less of this dark matter in the universe. It would all just be part of the black hole. Matt Wilson. So we just found a black hole 1,000 light years from Earth. Any chance there's one closer? If so, how much closer can it be for us to be safe? Yeah, astronomers looked at a fairly well-known star system. I think you can even see with your unaided eye, and figured out that there's actually a black hole in there. And they watched the way the stars were interacting, and one of them was just moving around, orbiting some invisible mass. And they realized that there's a black hole there. And the only way they knew that it was there was because it's in this complex multi-star system. And so the star was orbiting the black hole. So imagine a situation where you've got a black hole that has no stars orbiting around it. It's just free floating. And so there's almost certainly black holes closer than that 1,000 light years. And we may never know where they are, but they're going to be closer. Now, how close would it have to get to be? It would have to be within a few light years of the solar system for it to cause any kind of disruption on the solar system. We know that stars pass within tens of thousands of astronomical units within a couple of light years of the solar system every few million years, and yet the solar system has been going for billions of years and is roughly unharmed by these interactions. A black hole is going to have, say, 10 times the mass of the sun, more. But as long as it's far enough away, a few light years away, it wouldn't cause any impact on us. Now, if it gets closer, then absolutely it would start to throw planets around. It would start to smash planets into other planets and disrupt the entire solar system. But it all depends on how close it would have to get. But it would have to get very close, relatively speaking. Not 1,000 light years away. That's plenty far away. Brian. This is total BS. It doesn't work that way in science. If you want to say something is a black hole, you prove it. Is this guy really a doctor? No, that's not how science works at all. Science works in that you see a problem, an issue, there is a mystery. Like what happens to stars of a certain mass when they die? What is the enormous amount of gravity, some kind of massive, highly dense object that we seem to be finding at the hearts of supermassive black holes? What are quasars? These are questions, right? You can take a small telescope, you can look up in the sky and you can see a quasar if you want. Some of the brightest ones are visible, and yet these things are billions of light years away. You shouldn't be able to see one with a telescope, and yet you can. With a backyard telescope, you could see a quasar. So then what is it, right? How can this amount of energy be being focused like a point-like source across billions of light years away, or all of these other different mysteries that I mentioned? And so then astronomers come up with a hypothesis. Okay, here's one hypothesis. It's a black hole. And then they say, and if it is a black hole, then we would be able to take a picture of its event horizon. We would detect the collisions of them through gravitational waves. We would see their gravitational interactions with other objects. We would see them giving off high levels of X-ray radiation from seemingly nowhere. We would be able to detect them as their mass moves in front of some other object, and a whole bunch of other tests. And so you make these hypotheses and then you search for the evidence to see if that hypothesis is correct. Imagine if the Event Horizon Telescope took its picture and it got that beautiful ring of all of the material of the event horizon, and then right in the middle was a happy face. Suddenly, black holes disproved, just like that, right? You make a hypothesis, you're expecting to see that empty part in the middle, you take the picture and you don't see what you're expecting. So you throw out your hypothesis. That's how science works. And so if you or anybody out there on the internet says that they have some alternative hypothesis for what these things are, what happens to a supermassive star when it dies, what is the dense, massive object at the heart of many galaxies out there, what is causing stars to move in little circles around something that's invisible, all they have to do is explain, provide a hypothesis and then test that hypothesis, right? Is it some hologram? Great. What would a hologram look like? How can you prove that it's a hologram? Maybe a hologram would shimmer in a certain way. Maybe a hologram would not just be distorted through gravity in the ways that black holes do. You can make all of these predictions for whatever hypothesis that you have, and then you're attempting to disprove your hypothesis. So what we went through in that video was exactly how science works. Make a hypothesis, attempt to disprove it. If the hypothesis holds, then it is still your best guess, still your best theory on what it is that you're looking at. And of course, future evidence can always come along that disproves your hypothesis and you have to throw it out. And that's also how science works. And scientists are totally fine with that. They can't wait to have their hypothesis disproved because it gives them one more piece of information that gets them closer to the truth.
Here's a black hole fact. In theory, you can extract up to 29% of a black hole's rotational energy, thanks to the Penrose process.
Reme Wallet-Perez. Hey Fraser, I'm having difficulties understanding one question. Why is it that you can't escape once you fall into the event horizon? Considering you or any matter fall into the event horizon, but then got pulled by another greater power like another black hole that just happens to pass by, what happens then? Well, the definition of the event horizon is that is the point as you near the black hole where the escape velocity that you have to be going exceeds the speed of light. In other words, the only way for you to escape that region of the black hole is to be traveling faster than the speed of light. And by the laws of physics, you can't travel faster than the speed of light. Therefore, you can never escape the black hole. And even if another black hole came super close and was pulling on you with its gravity, it wouldn't be able to pull you out of the event horizon of that other black hole. And more likely, it would be pulling that other black hole into itself and the two would merge together. But still, there is no force, no way, nothing can escape unless you can travel faster than the speed of light that you can get outside of the event horizon. And even if you could travel faster than the speed of light, as I mentioned before, actual space-time gets tangled up so badly that there are no pathways that lead you out from the center of the black hole. You're going in, there's no way out. Aniello de Meglio. Aren't black holes an infinitesimal point in space? I'm getting confused between the terms black hole, singularity, and event horizon. Yeah, so when you think about a black hole, the part that we can see in that image of M87's supermassive black hole, that is the region around the event horizon. I think it's the photosphere and around that. That part that I mentioned, that point where nothing can escape the black hole, that is the event horizon. And it is just an arbitrary line in space. If you're a little outside of that region, if you're traveling the speed of light, you can escape. If you're inside that region, if you're traveling faster than the speed, or as fast as the speed of light, you still go inside. What's in the middle? We don't know, right? We know what's gone into it. We know that stars and planets and gas and dust and light and antimatter have all gone into the black hole. They've all crossed the event horizon. But what actually happens to them inside that event horizon is unknown, and it might be never known. One possibility is that it's some more exotic form of matter, take say a neutron star, which we can see. A neutron star is right at the limits of becoming a black hole. We can see them. Their escape velocity isn't faster than the speed of light. Therefore, light can escape a neutron star. They're very bright. They're very hot. We see them. You add a little more mass to a neutron star, that event horizon, right, starts to show up because it has crossed the amount of mass required in a dense enough region that not even light can escape it anymore. And so maybe inside that event horizon, just below the surface, there's the black hole, but the black hole is actually some sphere made of some kind of exotic matter. Or maybe the forces that are compressing it down just continue to smash it down and make it smaller and smaller until it's infinitely dense. Or maybe it is attempting to become infinitely dense. It's just getting smaller and smaller and smaller, faster and faster and faster. The bottom line is that we don't know, and we might never know. The problem is that there's no way to be able to see inside the event horizon. Dustman, I wonder what would happen if a star went supernova right next to a black hole. All right, so let's imagine this scenario. You've got a really giant star, maybe something with 20 times the mass of the sun, 30 times the mass of the sun, and it is orbiting a black hole. And the black hole is going to have 15 times the mass of the sun, 25 times the mass of the sun, some large amount. And the two stars are orbiting around each other, because that's the only way you can have a star and a black hole be really close to each other, is if they're in some kind of binary relationship. And so maybe their masses are roughly equivalent, but even if they're not, then the star is orbiting the black hole, or the black hole is orbiting the star, whoever has the most mass. And so then the first star went supernova a long time ago, and now the second star goes supernova. And when that second star goes supernova, before you had this anchor, you had these two objects that were orbiting around each other, and now one has disappeared. The mass has gone away. Now, in some kinds of supernova explosions, if the star is big enough, like 50 times, 60 times the mass of the sun, then when the star goes off as a supernova, it's gone. There's no remnant left behind. It is just a puff of star, and it's gone. And so now there's no gravitational anchor that's holding onto the black hole, and it's free to just go careen off in a direct line. If it has enough velocity, it could get kicked out of the Milky Way entirely. If the star that the black hole is orbiting together with is maybe a little bit smaller and it turns into a black hole, well, then they're still going to be orbiting around each other. Or if it's even less massive and it turns into a neutron star, they're still going to be orbiting around each other, just in a different configuration depending on the amount of mass that they had. Now, I'm sure you're wondering, like, what would the explosion of a supernova do if it was right next to a black hole? Well, the black hole is perfectly able to gobble it all up. So all of the energy that actually crosses the black hole event horizon goes in. All of the matter, all of the debris, all of the fragments, they all just go into the black hole and they get added to the mass of the black hole. And so the black hole gets a little bit more massive, not a lot, because the amount of that star that's actually going to hit it. And then any debris that's sort of sitting around it as the black hole is careening through this debris field, it's going to be gobbling that up, maybe turn that into an accretion disk around it, and then eat all that as well. So it's not going to do any damage to the black hole. You literally cannot do damage to a black hole. Anything you try to do just makes it stronger. But if the binary companion disappears because of its supernova, then the black hole is now unleashed into a random direction to fling through the Milky Way.
Well, you made it to the 3-hour mark. Congratulations. Now, have you been watching to see how things change? My appearance, the production quality of what we do, how we are trying out different ideas and formats? This just continues. All right, let's carry on.
Brian Stinsky, you were talking about a black hole being kicked out of orbit into a random trajectory. What would happen if it came close to the Earth? Say the distance the moon is from the Earth. That sounds kind of scary. Let's simulate that and see what happens. That's not good. All right, so let's simulate and see what happens if a black hole moves close to the sun. Also not good. The reason, of course, is because the black hole is going to have 8, 10, 20 times the mass of the sun, and that is going to completely disrupt the orbits of all the objects in the solar system, tear apart the Earth, the moon, the sun. Nothing can really compare against that kind of strength. Fortunately, we can see that this has never happened in the Milky Way. All of the planets are orbiting in roughly, nice ellipses around the sun. Clearly, a black hole has not moved through the solar system in the 4.5 billion years that we've been around, and so it's fairly unlikely that it's going to happen anytime soon. But if it did, it would be super bad. Mark Hathaway, is there one particular escape speed for a black hole to leave a galaxy? There is an escape velocity for the entire Milky Way, just in general, and that number is 550 kilometers per second. And just for comparison, the escape velocity from the solar system is about 42 kilometers per second. So it's more than 10 times faster. And it's not just black holes that can get, thrown out of the Milky Way. Just stars can do it. If you have some kind of interaction with the supermassive black hole at the heart of the Milky Way, or if you're in a binary companion and one star explodes, the other one is thrown out like a slingshot. As long as you're going faster than 550 kilometers per second, you are leaving the Milky Way and you're never coming back. J2, I wonder what would happen if Superman could reverse time on a black hole to the point that it was no longer spinning. Would it collapse into a giant explosion, spewing out whatever matter and energy it had consumed, or would it just fade away? Interesting. You wouldn't have to reverse time to stop a black hole from spinning. All you'd have to do is drop material into the black hole in the opposite direction that the black hole is spinning, and each piece of new debris that goes into the black hole would slow down its rotation a little bit. And if you had enough material, you could eventually just perfectly stop the black hole from rotating. Now, it wouldn't disappear, it wouldn't explode, it would just sit there, ready for a meal. Feed me. And in fact, so one of the really cool ideas of a way to generate power is this idea of the Penrose process. And what you do is you've got this rapidly spinning black hole, you drop material into the black hole, and as it just is about to drop into the black hole, it tears apart, part goes into the black hole, and part, now that it has less mass, gets spun out really fast, and then you capture that mass, absorb the kinetic energy, and you use that to power your advanced civilization. And it's probably one of the most efficient ways that you could use energy in the entire universe. I think it's like 39% of the energy, the sort of theoretical limit of energy. The problem is the more that you do this, the more you're slowing down your black hole, and eventually your black hole will stop. And then you're going to have to feed it a bunch to speed it up again until it's rotating, and then you can bleed off that energy again. So imagine a black hole as like a giant battery that you can speed up and speed down, like a big flywheel that you can extract energy from when you need it. Black holes are going to be incredibly useful for really advanced civilizations, for all kinds of things. So we should be, we should be very careful. We don't want to use up all of our black holes. Dizzy Are those huge stars that leave no remnant behind more common than stars that leave a neutron star or black hole? It seems that with how old the Milky Way is, that they should be common, but they're rare. How can that be? So the kind of star that we're talking about, the one that doesn't produce a supernova, just goes from star to black hole, it's believed that those only happen with the most massive kinds of stars, the stars that are hundreds of times the mass of the sun. And so those are not super common in the Milky Way, they're not super common in the universe. And in a recent survey, I think I mentioned this in the episode, that maybe about 10% of the stars could be going through this process, this unnova process, where they just collapse into a black hole and they never get the supernova. That's today with the kinds of star formation that's going on in the universe today, the kinds of nebulae that are collecting together and producing stars. But if you go all the way back to the beginning of the universe, before there was any heavier elements, there was just this primordial hydrogen and helium, and they were potentially forming stars that were hundreds of times the mass of the sun, maybe thousands of times the mass of the sun, maybe tens of thousands of times the mass of the sun. Astronomers are still trying to figure this out. And it's a very important question. And so what is a very rare event today might have been just the way all of the stars acted at the very beginning of the universe. These they're called the population 3 stars. And this is a time that astronomers are really excited to be able to eventually be able to see. The James Webb can't do it. Some of the biggest telescopes on Earth aren't going to be able to do it. There are a few experiments that might give some sign of these first stars, but it's going to take much bigger telescopes like LUVOIR or the Origin Space Telescope, or even bigger telescopes than that, to actually allow us to see so far into the universe that we're seeing those first stars form shortly after the Big Bang. And it is one of astronomy's greatest desires to be able to do that. Dustman, what if a black hole got spinning so fast that the disk spread out so much that the density was no longer above the threshold at which light cannot escape? So when you think about a black hole, all black holes are spinning, which makes them more complicated. As material's falling into the black hole is spinning faster and faster and faster. And as you add more material to the black hole, you're going to be essentially speeding it up, its rotation speed. And so I can sort of imagine your question. You're thinking like, could the black hole just keep going faster and faster and faster and eventually get so fast that it sort of flattens out and then just tears itself apart and then it's no longer a black hole? And the answer is no. And the reason is actually really cool, which is as the black hole rotates faster and faster and faster, it actually starts to fall under these sort of relativistic limits. In other words, say the black hole is rotating, I forget the speed, it's about 70% the speed of light. So as the event horizon, as the black hole is turning at closer and closer to the speed of light, it sort of requires more and more mass to make it go faster, in the same way that you can never approach the speed of light when you're in a spaceship. And so it eventually, the black hole reaches the maximum rotation speed that it can. And that rotation speed is not fast enough to tear it apart. One of the things that's kind of cool though, as the black hole is spinning faster and faster, is its event horizon flattens out. So instead of it being like a sphere, it flattens out into this oblate spheroid. And the limit is that the event horizon can never rotate fast enough that it flattens out so that the actual singularity can be revealed. It's this idea of a naked singularity. And the limit is that it can spin up, but it can never get to the point that you can actually see the singularity inside the event horizon, and it will never tear itself apart. And you can thank Einstein for the reason why. Zaz, question. When a neutron star becomes a black hole, is the star itself still there inside the black hole, or are all the neutrons torn apart when it's forming? I know we cannot see inside the event horizon, but there must still be a lot of compressed mass in there. The black hole must be composed by something to still be a black hole, right? Any theories? I think the way you describe that as a neutron star becoming a black hole is a really great model to wrap your head around a bit of what a black hole is. Imagine a neutron star, the remnant of a supernova that it's exploded. It's got several times the mass of the sun. It's compressed down to an area the size of like a city. Gravity is incredibly intense, but the gravity is not so much that light can't still escape from this object. And so a neutron star can shine. But imagine, say, the neutron star is continuing to feed on some other stellar material, and it grows and it grows and it grows. And at some point, it crosses some line where the escape velocity off the surface of this neutron star has exceeded the speed of light. And in that moment, it collapses into a black hole and disappears, because now not even the light can make it off of this neutron star. And so then you're wondering if that just happens, if it goes just from neutron star to black hole, is there still a thing inside the event horizon? And the answer is nobody knows. Sorry. Um, logically, maybe, but then we don't know if you cross that line, if something happens to the state of matter. I mean, a neutron star is already at the point where it is compressed, where really all of the protons and electrons have been mashed into neutrons, and it just refuses to be compressed anymore until it does. And then at that moment, all bets are off. Is there some object that's more dense inside the event horizon? Maybe. Or does this object just continue to compress down? And maybe it accelerates as it compresses, getting smaller and smaller and smaller. Astronomers still have no idea. When astronomers deal with black holes, they deal with them mathematically. They imagine an object of a certain amount of mass, say 10 times the mass of the sun, but compressed into a region of infinite density. Now, it might actually be infinite density or approaching infinite density as the black holes continue to compress down and accelerate, or maybe it's some set size. But mathematically speaking, astronomers deal with it just that it is a singularity. Ming on Mongo. This is a good example of why the notion of the so-called planet X may actually be a black hole is absurd, when only stars with several times the sun have enough mass to become one in the first place, and anything with that much mass, perhaps wandering around in the Oort cloud, would surely be obvious now. You are correct. In our current day, astronomers know of no way that a black hole can form by any other process than by the collapse of a massive star. Star dies, it implodes on itself, and it creates a black hole. And it's only with that infalling material, it moving it close to the speed of light, that you can actually get the force to create a black hole. And that's all we know of today. One other idea is that you can get infalling material directly that could form a supermassive black hole, but to get the kind of black hole that you would need to form some object that could be orbiting within the solar system, the only possibility is this idea of a primordial black hole. And these are black holes that could have been formed back to the first moments of the universe. And so at the very beginning of the universe, everything was almost of uniform density. But we can see in the cosmic microwave background today that there are little parts that were more dense and little parts that were less dense. And that's what the temperature variations in the cosmic microwave background to refer to. So one idea is at the beginning of the universe, you would have these regions of higher density and regions of lower density. And so the idea is that you would get these primordial black holes that would form in the regions of higher density. And they would be of any size. You could have black holes the size or the mass of a car, black holes with the mass of an atom, black holes with the mass of an asteroid, black holes with the mass of a planet Earth. And then they would be thrown out into the universe and would be free to wander around and cause havoc over time. And so one of the explanations for maybe the planet 9 that we can't see is that it could be a primordial black hole. And that would explain the gravity of some object in the outer solar system that is contributing to the weird movements of the objects out in the Kuiper Belt, and yet would also explain why it hasn't been detected so far. Maybe it's a primordial black hole. But there's not a lot of people that actually believe that that's the case. It's just one explanation. And when you're trying to come up with ideas to explain weird mysteries in the universe, no idea is too crazy. Now, you need to be able to rule them out, and I'm sure the primordial black hole idea will get ruled out eventually. In fact, I've even seen some papers that propose to do that. But just over time, as bigger telescopes come online that are capable of finding Planet 9, no matter how dim it is, and it's probably going to be the Large Synoptic Survey Telescope, the Vera Rubin Observatory, then the whole primordial black hole as Planet 9 argument will disappear. But until then, it's just a cool idea to think about, and it's a cool idea to think that there are these primordial black holes out there wandering the universe today. In fact, there's one theory that they account for dark matter, which is kind of cool. Not many people believe that, but still, it hasn't been ruled out yet. So until then, it's just on the table as an idea. Gennaro Canero. Hi, Fraser. Talking about black holes and primordial black holes, is there a theory model to explain the supermassive black hole? Are they thought to be primordial black holes, or models support a black hole merge approach? So you're asking one of the unsolved mysteries of the universe right now, one of the big challenges in astronomy. So I'm not going to be able to answer the question, because if I did, then I get a Nobel Prize. and I'm just a journalist. But I can help you sort of understand where we are in the problem right now. We now know that there are these supermassive black holes that seem to be at the heart of every single galaxy out there. And it seems to be that the size, the mass of the supermassive black hole grows in tandem with the size of the galaxy itself. As the galaxies get bigger, the black holes get bigger. And the farther and farther that astronomers are looking, the earlier in time that astronomers are looking, they're seeing galaxies which are too evolved. They're more evolved than they should be. They have black holes, supermassive black holes at the heart of them that are more massive than you would think there would be. And if you run the calculations, right, there is a limit to how much a black hole can eat. If a black hole is just nonstop at the buffet, just feasting as much as it can, there's still a limit to how big a black hole can get because the material just chokes up, has to wait its turn to die. But black holes can collide with each other. And that's one way that you can get black holes to suddenly double their mass, triple their mass, right? But the other idea is this idea of a direct collapse black hole. So you have some gigantic cloud of gas and dust, of like primordial hydrogen left over from the Big Bang. And one set of theories says, well, maybe you could just have this big cloud of material and it just swirls around and collapses down. And instead of turning into a star that then throws out stellar winds that blows away all of the material from trying to add to the size of the star, the whole thing just collapses directly into a black hole. No intermediate step. And maybe you could have these be significantly bigger than the size of the black holes that are possible today. You know, back in the early universe had this pure primordial hydrogen fuel that was more efficient than the fuel that they have today. It's all, it's got all this grit from stars, star formation. So that's sort of like one idea for how you could have black holes grow very big to get to this supermassive black hole size. Now, you talked about this idea of primordial black holes. We've talked about this a couple of times in previous episodes. This idea that there were ripples in space-time over densities at the earliest moments of the universe where they kicked out tiny black holes. But the reality is there's no limit to the size of these black holes. They could be as big as they can have as much mass theoretically as the observable universe. Now, we don't see that. We see a universe and not just one big black hole. Therefore, that didn't form, but there could definitely have been far more massive black holes formed in the over and under densities in the original universe, which then went on to accrete more mass or merge together to build up. Somehow we got where we are today with supermassive black holes. There had to be some chain of events, and it could have been primordial black holes as the first nuggets that then merged together, or direct collapse, or just some other sequence of black holes forming, merging together, giving us the black holes that we see today. I think we'll have an answer to this in the next couple of decades, probably sooner. And so this is one of these things to keep an eye on as the science continues to evolve. Vengeful sorrow. So it's theorized that black holes will evaporate over long periods of time due to Hawking radiation. But is that negated by the energy falling into them with all the light shining from stars in a galaxy? In other words, will the evaporation of black holes be put off until the universe is less dense with energy? So this idea of black holes evaporating, we've done whole videos about this and lots of other people have as well. So I won't go into all the details, but the gist is that over time, black holes, depending on their mass, will release photons. And in fact, the more massive the black hole is, the more slowly it will release its energy. And so the most massive black holes will last the longest, and the smallest black holes will actually evaporate the quickest. In fact, like when a black hole is finally about to completely disappear, it's like super white hot, putting out gamma radiation. But when a black hole is really big, it's occasionally putting out one photon. Oh, I got a leaf there. One photon every millions of years. I don't know the exact number. So you're exactly right that in our current universe, there are photons coming from the cosmic microwave background radiation of 2.7 Kelvin, and they're hitting everything. And so really, until the background temperature of the universe gets so cold that very few of those photons are hitting the black hole, evaporation won't even begin. We've got to wait until really the background temperature of the universe is almost indistinguishable from absolute zero. And only then will it be cool enough and few enough photons falling into black holes that they're able to give off more mass than they're accumulating from the universe. Andrew Planet, if a typical stellar class of black hole has a mass between 3 and 10 solar masses, how come a neutron star which has more mass does not automatically turn into a black hole? Right, when you hear about this idea of like what it takes to make a black hole, like a star like our sun, when it dies, it's going to turn into a white dwarf. When a star with more times the mass of our sun, say 3 to 8, 3 to 15 times the mass of the sun dies, then it turns into a neutron star. And then with more than that, then you get a black hole. And I guess the question you're asking is like, if you've got a neutron star that has many times the mass of the sun, why isn't it just turning into a black hole? Well, it's not just about having the mass of a neutron star. It's about having the event of all of that material falling in at close, closing in on the speed of light that is compressing that material down, that's causing that initial object. And you're getting this enormous bounce of stuff that's coming out at the same time. And so you're left with the remnant, a fraction of the mass that was in the original star remains as the remnant that's left behind. Visto2D asks, would the event horizon of an enormous black hole appear flat? Sure. Yeah. I mean, it depends on the size, right? If it was a black hole the size of 250 times bigger than the observable universe, then it would appear flat. But because a black hole, an enormous black hole is inside our universe, then pretty much any black hole that we can observe is going to be smaller than the universe. And so we would perceive it as a circle. But if you got really, really close to it, which I do not recommend, then you might have a difficult time being able to tell, measuring the curvature of the black hole. And so, yeah, but I mean, it would need to be really big. Jens Oddvar, what would happen if a black hole and a white hole crash? I know white holes are probably not real. The white hole would disappear because anything goes into a white hole, it causes the white hole to collapse. So mathematically, even though white holes probably don't exist, they exist as a mathematical sort of, if you reverse some numbers on the black hole mathematics, you get a white hole. Doesn't mean they're real, just means that you can reverse numbers on them. But the math also predicts that if there's anything, even a single photon, then the white hole will collapse, especially if there's a black hole. Mr. Mann, if gravity moves at the speed of light, how do black holes still have gravity? Gravity is not a force that is sucking things in. Gravity is a distortion of space-time. And so the more mass that you have, the more you distort space-time. And black holes have the most mass concentrated to the smallest amount, and so they distort the most space-time. So it's not about it's true that if a black hole just appeared, then you would have to take time for the gravity to reach you. But that's just the way forces are communicated in the universe, that light, magnetism, gravity, they all move at the speed of light. They all communicate their existence at the speed of light. But still, a black hole just is a distortion of space-time. And that's what causes things to go in orbit around them. Just in the same way that the moon is orbiting around the Earth, not because there's some kind of gravitational pull, but that the Earth is distorting space-time so that the moon thinks it's going in a straight line, even though it's actually going in a circle or in an ellipse around the Earth, which is kind of amazing. Tony Principi. Hey, Fraser, what is the significance of finding intermediate-sized black holes other than checking the box to say, we found them? Well, I think checking the box to say we found them is good. But no, I mean, we see stellar mass black holes, ones with, say, 10 times the mass of the sun. And we know that those are formed through supernova explosions. And then we also see black holes with millions, billions of times the mass of the sun. And how did the big ones form? How did you go from 10 times the mass of the sun to a billion times the mass of the sun? You would anticipate that there would be a collection of black holes of every size in between. And you would be watching with your gravitational wave experiments as these various masses of black holes are merging together to form the big monster black holes. But so far, almost every attempt to find an intermediate mass black hole has failed. They haven't been able to find them. There's been some hints that there are some lurking inside globular clusters. There was a really recent paper that just came out a couple of days ago where somebody saw an intermediate mass black hole through the lensing, the gravitational lensing of a gamma ray burst, which is kind of amazing, but like a total trick shot in terms of a science observation. And so understanding how we got supermassive black holes, I mean, they boggle the imagination, and yet we just have no idea why they are so massive so early on in the universe. And being able to see these intermediate mass black holes coming together would tell us a ton about how this process works. Mitch Harpino, when a star goes supernova that is massive enough to become a black hole, does that black hole come into being immediately after the star's collapse? Yeah, when a star, like a star with much more mass than the sun, is becoming a supernova, you get layers and layers of various elements that are forming inside the star. When you get iron in the middle, it's no longer generating an excess amount of energy through the fusion process. It's the equivalent of ash. And so the fusion process just halts at the center of the star, and the star collapses in on itself because it no longer is able to be pushing out with light pressure. And so the star collapses, and it happens very quickly. And at a certain point, parts of the star are coming inward at like 70% the speed of light. So it is coming in fast. And it's like this, it just collapses all into this one point. And the supernova that we see is essentially all the additional material that couldn't go into the black hole fast enough, bouncing off the black hole and going out into space. And so you've got a black hole right there and then. And the supernova is just, you sort of imagine like when you have a bathtub and you let out the water in the bathtub and you get all the water in your bathtub doesn't immediately go down the drain. It swirls around because there's only so much room to go down the drain. And same thing, a black hole can only consume the star that it was once before so quickly. And if it can, it sort of gets too full, and then that's how you get the bounce material. But in some cases, it looks like now supernova just entirely form into a black hole, that it is able to stay on top of it and just gobble up the entire star and turn it into the black hole. But it happens right then.
Here's a black hole fact. So there's a region outside of a black hole, outside of the event horizon, called the ergosphere. And in this region, you are forced to rotate with the black hole. Although if you still have engines, you can escape, theoretically.
Jeff Sonderman. Hey, Fraser, what are the next frontiers for gravitational wave astronomy? Will we get better detectors? And what might they discover beyond the black hole or neutron star collisions that we've seen? The age of gravitational wave astronomy has really just begun. And of course, the big thing was to find these giant black hole collisions of intermediate, sort of large stellar mass sized black holes. And of course, now we've also seen possibly a black hole collide with a neutron star. We've seen the neutron star collisions. So then you're going to go in both directions. You're going to have collisions between, say, white dwarfs, which are probably happening across the universe as well. We're going to have collisions between much larger, supermassive black holes. We're going to get possibly like the gravitational waves from a supernova that is asymmetrical. And so if the supernova blows off in one direction and does this wobble as it explodes, we should be able to detect those. And then we're going to be able to detect over time these objects as they're farther and farther apart. So right now, when we detect, say, two black holes about to merge, we only detect it, say, in the last minute before the black holes merge together. But imagine if they're farther and farther apart, and maybe we can start to detect them when they are hours apart, weeks apart, days apart. So that's pretty exciting. Then the other thing that we're just starting to get now is this idea of a gravitational wave background radiation, sort of in the same way that we have the cosmic microwave background radiation, that there's the potential for just different wavelengths of radiation. We could get, and it's possible this has already been detected, that there's already this gravitational wave background that we're already seeing, where you've got these black hole collisions happening across the universe, and now we're starting to see the ripples just bouncing around and moving around in space. This is being done through pulsars, and so astronomers have been watching with the Gaia instrument, one of my favorites. They've been watching the positions of pulsars and watching how the pulsars are bobbing back and forth out there in the universe, and they're detecting these large scale gravitational wave background information. And then the one that's really like the most exciting is to be able to detect the primordial gravitational waves. So if you could go right back to the beginning, before the cosmic microwave background, right back to the very Big Bang, when the universe was forming and you had various kinds of masses moving around at high speed velocities, you should expect some kind of gravitational waves being generated by all of this material as it's moving around. And that would answer so many questions. It would directly tell us the age of the universe. It would give us maybe a hint of what came before the Big Bang, whether the inflation theory is the right one, or maybe if there's other theories that work better, were there primordial black holes present at the beginning of the universe. And so there's so many other things that gravitational wave astronomy is going to do. We are just, it's like someone just handed us a brand new scope. This is like Galileo pointing his telescope at the sky for the first time. You know, his first telescope was like 9 power. And he was able to see the rings of Saturn, the moons of Jupiter, the fact that Venus goes through crescent phases, was able to see that the Milky Way is made of stars, was able to see the craters on the moon. This is where we are with gravitational wave astronomy, and it's just going to get better and better and better. JC. Hey, Fraser, love your work. Thank you. I'm wondering, what happens if a micro black hole passes through the Earth's core? Why would it not swallow the core and grow? Or if the density is the problem, I'm guessing one could pass through a neutron star and feed itself to a considerable size. Have we seen evidence for this? Thank you again for your amazing content. First, I think that, we have to sort of differentiate a few things first. So let's start with this idea of having a black hole at all. And the only way that we know naturally for black holes to form is via a supernova. And so you need to have a star with many times the mass of the sun, like more than 10, explode as a supernova. It then, all the material implodes down into the core and it bounces off and creates this black hole. And you end up with a black hole that is several times the mass of the sun. And so if a black hole forming the way that we know they can pass through the Earth, really, it would be the most dominant gravitational thing in the neighborhood. As it passed through the solar system, it would be warping the orbits of all the planet. It would kick the sun, into a different configuration. It would throw out planets. It would throw planets into the sun, and it would eat planets. So having a black hole pass through the core of the Earth is sort of like having a truck pass through the core of a fly. I don't know. It's not really for scale. Now, there is a theorized kind of black hole known as a primordial black hole. And so it's possible that there were overdensities back at the beginning of the universe when you had these tiny little regions that were so dense that little microscopic or various sizes of black holes. You could have ones that are microscopic. You have ones that are the mass of a house, the mass of the Earth. And this is all still in theory. Nobody knows for sure that these things exist. But let's just imagine that there is one of these primordial black holes, a very small one, say with one with the mass of a house. So it's not enough to really disrupt the gravity of the Earth, that for some reason perfectly passes right into the Earth and heads down through the Earth. And so what would happen? Nothing. Nothing. Because the gravity of a house is not that much. And when you have a black hole, it doesn't actually interact with the matter in any way. It's not like it's going to be bouncing, going to be slowed down. It's going to have its position change at all. So a black hole would be coming in at tens of thousands of kilometers per hour. It would pass through the Earth. It would burrow a tiny little hole in the Earth. It would add a tiny little bit of mass to itself. It would pop out the other side and it would just keep going through space, never to return. And so if something like that happened, we would never know. Now, I'm sure you heard this disturbing theory that maybe when they first turned on the Large Hadron Collider, there would be this black hole that would be generated in the Large Hadron Collider and it would fall into the Earth and then it would consume the Earth from within. And that would be a problem because in this case, the black hole is trapped inside the Earth. Think about it, right? When you drop something into the Earth it can't get out of the Earth again. The most it can do is going to fall all the way down through the Earth, reach the other side of the Earth, and then it'll be, it's going to speed up, go down to the core, then pass through, slow down, get right to right to the surface, like literally the same height as where it fell out of the Large Hadron Collider in Europe. I don't know what's in the antipode of Europe. And then it would fall back through the Earth, and it would be, eating particles as it went. And then it would do it again and do it again and do it again. And so it would end up gobbling up the entire Earth from within. Now, it would take a long time, and eventually you'd get to this point where the interior of the Earth was just like Swiss cheese, and then the whole thing would just kind of crumble in on itself into this new black hole. And now the Earth would be replaced with a black hole with the mass of the Earth orbiting around the sun forever. So if we ever do form a black hole with one of our science experiments, it's only going to be a problem for us. Arjun, shouldn't there be a few supermassive black holes around Sag A star? Since the Milky Way has been eating other galaxies, would they be hard to find? Now, Sag A star, that is the supermassive black hole at the heart of the Milky Way, more than 4 million times the mass of the sun. Where are all the other supermassive black holes that the Milky Way gobbled up? Well, actually, there's some pretty recent research that came out in the last couple of days that new simulations say that the Milky Way probably formed fairly slowly over long periods of time by consuming lots of smaller galaxies and not like a really big collision with another galaxy. Like when we collide with Andromeda in 7 billion years from now, it's going to be big galaxies coming together, huge supermassive black holes coming together. It's going to be crazy. But the kinds of interactions that the Milky Way has had in the past has been with dwarf galaxies. Some might have had supermassive black holes in them or intermediate mass black holes. Some maybe didn't. We're still not sure exactly how many of them out there do. When supermassive black holes interact with each other, they tend to find their way down to the center of the galaxy and then will interact with each other. They'll orbit around each other and then merge. And so where did all of the other black holes go? They joined Sag A star, or they were kicked out of the galaxy and are now roaming around deep space. There are supermassive black holes without a galaxy, just roaming around the universe. Enjoy. Jeff Sonderman. Fraser, would a spaceship with a warp drive be able to travel within the event horizon of a black hole and back out again? What would be the implications? It really depends on how your warp drive works. So, if you take Einstein's mathematics and you put in faster than the speed of light, then in theory, you should be able to escape a black hole. But the problem is that in reality, a black hole tangles up space-time so thoroughly that if you were flying your faster-than-light spaceship in the event horizon of a black hole, all pathways still take you to the singularity. So it's not about traveling so fast you can escape the black hole. The problem is that you're traveling the lines of space into the black hole again. All roads lead to the singularity. But it really just depends on how your warp drive works. If your warp drive allows you to create some sort of bubble that allows you to ignore the bending and twisting of space-time caused by the black hole itself, then maybe you could escape from a black hole. We're going to have to wait till someone invents one, and then we can find out what happens.
Here's a black hole fact. The shadow of the event horizon seen by the Event Horizon Telescope is actually about 2.6 times bigger than the event horizon itself. And this is caused by the distortion of light caused by gravity.
Cootie Exo. Why do people think that black holes lead to another universe? It sort of depends on who you ask. The answer is that we don't know what is on the other side of an event horizon of a black hole. What we do know is that when really massive stars, much more massive than our sun, die, they explode as a supernova, and then all of the layers come crashing in and they implode at the center. And so you have all the mass that was once a chunk of the star is now this object that is so densely held together that the escape velocity to leave this object exceeds the speed of light. And so when you kind of imagine, like, what's the escape velocity to leave Earth? How hard would you have to be able to jump to be able to escape Earth forever? It's fast. But if the Earth was more massive, then the speed that you would have to jump off of the Earth to fly off into space would be more. Maybe it would be 15 kilometers per second. If you were going to, even more massive, maybe it would be hundreds of kilometers per second, thousands of kilometers per second. Well, the speed you would have to jump to get off of a black hole is beyond 300,000 kilometers per second. And that's the speed of light. And so not even light can jump off of a black hole. So is that a portal to another universe, or is that just a really, really massive, dense, planet-like thing that you could just fall into and get crushed onto? We don't know. Maybe a black hole tears open the fabric of the cosmos and leads this portal to another universe. Or maybe if you just jumped into a black hole, you would just go smack onto the black hole at a ludicrously fast speed and just be pasted out onto the surface of the black hole at 1 atom thick. So I don't recommend that you try. Just wait for the scientists to figure out exactly what's going on before you plan your journey to a black hole. Steve Coates, could you make a repeating gravity wave generator? Well, sure. There, I just made a repeating gravitational wave generator. Whenever you move mass in space, you are generating gravitational waves. So if you wanted to make something that was detectable over long periods of time, you just need to have something that was moving more rapidly, that contained more mass, like a couple of neutron stars or black holes orbiting around each other. But the problem is that when they get to the point that they're really starting to generate gravitational waves that are detectable over long distances, they are spiraling inward and they're about to merge. So can we somehow move a mass like a black hole without it merging with another black hole in some way? It just seems like very, very difficult. But who knows? It might be that as we get better and better at detecting gravitational waves in the future, we'll get to the point where instead of just detecting, say, the black holes 1 minute before they collide with each other, we'll be able to detect them decades, centuries before they collide with each other. And so maybe some alien civilization could figure out a way to make those black holes wobble in such a way to be able to release gravitational waves. But then, of course, you could just shine a laser beam at someone to communicate if that's what you were trying to do. So, yeah. Vilk. How would a civilization close to a black hole experience time and perceive the age development of the universe? Thanks for the job you do. Kind regards from Norway. Yeah, this is pretty cool. So if you were a civilization that was living relatively close to a black hole, then you would be in the black hole's field of time dilation. And we saw in the movie Interstellar, right? Matthew McConaughey and team goes down to this planet orbiting this supermassive black hole. They are down there for a day, and when they come back up, decades have passed for the rest of the universe. And so imagine that was your home. You would be watching the universe move at high speed. You'd be seeing other planets zipping around the black hole. You would be seeing stars being born and then die. You would see the cosmic microwave background radiation would be blue shifted into a higher spectrum, maybe to the point that you could have solar panels that are absorbing the cosmic microwave background radiation because it's been pushed into, say, even like the visible spectrum. So it really just depends on how close you are to that black hole. And so it's been theorized that if a civilization wanted to live a really long time, they would huddle up close to a black hole. Now, one of the advantages of being close to a black hole is that you can throw matter into the black hole. You can harvest the energy as material is kicked back out of the black hole. There's bursts of radiation that are going to happen. But then you could just experience an accelerated universe because of the time dilation. So it's a pretty cool idea. And it's often been considered like the last comfortable place to live after the rest of the universe has cooled down. And so we talked about at the beginning about those civilizations that are waiting until the universe cools down. So maybe what they do is they wait, and at the very end, they set up shop around a black hole, tune the time dilation exactly how they like it, and then live out billions, trillions, quadrillions of years in an accelerated rate, doing whatever they do. Arjone, will the new LIGOs going online improve our resolution? How far can we hear collisions, Kagra, etc.? Yeah, right now we're in a bit of a downtime with the LIGO observatories while they're doing a bunch of upgrades on these various gravitational wave observatories. They put a bunch of new technologies in, ones that improve the sensitivity. They've got this thing called quantum squeezing, but essentially using quantum mechanics, they're able to, and I forget the exact way this works, but essentially you can know the position or the speed of a particle, but you can't know both. And so you can they're pushing this uncertainty in one direction that it gives them the kind of information that they want while sacrificing the other question. And so they're able to get a much larger volume of space that they're going to be able to observe. And they're going to be able to observe more interesting objects. They're going to be able to see stuff happen more often. So up until this point, we saw maybe one gravitational wave event every week. Now maybe we're going to see one black hole neutron star collision every week, and so on and so forth. So it's a pretty exciting time for gravitational wave observatory. And I just saw today that the Europeans have approved their next generation gravitational wave observatory. It's a 3-legged gravitational wave observatory, sort of like the way LISA is going to work, be this triangle with signals going around inside of it, with much longer arms than we have with LIGO. So what's great about gravitational wave observatories is each one that gets added to planet Earth, there's, as you say, Kagra, the one in Japan, there's one that's going into India. Each one just improves the overall capability of our ability to detect gravitational waves. And this is just going to continue. And as the space ones come online, we just get more and more sensitive about detecting gravitational waves. Cryptolicious. Fraser, Anton Petrov reported last month-ish that astronomers reviewing old plates noticed 12 stars disappeared. I'm not exactly sure what Anton was talking about, but there is a fairly interesting piece of news that came out in the last week or so. We reported on Universe Today, and so I'm guessing it's the same story. For the longest time, astronomers thought that when you had the most massive stars, they would explode a supernova and collapse in their centers down to a neutron star or a black hole. So when a star like our sun reaches the end of its life, it turns up to a red giant and then puffs out all its outer layers and then shrinks back down to become a white dwarf. And so the white dwarf is the remnant that's left over after the sun goes through this process. And if you have a star that's much larger than our sun, like maybe 8 times more massive than the sun, then when it dies, it builds higher elements in the core. When it reaches iron, all those outer layers collapse down inward, and you get this highly dense object called a neutron star. And you get this supernova as the material that's falling in bounces off the center of the star and goes out into space. And then astronomers thought, okay, so if we go even more massive than that, maybe 20 times the mass of the sun, 30 times the mass of the sun, then maybe in the force of this star imploding is so strong that it not only, it goes beyond turning it into a neutron star, it actually turns it into a black hole. And then same thing, all this material is piling up around the outside of this black hole. It can't feed on it quickly enough. It bounces out and you get this enormous supernova explosion. And then you're left with a black hole behind. But the new evidence seems to be that for those largest stars, they seem to just be disappearing. They're not going through this supernova black hole. And so the thinking is that maybe they just implode quietly, that there's no supernova. The star is there, and then it just folds in on itself and it turns into a black hole. And there seems to be growing evidence that for a large number of the most massive stars, they go out with a whimper, which is kind of terrifying when you think about this idea of just like you've got this whole star, a massive star, and then it just kind of folds up and it just disappears. And it's still there, but now it's a black hole. The yellow dart. The Large Hadron Collider could have created a black hole, but it would have been too small to be dangerous to Earth. Is it possible to build a collider big enough, equator size, to create a dangerous black hole? Right. So when physicists were creating the Large Hadron Collider, one of the worries was that as you were mashing particles with so much energy, they would be creating these dense objects that could be these microscopic black holes. And so for a while there, this was sort of a legitimate concern. And so a bunch of scientists ran the numbers to try and figure out if this is a thing that could happen. And what they found is, well, if it did happen, the black holes would evaporate before they even hit the ground, and so it wouldn't be an issue. And the way we know that this isn't a problem is because there are cosmic rays hitting the atmosphere of the Earth with millions of times more energy than anything that is possible to do in the Large Hadron Collider, and we don't get microscopic black holes raining down on top of us all the time. And so that scales up. And so for now and into the foreseeable future, the supernova, the supermassive black holes that are generating these cosmic rays are more powerful than anything we will be able to make here on Earth. But there could be some time in the future. Like, we create places that are colder here on Earth than are anywhere else in the entire universe. And we create places that could be hotter, like with some of our fusion reactions, that could very well be hotter than any place in the universe. So we are actually, through our technology, starting to push the limits of things that nature has cooked up on their own. But when it comes to the energy of particles crashing together, no, we can't match what cosmic rays can do yet. But who knows? Maybe there will come this time when there is some superconducting super collider out in space, and it will be generating energies higher than nature does on its own. And that would probably be of concern. Maybe people should do some extra math when they get to that point.
Here's a random black hole fact. Did you know that the supermassive black hole at the heart of the Milky Way contains 4.1 million times the mass of the sun? And yet, if you put it into our solar system, its event horizon would fit nicely inside the orbit of Mercury. Although Mercury wouldn't survive if you did that.
Greg Rumscheit, do you think that dark matter is tiny black holes? So this is one of the theories to explain dark matter, which is, of course, this mysterious matter that is spread around the universe. It's the vast majority of the matter that's out there. Up until this point, astronomers have like two main ideas. One is that it's some kind of particle that doesn't interact with regular matter, and so it's producing gravity, but we can't see it through electromagnetic radiation. The other idea is that it's the force of gravity working in a way that we don't understand at vast distances. But at this point, the sort of most of the evidence is really leaning on the side that it is some kind of particle, like some sort of massive particle that doesn't interact with regular matter, doesn't even interact with itself. And so one candidate particle that you could use is a black hole. A black hole doesn't shine with radiation. Black holes can collide, but in general, they have to get very close before they're going to actually collide with each other. And so astronomers haven't been able to rule out the idea that they're black holes. Now, you talked about them being tiny black holes in your question, but they don't need to be tiny. They can be tiny, or they could be 1,000 times the mass of the sun. And anywhere in between, there's different versions of counting up the total number of black holes. You could have like just a few really heavy black holes or a lot of really light black holes, and you would still be able to answer the problem of dark matter. And astronomers haven't been able to rule this idea out. But the idea of them being tiny black holes, because Hawking knew or has worked out that black holes should evaporate over time, that any of the black holes smaller than the size of a small asteroid, should have evaporated since the beginning of the universe. And so you wouldn't be left with these teeny tiny black holes. Although, something with, say, the mass of the moon compressed down would be a very small black hole. But that these could be wandering the universe, randomly running into planets, stars, each other, and they could answer what dark matter is. And so astronomers have actually done some surveys to try to confirm whether or not this is a real thing. And the most powerful way to do this is this technique called gravitational microlensing. And so what astronomers do is they look at a galaxy like Andromeda, and they watch the brightness of all the stars of Andromeda all at the same time. And they're looking for any stars to wink, and the winking will happen, or any stars to essentially appear out of nowhere and then disappear again. And that's because you get these, within Andromeda, you're going to have all of these stars that are lining up with each other perfectly. And when they do, the foreground star acts like a lens for the background star. But in this case, if you get a black hole, the black hole could be in the front and the star could be behind, and the two could line up perfectly. And now the black hole acts as a lens for the star that's behind it, making the star really bright, but there would be no foreground object that you would see. And astronomers have actually found some evidence that there are some number of these intermediate mass black holes located in other galaxies. So they still can't rule the idea out. But if you like ask most astronomers, they don't think it's true, but they won't rule it out. Lenny Lung, won't the universe just be all black holes at one point? It seems like a likely possibility, doesn't it? That any matter that gets too close to a black hole falls in. And so given enough time, every star, galaxy, planet, piece of gas, dust is going to make its way into a black hole. And then eventually you'll just have black holes of varying masses across the universe. Now, they all won't turn into one black hole because the expansion rate of the universe is accelerating. And so there are various black holes that will never be possible to meet. But actually, you won't get all the matter in the universe falling into black holes. You'll definitely get lots of it going into black holes, but there will still be lots of other degenerate matter. Like a star may die, explode as a supernova, turn into a neutron star, or expand as a red giant, turn into a white dwarf. So you'll have white dwarfs out there that just never happen to run into a black hole. You'll have neutron stars that never happen to run into a black hole. You'll have planets that were kicked out of their star system and just roaming around the universe, and they just never found their way into a black hole. So the far, far future is going to just be black holes and then stuff that didn't fall into black holes. But there won't be any stars. It'll just still be very dark. Jeff Wilkie. Given enough time, a black hole supposedly evaporates. Once enough evaporation has taken place, will the event horizon disappear, revealing a dense ball of mass, possibly a neutron star? I guess the evaporation will stop there. You're right that black holes will evaporate over vast periods of time. And from an outsider perspective, looking at a black hole and watching as it evaporates, what they're going to see is particles emanating from the event horizon of the black hole. The vast majority of those particles are going to be photons. They're going to be light, heat, temperature. And so what that means is it gives the black hole a temperature. Right now, any black hole that we could possibly look at is going to have a temperature that's essentially the same temperature as the background temperature of the universe. But over time, as the black hole evaporates more and more, that temperature goes up. And once the black hole reaches, say, the mass of an asteroid, the temperature is like room temperature. And as it gets even smaller, less massive, it gets hotter and hotter and hotter. And eventually, the black hole gets the mass of a house. It's reaching millions of degrees. It's blasting out gamma radiation, and it sort of gives off one final burst of gamma radiation, and then it disappears completely. So no, you don't end up with some remnant as the black hole is evaporated. It just heats up, gets higher and higher temperature, and eventually it just completely disappears. Astronomers have actually proposed that this is a way that you could detect if there are smaller mass primordial black holes out there across the universe. Maybe we can detect these pops of gamma radiation as these black holes disappear. Romulus XC. Hey Fraser, are we able to detect if any wormhole opens in our solar system? In the TV series Another Life, they detected it instantly. Obviously, wormholes, they're a staple of science fiction. Stargate used wormholes. Interstellar had wormholes, and I guess Another Life, I haven't watched this yet, if they've got wormholes. This idea that you've got some kind of connection in space-time between two places. And so I guess the question that you're asking is like, would we know if there was a wormhole? And in most situations, the answer would be no. No, we wouldn't be able to detect. Because imagine, like if a wormhole is just a window to another part of the universe, then you would just be seeing, say, if the wormhole was passing through your field of view, you would be seeing out the other side of the wormhole, and theoretically, you would just be seeing more universe. There was a paper that I read, I think we reported on it again in the last year or so on Universe Today, that you have certain situations where one end of a wormhole is, say, orbiting around a black hole. And in that situation, you probably would be able to detect it because the black hole would be distorting the light and the space-time around it in sort of the same way when you look at a black hole and you see the way light and stars are distorted around the black hole. And so if you had a wormhole and then on the other end of the wormhole was a black hole, then you would see through this tunnel and see the distortions on the other side of it. But in general, no. If there could be 1,000 wormholes here in the solar system and we wouldn't be able to spot any of them unless something really interesting was happening on the other side of it. But you can imagine situations where, say, stars would appear and disappear, or planets would appear and disappear. And that would be a pretty big clue. So it really all depends on what's on the other side of the wormhole. Pontus Ignell, would it be possible to use a black hole or such to pull something out from within the event horizon of another black hole? No. Even a black hole cannot pull something out of another black hole. The whole point is that the event horizon of a black hole is the point at which you would have to be moving faster than the speed of light to be able to escape. And since nothing can move faster than the speed of light, nothing can pull you out of the black hole. So once you cross the event horizon of a black hole, you are inside that black hole's event horizon and you're never coming out. Even if a supermassive black hole comes really close, even it can't pull you back out of the black hole. You're gone for good. Diana Galaxy. Fraser, do you know if things going into a black hole are squished or torn apart? Probably both. So as you fall towards a black hole, the force of gravity on you is different depending on how far away you are from the black hole. So literally, the force you feel on your feet is different from the force you feel on your head as you're getting close enough. And so eventually, those forces are so different that you get torn in half. And then those pieces get torn again. And then those pieces get torn again just because the amount of gravity is so different. To enter the Roche limit. Anyway, the tidal forces of the black hole will tear you apart. And they call this term spaghettification. So you sort of get torn into this long, thin stream of atoms that enters into the black hole. So that's the torn apart part. But then all of your atoms enter into the event horizon and join the black hole, whether it's a singularity or whether it's some larger object inside the event horizon, and you get mashed onto the surface of the black hole. And you are compressed, possibly infinitely. So, we don't really know what's going on inside the event horizon of a black hole. It could be that you just get added to some sphere that's maybe denser than a neutron star. And that I would call being squished, because like a teaspoon of neutron star is millions of tons. Like it's very dense. But maybe it is a true singularity. It's this point in space that is getting smaller and smaller at an accelerating rate, and your material just gets added to it. And that it's like super squished. So both. You both get torn apart and squished. Mauricio Togneri. Hey Fraser, what if two identical black holes are so close together that their event horizons overlap and you happen to be in that region? To which black hole will you fall into? I guess this is an extension from last week's question where someone was wondering if one black hole could pull you out of another black hole. Maybe if you were falling into a stellar mass black hole and a supermassive black hole came by and tried to pull you out of the black hole. And as I said, it doesn't work. And so if you're in a place where you've got two overlapping event horizons surrounding two black holes of identical size or different sizes, it doesn't really matter. The black holes are now in the process of merging. Once their event horizons cross over each other, then they can never get away from each other either. And so within a very short amount of time, those two black holes are going to merge to become one much larger black hole, or massive black hole. And so if you're stuck in between those two black holes, it's kind of like asking, like, what happens if you get stuck in between two semis coming together? I'm sure you can use your imagination to figure that out. Supercharged. Let's say the moon would disappear in an artificial black hole created by that accelerator. For how long would life survive on Earth? All right, so you're imagining that particle accelerator that we talked about in the beginning of the episode generates a black hole, and the black hole doesn't evaporate instantaneously, which is what it's predicted to do, but it somehow survives, falls into the moon, gobbles up the moon from the interior, and turns the moon into a black hole. There was a science fiction story that was like this. It was a Larry Niven story where astronauts show up on the moon and they find this ancient facility, and there's this weird device that's going, and they shut off the power, and it turns out the device was holding a little microscopic black hole in stasis, and it drops inside the moon and starts just carving out the inside of the moon. And they do the math, and at some point in the next few thousand years, the moon will just be hollowed out and collapse in on itself and turn into a black hole. So what would that do to life on Earth? Not much, because if you replaced the moon with a black hole with the mass of the moon, then you would still have the gravity of the moon. And so we would still have the tides in exactly the same way. And that's like the big impact. Like if the moon disappeared, then we would lose the tides, and a lot of species that had evolved in tidal areas would no longer be able to compete. They're the other kinds of animals in that area. And in fact, it's believed that the tides originally helped drive life forms to be able to push out onto the land, because they would live in the tidal areas, and the tides would keep them out of the water, out in the air, and then for longer and longer periods of time, and they would evolve to get farther and farther up until eventually they were able to handle living outside of the water all the time. And maybe that wouldn't have been possible without the moon causing these tides. But yeah, if you lost the moon, then we would still feel the moon's gravity. We would still have the tides, but we wouldn't be able to see it or find it, which would be really weird, because we would know the moon was out there orbiting around the Earth, but we wouldn't see it. But yeah, I mean, if you replace the sun with a black hole, the Earth and all the planets would still continue to orbit around it. You know, a black hole isn't anything special in terms of mass compared to a planet or a moon or whatever. Just be dark. Like there'd be no such thing as a full moon anymore. That would be a problem. King Majah. I'm a bit confused. If a star spins too fast, you said its momentum could pull it apart. Could such a thing happen to a black hole? How fast would it have to be spinning? So I mentioned this in a previous video, that as a star spins faster and faster and faster, it's kind of like being on a merry-go-round. As it goes faster and faster and faster, you have a harder time holding on to the merry-go-round. So if the star spins faster and faster, it flattens out and becomes a lot wider in the middle, and the poles come closer and closer together. And eventually the outward force of this rotation is greater than the gravitational force that's holding it together, and the star just spins itself apart. And there's actually like a limit. Like astronomers have seen a maximum speed that stars can rotate. And you would assume that the ones that rotated faster than that just tore themselves apart. There's a maximum speed that asteroids can rotate, depending on what they're made out of. And again, it's like any that rotated faster than that would have just torn themselves into pieces. And so the question you're asking is, can a black hole do the same thing? And the answer is no, because nothing, not even a black hole, can escape a black hole. But black holes do rotate, and as they rotate faster and faster, the thing that happens is the event horizon around the black hole starts to flatten out, like a planet that's rotating too fast, like a star that's rotating too fast. And the event horizon flattens out and flattens out. And as the parts of the event horizon close in on the singularity, it's going faster and faster and eventually approaching the speed of light. Essentially, the limits predicted by Einstein. I forget the exact number, but it's like, again, it's like 70% or something like that, is like the maximum speed that a black hole can rotate. And then at this point, essentially, it's starting to run into relativity, literally the fastest that it is possible for it to spin. It can't spin faster than the speed of light. And so there's this idea, there's this concept where could you have a naked singularity? Could you have a black hole spinning so fast that the event horizon would flatten out to the point that it would reveal the singularity, and it would give a sense of, we could look at the singularity and know what it is? And the answer is no, that essentially the event horizon can shrink down, but it can never shrink down to the point that it reveals the singularity, and it can never tear itself apart. There's just a limit. Black holes reach this ultimate speed limit, and even as you add more mass to them, And as you keep trying to spin them up, they resist spinning any faster than that. Ted Krause, can a magnetar collapse into a black hole? So a magnetar is just another type of neutron star. Like when a star that is many times the mass of the sun dies in a supernova explosion that we talked about in the beginning, it can leave behind either a neutron star or a black hole as its remnant. How a magnetar actually forms, astronomers are still trying to figure this out, but it seems to have something to do with some kind of binary companion. So you get a neutron star, but you also have like some kind of like accretion disk around the star, or like a binary star that's orbiting around the star. And the interactions with the star and accretion disk can whip up the neutron star's magnetic field to the point that it becomes a magnetar, and it essentially has this incredibly powerful magnetic field, like so powerful it could dismantle you at an atomic level. And of course, the other thing that we see with fresh neutron stars is pulsars. So you've got this neutron star that's spinning hundreds of times a second and releasing these powerful blasts of radio waves, and they use them for timing and all kinds of interesting things. And then slowly, as these neutron stars get older, they wind down, they slow down, and they just become boring, plain old regular neutron stars, as opposed to cool magnetars or pulsars. And so the question you're asking is like, can you add mass to a neutron star to turn it into a black hole? And the answer is probably, maybe. So if you add mass to a neutron star, obviously you're going to reach a point where it can no longer be a neutron star. And so the question is, one idea is that when that happens, it suffers another core collapse and detonates as a different kind of supernova and disappears entirely. The other possibility is because you're adding material so carefully as it's sipping away at some binary companion, it's adding just a little bit of material at a time, that there might be some intermediate form in between a neutron star and a black hole. Like maybe you could have a star that's made entirely of quarks, like a quark gluon plasma, and it's smaller than a neutron star, but you can still see it. Light can still escape the gravity of this object. So as you add more material, keep sipping away at this companion star, you cross over this limit where the forces holding the neutron stars from smashing into each other, all the neutrons, all the particles inside of it, crunching into a black hole, is overcome, and it collapses down in and disappears, because now not even light can escape this object. So, you know, it's still various points of controversy as astronomers are still trying to figure this out. And so stay tuned to see if we can sort this out. Hopefully there are various tools out there. Like maybe we could detect one of these objects exploding. Maybe we could detect an object that is giving off a type of radiation, a signature that tells us that it might be one of these intermediate sized objects. We might be able to detect the moment when a neutron star collapses into a black hole. So yeah, it's a pretty interesting idea though. J.I. Pearson. If a black hole at the center of the Milky Way is 4 million solar masses, wouldn't it then only exert 4 million solar masses worth of gravity on the Milky Way? Yes. Yes. If the thing only has 4 million times the mass of the sun, then it only exerts 4 million times the mass of the sun's worth of gravity. You know, people think that the supermassive black holes at the hearts of various galaxies are like these giant anchors of the entire galaxy, that without this supermassive black hole, then the whole galaxy would just fall apart. And the answer, of course, is that that is not true. The mass of the supermassive black hole is a fraction of a percent of the mass of the galaxy itself, say the mass of the Milky Way or the mass of Andromeda. And if you took the supermassive black hole away, almost nothing would change with the galaxy. The thing that is the gravitationally dominant part of a galaxy is the dark matter halo that surrounds the galaxy. It is like 10 times the mass of the visible matter in the galaxy. And it is like this giant swirling sphere of dark matter. And way down inside that, you've got the galaxy that is sort of at the center of this dark matter halo. And way down inside that, you've got this supermassive black hole. And the whole dark matter halo is rotating, and the galaxy's inside rotating with it. And so it's the dark matter that dominates the movements of the galaxy, not the supermassive black hole. It is just another passenger along for the ride. Raphael Domenichini, can a star collapse directly into a black hole without a supernova, without ejecting any mass? In theory, yes. And it's seeming more and more likely that this is actually more common than we ever thought. The original idea with a supernova turning into a black hole was that you would always get this core collapse supernova, that runs out of fusion in the core. It burns different elements all the way up to iron. And then when it reaches iron, then it can no longer support fusion in the core and it collapses in on itself, produces a black hole, material bounces out and you get the supernova. And there's been a few examples now of what were stars that should have created supernovae that are just gone. They just disappeared. And so the thinking now is that in fact, if the conditions are right, you can have all this infalling material turn into a black hole. And it's so efficient that it doesn't get that supernova ejection event at all. And so it might be that there's a certain amount of mass, or maybe there's a certain amount of speed that the black hole is rotating and the size of its accretion disk, or maybe if it has some kind of interaction with a binary companion. But it's looking more and more likely that there are some giant stars that when they die, they just wink out. They just collapse in on themselves and disappear, and you're left with the black hole. And this is absolutely on the cutting edge of astronomy at this point. And I wouldn't be surprised if we learn a ton more about these in the coming years, especially as we get incredible observatories like Vera Rubin, which is scanning the sky every couple of nights. They'll be looking for stars that disappeared. And it might just be that we don't see as many supernovae out there as we should, because the stars are just imploding, which is amazing. John Minton. Hey, Fraser, how do neutron stars' lives come to an end if they turn into black dwarfs or explode? So neutron stars, of course, are the degenerate remnants left over when a star much larger than our sun goes supernova. And the star explodes, collapses down, all this material crams into the small area, and you're left with this neutron star remnant, this rapidly spinning object. In the beginning, it's a pulsar because it's spinning so rapidly, in many cases hundreds of times a minute, and releasing beams of energy. And then it slows down over time and eventually cools down to the background temperature of the universe. And then that's how it dies, is it just gets cool and stops being exciting. Now, in theory, more material can fall onto the neutron star. It could collect material from a partner, or maybe just over vast amounts of time. It will collect photons from the cosmic microwave background. It'll collect dust. It'll collect random shreds of planetoids and interstellar asteroids and things like that. And maybe it could collect enough mass that it would fall over some limit and become a black hole. But we haven't seen this happen yet, but you can imagine in the far future. James Moore, can a black hole absorb dark matter? In theory, sure. It all depends on what dark matter is, but the main assumption that astronomers have is that dark matter is a particle of some type. And anything that goes into a black hole stays inside of a black hole. The tricky thing about dark matter is that astronomers think that dark matter, even though it's some kind of particle, it doesn't interact with regular matter or itself very easily. And so when you have regular matter, say you've got gas and dust that's swirling around this black hole, this gas and dust is bonking into each other and slowing itself down. It forms this big accretion disk, and then this accretion disk spirals in and goes into the black hole because this material can kind of collide with itself and apply friction across the entire process. And that's what helps drag that material inside the black hole. But the thinking is that dark matter doesn't have any kind of cross section. Two particles of dark matter could fly towards each other and essentially pass through each other, or get, a Planck length apart and still not actually bounce off each other. And so you wouldn't get dark matter accreting around a black hole in the same way. Of course, one of the other theories is that dark matter is actually black holes, that there were black holes formed at the beginning of the universe, these primordial black holes. And so can a black hole absorb dark matter when that dark matter is a black hole? Yeah. The Late Night Gamer. Could a black hole be survivable with solar systems inside perfectly safe? Probably not, but it depends on the size of the black hole. So we know that when you have some compact object, I mean, just Earth is a good example, right? The Earth is an object with gravity. And if an object gets too close to the Earth, it enters what's called the Roche limit. And that's a region where essentially the gravity pulling on the front side of this object is different, so different from the gravity pulling on the back side of this object that it gets torn apart. And then those pieces get torn apart and they get torn apart. And so as a moon, say, got really close to the Earth, it would get torn apart and torn apart and torn apart and just go into orbit. And then it would crash down onto the surface of the moon. And the same thing would happen around a black hole. If you got too close to a black hole, the gravity pulling on your feet would be stronger than the gravity pulling on your head, and you'd be pulled in half. And then the gravity pulling on your feet would be stronger than the gravity pulling on your torso, and then that would be pulled in half. And so you would just be turned into this stream of particles as you would go into the black hole. And that would suck for you, and it would suck for the planet you live on. Obviously, the planet would just be smeared out and turned into, like, a solar system could not survive. But if a black hole is bigger, then the event horizon is smoother and the tidal forces on you are less and less extreme. And so for a stellar mass black hole, if you got really close, yeah, you get torn apart. But if you had a supermassive black hole, something, say, the size of the one at the heart of the Milky Way, then you could pass in through the event horizon of that black hole and not really know that you were experiencing these tidal forces. But as you got closer and closer to the center, you would. And that's where you're going. You're inevitably heading towards the center of the black hole. And so if you had, like, some of the most massive black holes in the entire universe, ones that are billions of times the mass of the sun, then you could imagine a planet passing into the event horizon and orbiting around inside this event horizon and not being torn apart. But there's going to be tons of radiation and other forces, gravitational forces and stuff that are going to be acting on it. And so that would probably still make it for a bad day. But if you could stay outside the black hole, they actually serve very useful things. One of the coolest ideas that I've ever seen, like a place to have the most population possible, would be you would have like a supermassive black hole, and then you would have smaller black holes orbiting around that supermassive black hole, and then you would have planetary systems orbiting around those black holes, and it would be gigantic and stable, and you could eventually come up with a solar system with tens of thousands of planets all orbiting black holes and relatively close to each other in perfect stability for a long period of time. And maybe that's what some future civilization will do. But no, you don't want to park your home inside a black hole. Max, what would happen to a warp drive inside the event horizon of a black hole? Could it potentially escape it? Sure. I mean, the whole point about a warp drive is that it can warp space so that you can go faster than the speed of light. And the definition of a black hole is a region where the escape velocity is so fast, you would need to be going faster than the speed of light to escape. Then in theory, you could use a warp drive to escape a black hole. In fact, like in Star Trek, right, if a spaceship ever fell into the event horizon of a black hole, it would be trivial because they go thousands of times the speed of light. It would be very easy. Like they could escape any kind of black hole. Now, there's one caveat to that. One of the sort of definitions for what a black hole does is that it also tangles up space-time inside the event horizon of the black hole so that all pathways lead to the singularity, to the center of the black hole. And so in a traditional sense, if you said, oh, if I could just go faster than the speed of light, would I be able to escape a black hole? And the answer is no, that in any direction, like if you could go faster than the speed of light, you would just reach the singularity faster because there are no pathways out. But who knows how your warp drive works? If your warp drive actually works by modifying space-time, dismantling, changing, then maybe you could clear a path forward. It all depends on how your warp drive works. How does your warp drive work, Max? Romulus XC. Hey, Fraser, what are your thoughts about rogue black holes? Do you think there could be one in the solar system in the future? Yeah, so there was a news story that we covered on Universe Today just in the last week or so about a rogue black hole that was discovered that's only 5,000 light years away. And so all of the black holes that have been discovered, all the stellar mass black holes that have been discovered so far are in some kind of binary system. that you can only detect their existence through the gravitational interactions of some other star that they're orbiting around. Maybe they're consuming material, their accretion disk is blasting off radiation, and so you can detect the existence of this black hole. You can't detect the black hole directly, but you can detect it because of what it's beside. But astronomers were able to directly detect a rogue black hole through, I think it was gravitational lensing. So they're able to just detect the existence of this black hole. And it's 5,000 light years away. That's very far as a human walks, but not very far when you think about just the scale of the galaxy. It's in our neighborhood. Now, if that black hole was here in the solar system, it would be in charge of the solar system. It would be 10, 12 times, 15 times the mass of the sun, essentially 15 times the mass of the rest of the solar system combined. So it would utterly destroy the solar system if it passed through. And so the fact that the solar system hasn't been destroyed, hasn't been completely disrupted, means that a rogue black hole has never come close enough to do any damage in 4.5 billion years, which means that you can extrapolate forward and say, oh, in another 4.5 billion years, 10 billion years, in the lifetime of the sun, the chances of a black hole coming that close to us are exceedingly low. So don't worry about rogue black holes. I mean, worry about them in that they're terrifying, but don't worry because one will almost certainly not come within our star system. Although rogue black holes do go through solar systems. There's one destroying a solar system somewhere out there in the universe right now. Jeff Wilkie. Would a diamond spaghettify entering a black hole? I don't know the answer for sure. So I guess the question is if you fell into a black hole, as you got closer and closer, the tidal forces of the black hole would tear you apart into two pieces, and then the two pieces would be torn apart, and then you just eventually end up as this single atom width stream that would get wrapped around the black hole. And so would the same thing happen to a diamond? It just depends on the size of the black hole, the event horizon of the black hole. If you have a supermassive black hole, you could fly in your spaceship through the event horizon of the black hole. It'd be very smooth. You wouldn't feel the tidal forces. You wouldn't even know that you passed the event horizon, but now you're stuck inside the black hole. Well, if you were getting really close to a stellar mass black hole, the tidal forces would be extreme and you would be torn apart in that horrible spaghettification way. And then would a diamond? I mean, depends on the size of the diamond, but I would expect, that there is a Roche limit, a point at which you get close enough to a black hole that even a diamond will be torn apart into its component pieces. Depends on the size of the black hole. And the math for that is beyond me.
Here's a black hole fact. If you made a black hole with the mass of the Earth, it would have an event horizon about the size of a marble, less than 1 centimeter.
Lazy beach bum. Are black holes really dark stars? Yeah, really, really dark stars. Like a black hole is just a star. It's just a type of star, a dead star. It was once a star, it exploded, the outer layers collapsed inward and smushed the center down and crunched it into so much density that the escape velocity of the star exceeds the speed of light. And therefore you can't see it because it is absorbing all the light that it's trying to emit. Any light that's trying to get past it goes into it. Any matter that's trying to go past it goes into it. But it really is at the heart of it just a star. It was once a star and now it is whatever it is inside the event horizon, and we don't really know. It is a star. It's definitely not a hole. Like I would say a dark star is a better description than a black hole because it's not black, although dark isn't great either, but it's not a hole. It's definitely a star. So I think you're 50% better of explaining what these things are than black hole. All-time epic. Can a solar mass black hole eat a supermassive black hole? No. Whatever is the more massive black hole is doing the eating. And so in this scenario, a supermassive black hole will gobble up a solar mass black hole. But what's really happening is that black holes are merging. Say you had two supermassive black holes that were orbiting around each other and they got closer and closer, and then they merge into one supermassive black hole with twice the mass. They are merging into one larger. And so you have a disparity in mass. You have one that is, say, 150 times the mass of the sun and one that is 40 times the mass of the sun. These two black holes merge and you end up with a black hole that is 190 times the mass of the sun. They are merging. And so at all times, whether you've got a black hole that's only, say, 10 times the mass of the sun and a black hole with 1 billion times the mass of the sun, they are merging. And now you have a black hole with 1 billion and 10 times the mass of the sun. Dylan Green, longtime listener, first-time caller. Is there any aspect of dark matter that can't be explained by black holes? What is the reason for scientists leaning towards the WIMP explanation? So you can't rule out black holes as an explanation for dark matter. If you have primordial black holes, if black holes could have been formed at the very beginning of the universe in regions of overdensity of varying masses, and as long as they're like within the mass of an asteroid to like 1,000 times the mass of the sun, they can explain dark matter. And so if it's 1,000 times the mass of the sun, you just need one of these black holes every giant chunk of space, or you could have one asteroid size in every star system sized amount of space, and it would explain it. And it has not been disproven, but it doesn't necessarily mean there's any evidence for it. But there are ways that you can disprove it. And so the way that astronomers are working to try and figure out if primordial black holes can explain dark matter is they're looking for gravitational lensing. So you look at a galaxy like Andromeda, you scan the whole galaxy for a long time, and you're watching for any brief flashes of light where a black hole is moving in front of a star or something else and acting like a lens. And when you have that lensing moment, it tells you the mass of the black hole that moved in front of it. And the frequency of these events will tell you whether or not black holes will explain dark matter. And so these surveys are actually being done. Astronomers are looking for it. The other thing is that if Hawking is right, the smaller black holes, ones that are smaller than, say, the mass of an asteroid, should have evaporated and in their final moments given off this blast of gamma radiation. And so astronomers have looked for blasts of gamma radiation out there in the universe, and they haven't seen them. So what that means is that if black holes are dark matter, then they have to be like planet mass or bigger. And they had to have been that way right from the very beginning, because that's the minimum amount of mass that could have evaporated. And so we wouldn't be able to see any evaporation events yet. And so over time, astronomers are constraining, if they are primordial black holes, then how massive they can be, where they can be located, how they interact. And we may get to this point where the research in gravitational microlensing has been done so well that it is essentially ruled off. Those lines have crossed, and now black holes have to be less than the mass of a star, and yet Hawking radiation rules out black holes larger than the mass of a star, and black holes disappear as a possibility. But the way science works is that you're allowed to come up with any crazy idea you want. Sure, black holes are dark matter, no problem. You then just have to try to disprove it. And so astronomers' time is spent attempting to disprove their own theories. And if you can't disprove it, then your theory might be right. So black holes as dark matter can't be ruled out, but there's no evidence that it is. And so more research is necessary. Cujo and friends, do you think we'll ever have the technology to send a probe into a black hole and receive data? No. No, the problem with black holes is that nothing, not even light, can escape them. So if you send your probe in, then it can't send its data back out. And those are the laws of physics as we understand them. So do the laws of physics not work as we understand them? Maybe. Will we figure out a way to defy the laws of physics as we understand them today and come up with a new way? Maybe. But don't count on it, but don't rule it out. We'll have to find out and see what happens. But no, unfortunately, the problem with a region that absorbs all matter and energy that falls into it is you can't get any energy out, even a signal that tells you what's going on inside of it. There might be some ways that we can learn about what's going on inside black holes by examining the event horizon, but there's no way for us to get any information from beyond the event horizon. Crow T Robot 313. Everyone describes black holes by their mass. It's almost never mentioned what their diameters are. Is there a rule of thumb about how large a black hole is in comparison to the sun? Are solar mass black holes a quarter the diameter, half size? What about supermassive black holes? You can really only measure black holes by two things: their mass and their spin. That's it. And so from that, you can essentially calculate everything else that's going on with the black hole. And when you talk about the size of a black hole, you're really talking about the size of the event horizon, the region, the point at which nothing, not even light, can escape the grasp of the black hole. I mean, the actual black hole itself that's inside the event horizon, it could be tiny, it could be infinitely small, it could be almost the size of the event horizon. We just don't know, and we may never know. And so when you're talking about the size of the black hole, you're talking about the event horizon. And that's kind of confusing because it's like you're saying, like, how big is the black hole? And if you talk to a physicist, you say, how big is a black hole? They'll go like, we don't know. And then you say, well, how big is the event horizon of the black hole? And they'll go, well, that we know. And so we're going to have to talk about the size of the event horizon. And there's a very specific, very relatively straightforward math to calculate the event horizon size of the black hole compared to the mass. If you know the mass of your black hole, you can calculate the event horizon. And I like to use Wolfram Alpha as doing a lot of the calculations that I do for some of the shows. And so if you just type in Wolfram Alpha, black hole mass sun, you get the event horizon radius of 2,953 meters. In other words, 3 kilometers. So if you had a black hole with the mass of the sun, which you can't, then it would be 6 kilometers across, or have a radius of 3 kilometers. Now, if you had a black hole that had 10 times the mass of the sun, which is a more normal size, then you'd have an event horizon that is 29 kilometers in radius. In other words, it would be 60 kilometers across. And if you had a black hole that was 1,000 times the mass of the sun, then you'd have an event horizon that is 2,953 kilometers radius. So 6,000 kilometers across. And so you can see this number just goes up. And so you can just go run this math. And you can see it's a very linear progression. As the mass of the black hole goes up, the size of the event horizon goes up. HPA 97. If Planet 9 is a primordial black hole, wouldn't it be almost impossible to detect it due to having an incredibly small event horizon? So one of the explanations for Planet 9 is that it's a primordial black hole. And this just sort of goes to explain why we haven't seen it yet, how we could have an object that is interfering with other objects in the outer solar system through its mass, and yet it seems to be invisible. It's very hard to detect. Now, the most likely answer is just that it is faint, or that it is dark, or that it is like a little farther away than we thought, or it's just we haven't scanned the sky with enough detail to be able to find it. But this kind of crazy theory is that it's a primordial black hole left over from the formation of the universe, which is one possible explanation for dark matter. Almost certainly not true, but you can't rule it out. So put it on there as the theory. So the question is, like, how would you detect it? And black holes, even when they're not actively feeding, will occasionally give off gamma radiation. The supermassive black hole at the heart of the Milky Way does this from time to time. So when a little bit of material falls in, it doesn't have to be a lot either, like an asteroid's worth of material falls into the supermassive black hole, it's such an extreme event that it releases this burst of gamma radiation. And so the theory is that if we do have this primordial black hole, it's still occasionally eating teeny tiny little bits of matter, the occasional hydrogen atom. It's releasing this little bit of gamma radiation as these annihilations occur, I guess, as this material is added to the mass of the black hole, and you get little pops of gamma radiation that could be detectable if you had a spacecraft out there looking for it. So that's how you might be able to find it. But it's a long shot. Brandon Louisides. How do the gamma rays escape the gravity of the black hole? The gamma rays are not coming from the black hole itself. They're coming from the event horizon. And so you can imagine as some tiny asteroid, some tiny little piece of dust slams into the primordial black hole's event horizon, the dust gets smashed up, turned into plasma. And the plasma, just as it's going into the event horizon of the black hole, releases a little chirp of gamma radiation. And it's that gamma radiation that you detect. So it's coming from just outside the event horizon. And it's the same case. Whenever we detect gamma radiation coming from black holes across the universe, we're not detecting it from within the black hole's event horizon. We're detecting it essentially matter that's just about to die. The moments that it's dying, it is melting and releasing this gamma radiation. Stubby 1085. I've heard that if black holes have a Planck star center, they will eventually go supernova. What would a supernova for supermassive black hole be like? There's no reason to believe that a black hole is going to go supernova. There's no possible way. Imagine, right? The force of gravity that is holding a black hole together is so strong that nothing, not even light, can escape it. You can't explode as a supernova. Gamma radiation can't escape out of it. Material, debris, nothing. Once it becomes a black hole, there's no way back. Now, the idea of a Planck star is that maybe, you say you've got a neutron star, which is already a very compact object. You've got all the protons and the electrons mashed together, and they are sort of forming this ball of neutrons. And then maybe it's feeding off of some companion object and gathering more. And maybe then it reaches some limit that makes it compress down one more step and moves into a smaller object. And we don't know. They're called like strange stars or Planck stars. And we don't know if these things can possibly exist. And then if this object continues gathering more material, then maybe it finally collapses that one more step and becomes a black hole. But once it's a black hole, the only way it's ever going to die is through Hawking radiation, through slowly evaporating its mass over the entire lifetime of the universe. Indra, how do supermassive black holes form? We don't really know. I mean, a supermassive black hole is one at the heart of the Milky Way, 4.1 million times the mass of the sun. There's one at the heart of Andromeda, like 100 million times the mass of the sun. That's a very massive object. And the farther that astronomers look out into space, the further back in time, just to hundreds of millions of years, they are detecting supermassive black holes. And so the one idea originally was that supermassive black holes formed through the mergers of smaller. You had giant stars, the stars died, formed black holes, the black holes merge, a bunch of them merge. You had 10 black holes that emerged over here, form a 10 over there, they merge, you get 20 mass black hole, and so on and so forth. But it seems like they're too soon, that the supermassive black holes were already fully formed just too early into the universe. And so the other theory is that they just formed directly, that you had this giant ball of gas and dust that just collapsed down in on itself and turned into a giant black hole directly without having to go through all those intermediate steps. And then the third possibility, and not a lot of people believe this, is that they could be primordial black holes. So back at the beginning of the universe, there were overdensities and underdensities, and it's possible that those regions that were overdense just turned into black holes right at the beginning of the universe. And so we should have these, of all sizes, supermassive black holes with less mass, black holes down to the mass of an asteroid or a house, could have been all existed at different masses. And then the supermassive black holes that started out just gathered more mass and sunk into the bottom of galaxies and galaxy clusters. So, but right now we don't know. It's one of the mysteries in astronomy, which is like, how do they get so big so fast? Let's find out. Douglas Wilkinson, when two black holes collide, the resulting black hole is always several solar masses less massive. How is this possible? Yeah, when you see reports of two black holes colliding, you get the two black holes, their masses, you get a mass of the black hole that remains, and it feels like the numbers aren't adding up. And the other thing that you see is that a large amount of energy is released from this collision that takes away from the mass. And what's really happening is that essentially the black holes, as they are spiraling into each other, have a tremendous, like a mind-bending amount of kinetic energy. And when they collide, that kinetic energy is converted into gravitational waves. And so the gravitational waves aren't actually coming from the black holes themselves. It's coming from the kinetic energy of their collision. And so you'll see things saying like 5 solar masses of energy, or 5 times the mass of the sun of energy was released, things like that. And that's coming from the kinetic energy of the colliding black holes, not from the black holes themselves. They're not actually giving up their mass to create this new larger mass black hole. It's the energy of their collision that's causing it. Liam O'Reilly, do you think that dropping antimatter or dark matter in a black hole would do anything? Sure. Dropping either antimatter or dark matter into a black hole would increase the mass of the black hole by the amount of the mass of the antimatter or the dark matter that you dropped into it. And we get this question a lot about antimatter. People say, like, could you use antimatter to destroy a black hole? And the answer is no. Let's say you had a star that was 10 times the mass of the sun, fully made of antimatter, and you fed it to a black hole, and the black hole was 10 times the mass of the sun, you would end up with a black hole that had 20 times the mass of the sun. It would gobble up that antimatter star and gladly add its mass to its own. And when you think about this process, like, what is antimatter, right? Antimatter is the equivalent of matter, has an opposite charge. When matter and antimatter interact, they release an enormous amount of energy. They annihilate and release essentially pure energy in form of gamma radiation. And yet, if you could take a whole bunch of gamma radiation and compress it down into a small area, you could turn that into a black hole. And black holes are perfectly fine to feed on photons of light that fall into them, photons that come from the cosmic microwave background radiation, cosmic rays, particles, antimatter, anything. Anything that goes into a black hole just adds to the mass of the black hole. Now, we don't know what dark matter is, but we know that it has mass. So if you add mass to the black holes are very good. They have one job, which is to get more massive as they consume things. So we don't know what dark matter is, but we can be pretty confident that if you added it to a black hole, you would just end up with a more massive black hole. Chris Ryans, if black holes shrink through Hawking radiation, do they not also lose mass? And how do they not lose enough mass to no longer be a black hole? Hawking radiation is this idea from Stephen Hawking that black holes can emit radiation from their surface and they evaporate. And the science is very complicated and it's more of a particle physics answer. And I'm not great. I don't have a really nicely rehearsed, here's why Hawking radiation happens. But we've done episodes about it. Lots of people have done episodes about this idea. So we're just going to sort of assume, right? You've got a black hole. You've got various particles that are being evaporated, that are being released from your perspective from the event horizon of the black hole. Mostly it's photons. You're mostly seeing heat. And so it gives the black hole a temperature. And the larger the black hole, the more massive the black hole is, the larger the event horizon is, the colder that temperature is. And for the most massive black holes, they're going to be kept from really evaporating or losing any mass because they're gathering the background heat from the cosmic microwave background radiation. But eventually, the background will cool down to almost absolute zero, and even those really massive black holes will start to evaporate. And as they evaporate, they'll get smaller and less massive as their mass is given off in radiation. And over time, as the black hole gets less and less massive, its heat, its temperature from an external perspective starts to go up. And as you get closer and closer to, say, the mass of an asteroid, it starts to pick up really quickly. The mass of a house, now your black hole is starting to look almost room temperature. But it's still black hole. It's still the mass of a house compressed down to such density that it remains a black hole. And then it gets down to the mass of, a car, right? And it's still a black hole. And the temperature gets hotter and hotter and hotter. It gets hundreds of degrees, thousands of degrees. And then in the end, it just gives off one final flash of gamma radiation, which is like the highest energy that it can release, and it's gone. And so it never like unblack holes into a neutron star and then unneutron stars into a white dwarf. It's just black hole right until the last moment. And what we would perceive as these black holes were evaporating away is these flashes of gamma radiation out there in space. And I did a great interview with Celeste Keith about primordial black holes just a week ago. And you should definitely check it out because we talked about a lot of these topics about how can we detect these primordial black holes? How long will they take till they disappear? And so on. And it's a pretty cool idea. Futurism memes. Hey, Fraser, why don't supermassive black holes suck anything up? Well, black holes don't suck. Yeah, they're pretty awesome. So they don't suck. But we imagine, or somehow people imagine, that black holes are like these vacuum cleaners that are sucking in whatever, the entire universe. But the reality is that for all intents and purposes, a black hole is just an object of mass. And you could replace the sun with a black hole of exactly the same mass, and all of the planets would just continue to orbit around this black hole. They wouldn't be sucked into the black hole. They would just orbit around it forever. And so the supermassive black hole at the heart of the Milky Way, it is just an object with a lot of mass that various stars are orbiting around it. And it's not sucking anything in. Now, stuff does collide with supermassive black holes, and you get like when a planet or a star goes into a black hole, you get this blast of radiation that comes out of it because it got too close. But it's kind of in the same way that if you got too close to the sun, you would fall into the sun. If you got too close to the Earth, if the moon got a lot closer to the Earth, it would go past the Roche limit, where the near side of the moon is pulled so strong, much stronger than the far side of the moon, that it gets spaghettified. It gets torn into pieces. It's stronger than the material strength of the moon can hold it together. And the moon would be torn into this ring, and this ring would go around the Earth, and then all the parts of the ring would be torn up, and they would all collide with the Earth, and you would end up with no moon and a very bad day for the Earth. And it's the same thing with a black hole. It's the same thing with the sun. It's the same thing with the supermassive black hole. It's just gravity doing what gravity does. Mac. Hey, Fraser, why do we never see moving images, real-time video of objects in the universe like the swirling around a black hole or pulsars pulsating, twin neutron stars circling each other, and so on? Will JWST be able to do this? There's a bunch of answers to this question. Like in some cases, it's because the object that you're looking at is too large and moving too slowly. And so, for example, if you were looking at, say, a supermassive black hole that was slowly rotating, and if it's, say, many million times the mass of the sun, it's going to take a very long period of time for things to change dynamically over time. But a lot of it is just that what astronomers see in their telescopes is not what the artist's impression is telling you. Like in the artist's impression, you're seeing these incredible swirling black holes with jets that are pouring out of them and accretion disks. But what astronomers see is one dot of light. And from that one single dot of light, and they're able to measure the brightness of that light, they're able to tell what material is circulating around the black hole, how the brightness is changing, when it's feeding, and so on. There's another classic example. There's a kind of star called a Mira variable. And these Mira variables are sort of will pulsate and grow in size significantly over a very short period of time, going from relatively small, say around the size of a normal star, and they'll puff out beyond, say, the orbit of Earth, and then they'll shrink back down, and they'll do this again on a very regular schedule. And if you could actually see that, it would be amazing. But again, what astronomers can see is one pixel of light in their sensor that changes in brightness over a very set schedule. You can have eclipsing binaries. You can have two stars orbiting around each other, sharing material. It would be just incredible to see up close. And again, what do you see? You see what looks like one dot that changes in brightness on a very set schedule. So the problem is really that there just aren't a lot of objects that we have the kind of resolution that you could see changes happening. For the stuff that we can see, when you think about how we can see the rotation of Jupiter, or how we can see the transit of Jupiter's moons across the planet, like these are things that we can record and actually see their movements. But there have been a couple of things astronomy related which have changed over time, and astronomers have been able to track them. One is there's a very famous star called V838 Mon, and the Hubble Space Telescope has been tracking this nebula that's surrounding this star for almost its entire time in orbit. And you can see what is this explosion blasting away from the star over multiple frames. But each frame is several years later, and the astronomers come back, they take another picture, and they show it. You can see the cloud of material expanding from the site of supernova 1987A, the closest supernova that we saw in the sky. We're now well over 30 years since this thing happened, and you can see how the light is changing as this supernova is expanding. We've seen some exoplanetary systems where you can actually see the planets moving around in orbit around the star. So just as our techniques get better, as our telescopes get better, we're going to be able to see more and more targets and actually see them dynamically change in ways that I guess your imagination is hoping to see. So will James Webb be able to help? Absolutely. It's going to be able to see things that were before just blurry blobs and actually bring in resolution. And if it comes back and looks at them every couple of years, we'll start to see. Brandon Warren, would it ever happen where two black holes could be on a ballistic collision course, that the two collide head on with enough kinetic energy that instead of merging, they destroy each other? Nope. Even if two black holes just crashed into each other directly, and you don't get that gravitational wave chirp as the two black holes spin closer and closer and merge. No, if they just crash into each other, boom, you get a new black hole that contains the mass of the two black holes that collided together, and now it goes off in search for more meals to feed upon. You can't destroy a black hole. You can't get out of a black hole. They're monsters. Dr. Brian Keating, what are the odds that the Event Horizon Telescope shows a movie of Sagittarius A star? I like the odds. Someone on Twitter said, if someone gives you a present and there's a tail wagging, you suspect you probably got a puppy for your birthday present. It is the Event Horizon Telescope. This is the same people that took a picture of the supermassive black hole at the heart of M87. At the same time that they gathered the data for M87, they also gathered all the data for the supermassive black hole at the heart of the Milky Way. It's the Event Horizon Telescope people. It's the Milky Way. What could this exciting discovery be? I'm guessing aliens. I'm guessing they've discovered aliens. I would just be shocked. The exciting thing would have if they had something to announce that wasn't that they were going to show us a picture of the supermassive black hole at the heart of the Milky Way. A lot of people ask me, why didn't they release that picture first? Because it's closer and it should have been easier. And the problem was that the dynamics of the area around the supermassive black hole at the Milky Way, it's smaller, it's a lot quicker. And so the image is changing over time. And so it's been really tricky to untangle the data that they gathered when they did their observing run for Sag A star. My hope is they're done, but we could always be surprised. Someone suggested that maybe there's a second black hole that's been discovered in the area. And so that would be interesting. We're just going to have to wait, but I would just be shocked if it wasn't, here's the picture you've all been waiting for. It's been years. Let's see that picture. Saravana Prasad Venkata Subramanian. Is there a size limit for a black hole, or do they just grow endlessly? There is no size limit. Black holes can grow endlessly. As long as there's material to feed on, black holes will grow and grow and grow. And you can imagine in the far, far future, there will be black holes, because all the stars will have died. All the galaxies will have just died. There will be black holes. And over time, everything will find its way into a black hole until you end up with black holes, like a lot of big black holes. And black holes will merge. And then you will also have stuff that just has avoided falling into a black hole, which is perfectly reasonable to expect. Even the cosmic microwave background radiation will fall into black holes and just continue to make them bigger. And the only thing that will stop them from making them bigger is in the distant future when they start to evaporate again, because there's just not enough material falling into them. But it's like a 1 followed by dozens of zeros years before that starts to happen. But until that, and they're just going to keep feeding and feeding as long as there's material to fall into them. But eventually they'll run out. It's just everything will have either fallen in or will be on stable orbits, moving away from them, and they won't be able to grow anymore. Selena Girl 69, do black holes eat dark matter? Yeah, in theory, we know that dark matter has some kind of gravity to it. So it's definitely attracted to other mass. And so if a piece of dark matter falls into a black hole, it should go in and add to the mass of the black hole. We don't know what it is, but we know that it'll add to the mass of the black hole. Chains 9, will dark energy ever get strong enough to tear apart black holes? Maybe. Dark energy is this mysterious force that was discovered back in 1998 that was a big surprise, and it turns out the universe is not slowing down as the mutual gravity of everything is pulling it together, but in fact it is accelerating. It is as if The analogy I always like to use, you take a ball, you throw it up in the air. What you'd expect is the ball is going to come back down to your hand. And you can measure the force of gravity by figuring out how long it takes for the ball to go up and come back down to your hand. Now imagine you threw the ball up in the air and it just accelerated away off into space. That would be surprising. You'd be like, that was not what I expected. And that is what the discovery of dark energy was. It's mind-blowing. So the question is dark energy consistent? Is it the same strength? Is it some repulsive force that is appearing in every cubic meter of space? And as you get more space, you get more dark energy, but it's constant. Or is the strength of the dark energy increasing? And if the strength of the dark energy is increasing, then in theory, you'll have this situation where, in fact, the power of the dark energy is so strong that it starts to tear galaxies apart. Because right now, a galaxy is held together by its mutual gravity, and it's stronger than the dark energy. But maybe one day the dark energy will be stronger. And then galaxies will be torn apart, and then star systems will be torn apart, and then planets will be torn apart, and then black holes will be torn apart. And eventually, every possible thing in the universe will be torn apart. And that's this idea of the big rip. And the answer right now is we don't know. There's no reason to believe that it is changing over time, that it is increasing. But but the measurement for dark energy hasn't been done with a level of precision to know an answer to that. But we will get an answer in just a couple of years. So the Nancy Grace Roman Space Telescope, which is kind of like a twin of the Hubble Space Telescope, one of its jobs is going to be to measure the strength of dark energy over time. And if we can tell, dark energy back in the early universe and more recently is exactly the same, then we can feel really comfortable that the strength of the dark energy isn't increasing. But if in fact dark energy was less in the past and more today, then yeah, we're leading towards that big rip scenario for the future. How does that make you feel? Does it make you feel like, oh no, my black holes are going to be torn apart at an atomic level? That makes me feel sad, existential. Isn't that weird? Like it's all going to happen long after we're dead. And yet, to know that our universe is going to be torn apart at an atomic level as opposed to cool down to the background temperature of the universe. But one gives us more time than the other. I don't know. It's funny.
Here we are at the 5-hour mark. Congratulations, you're halfway through. Now, here's a random black hole fact. Did you know that if you took all of the mass and energy contained within the observable universe and put it into a black hole, you have a black hole with an event horizon roughly the size of the observable universe? Weird. All right, let's carry on.
Cujo and friends. Will James Webb look at Sag A star? I got this question quite a bit. After we saw the incredible picture from the Event Horizon Telescope of Sag A star, people were wondering if James Webb, the greatest telescope that humanity has ever created, will also be able to look at Sag A star and do an even better job. And the answer is yes and then no. So yes, James Webb is an absolutely phenomenal telescope capable of producing images that will blow everything else out of the water that's been sent to space so far. But it's just a single telescope. So the thing that's really important to understand about the Event Horizon Telescope, the one that took the picture of the Sag A star black hole, is that it is a collection of telescopes spread out across the entire planet Earth. You had telescopes in Antarctica, telescope in Greenland, telescopes in South America, in North America, in Europe. And together, those telescopes, when they gathered their data, were essentially acting like a single telescope the size of planet Earth. And it's really hard. Like James Webb is big. James Webb is 6.5 meters across, but it is not the size of planet Earth. That is a very big telescope. Now, the trick when you do interferometry, when you gather the light from many telescopes at the same time, is that it allows you to get the resolution of a telescope the size of the Earth. So literally, if we replaced the Earth with a giant telescope, you couldn't get better resolution than what was gathered by the Event Horizon Telescope. But it doesn't give you the brightness. It doesn't allow you to see really faint objects. So when you're going to do a big interferometer, you have to look at very, very bright objects. And in the radio spectrum, there's not much brighter than the supermassive black hole at the center of the Milky Way and the one that was around at the center of M87. So James Webb will absolutely be looking at the center of the galaxy at some point. And it's actually really well equipped to do that because it's an infrared telescope. And one of the big problems for the longest time is that astronomers were unable to look into the center of the Milky Way. They actually had a name for it. They called it the zone of avoidance. In other words, if anything you wanted to look at was located in the zone of avoidance, essentially obscured by the core of the Milky Way, there was too much gas and dust to be able to image it. But astronomers, when they launched space telescopes, were able to use infrared. And infrared, that wavelength, penetrates gas and dust quite nicely. And so very dusty objects like the core of the Milky Way or newly forming planetary systems, things like that, now suddenly you can see infrared through what would have been opaque in other wavelengths. And so some of our best understanding about the supermassive black hole at the heart of the Milky Way, Sag A star, was taken with infrared telescopes. And sort of the greatest part of this is that we confirmed, and this is Dr. Andrea Ghez, who won the Nobel Prize. She predicted and she observed using infrared telescopes the stars whipping around this invisible space at the middle of the Milky Way. And they were able to calculate the mass of this object. Whatever it is, it has to have 4.1 million times the mass of the sun. And so what James Webb will be able to do is do the same thing that these infrared telescopes did, observing the region around the supermassive black hole. But you'll get blobs of gas that maybe are in the area. You're going to see stars as they go by. You're going to get a much better measurement of the positions of these stars and use that to calculate whether Einstein was correct about gravity and things like that. But the resolution of the Event Horizon Telescope, a telescope as big as a planet, is just so much greater. And we talked about this, that the size of the object that it was observing was as if you put a donut on the moon and then you observed it from that distance. And so, yes, James Webb will absolutely be used in observing the core of the Milky Way, but no, it's not going to be able to do a better image than the Event Horizon Telescope. Hectic. Both images from the Event Horizon Telescope seem to show that both the black holes are oriented directly towards us. Now, isn't that a bit weird? Could you elaborate? Right. One of the big surprises from the team using the Event Horizon Telescope to image Sag A star was that it does appear that the black hole is roughly face on. Now, it's not face on like we're looking down one of the poles of the black hole as it's spinning. And if some powerful jet emanated from the black hole will be blasted directly at us, it appears off axis by about 30 degrees. And so that's like almost halfway, 45 degrees, right, would be oriented mix between us. And if it was 90 degrees, then we'd be seeing it completely edge on. So I wouldn't call that exactly facing us. It's kind of what you would expect as a random outcome from a random distribution. But the thing that was a real big surprise to the astronomers was that the orientation of the black hole doesn't line up with the orientation of the Milky Way. One of the big expectations is that the Milky Way is turning and has an axis of rotation, and the black hole, shouldn't it be rotating in the same way? And it's not. It's flipped over on its side. And that's weird. And that was a surprise. And it makes you wonder what kind of event happened in the history of that black hole that caused it to be turned over on its side. Probably some interaction with another black hole, or like a lot of material falling into it that was coming in from a funny angle. So we're going to need to do a lot more observations of the event horizons of other black holes to start getting a sense if there's any kind of lining up between the rotation of the galaxy and the rotation of the black hole. M. Shepard, if a small primordial black hole passed through the Earth, would it experience any drag or friction? No. Now, if a small primordial mass black hole, so imagine like some black hole formed at the beginning of the universe and still hasn't evaporated till now, or maybe aliens fire a black hole. They from their particle accelerator at the Earth, it would pass through the Earth. It might accidentally bump into a couple of particles on its way through the entire Earth, but even that is unlikely. It's important to understand that when we think about matter and it feels like a physical object, right? When you're sitting in a chair, the chair is pushing back against you, but matter is actually mostly empty space. And when you have a primordial black hole, it might still have an escape velocity that goes beyond the speed of light, but it's a very small object and it will have a very small cross section. And the event horizon is going to be as small as an atom. And so the chances of this black hole bumping into a particle and gobbling it up are incredibly low. So even if it does pass through a couple of particles as it moves through the Earth, it'll pass right out the other side. No one will even notice. There'll be no change and it will move on. Tom Watson, if a planet falls into a black hole and then the black hole radiates away through Hawking radiation, where does the planet go? Good question. This is the black hole information paradox. And this is an unanswered question right now. For the longest time, black holes, like what happens to a black hole, was not that much of a concern. I mean, obviously it's a concern. You will be dropping material into the black hole and the black hole will grab it and store it. And so this was fine. I mean, you've got a planet and now the planet has turned into black hole. But when Hawking devised this idea of Hawking radiation, he introduced this really weird paradox, because as a black hole is evaporating and with Hawking radiation, and we've done whole videos about this and many people have done, so I'm not going to go too far into the details of it, but the particles that are coming off the black hole are coming from the event horizon, and they don't seem to be coming from the actual black hole itself. And so this violates one of the laws of physics about this idea of the conservation of information, that a planet went into the black hole and you can't just destroy the planet. You can't destroy all of the information that is associated with the planet, the location, the position, the spin of all of the particles. There's like dozens of factors that describe every particle inside any kind of one object. And it seems like a black hole, as the planet goes into the black hole, it wipes the information from the universe. And that seems to be just a paradox, a violation. And astronomers don't have a good answer for this yet. They are still trying to work. And there's been many ideas about it, like somehow as the black hole evaporates, it still releases the information that was encoded in the planet back out into the universe. There have been other ideas. And this is one of the big unsolved mysteries. If Hawking radiation is a thing, then this black hole information paradox is going to have to be sorted out. And right now, we don't have a definitive answer for it.
Here's a black hole fact. Black holes can spin at relativistic speeds, and yet the universe prevents them from spinning so fast that they reveal what's inside their event horizon.
Serban Nicolau. Is the orientation of the Sagittarius A black hole due to a previous merger with another black hole in an engulfed galaxy? One of the really interesting discoveries made with the observations of the supermassive black hole at the heart of the Milky Way, Sag A star, was that the black hole's rotation, its orientation, didn't line up with the orientation of the Milky Way. It's sort of rolled over on its side and roughly pointing towards us, like off by 30 degrees. And this was quite a surprise. Astronomers weren't sure. They thought it might be lined up with the Milky Way. Maybe it was off axis. And so how did a supermassive black hole, something with 4.1 million times the mass of the sun, end up not on axis? How did it get rolled over? And the answer seems to be through mergers. And this sort of goes back to the fundamental question of where supermassive black holes come from in the first place. Did they form from some giant cloud of gas and dust that just collapsed into one enormous supermassive black hole? Or did they form through the mergers of smaller black holes? And if you've got a black hole that's kicked over on its side, then that probably happened because two black holes collided, or maybe a third one, and you got this event that rolled it over on the side. When we look here in the solar system, we see that Uranus is rolled over on its side. And we see that Venus has been flipped over 180 degrees and is rotating backwards compared to the other planets in the solar system. So this adds some line of evidence to the possibility that the supermassive black hole at the heart of the Milky Way is the result of many mergers with other black holes that got it into its current position. Timothy Aaron. Can quasars appear anywhere in the universe or only near the edges? Quasars are actively feeding supermassive black holes. And they were a mystery for quite a while. We didn't really know what they were. They were first discovered, and astronomers knew that there were this point source of really bright radiation, and they could tell from the redshift that these objects were very far away, but they didn't know what they were. And it took a long time for them to work out the details, and they were finally able to discover these supermassive black holes that were the hearts of various galaxies, and realize that when one of these supermassive black holes is actively feeding on material, it blasts out radiation in twin jets. And if you have that jet pointed roughly towards us, then we see that as a quasar. And it's funny, actually, if you watch Cosmos, the old Cosmos with Carl Sagan, and he talks about quasars, and he's like, we're not really sure what they are. And that was back in the 1980s. Like, maybe they're black holes, maybe there's something else. And it's interesting how now, here we are, 35 plus years later, we know with certainty what these are, quasars. And you're right. We see quasars really far out. At this point, astronomers know about 1 million quasars scattered across the universe, but the closest quasar is 600 million light years away. So a little over 500 million light years away. And when you think about how light has been traveling to us for 13.8 billion years since the beginning of the universe, and the vast majority of the quasars are much farther away, isn't it weird? You expect if there's 1 million quasars, you would see them at all kinds of distances, but actually we see them farther away. And there is a reason. And the reason is because the universe that we find ourselves in today is a lot less active. There's a lot less galaxy colliding, a lot less star formation, just a lot less gas and dust that is going into brand new stars. And back in the earlier universe, there was a lot more mayhem, a lot more of galaxies colliding with each other, a lot of galaxies suddenly blasting tons of star formation, lots of gas and dust falling into the supermassive black hole and turning on the quasar. Now, it's possible that the Milky Way will gain a quasar in the far future when we collide with Andromeda in like 5 billion years from now. As the two galaxies collide, they bring fresh gas and dust, and it could start the supermassive black hole up again as a quasar. But really, we've missed the party. That where we find ourselves in the universe now, 13.8 billion years after its formation, most of the active star formation, most of the galaxy collisions and stuff happened within the first few billion years, and it's been going downhill ever since. And so we see quasars far away because we're looking farther and farther back in time when the universe was more active. Bobby Reynolds, can a black hole get crushed by its own gravity or eat itself? Like, a black hole is already crushed by its own gravity. Like, it wouldn't be a black hole if it wasn't matter that's crushed by its own gravity. If you took like maybe 10 times the mass of a black hole and you just let it hang out there, it would collapse into a giant star. The star would die as a supernova, and then it would form a black hole at the middle because the gravity is too strong for it to be able to resist. So it's already happened. But, what's kind of interesting is that black holes can eat other black holes. Like, what if a black hole got too close to another black hole and fell within its event horizon, and then the two black holes just merge? But yeah, like, a black hole is already the result of being crushed by gravity. Like, as far as we can't imagine a more crushed by gravity situation than a black hole. Gonzalo Lozada, do you think that antimatter black holes could exist? What would happen if it collides with a regular black hole? This is a question I've done a whole video on, and we covered this in Astronomy Cast, and it's interesting, this question keeps coming up. So there is no such thing as an antimatter black hole. There are just black holes, and black holes are made of black hole. They're not made of matter, they're not made of antimatter. And so follow this thought experiment. If you take the Earth and you feed it to a black hole, you've got a black hole that now has the mass of the Earth. But if you take an Earth's worth of energy and you feed it to a black hole, maybe in the form of light, you will get a black hole with the mass of the Earth, because through E equals mc squared. So you've got the
E, which is the energy that you're putting in, is going to be equal to the mass of the Earth times the speed of light squared. So it's an enormous amount of energy. And yet, if you fed that to a black hole, you would get a black hole with the mass of the Earth. And you wouldn't know which one it was. Was it a black hole made of energy or a black hole made of mass? So when you put matter and antimatter together, what you get is energy. And that can turn into a black hole just fine. And so if you had a black hole's worth of matter and a black hole's worth of antimatter and you mash them together, you would get 2 black holes worth of energy via E equals mc squared would be twice the mass of the black hole. So it just doesn't matter. Matter, antimatter, energy, it all just makes more black hole. And so if you mashed a matter black hole with an antimatter black hole, you ended up with a black hole with twice the mass. You wouldn't get that annihilation, that sweet, sweet annihilation that you were hoping for. This is not the way to get rid of black holes. Bravo 01. What would happen if you suddenly remove the black hole at the center of the galaxy? Does it really hold the galaxy together? Nothing would happen. A black hole, supermassive black hole, even though it can be millions or even billions of times the mass of the sun, is a fraction of the mass of the galaxy. It's about 1%. So if you take all the mass of the entire Milky Way and you take the supermassive black hole and you pluck it away, then the mass of the Milky Way is now 99% of the mass of the Milky Way. And nothing really changes except for stuff that was in the environment around the black hole. You've got these stars that are orbiting like comets around the black hole. They fling off into deep space, but the rest of the galaxy doesn't even notice. People always think of these supermassive black holes as the anchor, that they're the center of the galaxy, but really they're just the densest spot, the place where a black hole sunk down to at the very middle. The thing that really holds the galaxy together is the dark matter halo. What we see as this visible galaxy, this spiral galaxy, is actually just this tiny portion of this much larger blob of dark matter that is rotating in space, and the galaxy's inside rotating with it. So no, if you remove the black hole, nothing would change. And that 1%, that's just the visible matter. Like, that's not even the dark matter halo, which is more, several times more than the mass of the Milky Way itself. So no problem. Nutty Gains. Fraser, I'm confused. If nothing can escape a black hole, how can we see the radiation from the black hole? Love your videos. When we see radiation coming from a black hole, we're not seeing the radiation coming from the black hole. We're seeing it from the environment around the black hole. So when you've got a black hole, it has an event horizon of a certain size. And when material falls down into the black hole, conservation of momentum gets it spinning around and around the black hole faster and faster and faster. And that material is essentially trying to go into the black hole, but it's also trying to spin away from the black hole. And so it's held in this balance between going in and flying away. It can't get away. It's held by the gravity. And so more material piles in, and you get this torus, this donut, this disk of material around the black hole, which piles up and gets hotter and hotter. And eventually, around a supermassive black hole, it turns into a star that is orbiting around the black hole like a star. It's not actually a star, but it behaves like a star. It is fusing hydrogen into helium. It is releasing an enormous amount of energy, and it is casting out this energy into space, kind of like a star. And it's really just waiting to die. It's like the final scream of material before it goes into the black hole. And then when you add to that the black hole is spinning, like in some cases, 70% the speed of light, it is tangling up space-time. Its magnetic fields are twisting and turning around with this accretion disk, and it creates these beams of magnetism that go above and below the black hole, that channel this material up and down the poles of the black hole. And so if we are looking straight down the gun sights of an actively feeding black hole that's got this huge swirling mass of material around it, it's got this magnetic tunnel gun of material blasting out of it, then you can see this very bright radiation. But yet if you could get really close to the black hole, you would see this like super bright accretion disk around it. You would see these
pillars coming above and below it. And then inside of that, you would see this really bright area, the photon ring, where light is being pulled around in a circle around the black hole. And then inside that, you would see nothing. You would just have the event horizon of the black hole, this sphere, where whatever made it into that event horizon, now it's gone for good. No radiation is coming from that. It's only coming from the area around the black hole. And the analogy that I always like to use is, imagine you're in the bathtub and you pull the plug on the bathtub and the water is trying to get into the drain, but it can't because the drain is only so big. And so the water will start to turn around the drain, but it's all going down the drain in the end. And it's the same thing with a black hole, I guess, except for all the stuff that gets kicked back out because it's in such a bizarre, hostile environment around the black hole. Ernesto Marone. Hey, I'm curious about accretion disks on a black hole. Could a rogue planet pierce through? Density, thickness, temperatures. I've asked sometime before and I never got an answer anywhere. All right, this is your chance. I will give you your answer. So what is an accretion disk around a black hole? First, let's sort of take a look at the thing that you're trying to puncture with your rogue planet. An accretion disk is this super hot stream of material that is being fed into the black hole. So as a black hole is tearing apart a star or a planet, it can't eat the whole thing at the same time. It has to chew on it bit by bit by bit. And so what it does with its incredible tidal forces is it tears this object into a thin stream of material and it's whirling around the black hole. And over time, these particles are bumping into each other, and some of them are given enough of a drop in their orbital velocity that they can then fall into the black hole, while others are held up in this accretion disk for longer periods of time. Like, it actually takes a long time for material to fall into the black hole because everything is going around so fast and it's in kind of perfect balance. It's only through their interactions that material can be fed into the black hole. So let's take your scenario. You've got this rogue planet that is, and I'm like, why a rogue planet? But sure, a rogue planet is passing near the black hole and it's trying to go through the accretion disk. Well, the accretion disk is all of the planets that got too close to the black hole, all of the stars that got too close to the black hole. Well, your rogue planet has gotten too close to the black hole. It is no longer a rogue planet. It is now part of the accretion disk. And so it gets torn apart by the black hole and added to the accretion disk, and it takes its turn to go into the black hole. So I would say no, a rogue planet cannot pierce through the accretion disk of a black hole because it just can't survive the journey to get anywhere close to the accretion disk of a black hole. Everything just becomes part of the black hole.
Here's a black hole fact. The most massive known black hole is TON 618 with an estimated 66 billion times the mass of the sun. That if we brought it here into the solar system, it would have an event horizon 40 times greater than the orbit of Neptune.
By Gabtier 11. Hey Fraser, I have a question here. When we see the renders of accretion disks around black holes, we see them glowing very bright. Is it only due to that they are hot, or is it possible because there could be fusion in the open due to the extreme conditions? Thanks. Yeah, so when we see a black hole, right, we're looking at this object that is so intense that nothing, not even light, can escape its grasp, and so it is invisible. And yet, we know that black holes can shine brightly. In fact, quasars, which are supermassive black holes that have active galactic nuclei, where the quasar is actively feeding on material, these can be producing jets that are visible across billions of light years. Some of the brightest objects in the universe are black holes. So, why is that happening? And that is because black holes will accumulate accretion disks around themselves. And like, you could think of accretion disks, like the analogy that I always like to use is like you're in the bathtub and you pop the drain on the bathtub, and it's not like all of the water instantly goes down into the bathtub. Some just circles around, swirls and swirls as the limited exit pipe of the bathtub can slowly try to drain out the water that's in your tub. And it's kind of like that. So you see how the water takes on this circular, it starts to swirl. And it's similar to a black hole, but this is just like an analogy. It's not exactly what's going on here. So material is falling down into the black hole. The black hole is spinning. Material can't go directly into the black hole. It needs to go into orbit around the black hole first. I mean, like some can, if it hits perfectly into the event horizon, it goes straight in. But most of the stuff is doing a glancing blow. And when you think about orbital mechanics, stuff doesn't go straight in. Like if you have a satellite and you are having that satellite orbit around the sun, for example, it's going to follow that orbit forever. And if you give it a kick, if you hit it sideways, you're just changing the orbit. You're not going to cause it to spiral inward into the sun. You're just going to give it a different orbit, and you give it another kick and now it has a different orbit. The only way to make that satellite actually go into the sun is if it has a constant thrust, a constant acceleration that is slowing, I guess, a constant deceleration that is slowing it down. So it's got to have like a rocket engine on board. And so you've got all this material that is going around the black hole, and the stuff that is just missing is going into orbit. It's encountering other material that's already there. It's bouncing into itself, and it is essentially removing some of its orbital velocity and trapping it in orbit around the black hole. And more stuff that falls into the path of this region, this accretion disk, gets added to the accretion disk, and the accretion disk gets bigger and larger. And as more and more material falls into it, for like supermassive black holes, it can take on the consistency of a star. Like the stuff that is the most dense, the hottest, is actually starting to perform fusion inside this accretion disk. And that's where you get some of the really bright disks around these stars. They are glowing brightly in X-rays in the same kind of way as if they were a star. And what's really cool about this is you've got this accretion disk that's going around the black hole. And it could go that way forever, right? Like why, what would, as I mentioned, you got to give it some kind of kick. And so what's happening when you sort of really look at it very closely is these particles are jostling against each other. Some particles are getting kicks that are a little bit away from the black hole. Some are getting kicks a little closer to the black hole. And eventually particles are kicked so that they get close enough that they fall into the event horizon and they disappear. And so actually an accretion disk can be very stable around a black hole for a very long time before material gets kicked in and actually falls into the black hole. But yeah, they're bright because they are essentially one big star that is around the black hole, that is fusing hydrogen into helium and possibly other heavier elements, releasing enormous amounts of X-ray radiation and other wavelengths out into the universe so that we can see them and know, hey, that galaxy has a supermassive black hole in it. Sandesh D'Souza. Hey, Fraser, have we recorded any death of a black hole? Do we have the technology to see this event? So there's this theory by Stephen Hawking that black holes can die, that they can evaporate over long periods of time, releasing this Hawking radiation. And over time, as this Hawking radiation is released by the black hole, it decreases in mass. And as it decreases in mass, it increases in temperature that you're seeing the black hole. And as it loses more and more mass, it gets hotter and hotter and hotter. It loses its mass faster and faster. And eventually, it just releases one final blast of gamma radiation, and then it's gone. And the entire black hole has been released back out into the universe. This process happens at extremely long timelines, well beyond the amount of time that it would take for all of the stars in the universe to be born and die. Even the red dwarf stars that could live for 10 trillion years, the black holes won't start evaporating until a time way beyond that. And so the smallest mass stellar black holes will evaporate first, and then over time you move your way all the way up to the most massive supermassive black holes will have finally evaporated away, and there will no longer be any black holes in the universe. It's expected that this era will begin at 1 to the power of 40 years. In other words, a 1 followed by 40 zeros. So like if a trillion is 12 zeros, a quadrillion is 15. It's a big number, right? And maybe it could take 1 times 10 to the 100 years before the last supermassive black hole evaporates. And so again, this is an enormous number. So no black holes that are currently in the universe will have evaporated and died in this fashion. But there's this other idea of primordial mass black holes. And these are black holes that could have been formed during the early universe. And unlike the stellar mass black holes and the supermassive black holes, these could be any size at all. They could have the mass of an atom. They could have the mass of a house. They could have the mass of a planet, theoretically. And so, as I mentioned earlier on, the less massive one of these black holes are, the faster they're going to evaporate. And so it's believed that if there are any primordial mass black holes smaller than about the mass of a medium-sized asteroid, like imagine the kind of asteroid that the DART mission crashed into, those will have all evaporated across the entire universe. And every year that goes by, the next smallest mass of black holes evaporates and is gone from the universe. And you slowly ratchet your way all the way up to those first stellar mass black holes in that one with 40 zeros after years from now. And so, as I mentioned earlier, they're going to give off this flash of gamma radiation. And so this is something that astronomers have gone looking for and have theorized that, okay, if primordial mass black holes are a thing that exist, we should be able to see them out there somewhere in the universe. Let's look for those flashes of gamma radiation. They've looked, they haven't seen them, but it's not expected they would necessarily be very bright, and it's not expected that it would happen very often. And so you wouldn't necessarily see it. But this was like one idea for what maybe gamma ray bursts could have been, or maybe the background gamma radiation that we see in the universe is these primordial mass black holes disappearing one after the other. So this is an ongoing inquiry, and if anyone ever has like positive proof that they've watched a black hole evaporate, I'll let you know. Big brown sound. Question, is it more difficult to find a black hole or a brown dwarf? That's an interesting question because both are actually very challenging objects to find, and the method for finding each one of those objects is quite different. So let's talk about what it takes to find a black hole. So black holes obviously are invisible. They gobble up their own light, and so you can't see them. The only way you can see a black hole is if it's interacting with some other object. The most famous black hole is Cygnus X1, which is located about 7,500 light years away from here. It was actually discovered back in like the 1960s, 70s. It was the brightest X-ray object in the sky. So when astronomers launched the first X-ray telescopes into space, suddenly they saw this really bright X-ray source because the Earth's atmosphere blocks X-ray radiation. And they worked out that what this is a black hole. There is a black hole in orbit around a star. The star is feeding material into the black hole. The black hole has built up this accretion disk. It's got these jets that are coming out of it. And it is telling us that the black hole is here. And over time, astronomers have mapped this black hole better and better and better. And actually, fairly recently, we learned they were able to see exactly where the accretion disk starts, how the accretion disk forms these jets. We actually covered this in Space Bites just a couple of weeks ago. So that's one way that you can find a black hole. The other way that you can find a black hole is through its gravitational interaction with another star. And so actually this is another piece of fairly recent news, which many of you are probably familiar with. So astronomers look through the Gaia data, and Gaia is like my favorite spacecraft. And they were looking at the motions of hundreds of thousands of stars that were in binary relationships. So they could see these stars as they were wobbling back and forth because they're in some kind of gravitational dance with some other object. And they were able to eliminate all of them. They were like, that's a star, that's got a neutron star, that's going around a white dwarf, because they were able to see the other object in this binary interaction. But they were able to find one out of the 100,000 binary objects that they looked at where the star was just being tugged around in a circle around nothing. And they were able to calculate that, in fact, the black hole is there pulling with its gravity back and forth. Now, The supermassive black holes, you can find them again through their gravitational interaction. So astronomers were able to peer down into the middle of the Milky Way with an infrared telescope and see how the stars move around the center of the Milky Way as if they're like comets going around a star. Yet these stars are going around nothing. And when you do the math, when you look at the orbit that these stars are taking, you calculate that there has to be a mass there with about 4.1 million times the mass of the sun, and yet there's nothing there. And so that is a black hole. But then also astronomers back to the Cygnus X1 with the accretion disk, astronomers have been able to find active galaxies out there where you've got a supermassive black hole that is pulling in gas and dust, blasting out jets of material. There's a black hole there. So if you want to find a black hole, you either have to map the movements of hundreds of thousands of stars to see if any of them are orbiting nothing, or you use a very powerful telescope to search for active galactic nuclei, and those will tell you that, or very bright X-ray sources here in the Milky Way, and that will tell you that there is a black hole there. A brown dwarf is a very different object, right? A brown dwarf is a failed star. So it's made out of hydrogen and helium like the sun, but it hasn't gathered up enough mass, doesn't cause enough pressure and temperature in its core to be able to fuse hydrogen into helium directly. Instead, it does a form of fusion in its core where it fuses deuterium, and it gives off dramatically less light and heat. But it does give off some heat, and so you can detect these in the infrared spectrum. And these have been known for a few decades now, since really infrared astronomy has taken off. The most successful brown dwarf hunter was probably the WISE telescope, which was really a precursor to JWST. And now astronomers have seen these in JWST as well. And so in order to find a brown dwarf, you need to have an infrared telescope, and you just have to start looking. In some cases, you can look around some star, see if there's some kind of gravitational interaction like you would find an exoplanet. But in other cases, you just scan the sky looking for objects that are very dim, but they're visible in the infrared spectrum, just not very. You can't find them very far. I mean, you can only find them within a few dozen light years of Earth, unless you do find them around some other object, because they are so dim, so faint. And so astronomers are really still getting a handle on how many of them there are out there. So which is more difficult? Well, it's like black holes have a giant impact on their environment, even though they are invisible. And so you can see black holes that are millions of light years away, billions of light years away, and they're very bright if they're interacting with their surroundings. While brown dwarfs, if you have an infrared telescope and you know where to look, they're relatively easy to find, but you can't find them very far away from us. So if I had to choose, I would say a brown dwarf is more difficult only because we know of less of them. Bravo 01. Could there be hidden habitable worlds with advanced societies within the realm of an event horizon of a black hole? Within the event horizon? Like inside the black hole? No. Well, maybe. It depends on the mass of the black hole. So when you have a black hole, a stellar mass black hole, say a black hole with 10 times the mass of the sun, then the event horizon of that black hole is actually very small, just a few kilometers across. And if you get within the event horizon of that black hole, the tidal forces are going to tear you apart. That's that spaghettification. And we don't know what goes on inside the event horizon of a black hole, but you can assume it's just more spaghettification. Worse, because now all of space-time is tangled up into knots, and your atoms live in space-time, and they're now getting tied up into knots. So that would be a bad day. But if it was like a really massive black hole, say like the supermassive black hole at the heart of the Milky Way, or maybe like one of the really big ones, like the ones that are billions of times the mass of the sun, then they can be as large as the solar system. You could fly. There's no tidal forces, or almost no tidal forces, and you could fly into one of those black holes and not even realize it, but you're on a one-way trip. And so could you survive? Like, could you go into orbit around the singularity? We don't know. We don't know what's going on inside the event horizon of a black hole. It might be that a black hole is just like 1 centimeter below the event horizon, and then that's all black hole inside. Or it might be that the singularity of the black hole really is an infinitely dense, infinitely small object at the center of the event horizon itself. So we just don't know. So I wouldn't want to live inside a black hole event horizon, but living beside an event horizon is absolutely feasible. So when you think about the movie Interstellar, where they had these planets that were orbiting around this supermassive black hole, Kip Thorne, one of the pioneers of gravitational wave astronomy, did the math and figured out what it would take to be able to have a planet that close to a supermassive black hole. As you feed material into the black hole, it releases energy, releases heat that you could use. The downside, or maybe it's the upside, is that you're going to experience significant amounts of time dilation depending on how close you are to the black hole. And so you're going to experience a sped up universe because you're really close to the black hole. But this has been proposed. Like if you're nearing the end of the universe and all of the usable forms of energy have long gone, you could huddle up close to a black hole. And in fact, you would start to see a blue shifting of the cosmic microwave background radiation itself. It would go from microwave back into infrared and maybe even to visible light and higher. And so it would be like the whole sky was bright because you are seeing the blue shifted version of the cosmic microwave background radiation. And you could have used that for solar power until even that faded away. And the only way you could dilate your time faster would be to get closer to the black hole and fall into the event horizon. So it's a cool idea. And in fact, there's a great website where someone proposed like the largest possible civilization, where you would have like a really enormous supermassive black hole, and then you would surround that with other supermassive black holes. And then those supermassive black holes would be surrounded by more black holes. And then you would have planets orbiting around. And there's a way that you could make this whole thing be stable. And you could have millions of habitable planets orbiting in this system all together. Or maybe it was like a black hole in the middle and then stars. Anyway, you can sort of use black holes as gravitational anchors to build very complicated and very high population civilizations. And wouldn't it be cool, right? If you had a planetary system which consists of 10,000 Earth-like planets orbiting around 100 stars, and everything is in perfect clockwork motion. Nothing is getting out of balance. And if you want to fly to another planet, it's a short hop. We could do it with our technology. It's a really cool idea. So I wouldn't want to live inside a black hole, but it would be interesting to live near one. At Disinclined to State 9485, hey Fraser, a thought occurs. If two black holes by an unimaginable fluke had precisely opposite spins and then they merged, would they cancel out? What would a black hole that doesn't spin be like and look like? Yeah, in theory, right? Like all black holes are spinning. And the spin is the angular momentum that's left over from when they were a star and all of the material that falls into the black hole, and it spins it up. And in many cases, it's spinning it up to a significant percentage of the speed of light. And that is just caused by the accumulated material that falls into the black hole. It adds to the spin. And so, yeah, if you had two black holes that merged with each other and they had precisely opposite spins, they would cancel out and you would be left with a black hole that isn't spinning. And, you know, this is like, from what I understand, when you take your advanced astrophysics degree, you learn about black holes. First, they start things a little easily and they say, like, let's just imagine that the black hole isn't spinning. And then you learn all these calculations based on a non-rotating black hole. And then they go, but really, they're all rotating and life gets a lot more complicated. And the reason life gets a lot more complicated is because the black hole itself, well, all mass, but especially black holes, as they are rotating, they are frame dragging. They are pulling space and time around with them as they go. And what happens is that when you've got this accretion disk that forms around a black hole, if a black hole wasn't spinning, then actually matter would be able to fall into the black hole, into the event horizon sooner than one that is rotating. And one that's rotating, of course, this matter is sort of pulled around, swirled around as it's frame dragging. It gets a lot closer to the black hole. And astronomers can actually calculate how fast the black hole is rotating and how much of a gap there is between the black hole event horizon and the beginning of the accretion disk. And they look for a very specific kind of X-ray radiation that's coming from this accretion disk. There's a very specific kind of wavelength of X-ray radiation that iron gives off as it's just about to die. And in a black hole that is actually rapidly rotating, the energy level is lower because it's actually gotten closer. So I guess it's kind of like stretched out, spread out the amount of time it's taking for that iron to go into the black hole. And with a fast rotating black hole, one of the things that you get is essentially the event horizon flattens out like a oblate spheroid, and the poles of the event horizon sort of come together the faster this thing is spinning. But you can't actually reveal what's inside the black hole. There's like a limit. And so that's the idea of a naked singularity. So you can't get a naked singularity. But I can think of another situation where you might end up with a black hole that isn't rotating, and that is a pet black hole. That is, if you've got some super advanced civilization has a giant Dyson sphere around a black hole, and they are dropping matter into the black hole to extract the energy. It's called the Penrose process, and it's essentially one of the most efficient ways that you can gather energy in the universe. The black hole becomes a giant battery, and you are dropping material into the black hole. As this material gets broken up, part of it goes in, but part of it gets ejected sort of as it's just about to arrive in the black hole. It actually gets ejected out into space. You capture the energy from that ejected material, and you are harnessing energy from the black hole. But every time you drop material into the black hole and you harvest some of this rotational energy, you are slowing down the black hole just a tiny little bit. And so over vast periods of time, as your civilization consumes an enormous amount of energy coming from the black hole, it will slow down and slow down and slow down. And eventually the black hole will stop spinning, and you will no longer be able to extract any energy from it until you find ways to spin it back up again. You're going to have to go and find some galaxy to tear apart and feed into your supermassive black hole to spin it back up again so that you can then extract that rotational energy again. So that's what a black hole, if it didn't spin, would look like. David's Dream Factory. Is there a potential habitable zone around a black hole's accretion disk? We're going to have to use the term habitable zone quite liberally here, but in theory, there are a bunch of ways that you can live in a habitable zone around a supermassive black hole. But there are a lot of downsides. But some of the methods for keeping your planet warm, I think you're going to find really surprising. So let's just sort of think about the idea here, right? You've got this black hole, supermassive black hole. It's going to have millions, maybe billions of times the mass of the sun. And the black hole is going to be rotating, and it's going to have some amount of material that is falling into the black hole and getting accreted. And as this material falls into this accretion disk around the black hole, it compacts together and it heats up and it releases radiation. And that radiation is useful for a civilization that is relatively close. And the key is that you want the amount of material falling into the black hole to be a very constant amount. Like in the same way that we want the output from the sun to be a very constant amount, the same thing you want with the black hole. If the black hole is feeding on stars and then not feeding at all, and then feeding on another star, then you get these spikes in radiation that will change the size of the habitable zone significantly to the point that you are doomed. So you want to keep it just like whatever you do, you need to control how much material is falling into the black hole. So that's kind of like the main way. And, I can't give you any hard and fast numbers. I mean, every object, whether it's a neutron star, whether it's a black hole, whether it's a white dwarf, whether it's a dwarf star, whether it's a regular star, whether it's a brown dwarf, like anything that is giving off heat will have a habitable zone, a place where liquid water can remain liquid on the surface. But just the size of that is going to depend on the mass of the black hole. And, from my understanding in the movie Interstellar, when Kip Thorne and others did the math for the black hole in that, they actually calculated this point where that planet would be in the habitable zone of this supermassive black hole. I think it was like 250 million times the mass of the sun. So, it was a pretty big black hole. So that's the first way that you could have a habitable zone. But it's not the only way. So the next way that you could have it is due to time dilation. This fact that as you get closer to the black hole, then time slows down for you compared to the rest of the universe. Of course, in Interstellar, they were on this planet for a day, and when they came out, it had been 30 years. That was something like a 60,000 times acceleration of time. And that acceleration of time also causes a blue shifting of all of the radiation sources that are around this black hole. And so if you're going to have some star that is very far away and is giving off faint radiation in the red end of the spectrum, as you're close to the black hole, that light is going to blue shift and going to get into the visible light. And so you could very much have sources of illumination falling on your planet from stars that actually aren't part of the system. And if you get close enough to the black hole, the cosmic microwave background radiation itself will move into the visible side of the spectrum to the point that you could have the surface temperature on your planet be habitable thanks to the cosmic microwave background, which is in all directions and nice and even, and it's great. But you're going to get very close to the black hole for this to happen. And the downside is that you're going to experience an enormous amount of time dilation. And so you might experience 1 year and the rest of the universe experiences 10,000 years. So you have to be okay with not being able to interact with the rest of the universe at the same level of time. Another possibility is that you have neutrino flux that is coming out of the accretion disk around the black hole that's going to be impacting your planet and potentially heating up the mantle and raising the temperature on the planet. And then the other thing is that there could be gravitational waves that are coming off of the black hole as it's interacting with other objects, and they are going to be deforming the crust of your planet and keeping it warm as well. So there's some combination of the heat coming from the black hole, the time-dilated radiation coming from the entire universe, the neutrino flux coming off the region around the black hole, and gravitational waves. You can have some combination that someone might consider to be habitable. But all of the reasonable kinds of radiation that are going to get shifted into higher levels, all of the already extreme kinds of energy like X-rays and gamma rays, those are going to be pushed even to higher and higher energies. And so you're going to have some way to protect yourself from all of the downsides of being close to a black hole. But theoretically, all black holes have a habitable zone or various types of habitable zones.
So here's a random black hole fact. Black holes are neither black nor holes. That's it. Let's move on.
Scott Bringlow 6408. Love the podcast. I was reading about direct collapse black holes, and I was wondering if you can give an overview of the theory. Sure. So we have black holes here in the universe today. We have two kinds of black holes. We have the stellar mass black holes and we have the supermassive black holes. And the stellar mass black holes, they are formed when giant stars explode, and they form this black hole as part of the process. The supermassive black holes, astronomers aren't entirely sure where they came from, but they can be millions or even billions of times the mass of the sun. And the farther back in time that astronomers look with more and more powerful telescopes like JWST, they're able to see that these supermassive black holes were present at the hearts of galaxies, even within the first billion years of the universe. And the big question that astronomers have is like, what came first, these giant black holes or the galaxies that they're in? And how do you get a black hole with millions of times the mass of the sun so soon after the Big Bang itself? And there's a bunch of theories. One is that just regular stellar mass black holes found each other, merged, got bigger and bigger and bigger, and eventually you're just left with these really enormous black holes. It's kind of exponential, doubling as two black holes meet, and then two more black holes meet, and those black holes meet, and very quickly you find your way to these enormous black holes. But another idea is that the seeds of these supermassive black holes formed early on, directly out of the gas that was left over from the Big Bang, the primordial hydrogen and helium. And so unlike the process where you've got this giant star that has to go through its life for a couple of million years, then it's got to die, explode as a supernova, and the core collapses into a black hole, you could have some overdensity of hydrogen and helium in the early universe where the gas sort of swirls in, collects in this area, and it is enough material in this spot that it's able to collapse directly and turn into a black hole. And this is the direct collapse black hole. But the challenge is that as you bring this material together and as it gets closer and closer and closer, it starts to heat up. And that process of heating up will cause this outward pressure that's going to stop this material from being able to come down. And so the big challenge in astronomy is to figure out a way that you can actually remove heat from the process, that you can somehow cool this cloud to keep it from being able to puff up and prevent the process of turning into the black hole. And, this is still an ongoing series of research right now, but it appears that in certain conditions, you can have gas strip heat away from the larger cloud of gas where the black hole is going to eventually form, and you've got some kind of balance that you can strike. Now, if this theory is true, there should be some evidence of these early direct collapse black holes, and that will be radio jets. So just as quasars, for example, as they're feeding on material and they're getting this big accretion disk around them, the magnetic fields whipping around the black hole, interacting with the disk, create these jets of material that come above and below the black hole. And you would expect something very similar in the early universe. You would expect to have these early black holes forming these accretion disks, building up these jets that would be appearing above and below the black hole. And it would be visible in the radio waves now that it's redshifted so far from our perspective. And what's kind of cool about this is that the radio waves should be able to penetrate a lot of the surrounding gas that would be obscuring them from our view. And so there might be a way to detect these radio waves. And if we did, it would be very distinguishable, be a very specific kind of signal that would be very different from any other radio source that we would expect at that time. What's the machine that can do this? Probably the Square Kilometre Array, which is under construction right now. We probably won't see it until the 2030s. So we are within a decade of having the kind of telescope that could potentially gather evidence of these direct collapse black holes. And if that's true, then one of the major unsolved mysteries in cosmology, how did black holes get so massive so quickly, is solved. It's pretty exciting. John Hamilton, how do we know a black hole is spinning if nothing can escape it? Why isn't the information about its spin lost behind the veil of its event horizon? Shouldn't black holes therefore be spheres? We can detect the spin of black holes, and that's done through the interactions of the accretion disks around the black holes. So black holes, when they're spinning, they twist up space-time through this process of frame dragging. And outside of the black hole, you've got this accretion disk. And so the black hole, as it is twisting up the space-time around it as it's rotating, it's allowing the accretion disk to get closer to the black hole than it would if the black hole wasn't spinning. And you can actually look at a black hole, measure the distance of the accretion disk from the event horizon, and that will tell you how fast the black hole is spinning. Adon Barillon. How can black holes exist if their formation cannot be observed from the outside? All right, if you follow black holes and their event horizons enough, you've probably heard this concept that from an outside observer, as you're watching material fall down onto the black hole, it experiences time dilation. Again, we always use that example of Interstellar when the astronauts went down to the planet in orbit around the supermassive black hole. They spent a day on the surface of the planet, and yet when they came back out, the rest of the universe had experienced 30 years. And so they were experiencing time dilation. And so from the perspective of an outside observer, as material falls down closer and closer to the surface of the black hole, it experiences this time dilation. And if you're watching this material fall down into the black hole, over time, you'll see it move slower and slower and slower, and eventually it'll appear to just freeze on the surface of the black hole. And then it will start to redshift away, and it will just
fade away. From the perspective of the person falling into the black hole, you see the universe around you speed up, and you're actually watching hundreds, thousands, millions, billions of years pass by while you're standing there or being torn asunder by the tidal forces around the black hole. And so this question a lot of people get is, you're looking at the black hole. How can the black hole increase in mass if the material that is falling down onto the black hole never reaches it? It's all a matter of perspective. And so the thing to really keep in mind is that a black hole of a certain amount of mass has a certain size of event horizon. And as new material falls down towards the black hole, mathematically, from an outside observer, the black hole gains mass. So say you have a black hole with 10 times the mass of the sun, and then you feed it a star, then the black hole will gain in mass by another star. And the event horizon around the black hole will expand outward because the size of the event horizon matches the mass of the black hole. And it will include that material that fell into it. From your perspective outside, you see this astronaut, star, whatever, falling into the black hole and sort of freezing up and fading away. But from the perspective of the black hole, as it's increasing its mass, as it's increasing the size of its event horizon, it's able to absorb this additional mass. And mathematically speaking, the black hole has this additional mass pretty much as soon as it falls near to the event horizon. Aaron Calhoun, how massive does a star need to turn into a black hole after going supernova? So astronomers think that when the most massive stars die, they turn into various degenerate objects. So black holes, neutron stars. Actually, the most massive stars, when they go supernova, they just detonate entirely and disappear like a big puff of exploded star, and there's no remnant at all. But smaller than that, like less than, say, 50 times the mass of the sun, down to 8 times the mass of the sun, you're going to get a supernova. Smaller than that, actually. But anyway, the ending result is that if you have an object that has less than 1.4 times the mass of the sun, you get a white dwarf. If it's more than that, up to about 2.2 times the mass of the sun, you get a neutron star. And then beyond that, 2+, you get a black hole. But that is like the final result. Like that's the amount of material that's compressed into a small area that turns into a black hole. And so I think the question you're asking is like, how much star will give you that black hole? And it really just depends. Like it depends on how that star dies. How quickly does that star blast off its outer layers into space? How symmetrical is the explosion that happens when the material collapses inward? But it's roughly 8 to 10 times the mass of the sun at the bottom end. And so if you have less than 8 times the mass of the sun, you will most likely get a neutron star. And if you have more than that, you will most likely get a black hole. But it's a sort of moving target as people are figuring out more and more about this. And then one other thing, we talked about this last week, is this idea of an unnova, that there are certain objects out there that instead of, all the material collapsing inward and then you get the black hole and the material bounces, you actually get the material just coming together and then just turning into a black an And so it might be that actually smaller objects can turn into black holes as well, depending on how that material comes together. And that's still an unsolved mystery in astronomy. Dicky Chap. Hey, Fraser, something I've never been comfortable with is Hawking radiation, how the scientific community can be so sure it exists when there's no experimental proof of it. Isn't the entire principle of the scientific method that you make a hypothesis, you devise an experiment to prove it, and if that experiment determines conclusive evidence, then the postulation becomes accepted? Why is it universally accepted when there is no known way to prove it? Thanks. Hawking radiation is absolutely not universally accepted. It is a prediction made by Stephen Hawking that radiation and other particles should be able to escape a black hole as the black hole evaporates. We've done other videos about exactly how Hawking radiation works, and I've done bad ones. Like, there's much better places out there, like PBS Spacetime, where you can get really a great explanation of how Hawking radiation works and what the predictions are made by Stephen Hawking. But you're absolutely right. It has not been detected. It has purely been hypothesized by Hawking. And then you've got a lot of other scientists who are taking the ideas that are proposed by Hawking, doing the math, adapting it, applying it, seeing if it makes sense in other theories that are working. They're attempting to come up with ways that you can disprove his theory or ways that you can extend it. But you're exactly right. The proof is in the pudding that, my favorite people in the scientific community are the experimenters. So, like, the theorists are fine, right? Stephen Hawking, he's okay, but it's the experimenters who I really have a fondness for, because they are building an apparatus to search the universe to collect data. And in many cases, they don't know what to do with the data, right? When you look at the people who are detecting the accelerating expansion of the universe, that was not what they were planning to figure out when they measured the distance to these different supernovae. When you look at the people who were able to create the Large Hadron Collider or the LIGO facility to be able to detect gravitational waves, like, just the detail that goes in, the work, the painstaking process to make an experiment that is able to make those kinds of detections. Like, I have so much respect for the people who decide as scientists that they're going to follow the experimenter route. And the experimenters and the theorists, they work hand in hand. So the theorists come up with ideas, and then the experimenters try to prove those ideas or disprove those ideas. Or the experimenters study stuff and they generate data, and then they go, like, they hand this stuff in a pile in front of the theorists, and they go, I don't know what to do with this. What does this mean? And the theorists go and they do their math. They try to figure out what all this stuff is and how to be able to make sense out of it. And so the two really have this great hand in glove relationship, hand in hand together. But, like, I really like the experimenters. And so Hawking radiation is the perfect example of the kind of problem that theorists came up with it, did the math, made the predictions. Every other part of black holes is lining up nicely to what Hawking has predicted, but no, nobody has detected the existence of Hawking radiation. And nor could we using astronomy. Like, the distances are so vast, the time scales for giant black holes to radiate away is so long that we may never be able to find it. But there have been attempts. So one prediction made by Hawking is that you're going to have the smaller black holes are going to radiate away faster than the bigger ones. And if you have, say, primordial black holes, ones that were formed at the beginning of the universe, they would evaporate within minutes, within years, within millions of years, within a few billion years of the beginning of the universe. And so we would look out into space and be looking for that final gamma ray pop as the smallest primordial black holes are evaporating away. Astronomers have looked for it and they haven't found it. So the prediction that there are primordial black holes and that we can detect them through Hawking radiation hasn't paid off. But you can see, like, Hawking made this prediction. Astronomers tried to use that prediction to find primordial black holes that are evaporating, and so far they haven't been able to do it. And the other way to go about this is with the Large Hadron Collider. So when they smash atoms with high enough energies in the Large Hadron Collider, one of the possibilities is that you could get a black hole form from the particles. It would be very small, and yet it could form. And then it would, before it even hit the ground, it would have evaporated away in a little burst of Hawking radiation. And that's something that the experimenters could detect. And so far, they haven't been able to detect it, but there's another run of the Large Hadron Collider that's coming up that's going to try to do it. So this is the process. Like, Hawking made a prediction. He took a theory. Everyone thought the theory was very elegant. They liked it, but it is provisional and nobody has been able to find evidence to prove it. And they may never. And so it can never cross over into
a more established theory. And like at this point, people in the comments are going to have an argument about what the word theory means versus hypothesis versus, I don't know, criteria versus like all of these kinds of terms. But like Hawking had a hunch and experimenters are trying to see if his hunch might be correct. And we'll find out. Or we might never find out. That's okay too.
Here's a random black hole fact. Did you know that the tidal forces that you would experience getting close to a black hole are less the more massive the black hole is? And so if you got extremely close to a black hole with the mass of, say, 10 times the sun, you would be torn apart, spaghettified. And yet you could comfortably fly your spacecraft into the most massive black hole in the universe and you wouldn't even feel it. And yet you would never be able to escape.
Lars. So I keep reading clips about this black hole that is at the theoretical maximum mass allowable. What would limit the mass of a black hole? Would there be a hypothetical consequence of trying to cross that line? Yeah, this idea of the theoretical limit of a black hole, I'm not sure where this came from because astronomers keep finding quasars earlier and earlier in the universe, and they're surprised at how big these supermassive black holes already are, that they have put on more mass earlier than they ever thought in the universe. And it's making them start to question what are the underlying mechanisms for how these supermassive black holes come together. And we thought we knew those limits, and yet they keep finding larger and larger black holes. And so the original idea was that you had the first primordial hydrogen and helium left over from the Big Bang, and then some of this material collapsed down into the first stars. The first stars exploded. They enriched the surrounding material with heavier elements. Those clouds collapsed down. They formed the first like proper stars. Those stars exploded as supernova. They created black holes. The black holes found their way to each other. They merged with each other. And then the black holes that had merged and merged, they kept merging. And then you got supermassive black holes and larger supermassive black holes. And then you got one that has millions and eventually billions of times the mass of the sun. And this new black hole, the one that I'm sure you're talking about, I think it has like 30 billion times the mass of the sun, which is just terrifying. Like, I mean, it's just like a theoretically large number. And good news, it's really, really far away. But boy, that is a massive black hole. And you're seeing it really far away. And so you're seeing it earlier in the universe. And the question is like, how did it get so big so fast? And there are other ideas like, you know, that traditional idea of you just doing it the hard way with stars merging together and making bigger black holes. Like maybe those first stars that formed, the population 3 stars, maybe they had tens of thousands of times the mass of the sun, and they formed black holes that were tens of thousands of times the mass of the sun. And so that first step, when you go those first black holes and they're finding their way to each other, you don't need all those intervening steps. You just got monster black holes merging with other monster black holes. Or maybe we have this idea of primordial mass black holes. Maybe you've got these overdense regions in the early universe where black holes of all different sizes are forming just right out of the initial material that was available in the universe before even the cosmic microwave background radiation was released. Like you're looking at within the first 10 minutes of the universe, you could have black holes of varying size. Well, then maybe you could have a black hole that is 1,000,000 times the mass of the sun that formed just a couple of minutes after the Big Bang. That could find another 1,000,000 mass, or maybe you just right away, you got a 30 billion mass sun right shortly after the Big Bang. And now it's just been gobbling up small pieces and they're all just rounding errors for the size that it is. So how you get a black hole that big, that early is still an unsolved question, still an interesting mystery to solve. But the question you're asking is, you know, is it the theoretical maximum mass allowable? And the answer is no. Now, when they say that, it's kind of like saying that is a big black hole and we don't know how a black hole got that big so fast. But not that like that is as big as the laws of physics will permit a black hole to be. There is no limit to how massive a black hole can be. You could feed all of the mass and energy in the entire observable universe into a black hole, and it would be fine. It would just be a black hole with the mass of the observable universe. An interesting coincidence, a black hole with the mass of the observable universe is has an event horizon the size of the observable universe, but it's probably just a coincidence. So yeah, there's no limit. You just keep feeding black holes, just make them more and more massive forever, and they're fine. They love it. Keep feeding black holes. AF911 vids. Isn't it dangerous to do these high energy extreme experiments on the Large Hadron Collider? From my limited knowledge, these experiments try to create these extreme conditions by colliding particles at extreme speeds to measure and discover unknown particles. What if this process, we create a particle that interacts with regular particles in a dangerous way? What if we create a small black hole that doesn't behave like we thought and just eats up the Earth from the inside out? I'm just speculating, but isn't there an inherent risk that we could create something in the LHC that could basically destroy humanity? Whenever we develop large-scale experiments using more energy that humanity has ever used before, there is a negligible but non-zero risk that something bad could happen. And when scientists were developing the Large Hadron Collider, your exact concern was brought up. What if, when we turn this machine on, we create a black hole that gobbles up the Earth? What if we convert planet Earth into some kind of strange matter that then expands outward from planet Earth at the speed of light? What if we collapse the very structure of at the quantum level and destroy the Earth and start destroying the universe at light speed? And so before they proceeded, scientists did a study to try and figure this out. And the answer came with the fact that the Earth is being hit by cosmic rays, which are being hurled out from supermassive black holes and supernovae and neutron stars at energies that are many orders of magnitude more powerful than anything we can produce in the Large Hadron Collider. And these particles are being accelerated to nearly the speed of light, and they are crashing into the atmosphere and causing enormous cascades of particles that we can detect down here on Earth. And so scientists looked at the amount of energy that's packed into these cosmic rays, and it is way beyond anything that we can do here on Earth. And so the universe is already running this experiment much more powerfully than the Large Hadron Collider could be. But you can imagine a larger version of the Large Hadron Collider, maybe something that is hundreds of millions of kilometers across, that is running particles at enormous strengths to the point that it exceeds the power of these most powerful, most energetic cosmic rays. And then you're in new territory. And then I would take those risks a lot more seriously, that we could be trying out experiments that the universe has never carried out before. But when you think about like a supernova, and you think about the enormous amounts of energy that's coming together, you've got a star with many times the mass of the sun that is collapsing in on itself, and parts of it are raining down at 70% the speed of light, and then you get a black hole. All right, that might be a problem. Sid Vicious, what if we created a black hole here on Earth? Would it be dangerous, and how would you stop it? So let's say that we did create a black hole with the Large Hadron Collider. Now, the theory says that if you do create a black hole, it's going to evaporate before it even hits the ground. But let's say it doesn't. Then what's going to happen? Well, the black hole is going to fall into the Earth, and it's going to be really, really tiny. And so chances are it's going to fall all the way down through the middle of the Earth and through to the other side of the Earth, to the exact opposite part of planet Earth from where you created it. Then it's going to fall back the other way, and it's going to return to where you formed it and it dropped into the Earth. And maybe it will encounter a particle along the way and gobble it up. And then if it does, then it'll move a little less than it did to get back to your instrument. And then it's going to fall back down into the Earth and go backwards and back and forth and back and forth. Now it's going to be influenced by the gravity of the sun and the moon and the other planets in the solar system. So it's going to shift around, and occasionally it will bump into a particle and it'll eat it, become more massive, and they'll be capable of consuming more mass. And then it will eventually settle down into the middle of planet Earth and start gobbling up the planet from within. And for a long time, like a long time, it would be no problem. And then eventually it would start to cause instabilities, and it would essentially gobble up the Earth from the inside out. But it would take, like, I've read the calculations, but like the chances of a black hole with that small of an event horizon will spend a long time before it even encounters its first particle. But as I said, it's impossible. The theory that predicts that you would form them also predicts that they would evaporate before they even hit the ground. So don't worry about it. And if these were happening, now it's a little more dangerous than the cosmic ray ones, because when you think about it, these cosmic rays are coming in at close to the speed of light. They are hitting the atmosphere. They maybe are creating black holes when they hit the atmosphere, and those black holes are moving at close to the speed of light, and they don't interact with anything. So they pass right through the Earth and away they go off into space and probably don't interact with anything else. You might have black holes passing through your body like neutrinos. But the difference on the one that we create here on Earth is that it starts on planet Earth and remains inside the Earth this entire time, which makes it slightly a bigger problem than the ones that are being formed by cosmic rays. But this is all theory, like it's just conjecture. There's no evidence that any of this stuff is real. Anelio de Meglio. Can what happens inside very dense neutron stars be extended to black holes? So are you talking about this idea that very large neutron stars, very massive neutron stars can have strange matter in their interiors? This was a news story that we picked up this week at Universe Today. When you've got enough mass in a small enough area, then protons and electrons are mashed together and you get neutrons. And that's what a neutron star is. Like, there's so much gravity, so much density that you can't even have protons and electrons anymore. You just get neutrons. But that if it's like right at the edge of becoming a black hole, well, then in fact, you're at the core of this neutron star, you're smashing even the neutrons so that they're kind of squishing out into quarks, which are the fundamental building blocks of neutrons. And so you've got this soup of quarks inside this neutron star. And then wherever it's like not quite as dense, then you've got neutrons surrounding that. And you add a little more mass and the whole thing just pushes over the limit and goes into the form of a black hole. And so like, we don't know what is inside the event horizon of a black hole. The gravity is so extreme that no signals can get outside of it. And so one possibility is that, a black hole is just like whatever comes after strange matter, like the density. You get to a point where maybe the quarks are crushed down into their fundamental object and the escape velocity exceeds the speed of light, and you get this object with this extreme escape velocity. Or maybe the thing just keeps collapsing down and becomes a singularity. And over time, and maybe it's increasing at an accelerating rate. It's getting smaller and smaller and denser forever at an accelerating pace. And so, we can't know what's inside the event horizon. So, astronomers practically, mathematically speaking, consider that it is a singularity, but we can just never know what's inside the event horizon. So maybe it's a thing, or maybe it's an infinitely small thing. Whatever it is, it's a lot of mass compacted into a very dense area. Martin Charles, 1121. Will Betelgeuse turn into a black hole? We don't know. Man, is that what this episode is? We don't know. We don't know. So the problem is the Betelgeuse is right at the line for the mass of stars that will form either a neutron star or a black hole. You need a star that is about 10 to 25 times the mass of the sun to turn into a neutron star. So it depends on how much of the mass of Betelgeuse is lost. Like, it's between 12 and 20, but it could be a little more massive than that. So it could very well, and it sort of depends on how much of the mass of the star is thrown out through its stellar winds. Like, if Betelgeuse was above 25 times the mass of the sun, then it would absolutely be turning into a black hole. But because it's less, now it just matters is how much of its mass is it's going to be sloughing off as it's going through this red giant phase. And it's already thrown a ton of material out into space around it in this expanding nebula of material. And it all depends on how much mass it sheds off into space before it finally runs out of fuel in its core, collapses down, forms either a neutron star or a black hole, and then detonates as a supernova. And so I guess better measurements of its current mass and knowing where it is in its life cycle would tell us whether or not it's going to turn into a neutron star or a black hole. But for now, it's too close to call. Formarosa Studio. If a bunch of mass in one place creates a black hole, how did the Big Bang happen? Would it not be able to escape? So this is the classic question. Why didn't the Big Bang just collapse back down into a black hole? And there's a really weird coincidence that if you take all of the mass in the entire observable universe, all the stars, the galaxy, all of the light, all of the dark matter, and you add up all of that mass, you get a black hole with an event horizon that is roughly the size of the universe. And so are we living in a black hole? And so I get this question all the time. And so back to last week's question show, which of course, I'm sure you watched, the universe is was maybe infinite before the Big Bang and is still maybe infinite to this day. And so in order to get a black hole, you need to have a local density that is high enough for it to form a black hole. You could have an average density be much higher than what it would take to form a black hole, but it's not going to form a black hole because you don't have this overdensity and underdensity where the material can collapse. So if you've got this side over here and this side over here, and they're pulling in opposite directions, and this side over here and this side, they're pulling in opposite directions, it can never find a place to collapse into a black hole if it's perfectly smooth. And so if the universe was uniform enough and sort of went on forever, then there was no place where the black hole could form. Now, there are some theories that there were minor overdensities and underdensities in various places. And so we might have gotten some primordial black holes that formed shortly after the Big Bang, but there wasn't enough of an overdensity or underdensity. But you're absolutely right. Like if the entire observable universe is all there was, then that would have formed into a black hole. It would have appeared and it would have just gone into a black hole. But it's not all there was. There was more all around balancing everything out. And so there was no one place where everything could turn into a black hole.
Here's a black hole fact. If you watched a friend fall into a black hole because of time dilation, you would watch them never actually go into the black hole. And of course, they would experience the reverse.
Ryan Mortensen, how large would an accretion disk have to be on Sagittarius A for its light to be visible from Earth? So the center of the Milky Way is shrouded in gas and dust. And so we, with a regular visible light telescope, can't see the center of the Milky Way. And in fact, for the longest time, astronomers called this sort of blob, the center of the Milky Way, they call this the zone of avoidance. But really it should be like the zone of don't bother. Right? Just don't bother pointing your telescope in that direction because there's just gas and dust and you're not gonna be able to see anything and you're just gonna be frustrated. And I know you want to see the center of the Milky Way, but it's not gonna work and you can't see what's on the other side because it's just obscured. So don't bother. But then we got infrared telescopes. And suddenly these telescopes are able to peer through the gas and dust, and astronomers were able to see the stars moving around the black hole at the heart of the Milky Way. They were able to see through this zone of avoidance, the zone of don't bother, to the galaxies that are on the other side and be able to figure out what the great attractor is. It's a bunch of galaxies. So imagine if the supermassive black hole at the heart of the Milky Way became a quasar and started to actively feed on stellar material. Maybe it would happen during our collision with Andromeda. And now suddenly this giant supermassive black hole turns on and is like gobbling up material and blasting out. We still wouldn't be able to see it with our eyes because it is obscured by the gas and dust, by the zone of don't bother. So you could point your telescope at it and you wouldn't be able to see it. And we could stand outside together and look up in the direction where we know is the center of the Milky Way and we wouldn't see anything. It's only with very powerful infrared telescopes that you could peer through that material and even just like detect the presence of the quasar itself. And it, like, objectively speaking, it wouldn't be that bright. So even if you did clear away the gas and dust, you probably still wouldn't be able to see it. It's just like not that impressive, which sucks. I know, right? Like you want quasar, like you just imagine it's going to be this amazing swirling cloud that we would see with jets that are coming out of it. But we wouldn't see that because we have neat cameras in our eyeballs And it takes giant telescopes, the ability to see in other wavelengths, the ability to make long exposures to be able to see that kind of thing. Shane McKinney, could we be in a black hole universe? So this is a theory that has been floated that, our entire universe is actually inside a black hole. And there's like an interesting coincidence, which is that if you take all of the mass of the observable universe and you imagine like all of the regular matter, all of the dark matter, and you sort of mash it into a singularity. And then you said, well, like how big of a black hole would that be? What would the event horizon of a black hole with all the mass in the universe be and all the energy, right? It would be the size of the observable universe. Like the event horizon of a black hole that contains all the mass in the universe is the size of the observable universe. That's weird. That's a coincidence. And it is probably just a coincidence that give us a few more billion years and those numbers won't match anymore. Sort of in the same way that the moon and the sun are the same size visually in the sky today, but that wasn't always the case. It's just a coincidence. Like something had to be the same. But, that interesting coincidence has caused people to wonder like, oh, are we living in a black hole? And then are the black holes that are in our universe, like, do they contain other universes? And are there people inside those black holes wondering if they're inside a black hole and then there's black holes all the way down? Maybe, but there's no evidence that that's the case. And so nobody has taken it that seriously. But there are science papers that propose that our universe is inside a black hole. Maulik mystery. Does the Schwarzschild radius have any effect on why the Big Bang would not have collapsed? Gravity is too weak in super extended space, but not in more localized clusters. So, like, the question that you're asking is, why didn't the Big Bang just turn into a big black hole and collapse in on itself again? And one of the really sort of weird coincidences is that when you take all of the mass and energy in the observable universe and you pretend like it was a black hole, it would have an event horizon the size of the observable universe. That's pretty weird. But it's just a coincidence. It's just a fluke that those two numbers are roughly the same. But back in the early universe, absolutely mass and energy were absolutely dense enough that they would turn into a black hole. But it's not about the mass and the density. It's about having density differences. So you can imagine you've got this early universe with all of this mass and energy that is incredibly dense. It would love to turn into a black hole. But the problem is that it can't choose, that it is so even that no place can actually be able to pull into a black hole while other parts are going to be pulling it away. And so everything was very balanced early on in the early universe. And so it could never get its act together to turn into a black hole. Like in the case of the kinds of black holes that form today, you need this incredibly dense region that is surrounded by much less dense area. And everything was just too even early on in the universe for it to be able to turn into a black hole. The other thing that's really important to understand is that, like, what is the observable universe today is just one tiny little piece of a much larger universe. Like, we see this region that goes out, 45 billion years in all directions. And it was once the size of a grapefruit, but that's not like the whole universe. That's just one little piece. And right outside the observable universe that we can see, there was more universe. And then there was more universe on the other side of that and more universe above it and below it, maybe infinitely in all directions. ASCII, how will dark energy overcome the pull of supermassive black holes in the hypothesis of the Big Rip? The Big Rip is this idea that dark energy, this force that is expanding and accelerating the expansion of the universe, isn't a fixed number. If you sort of imagine a cubic meter of space and you imagine that for every new cubic meter of space, there is a little amount of dark energy that is now pushing outward. And so the more space you get, the more dark energy you get. That's the conventional idea of dark energy, which I know it's already mind-bending to think that this is happening, but we don't know the amount, the energy from dark energy is a constant or it actually is variable. Like maybe there were times in the early universe when it was a smaller amount and maybe in the future it'll be a larger amount. And so one of the possibilities, if it is a larger amount, that you will get this expansion of the universe that is accelerating and it will accelerate. And so the consequence of that is that, like, right now, dark energy will never tear apart the Milky Way. because the gravity of all of the stars in the Milky Way, the gravity of the dark matter halo, holds the whole thing together. In fact, dark energy won't overcome our interaction with Andromeda. It won't overcome our interactions with any of the galaxies in the local group. But it's only when you get to dozens of light years away that dark energy is going to be the dominant force. And so these galaxies would normally be pulled together by their gravity, but at the same time, the dark energy is pushing them apart. And so they'll be like trying to fall towards each other, but they're actually falling away from each other. And so they'll just move away at accelerating rates. And that's just regular dark energy. So what if that is increasing? Well, then what that means is that after a while, Andromeda's falling towards us, we're falling towards Andromeda, and then the dark energy increases and they never quite get close enough, and then they start to fall apart. And then the dark energy overcomes the gravity inside the Milky Way and starts to pull the Milky Way apart. And then it pulls the solar system apart. And then it pulls planet Earth apart. And then it starts to pull black holes apart. And even eventually supermassive black holes, that there is nothing in the universe. If dark energy is accelerating, increasing, then there's nothing in the universe that could withstand this. And so it would be, if two things were welded together at the Planck scale, it would still pull them apart because nothing can overcome it. And so that's the Big Rip. And we still don't know if the Big Rip is a thing. We still don't know if the amount of dark energy changes over time. It would be surprising if it did, this is an idea that nobody can disprove yet, but there's no reason to believe that it's true. But there are a bunch of new spacecraft and observatories that are coming online. Vera Rubin, of course, on the ground is going to help with this. There's the Euclid mission from the European Space Agency, and then there's the Nancy Grace Roman telescope coming in 2027. So you're going to have these three instruments that one of their big jobs is to help collaborate to figure out and map out and get a really proper survey of where all of the dark matter, all the dark energy is and how it's changed over time. And we will be able to either confirm that the universe is going to tear itself apart or just put that idea to bed forever. HP 3.14. Could we manufacture a micro singularity and keep it alive by feeding it matter, like somewhere out in the Kuiper Belt? That's always my answer, right? Theoretically, yes. Practically, no. So what is a singularity? Singularity is a black hole. How do you get a black hole? You detonate a star, and the star produces a black hole at the middle of 10 times the mass of the sun, more. And that is not us manufacturing. If we were able to go and gather up all the material, create this giant star, explode it, then we would get a black hole. But I don't think that's what you're going for. You're probably thinking, could we do it in something like the Large Hadron Collider? And this was one of the possibilities. This is sort of like one of the theoretical capabilities of the Large Hadron Collider, is that you could collide particles with such force and energies involved, compacted into such a small area that you would get a singularity forming. You get a tiny little black hole. And then according to the theories from Stephen Hawking, you would have Hawking radiation and that black hole would evaporate. And it would evaporate very quickly. Like it would evaporate within 10 to the minus 83 to 88 seconds. So like, 0.00000 80 times, 1. That's a very short amount of time. So such a short amount of time that it'd be really hard to detect the radiation. And so we still have not detected Hawking radiation coming from singularities generated in the Large Hadron Collider. Maybe because they're not being formed, like almost certainly because they're not being formed, but maybe just because it's so brief that we're not able to detect it. But if you were able to make a dramatically bigger particle collider, like imagine you built a particle collider that went around the entire solar system, like at the orbit of the Earth, and you crashed particles together with much higher energies, maybe you could generate more massive black holes that would last longer because the more mass in the black hole, the longer it'll last before the Hawking radiation makes it evaporate again. And so then the other question is, could you then, if you've got a black hole that you're crashing all these particles together and you are forming this black hole, and then you are feeding more and more material in and you're trying to mash all of this energy into this really tight space, you could theoretically grow a black hole and over time have it be whatever mass is important to you. And in the beginning, you'd need to do it with the particle accelerator. And then later on, you could, once it was going, you could start to feed it regular matter. I mean, keep in mind that anything that is less than the mass of like a mountain is going to evaporate in a very short period of time, like within a couple of minutes. So you've got to work quick. Now, your idea of putting this out in like the Kuiper Belt is a good idea, because if you manufactured a black hole here on Earth, it would be pulled into the center of the Earth by the gravity. And so you would make your black hole, and then it would fall into the Earth, and then it would be gone. Now it would evaporate. But even if it didn't evaporate, like it would take trillions of years before it accumulated like a kilogram of mass. So don't worry about us manufacturing black holes and them eating up the Earth from inside. Like it would take a long time. But the idea of doing it out in the Kuiper Belt is great, because then you could balance the gravity. And so you would make sure that this black hole is formed, and maybe your whole particle accelerator is turning as the black hole is inside this particle accelerator, and it's always staying there. And then you're feeding it and make it bigger and bigger. And after a while, it's kind of like starting a fire. And then once you've got it to a certain point, you start feeding it material, and then you get it to whatever size you want. And then you sort of back away. And it is like you're balancing the Hawking radiation that's coming off of it with the amount of matter that you're feeding into it. And you've got your own pet black hole.
Here's a black hole fact. You can extract rotational energy from a black hole. You just drop stuff in, that stuff splits as it's about to fall into the black hole. Half of it goes in, the other half flies out with more energy than what you dropped it in with. And so that extracts the rotational energy from the black hole. This is known as the Penrose process.
Rich universe. Are there different types of black holes? No, there's just different masses of black holes. So there are the supermassive black holes, the ones with millions or billions of times the mass of the sun at the hearts of galaxies. There are stellar mass black holes, like ones like Cygnus X1, black holes that are, say, maybe 10 to 20 times the mass of the sun. And the LIGO Observatory has detected the gravitational waves from black holes of 15 to 100 times the mass of the sun colliding with each other. Now, there are missing kinds of black holes that astronomers assume are out there. One is what is known as an intermediate mass black hole. So that's a black hole that's going to be more than 100 times the mass of the sun, probably more like about 1,000 times the mass of the sun. And when you think about, we have the supermassive black holes, the ones with millions of times the mass of the sun, they had to be built up with building blocks of black holes with lesser mass. So you would expect to see a ratio of black holes out there, some which are the mass of the sun, others which are 1,000 times the mass of the sun, ones that are 10,000 times the mass of the sun, leading up to the ones that are millions. But we don't see that. There's the millions, and then there's the stellar, and there's nothing in between. There have been some indirect observations. So, for example, astronomers have looked at globular star clusters and noticed the movements of the stars in that cluster, and assumed that you would have to have a couple of intermediate mass black holes lurking around inside that cluster to be able to get the kind of movements that you see. And then the other proposed idea is that there would be primordial black holes. And these are the black holes that were formed early on in the universe when there were regions of over and under density in the earliest states of the universe. And you would have black holes just forming naturally of all different masses, ones that are the mass of a house and ones that could have 1 billion times the mass of the sun. Like wherever you got enough of a dense region, you got a black hole. And one of the ideas to explain dark matter that I really like, but who knows, there's no observational evidence that this is true, is that it's explained by these primordial black holes. That you could explain all of dark matter by either having black holes that had about the mass of an asteroid, of a heavy asteroid, or black holes that have about 1,000 times the mass of the sun. And different numbers of both of those would perfectly explain dark matter. They would behave in all of the ways that you would expect dark matter to behave. But there's no observational evidence that these primordial black holes exist. So we have to just wait for someone to find something. Rebecca Smith, how do scientists know how many black holes are in the universe? For the longest time, astronomers had no idea how many black holes there were in the universe. Like, we knew of one black hole. We knew of Cygnus X1, which is a few thousand light years away from us because of the radiation coming from the star and the black holes. They were interacting with each other. And then within the last couple of decades, astronomers started to realize that there were these supermassive black holes at the hearts of galaxies. And so astronomers would use that to say, well, if there's one at the heart of every one of these galaxies, count up the number of galaxies, and that's how many black holes there are. But like, how many black holes are there of the stellar mass variety inside a galaxy? And astronomers really had no way to work out that number. But thanks to LIGO and the ability to detect gravitational waves and the number of detections that they're making, like, you don't hear this anymore because they're happening so often, but there are gravitational wave alerts going out into the astronomical community almost every day now. And this is because we're in the fourth run of LIGO, where they've upgraded the technology each time. And they went from no detections to a couple of detections to a detection every week. And now we get multiple detections every week. You can actually go to this place called the GRACE website, and they give you real-time gravitational wave detections that are just sent out, just like the raw detection without any real scientific work done. And then scientists can look at the detections and try and figure out if it is a real gravitational wave collision. So you've got enough of these gravitational waves, different sizes, masses of black holes interacting with each other in different parts of space, that astronomers are starting to get this statistical number of black holes that are out there across the universe. And there's a great article that came out from Starts with a Bang, Ethan Siegel, who I've interviewed here on the channel. And he wrote a post talking about this, that astronomers have come up with a rough estimate of the mass function of black holes. And the mass function is where you kind of say, like, imagine the bell curve of all the different masses of black holes that are out there. There are this many supermassive black holes and that many 10 mass black holes, solar mass black holes, and sort of where they all fall along that. And their estimate is that there are 40 quintillion black holes in the observable universe. So if you add up all the black holes in all of the galaxies, you get 40 quintillion black holes. So astronomers think there are 10 million black holes in the Milky Way. That's an estimation that was developed based on Gaia data, looking at the numbers of various compact objects in the Milky Way. But we're not sure if the Milky Way is a good comparison. So there you go. There's your number, 40 quintillion. And they found that out through the increasing number of gravitational wave detections that have happened. I love that, right? That this is new, that thanks to gravitational waves, which is just wizardry, like it's sorcery already, you can detect black holes colliding every couple of days across the universe and use that to make these estimates of the amount of black holes there are in space. Thomas Quick, I've always wondered what would happen if you were too close to a large gravitational wave event. If you were too close, you would be torn into pieces. Like we think about a gravitational wave moving through space, and you sort of, and you see the pictures where, the planet gets distorted, sort of pulled and squished, and yet doesn't get torn apart. That's only because the gravitational waves are very long and very gentle, and the amount that is being pulled apart is tiny, but it's real. And you know that it's real because we couldn't detect it if it wasn't real. Like, what's actually happening is you've got these lasers that are firing these laser pulses down these long arms in the detector, and they're bouncing back and forth, and they're calculating, and they're actually interfering the light as it comes back in, and they're using that to calibrate along those two lines. And then if one of the arms gets stretched, then the light is no longer interfering nicely. You get this detection. And the only way that happened is for it to physically be pulled apart a bit and then put back together as the gravitational wave pulls past the Earth. And, here we are, hundreds of millions of light years away from the event, and yet it can still pull the Earth apart enough that it's detectable by our scientific instruments. But if you got closer, then that force would not be gentle. It would be tearing you apart. But the problem is that if you're close enough to, say, two black holes that are in the process of colliding, their gravity, the tidal forces that are coming from those black holes, the radiation that's coming from the accretion disks around them would be lethal in so many ways. Like, the gravitational waves would be the icing on the cake from all of the other ways that you experienced harm by being close to merging black holes. But it's real. Like, it really would be there, and it would cause you damage if you got too close and you were somehow resistant to tidal forces and radiation. Rudiger Wolf 9626. If black holes are immensely dense aggregations of matter, how does a black hole differ from the early universe immediately after the Big Bang, when the universe was very small and very dense? We get this question all the time. Why didn't the universe just turn into a black hole at the beginning? Like, it was as dense as a black hole. Why didn't it just become a black hole? And so to get a black hole, you need regions of overdensity. You need like all of the force of a star that is imploding to provide a region of overdensity where you just try to mash so much energy and so much matter into a tiny place that it turns into a black hole. But in the early universe, you had this balance of the forces of the energy. You may have had high levels of density, but you had everything around it balancing everything out. And so there was no way for it to form into a black hole. You also had this expansion that was going on. And so things were being pulled away from each other too fast to get turned into a black hole. And so even though it feels like, yeah, the early universe was just so compressed, it should have turned into a black hole, there was a lot of other stuff tangled up inside of it, including space-time itself and all of whatever was expanding the universe so quickly that it never got a chance to turn into a black hole. But there is this theory of primordial black holes, that maybe there were regions of over and under density to the point that you would get these little knots of density that would turn into black holes of every size. Black holes with the mass of an atom to black holes with the mass of a galaxy. And they could have all been there in these various overdensities. You sort of imagine like this early universe where you just got like folds in space that were so tight that it was just filled with black holes. And then other places where the density was lower, and so you just didn't get those black holes. And then those black holes were let off into the universe and have been roaming around ever since. And it could be an explanation for dark matter. It could help explain why we see very massive black holes early on in the universe, and like a lot of other things as well. But this is something that astronomers are still looking for, and they haven't ruled it out, but they also haven't confirmed it. Drew D, why can't we use 2 black holes to tear apart one black hole and see what's inside? Because nothing can escape a black hole, not even a black hole. And you can't use a black hole to get anything to escape a black hole. If you bring a black hole too close to another black hole, those 2 black holes are going to merge, and you will have not learned anything except what the mass of the 2 black holes were. So unfortunately, nothing can escape a black hole. Like, there's no way around this. Like, what if I take a pole and I just stick the pole into the black hole? Like, but then can I poke around? Like, but that to know. Nothing you could do. There's no way around it. It's like that's the law, is how they work. And who knows? Maybe at some point in the far, far future, we'll come up with some really clever technique to be able to probe what's going on inside the event horizon of a black hole. But no, like one of the ideas that I think is really cool is, like, as black holes spin, they spin faster and faster and faster, and eventually they're spinning at relativistic speeds. And Einstein predicted what is the fastest possible limit that a black hole can spin. And, it depends on the size of the black hole, but roughly you're kind of approaching the speed of light on the surface of the black hole. And as the black hole is spinning, it flattens out, or the event horizon flattens out and flattens out. But just at the point where whatever it is that's inside the black hole is going to be revealed because the event horizon is flattening out because of its spin, that stops it. That it can't get so fast. They call that a naked singularity. And you can't get a naked singularity because the laws of physics will not allow a black hole to spin so fast that it can reveal its singularity. It puts on the brakes and prevents us from being able to find out any information about what's going on inside. We just can't do it. J. Allen, if time stops at a black hole event horizon, wouldn't gravity go to infinity mathematically? Time doesn't stop at a black hole event horizon. It's just about perspective. So for the person who is falling into the black hole, you experience time normally. You are falling towards the black hole. You pass the event horizon. Maybe you look out into the universe. It all just, goes horribly, horribly according to plan. Now, from your perspective, falling into the black hole, you are going to experience time dilation. You're going to see the universe speed up. As you get closer and closer to the black hole, you're going to see the universe just go faster and faster. And, as you're just about to die and be spaghettified, you might see hundreds of quadrillions of years into the future of the universe. From an outside perspective, they're watching you fall into the black hole. and you seem to just stop. And then you just redshift away, and eventually you just fade away. But they don't see the spaghettification. And so from their perspective, when you think about your perspective, right, you're watching the universe in fast forward. They're watching you move in slow motion. They would have to wait hundreds of quadrillions of years to actually see that process. So black holes are weird, man. Hourglass sand. If two gravitational waves meet and crest high enough, will it poke a hole in space-time, looking like a vibrating black hole in and out of existence? So there's kind of two parts to this question. The first one is, can gravitational waves cause interference like electromagnetic waves, like water waves? And the answer is yes. That if you have 4 black holes colliding into 2 pairs close to each other and they're generating gravitational waves, you could get an interference pattern between the gravitational waves. Will it poke a hole in space-time? No, you'll just get a more powerful gravitational wave effect at the point of the peak. You'll get a less gravitational wave effect at the point of the trough, and it will have to be a fairly tight area for you to get that interference pattern. But still, it would happen. KGS, are event horizons the most perfect spheres the universe could get? Is there anything to disturb the smoothness or deform them? So event horizons, which is the sort of that dividing line between where light can escape the gravity of a black hole and where it can't escape, is this region around a black hole. Who knows what's inside the event horizon? We can never see it. It's only outside the event horizon that we can actually see this. And event horizons are only a perfect sphere when you assume a non-rotating black hole. So if a black hole doesn't spin, then the event horizon is going to be this perfect sphere. It is a number that falls out of the mass of the black hole. You know the mass of the black hole, you know the size of the event horizon. But black holes spin. They all spin. Many of them are spinning a significant percentage of the speed of light. And what that causes is the event horizon to flatten out, kind of like in the same way that the Earth is an oblate spheroid. Black hole event horizons are oblate spheroids. And so there's this idea of a naked singularity, that the hope is that you get a black hole spinning so quickly that the event horizon would compress down to the point that it would reveal the black hole inside the event horizon. But the reality is that, in fact, this limitation of relativity, that essentially there's a maximum speed that you can have this black hole spinning, always ensures that you can never reveal the singularity. So black hole event horizons flatten out. Now, are they the most perfect oblate spheroids that the universe can produce? Yes, they are.
All right, I'm pretty sure everyone has fallen asleep at this point, but if you are somehow awake at the 7-hour mark, go ahead and put some kind of surreal comment about rabbits and black holes and hats into the comments down below. And then that will confuse all of the people that are reading through the comments and wondering, what part of this did I miss?
Tommy36, why is the stellar mass black hole merger theory more popular than the direct collapse theory for supermassive black hole formation? The only way that we know to get a black hole is to have an implosion of a star. That it's not enough to just have a lot of material collected into a small area and then have that area collapse under its own gravity. That's how you get a star. And the problem is that there is a limit to the size of the largest star. So beyond about 100 times the mass of the sun, as materials are accreting down onto the star is getting so hot, it's so large, it's getting these outflowing winds and jets that are blowing away from the star, and then no more infalling material can fall down onto the star. And so that's why, like, the limits, the largest stars that we've ever found are like 150 times the mass of the sun. And even that is sort of up for grabs. And when a star that is, say, 100 times the mass of the sun detonates as a supernova, it doesn't even create a black hole. They're called pair instability explosions. And so there's no remnant left behind. And so you need the right size star to be able to get a black hole. And it is, you're going to end up with a black hole that is some number of times the mass of the sun. And then you're going to need to have those two stars find each other, and they're going to need to merge into a larger black hole. And then those are going to need to merge into others to merge into a bigger black hole, and so on and so forth. The direct collapse method, where you just have an enormous amount of material, and then somehow that material can come together and form an object that has so much gravity that it doesn't even turn into a star. It just turns directly into a black hole. This is absolutely a mainstream concept. But the question is, we see stars today that refuse to get bigger than 100, 150 times the mass of the sun. And so how could you get one that is 1 million times the mass of the sun, 4 million times the mass of the sun to get that supermassive black hole? And so the one possibility is that there's something different about primordial hydrogen and helium left over from the Big Bang, that the stars today, they're polluted with other heavier elements like oxygen or carbon, and somehow that pollution is the cause for stars not being able to form to become supermassive. And maybe when you just have pure hydrogen and helium, you can get these supermassive stars. But other people don't think that. They think that, yeah, you would get larger stars, but they would also live very short lives. They would explode as supernova, and they just wouldn't get 1 million times the mass of the sun. But the sort of interesting theory, and there's some evidence for this now, thanks to James Webb, is that, there needs to be some mechanism that is preventing the outflow winds from stopping from the star being able to halt its growth. And that there could be some kind of process in the early universe with these primordial stars that they're able to prevent the outflows. And so they do just keep accreting mass until they become a supermassive black hole. And having the direct collapse of supermassive black holes would solve so many problems, right? It would explain how you have supermassive black holes at the hearts of almost every galaxy out there. It could explain why we're seeing such big galaxies early on in these James Webb observations. Like, there's a lot of stuff that the direct collapse solution to the problem solves. But it's just, we don't see stars doing it today. Why would stars have done it in the past? This is the question. And that's why astronomers are skeptical that direct collapse is the answer. But if one day someone sees one in action, we see a direct collapse black hole starting to come together, and they understand the mechanism that stops it from halting its growth, then that will be the accepted scientific consensus. RM. What are the particles that are theoretically created during the process of black hole evaporation? Electrons, quarks, complete protons, neutrons? The vast majority of the particles that are going to be theoretically evaporating from black holes are just photons, just radiation, light at different wavelengths. When the black hole is very large, you're going to see very low energy photons. And then as the black hole gets less and less massive, smaller, the radiation coming from it is going to get hotter and hotter. Eventually, you'll get this final flash of gamma radiation, and then the black hole will be gone. And I guess there's the potential for other particles as well, but the vast majority is going to be photons. Elijah Petril, why do you think that black holes shrink? Is this due to quantum entanglement? So the concept that you're thinking about is known as Hawking radiation. And this is the calculation, the prediction that Stephen Hawking made that black holes evaporate over long periods of time. And the reason why they do this, or why this is expected to happen, is based on a bunch of sort of discoveries that were made about the universe. And there's like this traditional explanation that you've probably heard, where there's like virtual particles that are appearing right at the edge of black holes and then disappearing again. And some of them are going into the black hole, and somehow that makes the black hole get smaller. And that explanation, the one that was used by Stephen Hawking, is wrong. And he knew it was wrong. And it's weird that he said it that way, and people have been trying to clear this up for decades. When you think about just space itself with nothing inside of it, if you removed all of the energy, all of the mass, all you would be left with is these quantum fluctuations that are space-time itself. And if you were to sit in the middle of space you would be experiencing these quantum fluctuations, but they would all be balancing out. And so you wouldn't feel them. But if you started to accelerate in any direction, and this has been tested in the lab, you start to experience a energy that is coming from you accelerating through these quantum fluctuations in the universe. And the term for this is Unruh radiation. I'm never sure exactly how to pronounce it. I apologize. So that sort of, let's hold that understanding that as you accelerate through space itself, you experience radiation coming from these quantum fluctuations that are in the universe. So Einstein told us that when you are, say, in an elevator and you can't see outside and you are falling, it is exactly the same as if that elevator was really far away in space and it was accelerating, or you were in free fall, that you wouldn't be able to tell. These things are all relative, that they are equivalent. And so you can take that concept and say, okay, if you are close to a black hole, if you are close to any kind of mass and you are experiencing the gravitational pull of that mass, it is equivalent to the acceleration that you would be experiencing if you were just like firing your thrusters as you were moving through space. And so when you're close to a black hole, you should be experiencing that same radiation. But you're not accelerating through space. You're just hanging out near a black hole. And so that radiation from your perspective is literally coming from the black hole. You're getting photons that are coming from the black hole, which are caused by this acceleration. And so photons can't come from nowhere. They have to come from somewhere. And so the black hole literally gives up mass to maintain that equivalence of it causing acceleration around itself. And the part that's really kind of weird and interesting is that the less massive black holes actually produce more radiation, hotter radiation than the most massive, supermassive black holes. And this is because of the sort of the gravitational curvature, that there's a much steeper gravitational cliff, a bigger edge as you get very close to the black hole. We know that if you got close to a stellar mass black hole, the tidal forces are going to be tearing you apart. And there's this really powerful shear that's happening really close to the black hole. And this creates a kind of a more profound amount of that radiation. But as the black hole is really big, gigantic, you could drift through the event horizon of a supermassive black hole and you wouldn't even feel it. And so you don't have that giant gradient in acceleration. And so you get less of that radiation. And so weirdly, it's backwards, that the most massive black holes are the ones that produce the least amount of radiation. And so they actually shrink the slowest. It's the least massive black holes, the ones that are producing the most radiation, that are also shrinking down. And this is why as the black hole gets less and less massive, it puts out more and more energy. And eventually it just disappears in this puff of gamma radiation and it's gone. End mill. If a black hole is spinning near the speed of light and it feeds on a large mass, since it cannot exceed the speed of light, how do we reconcile the conservation of angular momentum? Right. So astronomers are able to measure the spin of black holes across the universe. And there's a few ways that they do this. And I've done interviews here on the channel about it, but the gist is either you can measure how quickly the sort of jets that are coming off of the black hole are turning, but you can also measure the accretion disk that's around the black hole. And so if you see a black hole with an accretion disk and the accretion disk is very close to the black hole, then that means that the black hole and the accretion disk are spinning in the same direction. But if there's a larger gap, then in fact, you've got the black hole spinning in the opposite direction against the accretion disk. And you can actually measure the rotation rate of the black hole. But black holes are limited at the speed that they can go. And in many cases, they're all right at the very top of that speed limit. They can't go faster than the speed of light. And in fact, they can't go, often they don't go, 99% of the speed of light. And that's because relativity kicks in. You've heard that you can't go faster than the speed of light with your spacecraft because you need more and more fuel, and that the mass of your spacecraft increases as you go faster and faster and faster. And so you need more and more fuel to be able to go faster and faster. And so you're limited by just how much fuel you're able to carry. And you could never, the amount of fuel that would be required to move your spacecraft would approach infinity. And essentially the same process is going here. As the black hole is spinning faster and faster, you are getting relativity is kicking in. It's having a harder time to do its frame dragging, to be able to spin around. And the conservation of angular momentum, it's still baked in. It's still in that black hole. It's just because it is spinning it closer and closer to the speed of light, it is compensating for it. Giovanni Foulmouth. Do all neutron star collisions create black holes? We don't know. So the neutron star collision, the kilonova, was first seen back in 2017. This was where we got that gravitational wave observatory observation, as well as the electromagnetic observation of two neutron stars colliding. And in the resultant explosion, we saw many times the mass of Earth in the form of gold and other heavier elements that had come together. And it looks like this is the answer for short period gamma ray bursts. And these were a mystery for a long time. What is the cause of short period gamma ray bursts as opposed to the long period gamma ray bursts, which appear to be core collapse supernova? Anyway, but then the question is, what's left over? So there are a couple of possibilities. So one possibility is that when the two neutron stars collide with each other, they just detonate. And there's nothing left over, just this expanding cloud of debris left over, of gold and platinum and all these stuff that came from that collision. And it's likely now that a lot of the heavier elements that we have here on Earth, the gold in your wedding ring, that came from kilonova and not from supernova as originally thought. The other possibility is that you get a black hole where you've got, two objects that are compact, that both of which are really almost black holes. They're between 1 and 2 times the mass of the sun. A black hole starts around, more than 2 times the mass of the sun. So if you mash two of those together, maybe you get a black hole. And then the other possibility is that you get a neutron star, because it's not massive enough for a black hole, but you get a long-lived neutron star as a remnant. And the jury right now is still out. So there's a lot of really interesting discoveries that have been made, where astronomers are seeing the maximum possible mass neutron star, which is a very weird thing to see. How do you get a neutron star with that much mass? Is it feeding off of some companion, or did it entirely feed off of a companion and now that companion is gone? You're seeing the minimum mass possible black hole. That's weird. Did that come from a neutron star that just tipped over and became a black hole? So no remnant has been detected from the 2017 gamma ray burst that I know of. But astronomers are definitely searching for one. If they find one, or in any of the other kilonova events that have happened since then, we'll get a sense of what the remnant is. But right now, all three options are possible. Stefan Anderson, 7519. Very interesting to hear you explain the Unruh effect. So would that mean that everything with mass creates Unruh radiation around it? Would an immortal being ultimately evaporate just like a black hole? So last week, I gave a fairly detailed explanation of Hawking radiation. And the important part here is that it's not this virtual particles appearing right beside the event horizon of a black hole, that actually there is a different, more complicated explanation for it, one that Hawking totally knew and should have given, but he felt like people weren't, smart enough to handle it. And so that's how we've got this virtual particles appearing. It's caused all kinds of miscommunications and misunderstandings for decades. And you talk to particle physicists and they wince. So hopefully I'm trying to set the record straight on Hawking radiation, and go back to that other episode if you want to hear the explanation. But the question that you're asking is one that has come up. And so if it's not a black hole's event horizon that is causing this radiation, but in fact, the gradient of the mass difference as you go down the gravity well, then does that imply that all mass evaporates? And the answer is Probably yes. So there was a paper that came out a couple of years ago where researchers asked this exact question. They said, well, does all mass emit Hawking radiation? That with a black hole, you've got the most gravity and especially the most gradient where you've got that event horizon. And so you're going to get the highest amount of Hawking radiation from the least massive black hole. You're going to have less Hawking radiation from a supermassive black hole. But in fact, they calculate that there would be some level of Hawking radiation coming from any mass, but that amount would be completely insignificant. And so I guess, would an immortal being ultimately evaporate like a black hole? Yeah. Yeah, over an infinite amount of time, that if there was nothing else, then eventually even that immortal being would evaporate. Edward Hinton. They say that you wouldn't know that you've passed over the event horizon of a huge black hole, so you could see the event horizon of a black hole and partially put your arm over it. What would happen? So for the small black holes, the stellar mass black holes, then the tidal forces are so extreme that they're going to tear your arm apart. They can tear your whole body apart as you get too close. So you will know that you are approaching the point of no return when you have been stretched into a stream of goo that is now orbiting around the black hole and on its way to go in. But for the supermassive black holes, the ones that have millions or maybe even billions of times the mass of the sun, the gradient of the gravity that you experience is so low that you can fly your spaceship through the event horizon and not even feel it. And yet there is no escape. You have passed the event horizon. You can never come out. And so what would happen if you flew right next to the event horizon and you put your arm into the event horizon? Well, the part of your body that is outside the event horizon could theoretically, if you're able to move your spaceship at close to the speed of light, could escape. But the part of your arm that you put into the event horizon is going into the black hole. It is a one-way trip. You do not come back out. So it doesn't matter whatever you try to come up with. Like, take a camera, put it on a long pole, stick it down into the event horizon, and then pull it back out. And you're like, there's no camera there anymore. It's just gone because nothing gets out. All roads lead to the singularity, and there's no way around it. So just inside the event horizon, going to the black hole. Outside the event horizon, there's a chance you could escape. Ryan Graver. Does Hawking radiation travel faster than light? One of the most interesting ideas that Stephen Hawking contributed was the idea that black holes can evaporate over time. And I've sort of gone into the process in previous question shows, so I won't sort of go into it. But essentially, over time, you get particles that are emanating from black holes, and the mass is coming from the black hole, and the black hole shrinks as it produces more of these particles. Now, the vast majority of the particles that black holes are going to be producing are going to be photons, and photons travel at the speed of light. So Hawking radiation mostly travels at the speed of light. But if a different kind of particle is released, maybe an atom of hydrogen, something like that, then they can't travel the speed of light. They have to travel slower than the speed of light. I don't know what the speed of them is going to be. They have to have gotten away from the black hole. So they had to be going fast, but they can't go the speed of light. So they would have to be going somewhere in between, fast enough to escape from just outside the event horizon of the black hole, but not so fast that they exceed the speed of light. Stephen Nard. Please tell me if a black hole is two-dimensional or spherical. So when you sort of see the pictures, the illustrations of what a black hole looks like, you see this sort of fabric of space-time, and then there is this well, and down at the bottom is the black hole. And that's a way to sort of wrap your mind around how black holes are distorting space-time. But that is like a two-dimensional representation of an effect that's happening in three dimensions. The reality is that you would need to sort of recreate that weird model in all directions and in all dimensions. A black hole is a three-dimensional object. Think of a neutron star, which is the result of a very large star that explodes as a supernova, and then the infalling material collapses down, and you end up with this rapidly rotating object that is incredibly dense and has these magnetic fields and so on. And the only thing that is stopping the neutron star from collapsing down is the pressure, the neutron pressure that stops these neutrons from being smushed into each other. But you could take the sun and you could replace it with a neutron star with the mass of the sun, which you don't get. I mean, they're generally a little bit more massive than that, but you could, if you could. All of the planets would continue to orbit around this neutron star sun, and everything would be just fine. And so if you think that a star is a three-dimensional object, a neutron star is a three-dimensional object. But if you feed a neutron star like one more bite that's wafer thin, one more straw, break its back, then it overcomes the pressure. The neutrons are now, they give up. They're willing to be squished together. And this thing compacts down into one more size. And that is the black hole. And now suddenly the event horizon forms around the black hole because that is the region where now not even light can escape this thing. And so it is still a three-dimensional object. You can orbit a black hole in any orientation in exactly the same way. So black holes, they are spherical. But like spherical is not exactly the right answer because they rotate. They're oblate spheroids, but they are three-dimensional objects.
Here's a black hole fact. The singularity inside a Kerr black hole isn't a single point, it's a ring. And there have been many papers with people trying to figure out what is inside that ring. There's probably a Nobel Prize waiting for you if you can figure it out.
Zostrich 12X. Wouldn't certain types of active galactic nuclei pose as near galaxy-wide sterilization threats to life? So this goes back to the episode that we had 2 weeks ago. That's sort of the way the cycle works, where someone was like asking for a sci-fi novel, definitely not because they're a supervillain, wondering if there's a way that you could sterilize an entire galaxy and not just any single star system. And I sort of brainstormed a bunch of ideas and I couldn't really come up with anything. Well, this is possible. And this is this idea that I mentioned in the previous question, that you can have a supermassive black hole and it can have this accretion disk that is going around the supermassive black hole. And this whips up these giant magnetic fields that twist around the black hole. And then you get material, instead of falling into the black hole, is funneled into these jets. And these jets can be millions of light years long, just going off into space. And you've got material that is moving at relativistic speeds through this jet. And, you know, the research on this is still fairly new. Astronomers aren't entirely sure what the effects are, but it appears that these can do one of two things if they hit a galaxy. One is that they can trigger enormous amounts of star formation. That essentially, this is one of those things that can cause gas clouds to start collapsing and beginning to form stars. And so if you've got this galaxy, it's got lots of puffy gas clouds in it, and then the death beam of a supermassive black hole, it's going to sort of goes across this galaxy, you could end up with star formation that is being caused by that. But the other possibility is that you get quenching. So in other words, the beam is so intense that it doesn't actually create collapsing clouds, but it's actually starting to strip away a lot of this material, this light, gas, and dust that's hanging out in these gas clouds. And that starves the stars for star formation. And so both kind of lead to the death of the galaxy, because in the one case, it's as if the galaxy is in an all-you-can-eat buffet and it quickly goes through all of its gas and forms all of its stars, and then it's out of star-forming material, and then it just turns red and dead. And then the other possibility is that it never even had a chance, that it just has all of its material blown away, can never really form a lot of stars, and so it's just undernourished, underfed. And both are very bad for the galaxy. And it wouldn't be like an instantaneous death knell for the galaxy. But when you think about it, to have heavier elements in a star system like we have here in the solar system, the sun needed to have collected elements from many previous generations of stars. That our sun is a third generation star, and it's, you know, little bits of kilonova have been mixed in, little bits of supernovae, stars that have lived and died and blown off their outer envelopes. All that's mixed in with the sun. And so we have all of the heavier elements, all the heavier elements that are around you right now, the gold in your jewelry, the iridium in your chips. All of this came from these, you know, supernovae and
kilinovae and things like that. And so if a galaxy ran out of heavier elements early on, it never got a chance to kind of build them up, then it would be really hard for it to form life down the road. And so there's this idea of a galactic habitable zone, places in the galaxy where there are enough heavy elements for life to be able to form. And so if you don't have those heavier elements, then maybe life can't form. And so in the first few billion years of the universe, as these death beams are blasting out of black holes, you could end up with galaxies being not sterilized, but starved. And so they never have the conditions for life to be able to form down the road. So I like that idea. It's pretty evocative. Maybe that's your science fiction story, you monster. Yngvi Freyr. If Vera Rubin doesn't find anything that is planet-sized, would a black hole be the only other explanation? No. The most likely explanation for the perturbations of objects in the Kuiper belt is some kind of effect from the overall galaxy, that you've got the sum gravity of all of the stars that are moving around in the Milky Way that are somehow causing the Kuiper belt objects to bunch up in certain ways. Maybe there was a rogue star that moved through, close to the solar system 1 million years ago, and that caused enough of a clustering of objects back at the time. The point is that there are just lots and lots of other ideas to exhaustively look through before you say, well, it has to be a black hole. Now, if it was a black hole, then it's going to be a primordial black hole. It means, because you can't get a black hole with the mass of planet 9 by the collapse of a star. It has to be something else. And it has to be one of these black holes that were formed at the beginning of the universe. And so there have been some proposals on how you might be able to detect the presence of a black hole. I mean, you could see some kind of microlensing as the thing is passing in front of other stars out there, but you have to be watching the entire sky, which there are some telescopes that are coming up that are going to be doing that, like the Nancy Grace Roman is going to be watching for these microlensing events. There's a survey called OGLE where they're watching for microlensing events. So that could be possible. But also the idea is that if it is a black hole, then it's occasionally going to gobble up a particle in the outer solar system, bits of Kuiper belt, things like that. And every time that happens, you're going to get a flash of gamma radiation coming from the black hole. And so if you had this telescope that was watching the entire sky in gamma radiation, you might be able to detect the presence of little bursts of gamma ray photons coming from a black hole that is orbiting around the sun. So if it is a black hole, it's still detectable. And so far, nobody has detected a black hole in the outer solar system. MTN Hermit. Do you think we have a second star, a brown dwarf, a small black hole? If we had a second star, we would see it because it would be the brightest star in the sky. After the sun, of course. So we definitely don't have a second star. Like, we're not in Alpha Centauri with 2 stars orbiting around each other. Now, could we have a stellar companion that's on an incredibly long orbit that comes by the Earth every 10,000 years? No. We've got really incredible space telescopes like Gaia, which are detecting the position of every star in our vicinity and their motions. And if there was a star that was in some kind of binary system with Earth, it would have caught it, and it didn't. Do we have a brown dwarf that is in our vicinity? And the answer to that is also no. For sure, 100% no. How do we know that? One of the telescopes that I mentioned earlier in this episode is called WISE. And it was an infrared telescope that was launched. And one of its jobs was to scan the vicinity around the solar system, looking for any infrared companions, brown dwarfs. And it did this complete survey of the entire sky, and it didn't see a brown dwarf in the vicinity. And so it was able to rule out the existence of a brown dwarf. In fact, WISE was able to rule out any Jupiter-sized objects within, I'm going to say 50,000 astronomical units. So about a light year away. It was able to rule out any Saturn-sized objects a little bit closer than that. So all we're really left, like when you go back to that answer about Planet 9, all that we're left with that's possible is some kind of Neptune-sized, Uranus-sized object that is within a few thousand astronomical units of the Earth and beyond. Anything closer than that would have already been observed. Anything farther than that that's bigger has been ruled out. And all you're left with is like Uranus, Neptune, Earth-sized objects in the outer solar system. So if Planet 9 is out there, it has to be one of those. Is it a black hole? Probably not. This has been an idea that maybe you could explain Planet 9 as a primordial black hole, but like the chances of it actually being a black hole and not just a planet, like we have tons of planets here in the solar system, are pretty remote. So we don't have a second star. We don't have a brown dwarf. We don't have a small black hole. We might have a Uranus, Neptune, or Earth-sized world, or a few in the outer solar system. Peace be upon you. Could all the black holes be the results of advanced civilization's final catastrophic technological disasters, and that's why we're not finding any? Of all of the responses to the Fermi paradox, this would be classified under the great filter. And so there would be this inevitable technology that all advanced civilizations reach, where it makes absolutely the most sense to do it. And yet when you do it, then it turns your entire star system into a black hole. I don't think we know of a mechanism that will turn an entire star system into a black hole. Like, you need to have all of that mass. You need to have this immense compression from imploding massive star to actually create a black hole in the first place. But, you know, from a science fiction perspective, from a horror standpoint, I do find this idea of a science experiment as the explanation for the great filter as kind of compelling. So I'm going to give you an analogy a bit, which is sort of one of the ideas about like artificial intelligence, right? You know, we know that in the past, people have created nuclear weapons, and at a certain point, the nuclear weapons are only created for various nation states. And there's like hopefully no one's going to use these nuclear weapons. And, you know, everyone knows it'll be catastrophic if it was. But with, say, artificial intelligence, there is a potential existential threat that eventually smart robots will take control of the future. And you can kind of imagine that how we get there is that the robots are providing us value. They're constantly making our lives better until they take over. And then all is lost. And so you can imagine some kind of science experiment, some kind of 0-point energy machine that is producing unlimited power for all humanity. But if you run them for too long, and if you extract too much energy out of them, then there's just this moment where the whole thing then turns your entire planet into strange matter. And then you create this bubble of strange matter that just expands at the speed of light, that is destroying all of the universe. Was it like Ice 9 in Kurt Vonnegut's book? So do I take them seriously? No, I don't take that idea very seriously. You know, we see the black holes. We see them interacting with their environments. So, and we see them early on in the universe before the elements for life were available. We see them just a few 100 million years after the Big Bang, and they're already super massively big. But boy, it would make a good science fiction story for sure. Shay 88. Hey, Fraser, do black holes ever merge? Since time essentially stops around an event horizon, do they merge or stay apart by an asymptotic boundary line? Yes, black holes do merge. And I think, you know, what you're getting hung up on here is that the perspective of an outside observer that is watching something fall into a black hole is that person, you know, as they fall into the enormous gravitational well of the black hole, as that sort of approaches infinity, we see them just get slower and slower and slower. And then they just pause on the event horizon of the black hole. And then they redshift out until they become invisible. But we don't actually watch them get torn up and disappear and go into the black hole event horizon. And that is our perspective as an outside observer. But what's really happening is that as the black hole is absorbing the material of a person falling into it, the event horizon of the black hole rises to meet them. It actually grows because the size of the event horizon is defined by the mass that's in the black hole. So the event horizon gets a little bit bigger. the person is absorbed into the black hole. And so the same process is happening when you get two merging black holes. You get two merging black holes, they get closer and closer together. They experience time dilation as they're going around each other, but at the same time, their event horizons merge and they become this new, larger black hole. And obviously this happens because we detect the gravitational waves that are coming from merging black holes. Thanks to LIGO and CAGRA and Virgo, we actually have evidence that this is happening, as well as the evidence coming from the pulsar timing array of merging supermassive black holes. So this process happens at every scale. Billions and billions of stars. Fraser, can you please explain how some black holes rotate and some don't? I thought everything in the cosmos rotates. I don't know where you've heard that some black holes don't rotate. Every black hole that's been observed rotates. And in fact, most black holes rotate at the maximum speed that is allowed by the laws of physics. You know, as they rotate faster and faster, relativistic concerns start to take over and put the brakes on how much faster they're able to rotate. It's about like 70% the speed of light. And so as material is falling into a black hole, it's going to increase the rotation speed. The problem is that a rotating black hole is very complicated, much more complicated than a black hole that doesn't rotate. And so generally when people are learning the physics about black holes, learning to calculate the event horizon and things like that, they imagine a non-rotating black hole. And then they learn the hard math, the one that includes a black hole that is rotating at relativistic velocities, that is torquing up the space-time around it, frame dragging, and all of the other, surrounded by an accretion disk that is also rotating at a different speed, and they're interacting. You've got time dilation. Like, it gets more complicated when the black hole rotates, and yet that is the reality. And as you said, everything seems to rotate, and black holes are no exception. An evolving ape, how big would a black hole be that is 1/100th the gravity of Earth, and how close can you get physically to it without being spaghettified? Now, I haven't done the math. Like, the black hole, the size of the Earth, would have an event horizon that's 1 centimeter across. And so it would be like a millimeter across, so like a fraction of a millimeter across. How close could you get without being spaghettified? Pretty close. I sort of think about, like, there would be tidal forces for sure. It would have the gravity of a small asteroid, and it would be a millimeter across. So I think you would experience tidal forces when it came in contact with you, but I'm not sure like how close you could get. A few meters away, and you would start to feel those tidal forces where it was starting to pull your body apart. It seems like I haven't done all the math. You'd be taking the gravity of a small asteroid like Vesta, but compacting it down into a millimeter. And so like you wouldn't experience a lot of gravity on the surface of Vesta, but if the Vesta was packed down into a millimeter across, it would be very intense if it got very close to you. Here's a black hole fact. It's estimated that there are 100 million black holes in the Milky Way. This guy, is a black hole star or quasi-star considered a likely possibility in astronomy, or just an interesting theory? I mean, the whole way that astronomy and science works in general is you come up with an interesting theory and then you try to accumulate evidence for what that thing is. And so, for example, the theory says that when a star with many times the mass of the sun dies and is no longer putting an outward force from the fusion, then the outer layers collapse inward and you get this supernova and a black hole forms, or a neutron star. And we see neutron stars out there in space. Like, we can detect them. They're rotating. Think about pulsars, magnetars. Like, we know neutron stars are forming. And yet neutron stars only go up to a certain size, certain mass. And then there's nothing beyond that certain point. So like, either the stars that are more massive, when they die, they're just blowing themselves apart, or they're turning into black holes. But astronomers wanted to know that these black holes were out there. And so they gathered evidence. And so the first black hole that astronomers found was called Cygnus X1. And this was a black hole that was in orbit around another star. And the black hole was siphoning material off of its partner star and throwing radiation into space that astronomers were able to detect in a very specific wavelength in X-rays, which matched what you would expect to see if a black hole was feeding on a star. But that's not enough. Astronomers kept going. The theory was that there were supermassive black holes at the heart of the Milky Way.
And astronomers were able to use infrared telescopes to be able to see stars that were moving around the heart of the Milky Way, like comets going around the sun. And they were able to measure the mass of this invisible spot. Like there was nothing there. And they were able to measure the mass at 4.1 million times the mass of the sun. And so that was more evidence that black holes are real. And then the Event Horizon Telescope was able to actually image the event horizon of the black hole at the heart of M87, as well as the black hole at the center of the Milky Way galaxy, with incredible resolution. And you could actually see the shape of the event horizon and match that against the theories predicted for what a black hole event horizon should look like. Think about Interstellar, and you got this match. And so just the evidence continues to build. Like, could they be wrong? Sure, they could be wrong. But every time more evidence is gathered, the more we know that these things are real. Like, I don't think there's very many people out now who would say, oh no, black holes aren't real. And you'd be like, well, how do you explain these X-ray stars? How do you explain the stars moving in the middle of the Milky Way? How do you explain the pictures taken by the Event Horizon Telescope? How do you explain, like, it goes on and on and on. Eerie. Could you ride a black hole's polar jets? Yeah, in theory, sure. There have been proposals for having futuristic ways of using the solar wind coming off of the sun as a propulsion system, as well as like using an electric sail that will interact with the magnetic field of the charged particles that are coming off of the sun. And the sun is like nothing compared to a black hole's polar jets. I mean, they are going at, like, while the sun's solar wind is going at hundreds of kilometers per second, these polar jets coming off black holes are going close to the speed of light. And so they would be probably the best, like the most efficient, like most powerful propulsion system you can possibly imagine out there in the universe. They're just waiting for us to get to them. All you have to do is get to a quasar that is sending out polar jets, which, could be a challenge. Armando Miranda, do black holes attract other black holes? And if so, does it matter how big they are? So, like, black holes are not vacuum cleaners. And so there isn't anything special that a black hole is doing in terms of gravity compared to any other object that is made of mass. And so, for a good example, like if you took the sun and you just replaced it with a black hole that had the exact same mass as the sun, then all of the planets in the solar system would just continue to orbit around the black hole sun just as they did before. So nothing new or special would happen just because you would turn the sun into a black hole. And so then out there in the universe, all the times you got interactions with black holes, it's exactly as if you had a star that was in that exact location that had, say a star that was 8 times the mass of the sun or 10 times the mass of the sun, and it's orbiting around another star. Well, you could just replace it with a black hole. It's exactly the same. And especially black holes don't specifically attract one another. Now, the rules do change when you get close enough to a black hole. When you get to a point where the tidal forces start to tear a star apart or a planet apart, then instead of it being a discrete sphere that is orbiting around something else, it's this smeary mess that is falling to the accretion disk and it's passing through the event horizon. And, the rules kind of change when you get really close to a black hole. But as long as you're sufficiently far away from a black hole, it's as if any other mass out there in the universe. Jingard, what are your thoughts on black hole stars or quasi-stars? The first stars that had a black hole at the core, which is one explanation for black holes at galaxy cores. So I don't have opinions. I'm just a science journalist. And so quasi-stars, is it like gravis stars? Like, there's a bunch of alternative ideas for things that could give off the same characteristics of black holes. And one of the amazing things about the Event Horizon Telescope was that it was able to measure the event horizon around 2 black holes, and they measured the predictions that were made by Einstein for what you would expect to see around a black hole. And so, there are still alternative theories for what could be these enormous, very massive, dense regions in space, but the black holes are the one that are widely accepted by the scientific community. DC, is it possible that dark matter could be explained by black holes affecting the rest of the universe, or many tiny black holes instead of a dark particle? Absolutely. One of the proposed theories for dark matter is that it's made of primordial black holes. But you can't get that kind of black hole in any way that we understand in the universe today. So they would have to have been left over from the formation of the universe, that you would have had to have gotten black holes formed within a few hours after the universe itself formed. And then those black holes would just be roaming out in space. And you could absolutely explain the presence of dark matter with those black holes. But then you would also have to know that primordial black holes exist, which would be pretty weird. J, is there enough mass in our solar system to theoretically turn the sun into a black hole? So the sun will never become a black hole. That it doesn't have enough mass when it dies to have the implosion that you get a black hole from. But is there enough mass in the solar system to theoretically turn into a black hole? Sure. If you had a way to compress all of that matter into the right density, it would be a black hole with the mass of the entire solar system, which is the mass of the sun. You could turn your house into a black hole if you could compress all of the particles in your house into a small enough volume that it would have a escape velocity that exceeds the speed of light. So a black hole is really just about getting matter and energy close enough that you get a gravitational field that is you can't escape from. Bucko. So Fraser, we can't see a black hole. So what would one look like? I'm still a bit confused. Well, like you can't see a black hole. It's like the definition of a black hole is that nothing, not even light, can escape a black hole. And so if you tried to look at a black hole, then all you would see would be the distortion of space behind the black hole, right? That you would be seeing like a lens moving through space, the size of the event horizon. You see distorted light that's coming from behind the black hole that's being wrapped around the black hole by the gravity of the black hole. And then you're also not seeing the starlight that's falling into the black hole. It is emitting nothing. So you don't see anything. Now, you probably saw Interstellar, and you've seen they had one in that Zack Snyder movie I was mentioning, Rebel Moon. And so, if you've got a black hole that is surrounded by a bunch of material with it falling in, you're going to get like the accretion disk around the black hole, and you're going to get this weird distortions of it. But if it's just like a straight up stellar mass black hole just floating through the universe that has no accretion disk, then you won't see it. You'll just see this distortion of the stars in the sky where the black hole is, but that's it. Ronaldo, why do black holes have different sizes and masses despite all of them having a singularity that is infinitely dense? So we don't actually know what's going on inside the event horizon of a black hole. They call it the singularity, but that's more of a mathematical description of what's going on inside the black hole, that you can treat all of the mass inside the black hole, inside the event horizon, as if it is a infinitely dense point of space that is containing all of the mass of the black hole. And that the sort of ramifications in space is that this creates the event horizon, this region around which defines the speed that you would have to go to be able to escape the grasp of the black hole. That once you are inside the event horizon, you have to be going faster than the speed of light to be able to escape the black hole. Or really specifically, all roads lead to the singularity. That even if you could go faster than the speed of light, you still couldn't escape a black hole, because now really it is sort of the future light cone of everything that is within the event horizon ends at the singularity. But if you are just outside the event horizon, then you can escape out into space as long as you can go the speed of light, or even like a little bit less, depending how far away you are from the event horizon. But we don't know what's inside the event horizon. Like it could just be that there's, if you could actually pierce down into the event horizon, just below the surface, there is this giant object, the black hole, and it is just right under. And so actually the density of the black hole is the event horizon density divided by the mass. But it could also be that a black hole is significantly smaller. Maybe it's, for every billion light years, it's, this much bigger. Who knows? Or it could be infinitely dense, or it could be getting even denser over time. And we just don't know what that answer is. And so to keep it simple, astronomers, when they run their calculations with black holes, they treat it as if it's infinitely dense at the center of the event horizon. But what it actually is, we don't know. We may never know. No one wants to go inside to check.
Here's a black hole fact. Black holes have an entropy proportional to their surface area, and this makes them the most theoretically information-dense objects in the universe.
JC Explorations, is it theoretically possible to travel through a massive black hole and end up in another universe? So we don't know exactly what happens when we fall into a black hole, but when we think about what a black hole is, right? A black hole is a dead star. So you take a star that is many times more massive than the sun, and it sort of has the collapse of its inner layers after it runs out of fuel. It collapses down, you get a supernova, this infalling material compresses it down, and you end up with an object where it is so dense that now the escape velocity from this object has exceeded the speed of light. And so if you sort of consider other objects that are pretty close, like you take a neutron star, right? A neutron star is an extremely dense object caused by a supernova, caused by this implosion. You end up with an object where the escape velocity is just shy, just a little less than the speed of light. In other words, if you tried to take off from a neutron star with the most powerful rocket ever invented, it wouldn't work. If you tried to fire beams of particles at hundreds of thousands of kilometers per second, it wouldn't work. It's only light, only photons finally are going fast enough they can escape the gravitational pull of a neutron star. A black hole is a neutron star, but worse. It's more dense, more gravity than the neutron star. And you can orbit around a black hole. You can go to orbit around a black hole just the way you can orbit around a neutron star, just the way you can orbit around a star, the sun. And so again, we don't know what's inside the event horizon because all of the light that would try to escape that is getting pulled down back into the black hole, that is the event horizon. That is the point where light can no longer escape. And so you can't see it because the light can't get out of it. That doesn't sound like a tunnel to another dimension. That sounds like just a bigger version, a more powerful version of a neutron star. And so if you try to fly your way into a black hole, what would happen is exactly what happened when you try to fly your way into a neutron star. You would sort of crash onto the surface of the neutron star and be smushed down and form this atom-thick layer on the outside of the neutron star. And with a black hole, it would be worse. I mean, we don't know what it is, but it's probably worse. And so, the analogy that I was used to think about was, a frog looking into a blender and kind of like, I wonder where that goes. Will it take me to another universe? Jonathan Gariepi, could supermassive black holes be made of the lost antimatter that was created during the Big Bang? Yeah, so the lost antimatter, the lack of a balance between the amount of matter and antimatter in the universe is a puzzle. And this is one of the big questions that astronomers have, that in theory, there should have been equal amounts of matter and antimatter in the universe after the Big Bang. And we know that there were almost the same amount, but they weren't quite. And so in the end, we live in a matter-dominated universe and not an antimatter-dominated universe, or one that is equally balanced. And so, people always ask various versions and flavors of this question, like, is the antimatter out there somewhere? And so the answer is no, because when matter and antimatter meet with each other, you get this enormous blast of gamma radiation, like the sort of pure E equals MC squared formula version of energy. And so if there was clouds of antimatter out there floating through space and they interacted with clouds of matter, we would be seeing just this gamma ray glow in all directions, or wherever these collisions are happening. And we just don't see that. I mean, we see gamma ray coming from gamma ray bursts, and we see it from the accretion disks around supermassive black holes, but we don't see this generalized gamma radiation that's coming from large clouds of antimatter and matter finally meeting with each other. And you could imagine, like, there are galaxies made of antimatter out there in the universe. But they would be interacting with matter. Like, wherever the line is between the matter and the antimatter, we would just be seeing enormous amounts of gamma radiation. We just don't see it. So, but the question that you're asking, I mean, it's kind of interesting because inside a black hole, it doesn't really distinguish between whether something is made of matter or antimatter or energy or whatever. That, the classic question, I've answered this many times in the past, is like, if you had a black hole that was made of matter, and you had a black hole that was made of antimatter, and you put the two of them together, what would happen? Would they cancel each other out? Would they explode? No, that you would get a black hole with twice the mass. And that's because once you get inside the black hole, there's no real distinction between whether you're matter, you're antimatter, or whether you're light. And sort of think about that, right? Like if the escape velocity of the black hole is greater than the speed of light, and you took a black hole's worth of antimatter and a black hole's of matter, and you combine them together and they turn into pure energy, well, the pure energy can't escape the, can't escape the event horizon of the black hole. And so you wouldn't see anything. And so in fact, you could take just energy and you could just compress light down into the same kind of enough density that it would form a black hole. It's something that's called a Kugelblitz. And so there's just no distinction. And so, it'd be really weird that all that antimatter just ended up inside the black holes and not in spilling out into other regions of the places where those black holes are feeding on to add themselves. And if there's any antimatter mixed in with that, then we see the gamma radiation and we know that was going on. And we just don't see that. We just don't see the evidence of antimatter out there in the universe. Nick Stokes. Does Hawking radiation affect dark matter? If not, could we have dark matter only black holes in the far future? So, we don't know if Hawking radiation actually does exist. But if it does exist, this is this process where black holes evaporate over vast periods of time. But what the evaporation product is mostly photons. And so if you look at a black hole and you have sort of removed it from all external sources and you're watching the radiation that's coming off the black hole, then you're going to see heat coming off the black hole. It's going to be just the occasional photon here. Yeah, every now and then you'll get a more complicated molecule is going to come off a black hole, a proton every now and then, but mostly it's just going to be photons. And so what impact does radiation have on dark matter? And it appears that dark matter and radiation don't interact with one another except through gravity. And it seems really weird to say like radiation affecting dark matter through gravity. Well, according to E equals mc squared, you can take any amount of radiation of photons, you run them through E equals mc squared, and that tells you the equivalent of the mass, and that's the amount of gravity that light produces. And so light, theoretically, is going to be pulling on dark matter and shifting it around, but not by very much compared to what mass is doing. And so you're asking, like, could you have dark matter only black holes in the far future? Well, the thing is that like black holes are just made of black hole. So you don't really distinguish between what a black hole is made of. If you take matter, you put it into a black hole, you get black hole. You put antimatter into a black hole, you get black hole. You put energy into a black hole, you get black hole. And theoretically, if you put dark matter into a black hole, you get black hole. So there's no distinguishing between them.
Here's a random black hole fact. Did you know that there is a region around a black hole called the photon ring, where light itself is going in orbit around the black hole? And so if you were at the photon ring and you were looking forward, you would see the back of your own head.
RTX agent, how does Hawking radiation work when nothing can escape a black hole's event horizon? The Hawking radiation isn't coming from the black hole. It's coming from the area around the black hole. And then the black hole is donating the material. So Stephen Hawking figured out this idea of Hawking radiation. He realized that black holes should evaporate over vast periods of time. And the way to understand this is imagine that if you just were in empty space, there was nothing, like no stars, no planets, no energy, nothing, just the vacuum of space with nothing in it, no fields, nothing. And if you were stationary, you wouldn't experience anything, right? There'd just be nothing. You had detectors on your spaceship, you wouldn't experience anything. But if we accelerate, and this has sort of been demonstrated, been proven in the lab, that if you accelerate, then you start to experience radiation. And the radiation is coming from just space-time itself. There are just the fields that permeate the entire universe. And so when you're just stable, you're not interacting with any of these fields. But once you accelerate, then you start to experience these fields, and they appear as particles that are kind of, you experience this radiation that's coming at you only when you're accelerating. So not when you're just coasting, but when you're accelerating. And we know through the equivalence principle that, Einstein figured this out, that accelerating is the same as being in a gravitational well, that they are interchangeable. And so if you're experiencing a constant gravitational well, it should feel exactly the same as if you are accelerating through the universe. And so when you have an object that is close to a black hole, if you were sort of sitting next to the black hole and you were no longer accelerating through the cosmos, but you're instead in the presence of this gravitational field, it's the equivalent of you accelerating, you're going to be experiencing radiation. Now, radiation can't come from nowhere. It has to come from somewhere. And the somewhere that it comes from is the black hole. And so from an outside observer, they're watching radiation slowly come from the black hole, which is just the consequence of this equivalence between acceleration through just space itself, interacting with the fields that permeate the cosmos, and the black hole's gravitational existence in those fields that permeate the cosmos. The two have to be identical, and so energy is released. So does that explain the question of why, in theory, radiation should be escaping? And the term for that is like Unruh radiation. Georgie on 2. What's the theoretical distance limit of the gravitational influence of the supermassive black hole in the center of the Milky Way? You are being affected gravitationally by every single thing in the observable universe. And so the answer to what is the gravitational influence of the supermassive black hole is really answered by the same question of what is the gravitational influence of everything that I can see, or everything where the photons of light can reach me, because gravity moves at the speed of light, and gravity can influence or can affect you for as far as the gravity has traveled. And so things that are 46 billion light years away from you in one direction, you are still experiencing the gravity. You are feeling the gravity of the cosmic microwave background radiation, even though there is not very much gravity. Like, be certain that these amounts are absolutely minuscule until you start to get to large objects like the Earth, the moon, the sun. Apart from that, you're really not feeling a lot of gravity, but you are feeling a little bit of gravity from the supermassive black hole, but just because you're experiencing the gravity from everything. Now, people sort of think that there's something special about the gravity of a black hole, that it's like a vacuum cleaner that sucks in material, but it's just gravity like regular gravity. And so, if you took a black hole and with the mass of the sun, and you replaced the sun with the black hole, then all of the planets in the solar system would just continue to orbit this black hole sun in exactly the same way they did. Now, this thing would be tiny. It would probably be, a kilometer across, smaller. So it wouldn't be very big, but it would still have that amount of gravity. And so the solar system would just behave exactly the same. And so when you count up the mass of the supermassive black hole at the heart of the Milky Way, it's only about 1% of the mass of the entire Milky Way galaxy. People think it is the anchor, the heart, the important part for holding the Milky Way together. But no, if you just removed the supermassive black hole, Milky Way would go on exactly as it had before, except things would be a little different right down at the middle of the galaxy. And you could replace the supermassive black hole with a cluster of stars, 4 million stars buzzing around each other, and the rest of the galaxy would think that black hole was still there. Raul Gagna. In a recent episode, you highlighted how CMBR photons feed black holes. Apparently, even for a black hole of just 6 solar masses, Hawking radiation will not exceed the CMB contribution until the CMB drops to 1.5 K. When will Sagittarius A star start shrinking? Will all stars in the Milky Way and local cluster have already died by then? All black holes are evaporating. And this is this idea of Hawking radiation. And in fact, it might be that all mass is evaporating, that you're evaporating, I'm evaporating, Earth's evaporating. It's just that we evaporate very little compared to what a black hole will do. It's the most extreme side of this. And so the problem with black holes evaporating is that they can only really start to lose mass once they stop gaining mass. And they're gaining mass all the time. Obviously, in the beginning, we've got all of the stars and planets and gas and dust that the black holes are vacuuming up. But eventually, all of those ready sources of fuel run out, and then the black hole is left. It's like starving, and all it's got is just individual particles of hydrogen that happen to remain in the cosmos, and they find their way into the event horizon, and the black hole is able to nibble on that and stay alive. And then when all those particles don't come by anymore, it's still being fed by the cosmic microwave background radiation. These are the photons left over from the beginning of the universe. And so they are still going to continue to feed and provide energy to the black hole, which, is the equivalent of mass, and that allows it to keep going. It's not until about 100 billion years from now when the background temperature of the universe will be so cool that the evaporation of the big black holes like Sag A star will start to take over. But this process is incredibly slow. There's a lot of mass. And so it's been estimated that black holes won't lose their mass for a 10 to the power of 100 years. So let's say 1 followed by 100 zeros. And that is a long, long time from now. So although the most massive black holes will start to evaporate in this sort of 100 billion years from now, it still will take just an insane amount of time before they're fully gone. Ellen Nelson, from our point of view, we never see an object cross the event horizon of a black hole. Do we not see an aggregate of objects there? So what you're describing is the fact that when an object falls into a black hole, it's falling into a very powerful gravitational field that causes time dilation. And so, it starts off, it's falling. It seems like it's moving at normal speed. And then it seems to look like it's going slower and slower. And then eventually it seems to pause right on the surface of the event horizon. And then it just fades away, red shifts and fades away from our perspective. But, you're asking, like, would you just see a whole bunch of things, all the silhouettes of all the stuff that have fallen into the black hole at various times? And like, maybe, if they fell in reasonable amounts of time, then that's what you would see is a sort of history of the things that had recently fallen onto the event horizon of the black hole from our perspective. So yeah, you could sort of, if you could see all the explorers who thought that it would be cool to go and explore inside of a black hole, and you could sort of see, the more recent version where they're screaming, and then the sort of the older version where they're screaming, but now they're screaming in slower motion than even the older version where they seem to be just paused screaming. And now they're starting to shift into the red. And then there's like someone looks like a ghost screaming, but just barely visible because they've shifted into the radio waves from our perspective. Laurent Laborde, is it possible for a black hole to explode or somehow stop being a black hole in some catastrophic way? Sort of. So we talked about black holes and how black holes can evaporate. And so in the beginning, at 100 billion years from now, the evaporation process will begin. The black hole will start to lose mass. And then over that 10 to the power of 100 years, it will lose mass faster and faster until it gets to sort of the end game where the mass of the black hole, like essentially the heat that is coming off from the black hole, this is how we see the evaporation of the black hole. We measure its temperature, and the temperature will rise and rise and rise very slowly. It'll be 3 Kelvin for a long time, and then it'll be 4 Kelvin. It'll be 5 Kelvin. And eventually it'll be room temperature. But black holes have to be very small, like the mass of a very small asteroid. And then they start to get hotter and hotter and hotter. Within a couple of days, a small enough asteroid, something that is, say, the mass of a mountain, will completely evaporate. And then it will sort of, the last moments is it will be this flash of gamma radiation, and then it'll be gone. And so the catastrophic way is when it finally has almost completely run out of mass. It will heat up to the point that it will be incredibly hot, pumping out ultraviolet rays, pumping out X-rays, pumping out gamma radiation, and then it'll just be gone. Gocha M. If a black hole loses enough mass, won't it stop being a black hole and expand into a neutron star or something? Less gravity should mean light can escape once again, and imagine the fusion that could be happening under all that compression. No, once something turns into a black hole, it can never unblack hole. And, it's not about the mass of the black hole. It's really about the density, that
Once you have compressed matter down to the point that it is the density of a black hole, once the event horizon forms that defines the point around the singularity where the escape velocity of this black hole has reached the speed of light, it's a one-way trip. You're never going to turn that thing into a not black hole. And people wonder, if you slam two black holes into each other, could they somehow tear each other apart and then not turn into black holes again? Nope. Just once it becomes a black hole, it can't go the other way. Now, this idea of evaporation, we've been sort of talking about this for the last couple of weeks, that Hawking realized that black holes should be emitting radiation, and that would be sort of taking away the mass of the black hole. And eventually black holes should decrease in mass. And, there's a really interesting idea about primordial mass black holes that, there could have been, back to those, we talked about those waves in that previous question, that there could be places where there were overdensities and underdensities, and maybe the overdensities were so dense that you got black holes forming in these regions of overdensity of tons of different masses. And the way Hawking radiation works is that the less massive the black hole is, the hotter the radiation is coming off the black hole. We see its temperature as hotter. And that any black hole that has less than 100 million tons of mass should have evaporated since the beginning of the universe. And these black holes would be incredibly tiny. They would be the size of an atom, and yet they would have the mass 100 million tons. And I actually looked up what is 100 million tons, and something that we can sort of wrap our minds around. And it is a quarter of the mass of all the human beings on Earth. So if you sort of imagine all the human beings, or if you took 2.5 billion people and sort of put them all into one ball, that is 100 million tons. But imagine that amount but it is the size of an atom. And so with a black hole like that, or with any black hole, as they get lower and lower in mass, their radiation, the heat, the temperature of that black hole just increases. And so it moves through different wavelengths. And in the beginning, it's just putting out cool infrared, and then it moves into the visible skin. You can actually see the thing bright, and then it moves into ultraviolet, and then into X-rays, and then gamma rays, and then the thing just disappears. One final blast of gamma radiation at the maximum temperature that it can reach, and then it's gone. And so, black holes are going to move through that process. The most massively, the ones that are 100 billion tons will slowly evaporate down until they have 1 billion tons, and then they have 1 million tons, and then they have 1,000 tons, and then they have 1 ton, and then they detonate as a final blast of gamma radiation. And you will never get this point where the black hole turns back into a neutron star. Critical mass 22. I understand it's very hard for a mass to actually fall into a black hole. What is the process, and how long can it take for a mass to finally cross the event horizon? So I think you're confusing a couple of concepts here that I should just sort of separate for you in your mind. So you have heard correctly that from an outside perspective, watching someone fall into a black hole, it takes them an infinite amount of time to cross the event horizon. And that is because the incredible gravitational forces around the black hole cause enough time dilation that from your perspective as an outside observer, you don't see them actually cross the event horizon. We talked about this last week or 2 weeks ago. The astronaut falls to the black hole and then slows down as they get closer and closer to the surface of the black hole. You're watching them, and they appear to pause on the event horizon of the black hole, and then they just fade away. They redshift and they fade away. From the perspective of the astronaut, it is a smooth journey that they fall to the black hole. They are torn apart by the intense tidal forces. They are spaghettified, and they then go cross into the event horizon. And for the most massive black holes, they may not even get spaghettified. You could fly your spacecraft right into a black hole, like a supermassive black hole, and not even experience any tidal forces. You wouldn't even notice, but now you're trapped. You're never going to be able to get away from the black hole. And maybe you run into the black hole itself immediately. Maybe you have to make your journey down to whatever is the singularity. We don't know what goes on inside the event horizon of the black hole. But even from the outside observer, as someone falls into a black hole, their mass is added to the mass of the black hole essentially immediately. And that is because
the event horizon of the black hole grows as it adds new mass. Essentially, the event horizon rises to meet the new mass that is falling into the black hole. You don't see it as an outside observer, but this process is happening. And so even from an outside observer, we are watching that mass. And we think about it, like, this is the way it has to be. I mean, we see black holes out there with 10 times the mass of the sun, ones with 1,000,000 times the mass of the sun, ones with 1,000,000,000 times the mass. Like, how did they get so massive? They had to have been continuously feeding in times that aren't so time dilated out to infinity. And so from an outside observer, you can measure the increase of mass as someone falls into a black hole. I mean, you probably can't measure that directly, but maybe, as a star falls into a black hole, you can measure the increase in mass from that. But you wouldn't see it disappear into the event horizon. You would see it redshifted and time dilated to forever. Master of the game. Are there different types of black holes? Not exactly. You can really only measure a black hole with two numbers. You can measure the mass of the black hole and you can measure the spin of the black hole. You might be able to measure the magnetic field of the black hole, but essentially that's all you've got. And so you can describe any black hole with just its mass and its spin. You don't know what it's made of. It's made of black hole. You don't know what are the particles that are contained inside of it. It's just made of black hole. And so really the only way to distinguish between different kinds of black holes is that mass and that spin. And as the mass of the black hole increases, then the size of the event horizon around the black hole also increases in size. So for example, you've heard about stellar mass black holes and supermassive black holes, and maybe there are primordial black holes with the mass of an asteroid. And maybe there's a black hole that's the size of an atom with, the mass of a mountain. Well, they're all the same thing, just different amounts of mass. And you can turn a stellar mass black hole into a supermassive black hole just by feeding it more material. Bob Hoppeldorf, are there any binary supermassive black holes? Yes. Astronomers have identified several examples of supermassive black holes that are orbiting around each other. Now, just to sort of understand how this works, right? You have two galaxies that merge, and both galaxies have a supermassive black hole that is at the heart of them. And then as the galaxies merge, they sort of tear each other apart and they merge into this larger galaxy. And the supermassive black holes that were at the center of the different galaxies, they both sink down into the middle of the galaxy and then they start to orbit around each other. And eventually they merge. And, we see very, very massive supermassive black holes, and they must be made up of the mergers from smaller black holes. And so this is the process that must be happening. So about a week ago, when I'm recording this, we reported on Universe Today the story about the discovery of an object called AT2021 HDR. And this was known to have like a flash of radiation every couple of weeks. And astronomers have realized what this actually is. This is two supermassive black holes that are orbiting around each other. And they only take 130 days to go into orbit around each other. And they estimate that it is sort of a combined mass between the two supermassive black holes of 40 million times the mass of the sun. So when you think about the Milky Way's supermassive black hole, 3.5 million times the mass of the sun. So this is a lot of mass, and yet they are orbiting each other very closely. And it's estimated that they're probably going to merge within the next 70,000 years or so. And so this is an example. Like, wouldn't it be great if we could just stick around and watch that merger happen as those black holes come together and turn into this future 40 million solar mass black hole? And then maybe they'll find another one and merge with that. And that's how you get black holes with billions of times the mass of the sun, just merger by merger. You've reached question 256. That's a really nice round number if you're a computer. Kyle Stedward had a random thought. If you could orbit right on the edge of an event horizon and then have a long pole and put the pole through the event horizon, what would happen? So the question you're asking is that if you were orbiting around a black hole and you're right at the edge of the event horizon, this place where the escape velocity of the black hole exceeds the speed of light. And then you took a pole and you put the pole down into the event horizon, what would happen? So
like, obviously the first thing is like, what is the tensile strength of the pole that you are using? Because it needs to overcome just immense tidal gravitational forces that are going to tear it apart at an atomic level. And no matter what the pole is made of, it is going to be just pulled apart. And, you know, you're not going to be able to bring anything back up. But I'm assuming that you have created this pole out of some sort of unobtainium, something that is so strong that it can never be. Maybe it's made of black hole. Maybe it's made of neutron star, or even tougher than that. It cannot be shredded by a black hole's tidal forces. And so you kind of then have to go back to the first rule of the event horizon, that nothing, not even light, can escape its grasp. And so there is no amount of force that you could put onto that pole to try and pull it back up that would allow it to escape the pull of the black hole. Once you're inside the event horizon, all paths lead to the singularity, including the pole. Now, you know, obviously it's going to pull you in with it. So, but there's something, you can't break the rule, which is you can't get out of it. Even if you know, and because the pole strong enough to handle the tidal forces is impossible, that alone will make the problem, not work. So even if you could, you can't get it out. Like it will be held fast. Tony Hobbs, if Sagittarius A star suddenly became an average luminosity quasar, would we see it from Earth? And if so, what kind of brightness would it have? The supermassive black hole at the heart of the Milky Way, Sagittarius A star. This is a supermassive black hole with 4.3 million times the mass of the sun. And it is not a quasar. A quasar is when a supermassive black hole is actively feeding, materials falling into it. It is blasting out all of this radiation, and it is visible. You know, these are the brightest continuous objects in the universe. We can see quasars from billions of light years away, times just after the beginning of the universe. And yet we can't see the galaxy that's around them. We can just see the quasar. And so the Milky Way and most galaxies no longer have a quasar, but it might have been that the Milky Way had a quasar in the past. And the best chance for the Milky Way to get a quasar in the future is when Andromeda crashes into the Milky Way, or I guess Milky Way crashes into Andromeda. Anyway, when the Milky Way and Andromeda merge, then both the black hole at the heart of the Milky Way as well as the black hole at the heart of Andromeda will start feeding. They will get material, and it's entirely possible that they will turn into quasars. So what would that look like from the Earth? You're standing here, you're looking towards the center of the Milky Way. What would you see? You would see nothing. There is an enormous amount of gas and dust that is surrounding the area. And, you know, astronomers call this the zone of avoidance. And that dust is so thick that if there was a quasar at the heart of the Milky Way, you wouldn't see it because the dust is obscuring your view. But what if there was no dust? What would you see? You would see nothing, in that the quasar would not be pointed at you. The quasar would be pointed at some other direction in the sky. And so it wouldn't be a very bright object in the sky. I think I did a video about this many years ago, and I think the agreed brightness is like magnitude 8. So if you had a reasonably good telescope then, and you knew where to point it, and you had somehow removed all of the dust from the center of the Milky Way, then you would be able to see the quasar, but it wouldn't be that bright. Now, if it was pointed directly at you, which would be very weird because it should be aligned with the galaxy, but if it was pointed directly at you, then it would be brighter. But still, if and when the Milky Way gains a quasar in the future, billions of years from now, people on Earth won't be able to see it. Christian Desalier. Fraser, can you explain how the extreme gravitational field of a black hole causes spaghettification, and does this process affect all objects that cross the event horizon? Sure. So spaghettification is essentially tidal forces. So we'll sort of look at a less extreme version of this. So when you have, say, an asteroid that is flying past the Earth, there is a point where the asteroid gets closer and closer to the Earth, where the essentially amount of gravity that is experiencing on the close side of the asteroid is different enough from the gravity that's feeling on the far side of the asteroid that it overcomes the force holding the asteroid together. It depends on what the asteroid is made of. If it's a collection of rubble, then it's going to sort of smear apart. If it's made of rock or metal, then it's going to take more force to actually shear it apart into multiple pieces. But you're going to get this breakup of the asteroid into multiple parts. And then the asteroid is going to continue to orbit around the Earth. And then each one of these little parts is going to experience that same tidal force that's going to shear it into multiple pieces. And the same thing's going to happen. And then those pieces will get sheared apart. And then eventually you'll just have this sort of debris field that is orbiting around the Earth. And then it will all enter the Earth's atmosphere and the asteroid will be gone. And so when you think about a black hole, it's the same process. You are in orbit, let's say feet first, going around a black hole. And eventually, you're experiencing it like around a black hole. It is the most extreme gravitational well that the universe can craft. And so you're going to get closer and closer to the black hole. And at a point where the amount of gravity, the force that you're feeling on your feet is so much greater than the force that you're feeling on your head that your body chooses to be torn in half. That's better, right? That the force, the meat glue holding you together is weaker, than this difference in the tidal forces as you get torn apart into two pieces. And then those pieces get torn apart into other pieces and more pieces. And eventually you get broken up into this sort of atom thick stream of material that is orbiting around the black hole, and you go in. And the strength and the sort of the tidal shear that you experience depends on the size of the black hole. The smaller black holes, the stellar mass black holes, have a sharper gravitational well than the supermassive black holes. And so, you could fall through the event horizon of a supermassive black hole and not even feel it. You'd be, you're trapped and you're heading towards the singularity, but you wouldn't necessarily feel it because the gravitational well is very smooth, very gradual, inevitable, but gradual. While with a stellar mass black hole, it is sharp. And so you can be spaghettified as you go into orbit. Wisp frog. Are there the same Lagrange points for an object orbiting a black hole? What if it is rotating fast? Finally, a Lagrange point question. I'm so excited. So a black hole is nothing special from a star. It's just that it is more dense. And so you could replace the sun with a black hole of the same mass as the sun, which can't form naturally, but let's say that you could. And the rest of the planets in the solar system would be happy to orbit around this black hole sun. You would still have the exact same Lagrange points. You would have the black hole Earth, L1, L2, L3, L4, L5 Lagrange points. Same with Jupiter. Everything would be exactly the same. And so if you imagine a more realistic black hole, the kind that could form, say, something that has 10 times the mass of the sun, and let's say that it has a star that is orbiting around it that is maybe 1 time the mass of the sun. I mean, the problem is you need to get, they have to be very significantly different masses for you to be able to get those Lagrange points. And so the sun is 99.5% of the solar system, and Jupiter is most of the rest. And so you get those Lagrange points when you have this factor of 200 in mass between the sun and Jupiter. So you would need say a Jupiter or a super Jupiter or maybe a brown dwarf or something orbiting, or a red dwarf orbiting around this black hole. But yeah, you would get Lagrange points. You could imagine a dwarf galaxy that is orbiting around a supermassive black hole. Supermassive black hole has, say, 100 million times the mass of the sun, and the dwarf galaxy has 1 million times the mass of the sun. And you would get Lagrange points that would be popping up in the same places as you would get here in the solar system. So it's, what's important is that you need to have something with a lot of mass that is orbiting by something with less mass, a fraction of its mass, and that creates the Lagrange points. Okay, Charles Cheap Pockets. Could a black hole have an atmosphere? Sort of. Like when you think about an atmosphere around the Earth, the atmosphere is this layer of gas that surrounds planet Earth, and it is held down by the gravity, but the pressure of this gas and the temperature of it stops it from turning into a liquid or a solid. It wants to remain a gas. And so you get this shape of the atmosphere, this density and thickness of the atmosphere because of the Earth's gravity, but also the chemical characteristics of the gas. The sun is another good example. The sun has an atmosphere. You have particles that are whizzing around the sun. And even though the sun has an enormous amount of gravity that is pulling material into it, also those particles have a lot of energy, velocity. And so they are held out away from the sun and they can form this atmosphere around the sun. And in fact, the corona, like when you see an eclipse, and when the moon passes perfectly in front of the sun, you can see these cool kind of petals that are around the sun, and that is the sun's atmosphere. And so a black hole will have a corona. It will have material that is surrounding the black hole. And a lot of times, when a black hole is actively feeding, it can't eat an entire planet, star, whatever. It actually breaks it up and tears it into this accretion disk that surrounds the black hole and whirls around it. And then these magnetic field lines are spinning around the black hole that are then sort of channeling material into these jets that go out of the north and south pole of the black hole. But you also get all of this hot gas that is surrounding the area that's glowing in the X-rays. And this is how astronomers find black holes in some cases, is they can see this essentially atmosphere, this cloud of plasma that is surrounding the black hole in its environment, caused by the intense magnetic field, the energetic particles that are around it that are blazing in X-ray radiation. And so, it wouldn't be a breathable atmosphere, but there's definitely a cloud of highly charged plasma around a black hole. Casey Ream, is there a consensus on how likely it is that these primordial black holes actually exist? There is no consensus. So we're at the place where scientists have proposed that conditions in the early universe were dense enough and that you had these regions of overdensity and underdensity that were so different that you could have black holes just forming in situ, just right there in the early universe. And then those could be any size. You don't need the process of a collapsing star to form a black hole. You just get any size of black hole from something that is the mass of like I said, a house, an asteroid, a star, 1 billion times the mass of the sun. You could have all of this stuff forming right there in the beginning of the universe. And then one of the proposed ideas that this could be an explanation for dark matter. But the problem is that there should be some evidence for these primordial black holes, because as they pass in front of stars, they would be warping the starlight and you would detect this microlensing event, and you would be able to see, if they're 10 times the mass of the Milky Way is made up of black holes, then there's a certain mass regime where so many of these are going to be out there that they would be easily detectable by watching as stars are flickering, as black holes are passing in front of them. And astronomers don't see that. Astronomers have done surveys to look for these black holes that are out there in vast numbers. And so they've been able to rule out various mass ranges for primordial black holes. Now you're left with some mass ranges that are either like 1,000 times the mass of the sun or more, because they would be very rare. Like you would occasionally see one of these pass in front of a star, but there wouldn't be a lot of them. If you added up these 1,000 times the mass of the sun versions, then you could come up with dark matter. Or they could be much lighter. They could be more like the mass of an asteroid. And then you wouldn't detect their microlensing events as they were passing, but there'd be a lot more of them out there. And so astronomers are continuing to come up with ways that you could check to see if these primordial black holes are out there. And there's been other ideas like, there could be a black hole that is orbiting around the solar system and there is no planet 9. There's actually a black hole, which, I don't think very many people think is a legitimate possibility. Or you could have black holes that are trapped inside of planets and they're causing excess heat in the planet that could be detectable. So, I think that if you ask most astrophysicists and people who research dark matter and you say, do you think that dark matter is made of black holes? They'll say, no, probably. It is probably not the most likely explanation for dark matter. And then if you say, well, can you rule it out? They'll say, no, they can't. Right. Which is fine. Like that's how science works, is that there's going to be ideas that are not the one that is supported by the vast majority of the evidence, but is still there and it's not been ruled out yet. And that's awesome. That's totally fine. You just wait. You just wait for the evidence before you make up your mind. And I think like a lot of people, okay, this is about to turn into a rant, so buckle up. But I think that, a lot of people want some kind of certainty about things that we see in the universe. What is dark matter? What is dark energy? Why are we alone in the universe? And they want that certainty so bad. The most extreme version of that is where people think that UFOs are aliens, right? They're like, I saw light in the sky. I don't know what it is. Therefore, aliens. Case closed. It's aliens. And if you don't believe that it's aliens, you're a bad person and you're part of the cover up, right? Like you have to be okay to be in this space where you are uncertain about the answer and about the outcome, and that you're just enjoying the process of watching the evidence build, watching as new ideas, new research proposals, new missions are launched, which are going to attempt another crack at this problem. And I think like the classic example, the one that I find most frustrating, but also kind of hilarious, is when people roll their eyes and go, dark matter, lol. That's ridiculous. Scientists just came up with this thing so they could make their equations work. And like anybody who says that, like, tell me you don't understand the search for dark matter without telling me you don't understand the search for dark matter, right? Which is like that it is this series of observations, these careful observations that have made over time that have built this growing understanding that the universe is not as we perceive it. And that nobody ordered this, nobody asked for this, and yet this is the uncomfortable truth. And that whenever you find these things that are surprising and shocking and not expected and so on, then the resolution is not going to come quickly. It's going to take its time. And so with dark matter, with primordial black holes, with why there's more matter than antimatter in the universe, what is dark energy, how did galaxies form so quickly, what was here before the universe? These are big questions, and we may not find out the answer in our lifetimes, but we will enjoy the journey. And if you're not entertained by the journey, then science might not be for you. Fiat hater. What happens to the information contained in matter that falls into a black hole? Have we deciphered this yet? So this is the information paradox, and this is this idea that information that falls into the black hole is seemingly destroyed when black holes evaporate. And I sort of need to go back a little bit here. So when you think about a black hole, right, it is going to be able to absorb matter, and matter is going to fall into the black hole, and energy is going to be able to fall into the black hole. And the traditional thought was that even if this stuff is falling into the black hole, the information that describes this is preserved. That, you may have a planet that goes into a black hole, and that planet is made up of all of these individual particles. And if you went down to the quantum level and you described every single field and every particle that's in that, you'll have this information. And one of the rules in physics is that this information can't be destroyed. It can be kind of changed, it can be transformed, but it can't actually be destroyed. And so all of this stuff falls into the black hole and is beyond the event horizon, but it's still preserved. It's still in there. And then the big idea that Stephen Hawking came up with was that he realized that over vast periods of time, black holes should evaporate. And they should evaporate in this sort of black body way where the particles that are coming off of the black hole have no connection to what it was that fell into the black hole. And so this idea that information must be preserved is lost. And this is this paradox, the information paradox. And this is a puzzle. And this is something that has been troubling scientists ever since Stephen Hawking came up with this. And we don't know what the answer is. People still put out papers all the time and they argue about different things. And so, there are themes to the answers that people have been providing. One of the themes is that the information of the material that falls into the black hole is actually written into the event horizon of the black hole. There's this idea of the holographic principle that it's sort of like a weird coincidence that the event horizon of the black hole has enough surface area to describe the information that's contained within the black hole. And so it may very well be that even though stuff is falling into the black hole and it's evaporating later on, that this information is still preserved on the surface of the event horizon. The other possibility is that somehow this information is actually preserved even when it radiates through Hawking radiation, that it may have been transformed, but the information is not completely gone. It's still there, and you could theoretically decode it if you could grab every single particle that is evaporating away from the black hole. But the other possibility is that it is destroyed, and that this assumption that information can't be destroyed is wrong. So, we're still in early stages. A lot of people have come up with some really interesting ideas and made progress in this complicated physics question. But until, we get a chance to actually see Hawking radiation happen, it's going to be hard to know really what's happening to the information. Cusick, why do people keep saying that black holes have immense density? The bigger the black hole, the smaller its density, for example. Black holes can be measured by two numbers, which is the mass of the black hole and the spin of the black hole. Now, you can also calculate the charge of the black hole, but let's just deal with the spin and the mass. So when you have the mass of the black hole, that gives you the size of its event horizon. And then, the mass, the size of the event horizon, and then you can calculate the density. And it's a relatively easy calculation to make. And so different size black hole event horizons are going to have different densities. And the event horizon is purely just that spot where the escape velocity exceeds the speed of light. If you are able to go the speed of light and no faster, because obviously that's the speed limit of the universe, that defines it. And so you can just go and take any black hole that you want. You take its volume in cubic meters, and you divide it by the mass, and that gives you the density. And so even though the densities can be, in some cases, lower, strangely lower than what you might be expecting, it's still, that is the implications of having that much mass compacted into that much of a space. James Huffman, how do we know the mass of a black hole if no information is accessible? Well, you don't need to have access to the information inside a black hole to know the mass of a black hole. All you need to know is how things orbit around the black hole. And that tells you what the mass is. And this is a relatively straightforward calculation. You can learn this in high school physics, where if you know the orbit of the object that is going around the black hole, or the Earth, or whatever, then you can use that to calculate the mass of the object. And so and there's a lot of different ways that you can do that. I mean, as long as there's something orbiting around a thing, that will tell you the mass very accurately. And Newton came up with these calculations hundreds of years ago. Sean E., is there some way we can know for sure if there's a black hole at the center of Uranus? In theory, right, if you had a black hole fall into Uranus, then it would pass right through and just go out the other side of Uranus. But, if there was some kind of like three-body interaction where the black hole and Uranus and then some other object were interacting with each other, then it could cause the black hole to fall down into Uranus and then remain there. And then what would happen? Well, depends on the size of the black hole. Like obviously is a black hole the size, produced by a star exploding, then the black hole is going to be much bigger than Uranus. And so it doesn't really make sense to have a black hole inside Uranus. But if the black hole was, say, a primordial black hole, like a black hole that's been around since the very beginning of the universe, formed through regions of higher and lower density at the beginning of the universe, then we could have these primordial black holes of any size, and ones that could absolutely fit inside Uranus. So imagine that you had this very small black hole, maybe something with, the mass of a mountain or a house or something like that, and it falls into Uranus. and through some kind of three-body interaction, and it sits around inside Uranus and starts to gobble up material inside Uranus. Well, it's going to get this little accretion disk around it where it's pulling in material, and it's going to probably emit gamma radiation from the accretion disk to produce heat. And so while it is consuming the inside out of Uranus, it's also going to be releasing heat. And so we would see an excess amount of heat coming from Uranus that would indicate that there is a black hole inside Uranus. And so that's how we would know. Here's a black hole fact. Black holes have a temperature that is inverse to their mass. And so a stellar mass black hole has a temperature of about 60 nanokelvin. And because they have a temperature that is lower than the cosmic microwave background radiation, which is 2.7 Kelvin, they are being heated up and their mass is growing. Look, one, could you get rogue black holes that move around? If yes, what damage can they do to our solar system? I got some terrible news for you. All black holes are moving around. That all of the stars in the Milky Way are all moving they're moving around roughly the galactic disk as they go around. It takes about 225 million years for the stars to complete one orbit, but the stars are bobbing up and down in the disk of the galaxy. They're moving side to side. They are interacting gravitationally with each other in these three-body interactions. And so nothing remains. It's like this NASCAR track with cars going back and forth side to side. And so there are black holes that are moving in this collection of stars. And every now and then a black hole gets close to a star and causes a bad day. It can disrupt the planets in the system. It can even gobble up the star itself, but it happens very rarely. And so if a black hole came through the solar system, even if it wasn't very close to the solar system, it would cause mayhem. It would start to disturb the orbits of the planets. If it got close enough, it would start to really kick out planets from the solar system or crash them into the sun or consume them. So it would be a very bad day. But when we look at our solar system, it's been around for 4.6 billion years, and we don't see any obvious signs that a black hole came through here in that entire period of time. And so we can feel pretty confident that we won't see a black hole in our lifetime in the life of the sun, because it's a very, very rare event. But it's not a non-zero event. Like right now, somewhere in the Milky Way, there is a black hole that is disrupting a planetary system right now. Or maybe it's happening multiple times. There are 100 million black holes in the Milky Way. And you don't even need a black hole. Like a neutron star would be a bad day. There are 1 billion neutron stars in the Milky Way. And you don't even need a neutron star. A white dwarf would probably be an unsettling companion to make its way into your solar system. And there are 10 billion white dwarfs in the Milky Way. So, it's a dangerous place out there, but also it's really big. And these kinds of things happen very rarely. So don't worry about it. Vince Baker, are black hole jets the result of things falling in? Sort of. So yeah, we see these pictures of black holes, and I'm sure at this point, if you're watching this, there's going to be a really cool animation of a black hole with a accretion disk around it and these jets that are going out of the poles of the black hole. And people say, well, if stuff can fall into a black hole and nothing can escape, not even light, then how can you have this material blasting away from black holes? Well, they're not coming from the black hole. They're coming from the region around the black hole where you can escape. And so what happens is that material that is trying to fall into the black hole, sometimes it can be too much. The black hole can't handle it. Sort of think about like a drain in your bathtub, right? You pull the plug out of your bathtub and the water goes around. It can't all fit down the pipe yet. And so it has to spin and wait until room is made. And so the same thing is happening with a black hole. All this material has to fall into the black hole. There's not enough room to go into the event horizon. And so this material has to pile up into this accretion disk and wait. And so as you get this black hole, it's rotating in the center of this giant accretion disk, you get these very powerful magnetic fields that form around the black hole. And then these create funnels that channel material away from the poles of the black hole. And you get the same kind of situation with, at the largest scales with supermassive black holes, but even at small scales where we have individual new stars forming. They have, they're not a black hole, but they still can create these jets, these outflows that go out from the poles. So it's not coming from the black hole. It's being fed by the accretion disk in the environment around the black hole. J.R. Corday. Lately, there's been a lot of talk in papers proposing that our universe might be inside a black hole. How are these studies proposing we get an entire universe's worth of mass from one black hole? Now, there have been people proposing that the universe is inside a black hole for a long time. And, one sort of interesting coincidence is that if you take all of the mass of the observable universe, it is roughly the same as a black hole with an event horizon the size of the observable universe. That's interesting. Probably a coincidence. But the talk recently about this comes actually from one paper. So not a whole bunch of papers, but one paper. One interesting finding. And that is that images from the James Webb Space Telescope seen out to the very edge, the farthest galaxies that Webb is able to see, most of the galaxies appear to be rotating in the same direction. And this is very surprising because around us more locally, we see galaxies rotating in completely random directions, which is what you would expect, right? You would expect it just to be chaotic and that there would be no direction that everything was spinning. And so one theory that the researchers who found this rotation said, well, maybe the whole universe is inside a black hole and this black hole is turning. And that would explain why you've got, whatever the direction is that the black hole is turning, that is also causing the direction of the galaxies that are spinning at the very edge of the observable universe. But there's also a very plausible other explanation, and that is that we live in a galaxy that is turning in one direction, and that, because of our motion in the galaxy, that's going to change the way we see these galaxies at the very limits of what James Webb can observe. And that if we had a better telescope, we would be able to see other galaxies that are turning in that same area that are in random directions. So it's, which is it? Is it more likely that we're in a black hole that is turning, or that we're part of the Milky Way and it's just an observational error? So I would not be surprised if that result goes away. It's cool, but, less likely than some issue with the way we're observing them. Kristen Holcomb, do you think the discovery of black holes in the middle of big red dots explain how black holes appear in the centers of galaxies? So this thing, and it's little red dots, and this was an entirely new class of astronomical object that was discovered by the James Webb Space Telescope. And so when Webb was doing one of its surveys of the distant universe, looking at, the farthest galaxies that it could possibly see, they found a bunch of these weird red, and even red, it's an infrared, but they're redder than other galaxies, and they're very small. And astronomers were trying to figure out what these things were. And the sort of conclusion that they've reached now is that these are galaxies that are black hole heavy. So they're fairly small, probably like dwarf galaxies, but they have a surprisingly massive supermassive black hole at the hearts of them compared to the mass of the rest of the galaxy. And then the region around the black hole is shrouded in dust. And so that's putting out a lot of infrared light that is then being redshifted compared to other galaxies. But this is we're at the very early stages of figuring out what these things are, because it's right out at the very edge of what James Webb can see. And James Webb is the most powerful space telescope ever built, designed for this exact purpose. But there's sort of a very interesting things that people are finding early on in the universe. Right now, the Milky Way has a supermassive black hole at the heart of it. And it is about 0.1% the mass of the galaxy is tied up in that black hole. And so, people always think, what would happen to the Milky Way if it lost its supermassive black hole? Nothing. It is not the anchor. It is not the bulk of the mass of the Milky Way. It is one tiny little bit of the mass of the Milky Way. But when you go back early on in the universe, the ratio of black hole to the rest of the galaxy seems to go up. And when you get all the way back to these little red dots, you're looking at black holes that are 10% the mass of the galaxy, half the mass of the galaxy. And so one of the big fundamental questions that James Webb is trying to answer is, how did those first galaxies come together? We know that there are supermassive black holes at the hearts of pretty much every single galaxy in the universe. And so the question is, did the black hole come first and then it assembled a galaxy around it? Or did the galaxy come together first and then the various black holes, stars detonated, turned into black holes, the black holes merged together, formed larger black holes, and eventually, it all sunk down to the middle and you got this supermassive black hole. And so if you're seeing a much more massive black hole compared to the mass of the galaxy, it's starting to give credence to the idea that these supermassive black holes were starting to form first. And then the rest of the galaxy was starting to accrete around it. And that's weird because you would think that for you to be able to get a supermassive black hole, you would have to go through this process of chaining together a whole bunch of smaller black, you'd have the first generation of stars, they would explode as supernova. Maybe some of them would leave behind black holes. Those black holes would find each other. They would merge into bigger black holes, and you would sort of go through this geometric progression until you finally reach things with tens of millions, hundreds of millions of times the mass of the sun, even billions of times the mass of the sun. But the other possibility is that if the conditions are right, you could get supermassive black holes just forming directly. It's called direct collapse. And what they think, this is difficult to achieve because as you have material that is infalling to some region of space, that region heats up. And as soon as it heats up to a certain point, then that blocks and prevents any further material from infalling into it. And then that sort of puts a limit at the size of the star that is possible to be made. And, those limits are around 100 times the mass of the sun. And so, how are you going to get a supermassive black hole when you're limiting the amount of mass to about 100 times the mass of the sun? Actually, those most massive stars, when they detonate, they don't leave any remnant behind. So you need smaller mass stars that can then lead black holes that can merge together. But maybe there's some kind of cooling effect, some kind of way that when the black holes were forming early on in the universe out of primordial or hydrogen and helium, as that material was falling in, it was able to, get rid of the waste heat so that material could actually efficiently come together and actually pack down into an area that would turn directly into a black hole. And that would give you a really nice answer. So, James Webb was designed to answer these kinds of questions. And so now finally, we can go from theory to actual observations. And, I think over the coming years, we will get some really good answers to these kinds of questions and more. Daniel Rizek, what do you think of the possibility of black holes being created by accident by past civilizations experimenting with mass and pushing their limits? Well, we know how black holes can form, which is that we have a star with many more times the mass of the sun that implodes. And in this event, you get a black hole. And we see black holes that have been formed. We see stars that have had supernova with the amount of energy capable of producing a black hole. So, all of the bits and pieces for what it takes to make a black hole seem to be fairly obvious. Could advanced civilizations create black holes? Theoretically, sure. People have wondered if the Large Hadron Collider could create a black hole. We weren't able to do it, but it still seems theoretically possible that a future collider with more energy could produce a black hole. And once you've made a black hole, it's going to evaporate in a fraction of a second. But if black holes don't evaporate, then you've got a problem. You've created a black hole. And now what are you going to do with it? And it's going to fall into your planet and start to gobble up your planet from within. So, what I think the chances of this are very low. Black holes seem to form in natural ways, and there could be some out there that were created by civilizations, but it wouldn't account for the number and the mass of black holes. There are 100 million stellar mass black holes in the Milky Way. That there are, say, 2 trillion galaxies in the observable universe, each of which has a supermassive black hole with millions to billions of times the mass of the sun at the center of it, those were probably just formed by stars crashing into each other, exploding, imploding, maybe large amounts of gas collecting into black holes. I can't see how people would be responsible for all that. Bentation Funkalogio. If a primordial black hole was light enough, could one play catch with it, assuming that you could see a subatomically sized black hole? Sure. I mean, a primordial black hole can be any mass. So it could be the mass of a baseball, and you could absolutely play catch with it. However, there are a couple of issues. Like, you could pick it up if you could hold it, but the problem is that you can't hold it, that it would be microscopic, and any of your atoms that got too close to this baseball mass black hole would start to absorb some of your atoms. So you wouldn't be able to hold it. Also, it would evaporate. So, anything smaller than a small asteroid, like a house-sized asteroid, will evaporate within about a day. So there is no way to have it remain stable, and there's no way to touch it, pick it up, except using gravity. Here's an interesting black hole fact. When black holes merge and we detect the gravitational waves with instruments like LIGO, this is because the black holes have converted several solar masses into energy. In fact, the first ever black hole collision that was ever discovered in 2015 converted 3 solar masses into energy in 0.2 seconds, which exceeds the energy output of every star in the observable universe. Farina Kumar, what do you think about double or triple black hole systems? I mean, we know that double black hole systems are out there because that's what the LIGO detector is finding, that astronomers are detecting the gravitational waves that are coming from binary black holes that are crashing into each other and sending out gravitational waves. There must be triple black hole systems out there. They're going to be rarer, but they're going to happen too, because we see triple star systems. The largest stars, the giant stars, tend to be in multiple star systems, 2 stars, 3 stars, 4 stars, etc. It's the red dwarfs, which are the most common stars, that are singletons generally, but it's the larger stars tend to be in larger systems. And so I'm sure out there are 4 black holes in a system because they were once 4 giant stars and they all detonated as supernova and they all turned into black holes. And now all those black holes they're spinning around each other and in a big quadruple star system. Casey Ream, if some massive stars can collapse into black holes without a supernova, how do we know that won't happen to Betelgeuse? Or could it? That would be anticlimactic if it did. Yeah, this is called an unnova, or a direct collapse black hole. The traditional idea is that when a star reaches the end of its life and it uses up all of the fuel in its core and the outer layers collapse inward and you get this compression and this enormous amount of energy, you get the black hole forming because there's like too much matter and energy in a small enough region, but you also get this release of energy. Essentially all the stuff bounces off of piles up and explodes with an enormous amount of energy. But astronomers have seen examples where there was a progenitor star out there in the cosmos, and then they went back and checked a few years later and it was just gone. The star had just disappeared. And so one idea that's happening is that these stars, they're going through this process. They're becoming a supernova. They're collapsing inward, but the black hole is capable of eating all of it. And so instead of it reaching some point where it's just too much and the thing explodes, the black hole just forms and just gulps down the entire star. And then now you're just left with a black hole. And so could this happen to Betelgeuse? We don't know. I mean, we don't know if this is actually the explanation for these disappearing stars. And if it is, we don't know what is the mechanism. Like, do you need some kind of perfect turbulence in the star to be able to make this thing happen? We don't know. So, maybe it would be crazy. Wouldn't it be crazy if Betelgeuse just disappeared? That would be bonkers. Here's a black hole fact. Primordial black holes created at the beginning of the universe are one possible explanation for dark matter. Now, astronomers have ruled out almost every version of that, but you can have primordial black holes that are between 10 to the power of 17 grams and 10 to the power of 22 grams that would explain dark matter. You don't need any particles, you just need black holes. 6 times as much mass in black holes as just all the other regular matter in the universe. Lance Herring, is it a proven fact that black holes do not suck in matter and shoot out dark matter through the other side? Well, the problem with a black hole is that there isn't another side, that a black hole is a sphere. Or, the event horizon of a black hole is a sphere. And so instead of it being a hole, you sort of imagine you're walking along, you see a hole in the ground and you throw stuff in the hole. Where does the hole go? But a black hole, when you think about the gravity of a black hole, it's a lot more like thinking about the gravity of planet Earth. You walk around, around the entire Earth and you're being held to the surface of the Earth because of the gravity. And so the same thing, that a black hole twists, affects space-time, causes this distortion in space-time that causes mass to be attracted to it. Or I guess mass thinks it's following a straight line. But anyway, the point is that it goes in 3 dimensions. And there is no exhaust port on a black hole. There is no other side to a black hole. If you go into the event horizon of a black hole, you get added to the mass of the black hole. Some people have proposed that, Hawking has calculated that black holes will evaporate over long periods of time, but it's definitely not the source of dark matter that's coming from them. Scott Simile, I heard that the picture of Sagittarius A was modeled after what the researchers thought it should look like and not a true representation of the black hole itself. Can you clear this up for me? So I'm assuming you're talking about the image from the Event Horizon Telescope that shows the black hole at the heart of the Milky Way. And it's real data, right? They really did take radio dishes around the world, turn them into a virtual telescope, and point them all together at the supermassive black hole at the heart of the Milky Way. And then all of them acted like a telescope that was the size of planet Earth. And it is the highest resolution telescope that has ever been made because, you've got a telescope that is thousands of kilometers across. But the first thing to understand is that they were gathering their data in the radio waves. So not visible light, but they were gathering radio waves. And so, what does it mean to see radio waves? When you're looking at pictures that come from James Webb, they're in infrared. What does it mean to see in infrared? You can't see in infrared. You can feel infrared. But if you want to be able to see infrared, you've got to wear special infrared goggles, or you've got to take a picture with an infrared camera and then look and then have the infrared camera shift the wavelengths to, wavelengths that you can see. So that's part of it. And then the other part of it is that it was an enormous amount of data that was required to be able to crunch down, to be able to produce that final image. And the image is not even the event horizon of a black hole. It's the shadow of the event horizon of the black hole. But the features that are in there, the way the gas is moving around the black hole, the orientation, all of the things that are in that picture and the things that helped the astronomers be able to confirm their calculations. So there are real data in that picture that astronomers are able to use, but obviously they had to colorize it because you can't see radio waves. So, there is, people always have this concern when, whenever there's an image that's taken in a wavelength, like James Webb, right? That's taken in a wavelength. And people are like, well, that's not actually a picture. That's not actually a photograph. No, obviously, but it's real data. And the data is being presented to you in a way that you can see it with your eyeballs that are designed, that evolved to see in the visible wavelengths. And so it's the same process. Uger E. When we're in the solar system, we orbit the sun. After we leave the system, do we start orbiting the black hole in the center of the Milky Way? Right. So we are on the Earth and the Earth is orbiting around the sun and the Earth is going 30 kilometers per second around the sun. And that if you get into Earth orbit, it takes, 7.5 kilometers per second to get into Earth orbit. And then you need about another 12 kilometers per second to escape the solar system. And so once you escape the solar system, you are now moving through interstellar space. You have escaped the gravitational well of the sun, and you are now orbiting like the rest of the stars in the Milky Way around the center of the Milky Way. And yeah, at the center of the Milky Way is the supermassive black hole. But the supermassive black hole is not the dominant force of gravity in the Milky Way. It really accounts for less than 1%. 0.1% of the mass of the Milky Way. The dominant force of gravity in the Milky Way is the dark matter halo that all of the stars and all of the gas and even that supermassive black hole are embedded within. And this giant dark matter halo is turning. And we, all of the stars inside the disk of the Milky Way, are embedded within that halo and turning with it. So yes, if you were to like form a rough circle, that the path that you would be taking around the Milky Way, at the center of that is a supermassive black hole. But to say that you were orbiting around it, it is not the thing that is holding you in place. It is the sort of sum gravity of all of the stars in the Milky Way, all of the gas, all of the dust, as well as that halo of dark matter. Graham W., could you detect an interstellar black hole if it passed in front of a star? I know it would be an absolute fluke to be watching the object at that exact time. So what you would see is a gravitational microlens where the black hole passes in front of a star and distorts the light of the more distant star in a way that we see this sort of flash of light. And this happens. Black holes have been discovered briefly by them passing in front of a star. But also rogue planets have been discovered in this exact same method. And other stars with planets around them have also been discovered using this method. So it's a very precise method. You know, you're watching this star and then something passes in front of it and it acts like a lens and distorts the view to that star and then goes out the other side. And you have to be watching large swaths of the sky to be able to do this. And there's a telescope that has just come online that's going to be doing a lot of this, and that's the Vera Rubin. So these micro-lensing events are the kinds of changes in brightness that Vera Rubin could detect. Although it's fairly rare, you know, it has to be watching at the right time. But the other telescope that's going to be coming online in another couple of years is going to be the Roman Space Telescope. That launches in 2027. And it's probably going to find hundreds of rogue planets through that microlensing event. But really, anything that is changing the brightness of stars in its field of view should be found. And this method of microlensing is the way that astronomers have been trying to search for primordial black holes. So we know that there are stellar mass black holes, and we know that there are supermassive black holes. But the question is, are there smaller black holes, the kind of thing that are left over from the formation of the universe? And they could be of any mass. And we don't know if they exist. And like, they could be one explanation for dark matter. And so the way that astronomers are trying to find out if they're out there is to look for these microlensing events, that you look at a giant field of stars and then you just count the number of times that a black hole of the right mass passes in front of a star. And then that gives you a sense of how many of these black holes there could be out there. And now it looks like, you know, astronomers have not seen these microlensing events from smaller black holes. And so it means that if they are out there, they're either sort of too small to cause a significant lensing event, or that they're too massive to happen very often. Like maybe they're 1,000 times the mass of the sun, or they're the mass of an asteroid, but they're not in between, because if they were, then we would see a lot of these lensing events of stars in the field of view. Here's a black hole fact. The smallest possible theoretical black hole has about 2 to 3 times the mass of the sun. And so if we ever find a black hole smaller than that, it must have been a primordial black hole. Ivan M. Is the density of a black hole the same in the center of the black hole compared to the edges? So we can describe a black hole in 2 major numbers. We can describe the black hole in terms of its mass, and we can describe it in terms of its rotation, its spin. Now, you can also theoretically measure its charge, but anyway, its mass and its spin. And from the mass, you can calculate the event horizon. This is the point where the escape velocity to get away from the black hole is the speed of light. And so as you get closer within the event horizon, then the escape velocity exceeds the speed of light. And if you are outside of the event horizon, then the escape velocity is a little bit less than the speed of light. And so light can escape. But we don't actually know what is inside the event horizon of the black hole. Mathematically, you can describe the black hole like the entire mass of the black hole. 10 times the mass of the sun, 1,000,000 times the mass of the sun, 1,000,000,000 times the mass of the sun. You can consider it in a single point, a singularity in space. And then you get, from that singularity, you get the event horizon forming as a size around that. But, if you could actually look inside through the event horizon and understand what it is that you were looking at, what would you see? We don't know. So there's a range of possibilities. One possibility is that the black hole is just right underneath the surface, whatever is, so think about it, go this way. So if you imagine, say, a neutron star is a ball of neutrons. It is the degenerate remnant left over when a star that is much more massive than the sun detonates as a supernova, collapses in its interior, and the protons and the electrons are smushed together to create these neutrons. And this gives you the neutron star. Neutron star is like the size of a city. They're 10 kilometers across. They're very small. And yet they have an enormous gravity. You would have to be going close to the speed of light to be able to escape from the surface of a neutron star. But if you are going the speed of light, you can get off. And that's why we can see them, because they can shine in radiation. And so imagine, right? You've got this spinning ball in space of neutrons from a neutron star, and you feed it material and you feed it material and you feed it, and it gains in mass and it gains in mass. It becomes more massive. And then eventually you hit this, and at the same time, the escape velocity off the surface of the neutron star is going up. And eventually it will get to the point that the escape velocity meets the speed of light. And you now have a black hole. And so an event horizon will form around this neutron star that is rapidly spinning. And so is what's inside the event horizon still in there? But now you just can't see it because the mass has exceeded the speed of light? Maybe. But maybe when it reaches that point, then maybe it continues to collapse. That in fact, the pressure that is holding the neutrons together is overwhelmed, and maybe it turns into a ball of quarks, or maybe the quarks are overwhelmed and it turns into something even smaller. And maybe it actually does turn into a singularity, that the forces of physics can't withstand this amount of material that is crunched into a density that is this high. And so you can imagine it actually does compress down into an infinitesimally small thing. And so in fact, inside, there is the black hole that has all of the mass of the entire black hole that is down into this one single point. And then the rest of the interior of the event horizon is empty space. But it doesn't matter, because we may never know. There may be no practical way that we can ever probe what is in the interior of the event horizon of a black hole. We might just have to be okay with that. Shabazz Razel, how is it possible that light cannot pass the event horizon, but a black hole has gravity? How do gravitational waves pass through the event horizon if they have the same speed as light? So kind of asking, how do gravitational waves, how can a black hole emit gravitational waves? And so gravitational waves are a consequence of moving mass. And so if a black hole moves, then the distortion of its mass in space-time is what is releasing the gravitational waves. And so you kind of can't have mass moving without gravitational waves. Black holes are made of mass, therefore they have gravitational waves. But so one interesting question is what happens if a gravitational wave hits a black hole? All right. Then it wasn't created by the black hole. So now it's sort of crossing into the event horizon of that black hole. And they'll go into the black hole, and they will actually be added. So the energy, or the mass equivalent of the energy in the gravitational wave, the exact part of the gravitational wave that hits the black hole event horizon, will join the black hole and be added to the mass of the black hole. The gravitational waves that were just missed the event horizon, they'll get caught up in the distortion, and they'll be refracted, and their directions will change because of the curved and twisted spacetime as they get really close to the black hole. But you kind of just can't get gravitational waves without moving mass, and black holes are the most mass moving. Naked Hand, my son recently asked, what happens if a star collides with a black hole? So the star is torn apart by the intense gravitational forces around the black hole. And astronomers have seen this in action. So they've seen examples out there where you have a black hole and the black hole has a star that is orbiting around it. And every time the star gets too close to the black hole, it gets torn apart a little bit, and then it releases a lot of energy, and then the star continues on this journey around the black hole and then comes back through the accretion disk or comes back close to the black hole, gets torn apart a little bit more, and the black hole just continues to snack on the star until eventually it has eaten all of the mass of that star and the star is gone and it's added to the mass of the black hole. Paul Wilson, is there an upper limit to how big black holes can get? No, there's no theoretical limit to how large, how massive black holes can be, that you could feed all of the mass and energy and dark matter and dark energy into a black hole and it would just become more massive. That nothing weird would happen to the black hole. If anything, it would make it more stable, more long lasting, that it would be able to last even longer before it evaporates away. So it doesn't seem to be any limit to what a black hole can eat. Steve Barbarick, when I see a picture of a black hole, it shows everything being sucked into it and something needs spit out. What is it spitting out? Yeah, the thought is like black holes pull in everything. How can there be stuff coming out of black holes? And yet you look at the illustrations and you see this giant accretion disk around the black hole and you see these jets coming off of the black hole. How's that possible? Well, so black holes spin, and as they spin, they torque up space-time around them. And they have this magnetic field that can form around the black hole. And that magnetic field interacts with the accretion disk. And these black holes are spinning fast. Like they are spinning at the maximum speed that is allowed by relativity. Like they're spinning at 60+% the speed of light. Imagine that, right? This object that is a few kilometers across that is spinning at 60% the speed of light. And then this magnetic field is churning up this area in this accretion disk around the black hole. And it creates these funnels that go out from the poles of the black hole that channel gas and dust out into space. And this happens at the small level. And so this material is not getting into the black hole. It's in the disk that's around the black hole that the magnetic fields are picking up and channeling outward. And then it is traveling out into space at relativistic speeds, close to the speed of light, off for tens of light years, hundreds of light years on the stellar scale. But this also happens on the biggest black holes. So the ones that have millions of times the mass of the sun, they also spin at close to the speed of light with enormous magnetic fields and these accretion disks. And then they produce these jets that go for tens of thousands, millions of light years off into space. And they're like these beams that can impact other galaxies. And so one of the really interesting pieces of research right now is what is the effect of these black hole jets as they travel through space? And so if you're in a galaxy that is just, happily minding your own business, and then one of these beams from a black hole hits you, then this is going to cause star formation in your galaxy. This is going to cause enormous amounts of material to be falling into the galaxy, starting to compress clouds of gas into additional stars. That this is going to set off a wave of star formation in your galaxy. And so it could be that it's very good that actually being hit by one of these death beams was the best thing that ever happened to you. But also it probably increases the radiation in the environment. And maybe it makes you use up your reserves of gas and dust too quickly. And then this material can also fall back down on the galaxy. So you've got the jets going out, it's being accelerated, but then the gravity pulls it back in. And it showers back down onto the galaxy. So this is a field of active research. And, we're seeing, we're reporting on this all the time on these kinds of how these jets, change the nature of the galaxy that the black hole's inside of, but also how this can actually cause issues with the galaxies that are around them. Paul Wilson, apart from Hawking radiation, is there a way to kill a black hole? No. Anything you try to do to a black hole just makes it stronger. And so you would have to starve a black hole. You would have to put it into a box and remove all of the radiation, all of the potential mass that could fall into it. You put it just to absolute zero, or just a little bit above absolute zero, and then you let the Hawking radiation make it evaporate. But there's no other way to get rid of it. You're stuck with your black holes until they evaporate. Shoots 234. My summer astronomy class just started. My professor says she loves black holes. Got any super interesting facts we could talk about in class? If you had a black hole with the mass of the entire observable universe, it would have an event horizon of the entire observable universe. See how she handles that one. Osiris MPG. Could a ship traveling to Alpha Centauri crash directly into a black hole the size of a few meters? How would such a collision unfold? How fast would it happen? Would the astronauts feel anything at all? So if a spacecraft hit a black hole that was a few meters across, then that would mean you have the mass of like Jupiter. I'm trying to think. So if you had a black hole the mass of the Earth, it would be a centimeter across. If you had a black hole the mass of the sun, it would be a kilometer across. So I'm sort of imagining something a few meters across. You're having the mass of Jupiter. And so if you crashed a spacecraft into Jupiter, it would be catastrophic for the spacecraft. So yeah, it would, the gravity of the impact would dismantle the spacecraft, very quickly. Now you could hit something with, say, the mass of an asteroid and it would just pass right through, punch a nice little hole because the gravity wouldn't be strong enough to really cause any failure to the superstructure of your spacecraft. But if you're going to hit the mass of Jupiter, unless you're, made of some kind of unobtainium, it's going to cause stress to the structural elements of your spacecraft. In other words, dismantle it. Supex Andrew Kirkpatrick. Can a black hole have a planetary system where the planets are far enough away from its gravitational pull that they are able to orbit the black hole safely, including stars and such? Yeah, absolutely. If you replaced the sun with a black hole with exactly the same mass as the sun, then the planets would just continue to orbit around this black hole sun for the same amount of time. Probably longer, because now the black hole isn't going to go through the end of the star the way that the sun will. So you could have the planets going around the black hole sun for billions and billions and trillions of years. As long as nothing came through to disturb the system, it would last forever. And so theoretically, there are black holes out there where the planets are far enough away that they're in a planetary system around the black hole. Now, it's not a great place to be because you're not getting any radiation from your star, but you're at least stable. People have proposed that this is a really good way to organize the solar system, that, you put a supermassive black hole at the heart of your system, and then you bring in stars and you put them in orbit around the black hole in a way that is stable. And then you could put planets around those stars, moons around those planets, and you could have systems that have multiple black holes, multiple supermassive black holes. You could have thousands of stars with 10,000 planets all in one big elaborate system, theoretically. So a black hole is not like a vacuum cleaner. It is just a thing with mass, like anything. It's only when you get really, really close to a black hole do things get weird. Do you experience the time dilation? Do you experience the extreme tidal forces? But once you're far enough away from it, still trapped in its gravity, everything is fine. Here's a black hole fact. You could cross a 40 billion solar mass black hole's event horizon and not feel anything. Owen Bowen. How can a black hole be used to generate power? So there are a couple of ways that black holes are theorized that they can use power. The first way is that you feed material to the black hole. Most of the material will go into the black hole, but you will also get high energy radiation coming off the black hole. You get gamma radiation. So theoretically, if you put like a mini Dyson sphere around your black hole, you will be able to capture the energy that is coming off the black hole. And really, it's just like as matter is falling into the black hole, as matter is going into an accretion disk around the black hole, there's lots of ways that black holes can release high energy radiation, X-ray radiation, gamma radiation. And so you could theoretically harness that. But the most efficient way to harness power or energy from the black hole is known as the Penrose process. And this was a clever idea thought up by Penrose, where you drop material into the black hole, and then the material will some of it will go in and some of it will be kicked out. So say you drop a, I don't know, cannonball into a black hole. And just as the cannonball is about to go into the black hole, you hit it at just the right angle. Then part of it goes in and part of it then gets a kick, almost like a slingshot back out. And then you can capture the kinetic energy of this material that wasn't consumed by the black hole. And then you can use that to power your starships or whatever. And I forget the exact number. I think it's 38% efficient. So the most efficient process you can get to get energy is matter and antimatter. So if you have matter, you have antimatter, you put them together, it is 100% efficiency. You can gather all of the stored, E equals mc squared between the matter and the antimatter as you put it together. With the Penrose process, it's 38%, efficient. So it is extremely efficient compared to almost every other form of energy that we possibly know of. And there's like a third way, and I forget what it is. Maybe do a follow on, of what, because there was like a paper that came out a year ago, 2 years ago that we reported on. And somebody had come up with a novel additional way that you could harness the energy from a black hole. Ian Salter, if Planet 9 turns out to be a primordial black hole, will we be able to use it as a gravitational lens? That's an interesting question. So, one really out there theory is that Planet 9 is a primordial black hole, left over from the Big Bang. And black holes can be used as gravitational lenses. And normally the gravitational lens, like people always ask me if it's so far to use the sun as a gravitational lens, why don't we use Jupiter? But the problem is that the actual gravitational lensing of Jupiter is not very good. And so you would actually have to go dramatically farther away from Jupiter to use it as a lens instead of the sun. The sun is the best lens that we have access to, but a black hole gives a very tight lens, but it's the event horizon of a black hole that has the mass of a dwarf planet is not very big, right? Like if you turned Earth into a black hole, you would have an event horizon of a centimeter across, right? It would not be a very big black hole. And so you would be able to use it as a gravitational lens, but you're not going to get the kind of gravity that you're hoping for. So you want to use the sun, or you want to use like a real black hole, a stellar mass black hole. Now you're talking. So yes, theoretically, you could use Planet 9 as a gravitational lens, but it wouldn't be a great one. Overall opposites. Can we use light bending around a black hole as a time mirror to see the sun in the past? Theoretically, yes. Practically, no. So, the first part, does light bend around a black hole? And the answer is, yeah, theoretically. In fact, when you look at these sort of artist illustrations, these mock-ups of what a black hole looks like, you're seeing light that is wrapping around the black hole from all angles. And so you sort of imagine as you get closer and closer to the black hole, your light is just going to all go in. Like once you cross the event horizon, all light goes in. But just outside the event horizon, there's another region called the photon ring. And this is a region where theoretically light can be in orbit around the black hole. But, the way the direction that the photons come in, they're not going to be in these sort of perfect circles. They're going to do loops around the black hole and then go back out in some other direction. And theoretically, there will be photons that have been emitted from the sun. They've gone all the way to a black hole. They happen to hit perfectly at the right angle into an area that's around the photon ring. And they come around the black hole and then they're emitted in exactly the opposite direction. And so the black hole acts like a mirror for the photons that are coming from the sun. So that's the theoretically part. The practically part is you've got to imagine sort of the numbers here, right? That you've got the sun. It's trying to go to a black hole that could be thousands, tens of thousands, millions of light years away. Like how far in the past do you want to be able to see the sun? You want to see dinosaurs? You're looking at a black hole that is going to be 65 million light years away, so that the light is 65 million years ago. And then you got to wait for the return journey of the light. But practically the number of photons that have gone all the way to this black hole that is that far away is almost none. But then the number that is made a perfect 180-degree turn around the black hole and come back to us is none, right? Like every now and then it happens, but you've got to be ready for that one photon, and you don't get to really make a sort of a comprehensive view of a dinosaur with one photon. So theoretically, yes. Practically, no. Rob McCachran, could black holes be the cause for gravitational effects we attribute to dark matter? Yeah, theoretically. One of the theories to explain dark matter is that there are black holes that are, they are definitely qualify. They are dark. They are made of black coal, and that they have gravitational effects. And yet if they're big, say 1,000 times the mass of the sun, then if you had enough of them, they would provide the gravitational effects, and yet they would be really difficult to pin down where they are out there. The other possibility is that you go the small route and you go with primordial black holes, things that are the massive asteroids, and then you just have a lot of them out there. So astronomers have definitely considered this, and they can't rule it out. So it could very well be that black holes can explain dark matter. Or it's a combination, that some amount of dark matter is black holes, some of it is axion, some of it is sterile neutrinos, and maybe some other particle. Disasterina, would the primordial black holes in the early universe have evaporated by now? How long would it take? So right now we know of one way to get a black hole, and that is to explode a star. And, you got to have a star that's about 25 times the mass of the sun. And then you're left with a black hole of several times the mass of the sun. And then that is the beginning that you can then accrete more material, and your black hole can get stronger, and black holes can find other black holes and merge together. And theoretically, that's how you get supermassive black holes. It's also possible that you could get supermassive black holes through direct collapse. You just have a giant cloud of gas. Under its own gravity, it starts to pull together and can turn into a supermassive black hole. But there is this sort of lower limit on what is the smallest possible, the least massive possible black hole. But there's been this idea kicking around that there could be primordial black holes, that in the early universe, the regions of over and under density moments after the Big Bang were so great that you just got black holes of all different sizes forming just naturally. That it's just space was so close together, energy was so close together. You had little Kugelblitzes everywhere, and they could be all kinds of different masses. Some could just be the mass of a few hundred atoms. Some could be 1,000 times the mass of the sun and would be still living to this day. And then all of these black holes would go on to evaporate. And as a black hole becomes less and less massive, it evaporates more quickly. And so people have done the math, and I forget the exact number, but it's like about 100 million tons, I think, that if you had a black hole that was, roughly the mass of a small asteroid, it would have evaporated by now in the universe. And then anything with more than that is still able to maintain some of its mass and wouldn't have evaporated yet. And so people have made this calculation and determined the amount of sort of how often you should see gamma ray flashes. And it was believed maybe that one of the explanations for gamma ray bursts early on was that these were primordial black holes evaporating and going through their sort of final death flash. Now we know that they're caused by really massive stars that are collapsing, but there was a real serious theory, and you can't rule it out. So people continue to wonder if there are primordial black holes, and they are looking for the flashes of radiation that would come from the smallest black hole, the least massive black hole evaporating. And then the next least massive black hole will evaporate. And then the next least massive one. And so over time, all the little black holes will evaporate. Church discography. What would happen if a gamma ray burst slammed into a black hole? The black hole would absorb all of the energy from the gamma ray burst. So like a gamma ray burst is kind of the birth of a new black hole anyway. There's two kinds of gamma ray bursts. There's the short gamma ray bursts that last less than 2 seconds. Those are probably caused by colliding neutron stars. And then there's long gamma ray bursts, which are caused by the death of a massive star, something that is like really big, dozens, if not more than 100 times the mass of the sun. Thing collapses, you get a black hole at the center of it. And then you get this radiation that comes out like a supernova, but you also get these collimated jets of material that come out of the poles of the object as it is forming this black hole. And we know that even if one of these things hits the Earth from halfway across the Milky Way, it can cause severe damage to the atmosphere, wipe out a lot of the ozone in the atmosphere, let more of the radiation from space make its way into the planet through the atmosphere and cause damage to life on Earth. So they're really bad. But black holes can feast on energy. No problem. And so you would imagine, let's imagine like the perfect scenario. You've got this gamma ray burst, star collapses, blasts out this collimated jet. The collimated jet blasts and a black hole happens to be perfectly in the path of that gamma ray burst. Well, the spread of the gamma ray burst is going to go, much wider than the event horizon around the black hole. They have an angle of like 5 degrees. So imagine the sort of 5-degree angle coming off the gamma ray burst as it's sort of going out into space. So by the time you are several light years away, it's very big. While the event horizon of, say, a stellar mass black hole is going to be, well within the orbit of Mercury. So they're very small. But some of the photons, the gamma rays, coming from the gamma ray burst are going to hit the event horizon of the black hole. And they're just going to go right in and they're going to add to the mass of the black hole using E equals mc squared. You just calculate the energy of the photons. That will help you calculate the amount of mass that the black hole absorbs, the equivalent amount of mass. And the black hole will get a little bit bigger. Its event horizon will get a little bit bigger, get a little more massive, and then it'll be a bigger target for future gamma ray bursts. So no, black holes can totally handle gamma ray bursts. Yum, yum. Here's a black hole fact. If a supernova is asymmetrical, then when it creates a black hole, that black hole can have a kick, which will have it moving through the Milky Way at high velocity. That sounds scary. Luke Skywalker. My daughter asks how black holes are made. All right. So I don't know how old your daughter is, but I'm going to assume that she has an intellect that scales beyond anything we can scarcely imagine. So she can handle what I'm going to be spinning. Why are stars stars? And they're stars because they are in this balance. So you've got gravity that is pulling the star in on itself, wants to collapse that star into itself. But then you also have the light pressure pushing against the inward pull. And this is amazing, right? Like at the center of stars, they are mashing hydrogen into helium. They are making heavier elements. And as they do that, it produces gamma radiation. And that gamma radiation, these photons that are bouncing around inside the star, push out against the star, stop it from collapsing in on itself. As a star, like a big star, gets older, it uses up all of the hydrogen in its core, and then it switches to turning helium into heavier elements. It can turn things into carbon and oxygen and neon, and it just keeps making heavier and heavier elements in its core. All the while, it is producing this gamma radiation that is pushing against the gravity that's pulling the star in. And it gets all the way up to iron. And iron is this very special element that when you make iron, you don't get the gamma radiation in the way that you did with all of the other elements before that. And so now there is no radiation that is blasting out of the center of the star in the same way that it was there before. And now there is nothing holding all of that gravity that was keeping that entire star out. It all just collapses in on itself, implodes. And it can go like 70% the speed of light as all this material is falling inward. And you get this black hole forming at the center of the star because it's just being compressed down where you've got all of the mass of this star just collapsing in on itself. And that's how you get a black hole. Lucas House, can you explain the black holes and dark matter paper that came out recently? I'm not sure which black hole and dark matter paper came out recently that you're talking about. Many of them have come out. And the gist is that one of the explanations for dark matter, right, which is this seemingly invisible matter that only interacts with regular matter through mass, but not through any kind of electromagnetic interaction. There's been a bunch of possible solutions. One is there's some massive particle that we just aren't aware of. We can't see so far. Another possibility is that we just don't understand gravity at the largest scales, that it works in a different way at galactic distances than it does in regular distances. And the third possibility is that it is made of black holes and that actually black holes fulfill all of the requirements. We can't see them, right? We can't see black holes. They have mass. We know that they have mass. And that there could be a lot of them out there.
Now, it doesn't feel like there can be enough black holes if you just go with the deaths of stars, because like whatever black holes are, there would need to be 5 times as much black hole mass as there is just regular stellar mass and gas and things like that. And so you would have needed a different kind of formation mechanism. Just then stars die, you get black holes find each other, merge, that it probably would have been something that would have formed early on in the universe. And this is this idea of primordial black holes. So you would have regions of higher and lower density early on in the universe. And that would be dense enough that you would just get black holes forming naturally. And you get them at all different sizes and shapes. And, this idea that black holes can explain dark matter has been around for a long time. And it just refuses to go away because it just hasn't been overturned yet. If you talk to most scientists who study dark matter, they're not going to say, oh yeah, dark matter is definitely explained by black holes, but they can't rule it out. But what they can rule out so far is black holes of varying masses. So they know that these things probably aren't like stellar mass black holes. They could be a ton of little black holes, some things with like, say, the mass of an asteroid, or they could be black holes with like 1,000 times the mass of the sun, but probably not anything in between. If there was that stuff in between, we would actually see stars flickering as black holes were passing in front of them from our perspective. We'd be seeing these gravitational microlensing that would tell us that those black holes are out there, and we don't see that. So we have to rule out that idea. But still, yeah, dark matter could be black holes. Ash 007. What if a rogue black hole comes our way? How much warning would we have if there was no accretion disk to spot it from a distance? So a rogue black hole that was on a collision course with the Earth or with the solar system would be detectable in advance. Let's say it's moving towards us at, say, the speed of 3I Atlas. So it's moving at the speed of tens of kilometers per second. But it has the gravity of several stars inside of it, right? It has the mass of minimum 3, upwards, could have 65 solar masses in it for gravity. And so even when it is thousands of astronomical units away, we would start to detect the gravitational interactions coming from this black hole. It would be starting to pull Kuiper Belt objects and planets off of their orbits. And as it got closer, it would become the dominant gravitational force inside the solar system, more gravity than the sun. And so the planets would go into orbit around this object as it was making its way through the solar system, or crash into the event horizon, or join now it would be gaining an accretion disk. So we would have years of notice that it was on its way, that it was going to be happening. People would be noticing, like, that's weird. The Kuiper Belt objects are no longer in the right orbits that they were before. That's weird. Neptune is no longer in the right orbit anymore. That's weird. And after a while, people are like, okay, we know that there is an object with 3 times the mass of the sun that is on a collision course with the sun. And we know when it's going to totally disrupt the solar system. And the solar system would be unrecognizable after something like that went through it. And so it just shows you that our solar system is not unrecognizable. The solar system is largely stable with the planets going around the sun. And so it looks like there have been no rogue black holes that have come through the solar system in the 4.5 billion years, the history of the sun. Mr. JP, is a black hole best described as a 3-dimensional spherical region of space with extremely strong gravity that can be approached from any direction rather than a literal hole? Yeah, black holes are neither black nor holes. They are not black. They are just absorbing all of the electromagnetic radiation that falls on them. And so they cannot emit radiation because they absorb it again. And so they are invisible because you literally can't see them. And they are not holes. There is something underneath the event horizon of the black hole where new material gets added to this thing. So if you drop a planet into a black hole, the planet's going to get torn apart and then added to the mass of the black hole. That is not a hole, right? It is added to the mass. Now, what is inside the event horizon? We don't know. It could be a singularity. It could be an object of some size. It could be right underneath the surface of the event horizon. We don't really know. We can just calculate the mass and the spin of the object. But yeah, you can approach a black hole in any direction in the exact same way that you can approach a planet or a star in any direction and feel the gravity, the sort of distortion of space-time.
Here's a black hole fact. The halfway point of evaporation by a black hole is known as the page time. And this is the point where it's starting to emit the information that fell into it that is now being destroyed. And this is the heart of the information paradox. Forerunner, is our universe the result of a black hole exploding? Where does all that matter inside a black hole go in the end? So we don't know where the universe came from, and people have proposed that we are the result of a black hole exploding, but it's very hard to make a black hole explode. That the only way to get rid of a black hole that we know of is for black holes to evaporate, and this is a process that is very slow. It takes a very long time. And you need a time when there's really no energy, no light, no matter, nothing can go into black holes. They're very, very cold, or the universe is very, very cold, and then they will start to evaporate. They'll give off heat. And you'll have these particles that are leaving the black hole, and it's like 10 to the power of 67 years. So 1 followed by 67 zeros is the amount of years it would take for just a stellar mass black hole. And it's like 10 to the power of 100 years. A Google years is what it would take for a supermassive black hole to fully evaporate. But when the black hole is almost out of mass, as it evaporates, it gets lower and lower in mass, and its temperature rises. And eventually, within the last few minutes, the temperature gets so hot that it explodes in this blast of gamma radiation. And astronomers have actually looked for this. They've actually looked out into the universe to see if they can find black holes, primordial black holes exploding because they have finally evaporated. We haven't seen any, but theoretically they are out there. And so this idea that where does all that stuff go? Well, it just gets added to the mass of the black hole. And then when the black hole stops feeding, then it slowly evaporates it all off again. So think about, I don't know, if you go out in the rain, and your clothes absorb a bunch of rain, and then when it stops raining, your clothes will start to evaporate that water off of your clothes, and eventually you'll be dry again. You'll be miserable, but you'll be dry. Or you'll be cold, but you'll be dry. And so that's what's happening with black holes. And so it doesn't look like some kind of mechanism where a black hole will just gather a bunch of material and then it'll get to this point where it explodes. That there is no limit. A black hole can consume as much as it wants. Right? As long as you're willing to keep feeding a black hole, it will take it. It's only when you stop feeding it that you actually get a chance for a black hole to explode. And only when they finally reach the end of their life and they've almost already completely disappeared. That's when they explode. Is Jordan, does any object falling into a black hole fall in the same direction along the different dimensions of space? So when you think about things falling into black holes, just imagine things falling onto planet Earth. That if you were, Earth is a sphere, the gravity of, the gravity is that it's actually a distortion of space-time. But if you sort of imagine it as a force that is pulling things, then it doesn't matter what angle you come in at on the Earth, you're going to fall and hit the Earth, right? If someone teleports you above the South Pole, 10,000 kilometers above the South Pole, you're going to fall and you're going to hit the South Pole. If someone teleports you and you're above the North Pole, you're going to fall and hit the North Pole. Black hole is exactly the same, right? It is the name is bad because it's not a hole. It is we can see theoretically the event horizon around the black hole. We don't exactly know what the black hole looks like, but it is a dead star that is all the mass of a star now compressed into potentially something that is microscopic. Maybe it's the size of the event horizon, doesn't matter. Practically speaking, if you were teleported above the South Pole of a black hole, you would fall and hit the South Pole of the black hole. If you were teleported to the North Pole, you would hit the North Pole. So think of a black hole exactly like you think of a planet or a star or whatever. Something where the force of gravity, effective gravity is exactly the same. Just more. Here's a black hole fact. If you surround a black hole with mirrors and then fire more lasers into it, the lasers will bounce around, extracting energy from the rotation of the black hole, and eventually it'll explode. And that's a black hole bomb. Reason 1024. Can the Hawking radiation process help grow a black hole? No. Hawking radiation makes black holes evaporate. So it's the opposite of growing them. It is shrinking them. It's the only way to kill a black hole is to cool down the universe to the point that the black hole starts radiating energy, and by doing so gives up mass and evaporates away to nothing. But it just takes a long time. Well, you've almost reached the end of this episode. 10 hours of questions about black holes. At this point, I can't even imagine what you're experiencing. Your mind is filled with concepts. You have questions. You have answers. You've probably transcended to another plane of existence. You must express this to someone. And yet, can they understand you? I don't think so. Normally, you can only watch YouTube videos, but we are now inextricably linked through this black hole information paradox. And so, I'd like you to express the complex feelings of emotions that you're experiencing right now. Let's just take a minute or two to get through this before we move on to the last question. Yeah, I know, right? Yeah, I felt that way too. Yeah, but, this is still a controversy. We don't know. No, that's a really interesting insight. Hmm. Yeah, of course. Wow. Yeah. Yeah, I get that. Yeah. Yeah, it makes you think, doesn't it? Right. Yeah, I can see where you're coming from. Look, what are you, some kind of supervillain? No, don't do that. It's a lot of school, but if you're really into it, maybe you should consider it. Yeah. I think that is the heart of this whole thing. I do wish more people understood that. Yeah, we may never know. But that's okay. All right. That was quite a palate cleanser. I think we're ready. You have sort of come back down to earth, internalized everything you've gone through. It's time for us to get on to the last question. Jimmy James, is one of those favorite movies, The Black Hole by Disney? Absolutely not. That movie is terrible. Well, you made it to the end. I'm impressed, a little terrified. Now, of course, you can just go back to the beginning and watch this masterpiece again. Try the other audio track. Use it to fall asleep forever. And of course, if you want to add to the accumulating knowledge of this channel, you can always join us on Mondays and ask your questions during my live stream. You might have noticed there were no mid-roll ads in this entire 10-hour video. And that's because we don't believe in ads. We don't like them. We don't want them. You don't like them. And so we don't have to put them in our videos. And that's because we are supported entirely by our patrons. And because of their financial support, we can switch off the ads in everything we do. There's no ads on the Universe Today website. There's no ads in the mid-rolls of videos. There's no ads in our newsletter. There's no ads in our podcast. Everything is available ad-free. And if you want to watch our videos completely ad-free, even without an ad at the beginning, you can do that by going and watching our videos over on Patreon, completely for free. And remember, you don't have to donate to participate to be able to watch those videos on Patreon. But of course, if you want to support us and help us keep everything ad-free and make it available, join us at patreon.com/universe today. So which supercut should we make next? All right, back to the beginning.